There are 5 sections to the GED test: reading language arts, writing language arts, social studies, science, and mathematics. The exact breakdown of question type varies from one section to another. However, more than half of the questions on the GED are multiple choice questions. There are multiple choice questions in each section of the GED, though they do not comprise as significant a percentage of the test as they used to. The multiple choice questions will give you 4 different answer choices. In most cases, you are seeking the one appropriate answer choice. Multiple choice items are considered a reliable standardized measure and are used on most standardized tests, so the format should not come as a surprise to you. When you are taking the GED, you will want to spend about 90 seconds for each question on average. This means that you should be strategic about answering and be prepared to work with the test format. The remainder of this lesson will offer you some examples of multiple choice questions you might find on the GED, and will offer you some strategies that are useful for multiple choice questions. On the reading, social studies, and science sections of the test, most of your multiple choice questions will be based on a passage, chart, or other type of primary source document. The test will present you with a split screen with the passage or document on your left side and the related question or questions on the right side. For instance, on the left side you might see a fictional passage about a character undergoing an obstacle. On the right, you might see a multiple choice question like, what characteristic best describes the main character in the passage you just read? Then you will see 4 answer choices. The answer choices might include courageous, foolish, heartless, and nefarious. You should select the answer choice that best describes the character at hand. When answering passage or document-based questions, remember that the answer will be embedded in the passage or document. You will be relying on your reading skills, but not on your prior knowledge about the topic. These questions will only have one correct answer. A different type of multiple choice question on the GED will have more than one correct answer. In these cases, the instructions will tell you how many answers you should choose. You may be asked to choose up to 3 correct answers, so read the instructions carefully. An example of a multiple select item might say, who was a past U.S. president? Choose 2 answers. The answers might read, Benjamin Franklin, Sonia Sotomayor, George Washington Carver, Abraham Lincoln. You would want to select the 2 answers describing past U.S. presidents. There are some good strategies to help you ensure your success on the multiple choice items of the GED test. Read the questions first. If you read the questions and answer choices before reading the passage or document, you will be able to look at the passage with a more careful eye. This will enable you to seek out the information you need efficiently. Read all of the answer choices. It is always important to read all of the answer choices before selecting one. You might be surprised if the last answer is a more appropriate response to the question than the first one. Look back at the passage. Do not forget that many of the answers to these questions are right there for you. Look back at the passage or document that the question is related to, rather than trying to rely too intensely on your prior knowledge. When in doubt, guess. On the GED, there is no penalty for guessing. If you really don't know the answer, you are better off taking your best educated guess, rather than leaving an answer choice blank. Use the process of elimination. Often, there will be one or more answer choices that you know are wrong, even if you are not sure which one is right. Eliminate the ones that do not make sense, and you will increase your chance of guessing properly. On the GED test, you will come across multiple choice questions in all 5 of the 5 sections of the test: reading language arts, writing language arts, social studies, science, and mathematics. Some questions will have you read a passage and then choose one correct answer from 4, while others will ask that you choose more than one correct answer from a group. In order to succeed on multiple choice questions, make sure that you Read the questions first. Read all of the answer choices. Look back at the passage. When in doubt, guess, and use the process of elimination.
There are 4 operations that can be performed when working with whole numbers. These 4 operations are addition, subtraction, multiplication, and division. We use these operations in everyday life for a multitude of tasks. The most basic of these 4 operations is addition. Addition is the operation that involves calculating the total amount of a represented group. To add a set of numbers together, we first need to line them up vertically by place value. Then add each column of numbers from right to left. If a column has a sum greater than 9, we will carry the tens place to the next column. Let's take a visit to the local mall to visit my good friends Val and Carrie. They own a local cookie shop where they are busy getting ready for their customers. Val and Carrie have several orders placed for today and need to know how many cookies they should bake. They have orders of 116 chocolate chip cookies, 524 sugar cookies, and 75 snickerdoodle cookies. Val asked Carrie to calculate how many cookies they should bake today. Carrie knows that to start adding these numbers together, she must line them up vertically by place value. So Carrie writes down 524, 116, and 75, lined up on the ordered form. Carrie begins by adding the column to the right. 4 plus 6 plus 5 equals 15. She knows that since her value is greater than 9, she must carry the tens place to the next column. So she writes down the 5 and carries the 1 to the next column. To add the next column, Carrie will need to add 7 plus 1 plus 2 plus the 1 that we carried. The sum of these numbers is 11. Again, Carrie must carry the tens place value since the total is greater than 9. Next, she needs to add the last column. 5 plus 1 plus the carried 1 equals 7. Carrie now knows that they need to bake 715 cookies to fill all of the customer orders. The next operation is subtraction. Subtraction is the operation that involves taking away value from the total amount. To subtract whole numbers, we will need to line the numbers up by place value from right to left. Next, we will subtract each place value. Occasionally, the value that we are subtracting is not large enough to take away the value. When this happens, we must borrow value from the next place value. When you borrow from the next place value, you are borrowing a set of 10. This set of 10 is added to the existing value and subtraction is continued. Let's check back in on Val and Carrie to see how they're doing on their cookie order. Val and Carrie have cooked all of the chocolate chip and snickerdoodle cookies, but still need to cook the sugar cookies. As they are preparing to start the sugar cookies, the phone rings. Val answers and it's their customer. She tells Val that she needs to reduce her order for sugar cookies. She had originally ordered 524 sugar cookies, but needs to subtract 134 of them. Val now needs to subtract the customer's original order of 524 sugar cookies by 134. To do this, he must first line up the numbers from right to left by place value. To begin, Val starts with the values on the right. 4 minus 4 is 0. Next, Val needs to subtract 2 minus 3. However, he knows you cannot take 3 from 2, so he must borrow. So he borrows a set of 10 from the next place value. As he borrows a set from the 5, its value becomes a 4. The set of 10 also increases the value of the 2 to 12. Val can now subtract 12 minus 3 is 9, and 4 minus 1 is 3. Val now knows he only needs to cook 390 sugar cookies to fill the customer's order. Multiplication is another one of the 4 operations. Multiplication is the process of adding multiple sets of the same number. To multiply, we will take each place value and multiply it to every value in the other number. If the number being multiplied has more than one value, you must add a 0 as a placeholder each time you move to the next place value. This process continues until all the places have been multiplied. Back in the cookie shop, Val and Carrie have finished their daily order. As they talk, Carrie wonders if they cook this many cookies daily, How many cookies would they cook in 126 days? To do this, she will need to multiply the daily cookie order of 715 by 126 days. To start this problem, Carrie needs to multiply the 6 by each of the values on top from right to left. If a value is greater than 9, the tens place will be carried to the next place and added to the multiplied value. 6 times 5 is 30, so we keep the 0 and carry the 3. Next we multiply 6 times 1, which is 6, then add the carried 3 to equal 9. The value 9 is written below. Then we multiply 6 times the 7, which is 42. Since there are no additional places on top to be multiplied, we write the 42 below. Next we must multiply each place on top by the 2. Since we moved one place on the bottom, we will need to add a 0 to the next line below. As we multiply the 2 to each value on top, we get 14,300. As we move to the next place to multiply, we must now add 2 zeros to the bottom because we have moved over 2 place values. Next we need to multiply the 1 by each value on top, which gives us 71,500. The last step to multiplying is to add the values together from right to left. After adding these values, the product is 90,090. Carrie knows that if they sell 715 cookies for 126 days, they will sell 90,090 cookies. The last of our 4 operations is division. Division is the process of taking a total value and dividing it into equal parts. The first step is to set up the problem. The value that is being divided is called the dividend, and the value that we are dividing into is called the divisor. To set up a division problem, you will use the format dividend divided by divisor. When dividing, we take the divisor and divide it into each value of the dividend from left to right. The number of times the value will divide into the dividend goes on top. The value is then multiplied and subtracted from the dividend. The process continues until all the places in the dividend have been divided. If there is a value that remains at the end, this is called your remainder. The wonderful smell of cookies has now attracted customers to the cookie shop. Val and Carrie are glad to see such a huge crowd. There are 12 customers that have gathered at the cookie counter. Val and Carrie know that they have cooked only 715 cookies. Val wants to know how many cookies each of the 12 customers ordered. In this problem, 715 is the dividend, and 12 is the divisor. The problem will be set up as 715 divided by 12. The first step is to take the 12 and see which value it will divide into. 12 will not divide into 7, so we must use the first 2 values, 71. 12 will go into 71 5 times, so we write the 5 on top. Next we need to multiply the 5 times 12, which is 60. This value gets written below the 71 in the dividend. Now we must subtract 71 minus 60, which is 11. We must also bring down the next value from the dividend. The new dividend is 115. Next we must see how many times 12 will divide into 115, which is 9. This 9 gets written on top. At this point we repeat the same process as in the previous step. We need to multiply 9 times the 12, which is 108, which will be written below the 115. Subtract 108 from 115, which is 7. Since we are out of values in the dividend, 7 is our remainder. Val can now see that he can sell each customer 59 cookies, and he will have 7 cookies left over. There are 4 operations that can be performed when working with whole numbers. These 4 operations are addition, subtraction, multiplication, and division. The most basic of these 4 operations is addition. Addition is the operation that involves calculating the total amount of a represented group. The next operation is subtraction. Subtraction is the operation that involves taking away value from the total amount. Multiplication is another one of the 4 operations. Multiplication is the process of adding multiple sets of the same number. The last of the 4 operations is division. Division is the process of taking a total value and dividing it into equal parts.
Yes, this video lesson is about word problems. I know for many, word problems are considered a nightmare, but they don't have to be confusing. Let me show you a 3-step process you can use to help you solve your word problems. You will need your algebra skills for solving equations with variables in them, so access that part of your brain right now so that you have that information at your disposal during this video lesson. We begin with a word problem. Tobias is scared that the banks will close on him, and he's afraid that a fire will come and burn everything he has. So he keeps his cash savings frozen in a big piece of ice in the freezer. He has $4,300 in frozen cash. His brother, Jude, keeps his cash stuffed inside a teddy bear. Jude has half the amount that Tobias has. How much money does Jude have stuffed in his teddy bear? The first step is to visualize the problem. See if you can picture what is going on. Draw pictures if that will help you. Pinpoint or highlight the important parts of the problem. For our word problem, we can picture 2 brothers with cash savings. We can picture Tobias opening his freezer to look at his cash. We highlight the important part of how much cash Tobias has. We do the same for Jude. We picture Jude giving his teddy bear a hug. We highlight the important part on the amount of cash Jude has in his teddy bear. But wait, we don't know how much Jude has. That's the amount we want to find out, so we label it with an X and highlight it. We might make a note next to the X that this is what we want to find out. We also understand from the problem that Jude's amount is half of the amount of Tobias. We write that information next to the X. We can write X equals half of Tobias' amount. Now that we fully understand the problem, we can proceed to step 2, which is writing our equations. From our visualization of the problem and by highlighting the important parts, we have already begun to write our equation. We only need one equation for our problem. The equation we have begun to write is X equals half of Tobias' amount. Now we just need to insert the numbers that we know of. We know what half is. We can write half as 1 divided by 2, or 0.5. We also know Tobias' amount. It is $4,300. Now we can finish writing our equation, X equals 0.5 times 4,300. The last step in solving a word problem is to solve the equations we wrote. Our problem only had one equation for us to solve. To solve this, we just need to solve for our X. Solving our equation for X just means that we multiply 0.5 with 4,300. Doing that, we find our answer to be $2,150. And we are done. Let's look at another example. Jenny has a job that she goes to every day after school. She works at the local cupcake shop. She works for 3 hours every day, 15 hours a week. She bakes 200 cupcakes every day. She earns $10 per hour. How much money will she earn after 2 weeks? Our first step is to visualize the problem. We picture little Jenny going into the cupcake shop every day and baking her 200 cupcakes. We don't highlight the 200 cupcakes because we don't need that information to solve our problem. We do highlight the part that tells us that Jenny works 15 hours every week. We also highlight the part that asks us how much Jenny will make after working for 2 weeks. We make a note that this is what we are looking for. Our next step is to write our equations. We understand that the problem is asking us about Jenny's work for 2 weeks. We need an equation that tells us how many hours Jenny will work in 2 weeks. We can label this with an H. So H equals 2 times 15. Yes, we multiply her weekly hours by 2 to find her hours for 2 weeks. We then need another equation to tell us how much money Jenny will earn in 2 weeks. We can label this with an X for the information that we want. We need the amount of hours Jenny has worked in 2 weeks along with her pay. This equation we can write as X equals H times 10, where X is Jenny's pay for 2 weeks. Our last step is to now solve our equations. We see that we have 2 equations. One equation requires the answer from the first equation. I go ahead and solve our first equation. H equals 2 times 15, which is equal to 30. Now I can solve my second equation by plugging in this information. X equals 30 times 10, which is equal to 300. Ah, my answer is $300. Jenny makes $300 after 2 weeks. Now I am done. Let's review now what we've learned. To solve word problems, we follow just 3 simple steps. The first step is to visualize the problem. Included in this first step is also highlighting the important parts of the problem that will help you to solve it. The second step is to write your equations. You will use the important parts of the word problem to formulate an equation that will help you to solve it. The third and final step is to solve your equations. This is where your algebra skills in solving equations with variables in them come in handy. So follow this 3-step procedure and don't let word problems scare you. This might sound repetitive, but don't be afraid of word problems. You've probably heard that before, and it's true. Don't shy away from these problems. Face your fear. Once you tackle word problems using the steps to solve a word problem, you will be that much stronger. These are 3 steps to successfully solve any word problem. The first is to visualize the problem. Fully understand the problem so you know what you need to solve and what is going on in the problem. The second is to write equations from the problem that will help you answer the question from the problem. The third is to solve your equations. This is easy to do for word problems that only require you to do one step, like simply adding 2 things. But what if the word problem is a bit more complicated? What if you need to do more than one operation to solve? What if you needed to multiply and then subtract to find your answer? How would you apply the steps to solving a word problem in this situation? Let's find out. We will use these steps to help us solve a somewhat complicated word problem. Sue is a baker. She bakes all kinds of goodies, like apple pies and cheese pies. Yum! On Mondays, Wednesdays, and Fridays, Sue bakes apple pies. She bakes cheese pies on Tuesdays and Thursdays. If Sue bakes 50 pies a day, how many more apple pies does Sue bake than cheese pies in a week? Our first step in solving this word problem is to visualize our problem. What's going on? The best way to do this is just to picture a little cartoon show in your head of what is going on. We see a little Sue the baker baking pies. 3 days a week, she is baking apple pies. The other 2 days of her work week, she bakes cheese pies. So she spends more time baking apple pies than cheese pies. That means she makes more apple pies than cheese pies. She bakes 50 pies each day she works. Now what is the problem asking us? It's asking us how many more apple pies does Sue bake than cheese pies. Okay, we can answer that. We have all the information we need to solve that. Now that we fully understand the problem, we can go through and underline, highlight, and make note of all the important pieces of information that we need. We highlight the part that says Sue bakes 50 pies a day. Next, we make a note that she bakes apple pies for 3 days and cheese pies for 2 days. In order to find our answer, we know we first need to find the number of apple pies she makes in a week and the number of cheese pies she makes in a week. We then need to subtract the number of cheese pies from the number of apple pies. Now we can go ahead and write our equations. We will label her apple pies with an A and her cheese pies with a C. To find the number of pies she bakes in a week, we need to multiply the number of days she bakes a certain pie by the number of pies she bakes in a day. So we have A equals 3 times 50 for the number of apple pies she bakes, since she bakes apple pies for 3 days. We have C equals 2 times 50 for the number of cheese pies she bakes in a week, since she bakes cheese pies for 2 days. Our final equation is x equals a minus c, where x is the answer we are looking for, a is the number of baked apple pies, and c is the number of baked cheese pies. Notice that we need to perform 2 different operations in order to find our answer. We need to multiply first and then subtract in order to find our answer. But wasn't it fairly straightforward once we fully understood our problem and made our little notes and highlights? Now, to finish our problem, we perform the operations as needed. We need to multiply first, so we go ahead and do that. We multiply A equals 3 times 50 to get 150. So Sue bakes 150 apple pies in a week. Next, we multiply C equals 2 times 50 to get 100. Sue bakes 100 cheese pies in a week. Comparing these two numbers, we see that we are right. Sue does bake more apple pies than cheese pies. The last step in our problem now requires us to subtract. So we subtract x equals a minus c, which is x equals 150 minus 100, which equals 50. We have our answer. Sue bakes 50 more apple pies than cheese pies. We are done. Now let's review. We learned that to solve word problems, we follow a three-step process. The first step is to visualize the problem to fully understand it. The second step is to write the equations needed to solve the problem. The third and final step is to solve those equations. We also learned that we can apply these steps to multiple-step word problems. We just need to keep in mind that we may have to do our problem in parts. We may have to perform one operation first, followed by another to find our final answer. But the more we practice and the more visualization we do, the better we will get. We begin with our number line, a line with numbers placed in order in regular intervals. Think of it as a ruler. It shows you the proper order of numbers. Knowing how to use a number line is one of the most basic math skills, and it gives you a good foundation upon which to grow your math skills. It is in this video lesson that you will learn how to find numbers on the number line, to plot numbers on the line, and then to compare these numbers. So are you ready to get going? Then let's go! We first tackle whole numbers on the number line. Recall that whole numbers are your counting numbers, like 1, 2, 3, and so on. Finding whole numbers on the number line is fairly easy. Why is this? Well, if you look at your number line or even a ruler, what do you see? Why, you see your whole numbers. You see 0 in the middle of the number line. To the right, you see your positive numbers. Going to the right from 0, we have 1, 2, 3, 4, and so on. You keep going to the right, and your numbers keep getting bigger. Going to the left from 0, we have our negative numbers, and these keep getting more and more negative. We have -1, -2, -3, and so on. So if we wanted to find the number 5, for instance, what do you think we would have to do? Yes, we would go to the right 5 spaces from 0 to find our 5. To plot whole numbers, we use a similar procedure. If we wanted to plot 3, we would start at 0, and then go 3 spaces to the right to find where our 3 is located. At this point, we place our dot. Now what about decimals, numbers with a decimal point, and fractions, numbers representing a part of a whole? How do we find and plot these numbers? For these types of numbers, first we have to realize that they tell you that your number is more than a whole number. These numbers have a part of a whole number included. For example, the decimal 3.5 tells you that you have 3 whole things, and then half a thing. If we thought about it in terms of pies, we would have 3 whole pies, and then half of a pie. So the numbers after the decimal point tell you how much of another whole you have, how much of another pie you have. Fractions are related to decimals, as you can go back and forth between fractions and most decimals. For example, the fraction 3½ can be converted to our decimal 3.5. We made the conversion by dividing the 1 and the 2 and then adding it to the 3. This is the kind of conversion we would make for mixed fractions. If we had the fraction 7/2, on the other hand, we would do a straight division to find our decimal. 7 divided by 2 is also 3.5. All these numbers are the same. The way that makes the most sense for me when looking for fractions on a number line is to convert these to decimals first, and then to look for them. And this is what I want you to do. Convert your fractions to decimal before working with them on the number line. To find your decimal, or fraction turned into a decimal, on the number line, we first find our whole number part, and then we figure out how much more we need to go for the part after the decimal, the part of a whole. For example, to find the number 3.5, we first find our 3. We find this by going 3 spaces to the right of 0. Now we need to figure out how much we have to go to account for the 0.5 after the 3. To do this, we can put little slash marks between our 3 and 4 to divide this section into 10 spaces. We would end up putting down 9 equally spaced tick marks to divide this area into 10 equal spaces. Now we can count and find the 5th tick mark to find our 0.5. If our decimal was 3.53, we would do what we did to find 3.5, and then we would divide the next space into 10 spaces, just like we did to find the 0.5, so we can find our 0.53. Make these tick marks little, so you can tell that these are even smaller than the other tick marks you drew. Our 0.53 would then be the 3rd little tick mark after our 0.5. To plot these numbers, you first find them on the number line, then you draw a point at that spot. So to plot the number 3.5, you first find it, and then you place a nice big dot at that location. Now that you know how to find and plot numbers, let's talk about comparing these numbers. Let's say you want to compare the numbers 5 and 6.5. You would first plot both of these numbers by finding them, and then putting a dot on them. Label these dots so you know which number is which. Now your job is to see which one is bigger. Because our number line gets bigger when you go to the right, the dot that is to the right of the other dot will be bigger. So comparing our numbers 5 and 6.5, we see that 6.5 is bigger than 5. 5 then is smaller than 6.5, and there we have it. This is how you use a number line to compare numbers. So now let's review what we've learned. We learned how to plot whole numbers, or counting numbers, decimals, numbers with a decimal point, and fractions, numbers representing a part of a whole. On a number line, a line with numbers placed in order in regular intervals. We learned that on a number line, the number 0 is in the middle. The numbers get higher and higher going to the right. The numbers get smaller and smaller going to the left. To the left of the 0 are my negative numbers, and to the right of my 0 are my positive numbers. To plot numbers on the number line, we first find our number on the number line, and then place a dot on it. We can label our point with the number we have just plotted. To compare 2 or more numbers with each other, we plot them on the number line and then compare where they are in relation to each other. If one dot is to the right of the other dots, it is larger than the others. If the dot is to the left, it is smaller than the others. Just remember, going to the right on the number line gets you to larger numbers, and going to the left gets you to smaller numbers.
Fields as diverse as finance, science, and politics all rely heavily on interpreting large amounts of numerical data. This can be challenging for many people, so tables and graphs are used to present the data in a way that is easy to understand. Although there are many different types of tables and graphs, you can interpret them all if you remember some basic guidelines. First, look at the title and any other labels. Some graphs may have a legend that will give you important information. The axis labels can also tell you a lot about the information presented in the graph. Next, look carefully at the graph to identify important information you need to know, and then use that information to answer the question. Let's look at a few different types of tables and graphs and see how to understand the information presented in each. Tables are the simplest way to represent data. A table compiles all the data into columns and rows so that it can be easily interpreted. This table shows the average number of visitors per day at 2 different lakes over an 8-year period. By looking at the row and column titles, you see that each row corresponds to a different year, and each column to a different lake. You could use a table like this to answer a lot of different questions. For example, which lake had more visitors in year 5? The table shows that in year 5, Lake Itawamba had an average of 74 visitors per day, and Lake Tishomingo had an average of 85 visitors per day. So Lake Tishomingo had more visitors in year 5. A pictograph uses images to represent a certain number of items. For example, suppose you had a lemonade stand and wanted to record how much lemonade you sold each day. From this pictograph, you can determine how many glasses of lemonade you sold on Thursday. Did you get 40 glasses of lemonade? Great! Looking at the pictograph, you can see that there are 4 lemons on the line that says Thursday, and you also know that each lemon represents 10 glasses of lemonade. This means that you sold 40 glasses of lemonade on Thursday. A line graph plots individual data points as dots and connects them with lines. These are great if you want to see how a quantity is changing over time. This line graph represents the distance an object travels over time. Even though there is no title, you can look at the axis labels and see that the x-axis measures time and the y-axis measures distance. Using this graph, you could find the position of the object at any time. You could also use this graph to determine that the object was speeding up, because the difference in distance between any 2 consecutive seconds is increasing. Bar graphs use bars of different heights to represent data. As with the other types of graphs, you first want to read the title and the axis labels to make sure you understand what data is being presented. In this bar graph, you can see that the x-axis has months and the y-axis says temperature. Therefore, this graph is showing you the average temperature during each month of the year at a certain location. Now, you are ready to analyze and use the data presented in the graph. Can you use the graph to calculate the temperature difference between the warmest and the coldest month of the year? First, you need to determine which month is the warmest and which is the coldest. Looking at the graph, we can see that January is the coldest and July is the warmest. Next, note the average temperatures in both January and July. In this graph, the average temperature in January is about 30 degrees, and the average temperature in July is about 75 degrees. Finally, subtract the 2 temperatures to find the temperature difference. 75 degrees minus 30 degrees equals 45 degrees. A circle graph, also known as a pie chart or pie graph, divides a circle into sections to represent the relative sizes of each category. Circle graphs are great for showing relative sizes, although they don't typically show the absolute numbers of any category. For example, a circle graph of the ages of people in a city might show that 43% of the citizens are under the age of 30, but it wouldn't say exactly how many people are under age 30. Look at this circle graph and see if you can determine what data is being presented. This is a graph of the dinner selections made by clients of a catering company, and it has a legend that tells you what each color represents. The owner of the company might use a graph like this to determine how many of each type of dinner to produce for an event. What if the company was hired to cater a dinner for 400 people? About how many chicken dinners should they prepare? You can answer this question using the circle graph. From the graph, you know that 46% of people typically choose the chicken dinner. So if there are 400 people total attending the dinner, you can calculate how many chicken dinners to prepare. 46% equals 46 divided by 100. X equals 400 times 46 over 100 equals 184 chicken dinners. No matter which type of graph you're looking at, you want to always first read all the labels and try to understand exactly what the graph is showing you. Then, analyze and use the data to answer the question. Here are the different types of tables and graphs discussed in this lesson. Tables compile data into a list or group of lists. Pictographs use images to represent a certain number of items. Line graphs plot individual data points as dots that are connected by lines and are used to show trends over time. Bar graphs use bars of different heights to represent data. Circle graphs, or pie charts or pie graphs, divide a circle into sections to represent the relative sizes of each category.
A dataset is a collection of numbers or values that relate to a particular subject. For example, the test scores of each student in a particular class is a dataset. The number of fish eaten by each dolphin at an aquarium is a dataset. Datasets can be written as a group of numbers in random order, in a table form, or with curly brackets surrounding them. The datasets are usually labeled so you know what the data represents, but when working with datasets, what the data stands for is not always provided and is not always needed to finish the problem. The 3 ways to work with datasets are to calculate their mean, median, and mode. But before we can calculate these 3 pieces of information, we first have to prepare our dataset by rewriting them in ascending order from the smallest to the greatest. So, our two dataset examples from earlier need to be rewritten as follows. Now, we can go ahead and start working with these datasets. The mean of a dataset is its average. To calculate the mean, we add up all our values and divide by the number of items we have. The mean equals the sum of the values over the number of items. First, we need to know how many items we have in our datasets. To do this, we count how many values we have. For the test scores, we have 7 items, and for the fish eaten, we have 8 items. Second, we need to add up all our values. For the test scores, we add up 64 plus 89 plus 89 plus 92 plus 94 plus 95 plus 100 to get 623. We then divide this number by the number of items this dataset has, which is 7. We get 623 divided by 7 equals 89. 89 is our mean for the test scores dataset. For the fish eaten dataset, we do the same thing. We add 8 plus 10 plus 10 plus 10 plus 12 plus 15 plus 18 plus 20 equals 103, and divide by the number of items to get 103 divided by 8 equals 12.875. So, 12.875 is our mean for the fish eaten. The median is the middle value of our dataset. It is the number in the exact middle of our dataset when it is written in ascending order. Calculating the median is different for datasets with an odd or even number of items. If the dataset has an odd number of items, we find the middle value, and that is our median. The test scores dataset has an odd number of items, which are 64, 89, 89, 92, 94, 95, and 100, so our median is the middle value, or the fourth term in the sequence, which is 92. Notice how the fourth term has the same number of terms before and after it. It is the middle term in the dataset. If the dataset has an even number of items, though, we need to find the two middle values and get their average. The fish eaten dataset, for example, has an even number of items. So we need to find the two middle values from 8, 10, 10, 10, 12, 15, 18, and 20, which are 10 and 12. These are the fourth and fifth terms respectively. If you notice, these two terms have the same number of terms before and after them. They are in the middle. Our median then for the fish eaten dataset is the average of 10 and 12, which is 10 plus 12 divided by 2 equals 22 divided by 2 equals 11. The mode of a dataset is the number or value that occurs most often in the dataset. It is possible to have more than one mode in a dataset, and it is also possible to have no modes in a dataset. Looking at our test scores dataset, 64, 89, 89, 92, 94, 95, and 100, we see that the number 89 occurs most frequently. All the other values are not repeated, so our mode for the test scores dataset is 89. The fish eaten dataset of 8, 10, 10, 10, 12, 15, 18, and 20 has a mode of 10, because that number occurs 3 times, while all the other numbers occur just once. Let's review. Datasets are a collection of numbers related by a topic. The 3 ways to work with datasets include mean, median, and mode. The mean is the average of the dataset, the median is the middle of the dataset, and the mode is the number or value that occurs most often in the dataset. Before working with datasets, we must write them in ascending order. Central tendency is defined as the typical value of a set of data. There are 3 main ways that we measure central tendency: mean, median, and mode. The mean is the average of all the data. To find the mean, add up all the values and then divide by the number of values. The median is the value that is exactly in the middle of a list of the data after it's been arranged in numerical order. The mode is the most commonly occurring number in the dataset. Although these measures of central tendency are very useful, sometimes it's not enough just to know the mean, median, or mode. Sometimes you need to represent data graphically in order to see any underlying patterns. One of the simplest ways to represent a set of data graphically is a dot plot. Dot plots are graphs that show the number of times that each data point occurs by the placement of dots. For example, if a teacher wanted to know how many books his students read last month, he could collect the data, organize it into a table like the one on your screen now, and then make a dot plot like the one shown on screen now too. In this dot plot, each dot represents one student. Dot plots are really good for identifying the mode of a dataset, which in this case are 7 and 9. This means that more students read 7 or 9 books during the last month than any other number of books. The median can be found by locating the point that is exactly in the middle. Here, the median is 4.5 books, because there are 50 dots in total, and dot 25 is at 4 books, and dot 26 is at 5 books. To find the mean, you need to calculate a weighted average. Multiply each number of books by the number of students above it. Then add all these and divide by the total number of students, 50, to find the mean. Mean equals 0 times 3 plus 1 times 3 plus 2 times 7 plus 3 times 6 plus 4 times 6 plus 5 times 3 plus 6 times 4 plus 7 times 8 plus 8 times 2 plus 9 times 8 over 50 equals 4.8 books. A histogram shows the frequency of how often a certain value occurs using a bar graph. Histograms are used to visualize the distribution of data. To make a histogram, 1. Decide how many groups you want to have and separate the data into groups. 2. On the x-axis, label the value of each group, and on the y-axis, label the number of data points in each group, the frequency. And 3. Draw a bar that is the height of the frequency for each group. A histogram of our example data is shown on your screen now. This histogram has a group size of 1 book, so there are 10 different groups. From a histogram, you can quickly see how the data is distributed, and this helps you decide how to analyze the data further. In this histogram, there is not a clear pattern in the data, but in many cases there will be. Box plots, also known as box and whisker plots, only show a summary of the data, including the median and minimum and maximum values. They are used to quickly compare different sets of data with each other. To make a box plot, 1. First find the median of the data and draw a line at that point. 2. Next, divide the data into 4 quartiles. With the data arranged in sequential order, the lowest 25% would be in the first or lower quartile, the second 25% in the second quartile, the third 25% in the third quartile, and the highest 25% in the fourth or upper quartile. 3. Draw lines on the graph showing the locations of the lower and upper quartile, and draw a box enclosing these and the median. This box will contain the middle 50% of the data, a region known as the interquartile range. 4. Finally, add bars to the left and right of the box to show the maximum and minimum values of the data in the set. The box plot on your screen shows our original example data in blue. On the box plot, you can clearly see the median of the dataset, the interquartile range, and the maximum and minimum extreme values. Box plots can also give you information about the amount of spread in the data. If the box is very small, you know that most values are near the median, but if it is large, then the data is more spread out. One big advantage of box plots is that they can allow you to compare different sets of data quickly. If the teacher wanted to compare the books read by more than one class, Class A and Class B, he could show this on the same box plot and compare the data. Let's review what we've learned. The central tendency is defined as the typical value of a set of data. There are 3 ways to characterize central tendency. The mean is the average of all the data. The median is the value that is exactly in the middle of a list of the data that is in numerical order. The mode is the most commonly occurring number in the data set. Dot plots, histograms, and box plots are all common graphical ways to represent data sets. A dot plot represents data by placing a dot for each data point. A histogram groups the data into ranges and then plots the frequency that data occurs in each range. A box plot is used to compare multiple groups of data, and it shows the median, interquartile range, and maximum and minimum values of the data. Remember that the interquartile range is the middle 50% of the data. Each of these graphical methods have their advantages and disadvantages. It will be up to you to decide which fits what situation most effectively when you're using them.
Most people are familiar with the method of finding the average or the arithmetic mean of a series of items. You simply add up all the item values and divide by the total number of items to calculate the average. However, this only works when all the items are weighted equally. Let's say you want to find your current grade in your English class. Most classes usually assign a different weight or value to papers than to homework assignments, quizzes, and tests. In this case, you might need to use a weighted average or weighted mean, which is an average where each value has a specific weight or frequency assigned to it to calculate your grade. There are two main cases where you will generally use a weighted average instead of a traditional average. The first is when you want to calculate an average that is based on different percentage values for several categories. One example might be the calculation of a course grade, like we just mentioned. The second case is when you have a group of items and each has a frequency associated with it. In these types of situations, using a weighted average can be much quicker and easier than the traditional method of adding up each individual value and dividing by the total. This is especially useful when you're dealing with large data sets that may contain hundreds or even thousands of items, but only a finite number of choices. The formula will read as follows. Weighted average equals sum of variables times weight divided by sum of all weights. Let's take a look at some examples. Example 1. A student is enrolled in a biology course where the final grade is determined based on the following categories. The student has earned the following scores for each category. We need to calculate the student's overall grade. To calculate a weighted average with percentages, each category value must first be multiplied by its percentage. Then all of these new values must be added together. In this example, we must multiply the student's average on all tests, 83, by the percentage that the tests are worth toward the final grade, 40%. Please note that all percentages must be converted to decimals before you multiply. Similarly, the final exam score, 75, will be multiplied by its percentage, 25%. The same will be true for both the quizzes, 90 times 25%, and homework, 100 times 10%. Thus, the overall calculation would be 83 times 0.4 plus 75 times 0.25 plus 90 times 0.25 plus 100 times 0.1. So 33.2 plus 18.75 plus 22.5 plus 10, which equals 84.45, or 84% if rounded down. Note that when the weights are added together, the total should be 1 or 100%. In the previous example, add 0.4 plus 0.25 plus 0.25 plus 0.1, which equals 1 or 100%. Example 2. A student has earned the following averages in his history course. The overall course grade is comprised of, we need to figure out what score he must earn on the final exam in order to earn a final grade of at least 90% before rounding. We will use the same method for calculating a weighted average that we used in the previous problem, except that now we already know the overall grade and do not know one of the category values. First, we will multiply each value by its percentage to get the following. 90 times 0.3 plus 88 times 0.2 plus x times 0.2 plus 85 times 0.2 plus 95 times 0.1. Note that a variable x is used in place of the value for the final exam score, since that is what we're trying to find. Simplifying that provides 27 plus 17.6 plus 0.2x plus 17 plus 9.5, or 71.1 plus 0.2x. We'll set this equal to 90 since that is the overall minimum grade the student wants to earn. 71.1 plus 0.2x equals 90. Subtracting 71.1 from both sides gives 0.2x equals 18.9. Dividing both sides by 0.2 yields x equals 94.5. Thus, this student must earn a 94.5 or higher on the final exam to achieve an overall course grade of at least 90%. Now let's look at an example of these weighted averages, or weighted means, with frequencies. Example 3. This chart shows the number of runs a Major League Baseball team scored in a game and the number of times each value occurred. Let's calculate the average number of runs the team scored over the entire 163-game season. To calculate the average, we need to first multiply each value, number of runs scored, by its frequency and add up the values. Note that the weights do not always add up to 1, such as in this example. In this case, you simply divide by the sum of the weights. The calculation should look as follows. 0 times 8 plus 1 times 27 plus 2 times 30 plus 3 times 21 plus 4 times 23 plus 5 times 23 plus 6 times 17 plus 7 times 7 plus 8 times 3 plus 9 times 2 plus 12 times 1 plus 15 times 1, which equals 0 plus 27 plus 60 plus 63 plus 92 plus 115 plus 102 plus 49 plus 24 plus 18 plus 12 plus 15, which equals 577 runs. Then divide that value by the number of games, 163, to get 577 divided by 163, which equals 3.54 runs per game. The average or arithmetic mean of a series of items means you simply add up all the item values and divide by the total number of items to calculate the average. A weighted average, also known as a weighted mean, is an average where each value has a specific weight or frequency assigned to it. There are two main cases where you will generally use a weighted average instead of a traditional average. The first is when you want to calculate an average that is based on different percentage values for several categories. The second case is when you have a group of items and each has a frequency associated with it.
The probability of simple events is finding the probability of a single event occurring. When finding the probability of an event occurring, we will use the formula number of favorable outcomes over the number of total outcomes. After calculating this probability, your answer will need to be in simplest form. Let's look at an example of simple events. Sam owns a large fish store with many colors of fish. He keeps all the fish in a large aquarium. In his main aquarium, he has 5 red fish, 6 blue fish, 14 white fish, and 5 green fish. A customer comes into the store and wants to buy a blue fish to take home. What is the probability that Sam will reach in and scoop out a blue fish on his first scoop? To calculate this probability, Sam needs to find out the total number of fish in his aquarium. Sam needs to add the 5 red fish, the 6 blue fish, plus 14 white fish, plus 5 green fish, to equal 30 total fish. Sam must also know the number of favorable outcomes. In his tank, there are only 6 blue fish, so his number of favorable outcomes is 6. The formula to calculate the probability is the number of favorable outcomes over the number of total outcomes. The number of favorable outcomes is 6, and the number of total outcomes is 30. So the probability of Sam scooping a blue fish the first time is 6 out of 30. Remember, all fractions must be in simplest form. So 6 over 30 will reduce to 1 over 5. The probability that Sam will scoop out a blue fish on his first try is 1/5. Compound events are a bit more complex than the simple events in the last example. Compound events involve the probability of more than one event happening together. With compound events, we will use the same formula to calculate the probability of each event occurring. To calculate the probability, we will use the formula number of favorable outcomes over the number of total outcomes. Once we find the probability of each event occurring, we will multiply these probabilities together. Let's look at an example of compound events to see how to calculate more than one event occurring. Wendy and Kim are playing a new deluxe board game titled Ed Portalopoly. It is Wendy's turn, and she needs to roll the 2 dice and get both to be a 6 in order to land on the jackpot. What is the probability that Wendy will roll a 6 and then roll another 6? To start this problem, we need to calculate each event separately. The total number of outcomes on the dice is 6, and the number of favorable outcomes is 1, because there is only 1 6 on a dice. So the probability of Wendy getting a 6 on her first roll is 1 out of 6. Next, we need to calculate the probability of Wendy getting a 6 on her second roll. Since these dice are the same, the probability of getting a 6 on the second roll will also be 1 out of 6. Now that we know the probability of both events happening, we need to multiply these two fractions together. So 1/6 times 1/6 would equal 1/36. So the probability of Wendy rolling both dice and getting a 6 on both is 1/36. Complementary events are another type of event in which we can calculate the probability. Complementary events are events that add together to equal a whole or 1. For example, if the probability of it raining today was 2/5, what would the probability be of it not raining? The probability of it not raining would be 3/5, because 2/5 plus 3/5 would equal 5/5 or 1 whole. We know that there are only two choices. It will either rain or not rain. Let's check back on Wendy and Kim playing everyone's favorite board game, Ed Portalopoly. It is now Kim's turn to roll. If she rolls 2 dice to add together to equal 8, she will land in jail. Wendy is hoping that Kim lands in jail on this turn. What is the probability that Kim will not roll 2 dice whose sum is 8? Wendy needs to first calculate the probability that Kim will roll the 2 dice and get a sum of 8. To find this probability, she will use the formula, number of favorable outcomes over the number of total outcomes. Since Kim is rolling 2 dice and each dice has 6 sides, there are 36 total outcomes that she can get. To find the number of favorable outcomes, Wendy decides to list out possible ways that the 2 dice can add to 8. She knows that Kim could roll a 2 plus a 6, or a 3 plus a 5, or a 4 plus a 4, or a 5 plus a 3, or a 6 plus a 2. She can see that there are only 5 different ways to roll 2 dice whose sum will be 8. Wendy now knows that the probability of Kim rolling 2 dice and getting a sum of 8 is 5 out of 36, or 5/36. Wendy also wants to know the probability of Kim not getting the 2 dice to add together to equal 8. These two events are complementary because they will equal 1 or 36 out of 36. Since the probability of Kim getting the sum of 8 was 5 over 36, we can subtract to find the probability of her not getting the sum of 8. 36 over 36 minus 5/36 would equal 31/36. The probability of Kim not rolling the 2 dice and getting the sum of 8 is 31 out of 36. So the chances that Kim does not land in jail on her next turn is 31 out of 36. In this lesson, we looked at 3 different types of probability. The probability of simple events is finding the probability of a single event occurring. When finding the probability of an event occurring, we will use the formula, number of favorable outcomes over the number of total outcomes. Compound events involve the probability of more than one event happening together. With compound events, we will use the same formula to calculate the probability of each event occurring. Once we find the probability of each event, we will multiply these probabilities together. And the last one was complementary events. Complementary events are events that add together to equal a whole or 1. Independent events are events that do not affect the outcome of subsequent events. In an independent event, each situation is separate from previous events. An example of an independent event would be selecting a card from a deck of cards and then returning the card to the deck. After you return the card, select another card from the same equal deck. Dependent events are just the opposite. Dependent events are events in which the previous attempts affect the outcome of subsequent events. Dependent events are just like they sound. Each event is dependent upon what happened in the previous attempt. An example of a dependent event would be selecting a card from a deck of cards and not replacing the card. Then you draw another card from the now smaller deck of cards. The probability of an event occurring is a ratio that states the likelihood of an event happening. To find the probability of a single event, you will use the ratio of the number of favorable outcomes over the number of total outcomes. Let's look at an example. What is the probability of selecting a king from a standard deck of cards? Looking at the deck of cards, we know that there are 52 cards in each deck. The number of total outcomes is 52, because we could select any of the 52 cards when choosing at random. We can also see that there are 4 kings in each deck of cards. so the number of favorable outcomes would be 4. We can see that there is a ratio of 4 to 52 chances of selecting a king at random from a deck of cards. All ratios must be in simplest form though, so 4 over 52 will be reduced to 1 over 13. The probability of selecting a king at random from a standard deck of cards is 1 over 13. Sometimes you will be asked to find the probability of more than one event occurring in consecutive order. When this occurs, you will need to multiply both probabilities together to calculate the combined probability. Let's look at an example where you'll be asked to find the probability of more than one event occurring. What is the probability of rolling a standard die and getting a 2, and then rolling again and getting another 2? To start this problem, you will need to calculate the probability of each event happening independently. The probability of rolling a 2 on a standard die can be found by using the formula, the total number of favorable outcomes over the total number of possible outcomes. On a die, there are 6 total outcomes, and only one of the outcomes is a 2. So the number of favorable outcomes is 1, and the number of total outcomes is 6. So the probability of rolling a 2 is 1 out of 6, or 1/6. Since the probability of rolling a 2 is 1 out of 6, or 1/6, the probability of rolling a 2 on the next roll would be the same. To calculate the probability of both events happening together, we will need to multiply the two probabilities together. By multiplying these two probabilities together, you get 1 over 36, or 1/36. So, the probability of rolling a die and getting a 2, then rolling a die again and getting another 2, would be 1 out of 36. Again, independent events are the events that do not affect the outcome of subsequent events. The last situation was an example of an independent event. The rolling of a die and getting a 2 did not affect the outcome of the second event of rolling the die again. Each rolling of the die is an independent event. Let's look at another example of an independent event. Jamie and Sam were having a debate and decided the best way to settle their dispute was by flipping a coin. Jamie decided to be heads and Sam decided to take tails. Jamie is now curious. What is the probability that by flipping a coin 2 times, they will receive a heads each time? To find this probability, Jamie must find out the probability of each event occurring separately. To calculate the probability, Jamie must use the formula, the number of favorable outcomes over the number of possible outcomes. Jamie knows that her coin has 2 sides, and only one of them is heads. So the probability of Jamie getting a heads on her first flip is 1 out of 2. As the boys prepare to flip a coin for the second time, they know the probability of flipping a coin and getting a heads is 1 out of 2. The probability of getting a head on the second flip is also 1 out of 2. To find the probability of these two events happening together, we need to multiply these two probabilities together. When we multiply 1/2 times 1/2, we get 1/4. Jamie now knows that the probability of flipping a coin twice and getting heads both times is 1 out of 4, or 1/4. Just the opposite of independent events, dependent events are events in which previous attempts affect the outcome of subsequent events. Dependent events are just like they sound. Each event is dependent upon what happened in the previous attempt. Let's look at an example of these dependent events. James the superb magician likes to dazzle and amaze his audience with a card trick in which he selects 2 cards at random from a deck of cards, but announces the cards that he will select prior to selecting them. James asks for an audience member to join him for the trick. Wendy, a female audience member, raises her hand to volunteer. The crowd gives her a rousing applause as she makes her way to the stage. James explains to Wendy that he will select a card at random from the deck of cards. Wendy examines the deck of cards to make sure the deck is fair. James announces that he will first draw an ace from the deck. Wendy wonders what is the probability that James will select an ace from the deck of cards. She knows that there are 4 aces out of 52 cards. James explains to Wendy that he will now select another card from the deck, and it will also be an ace. Wendy is perplexed at how James could be lucky enough to draw 2 aces in a row from the deck of cards. She thinks to herself, what is the probability of James selecting an ace and then without replacing the card selecting another ace? Wendy knows that to find the probability of him selecting an ace from the deck of cards, she will need to use the formula total number of favorable outcomes over the total number of outcomes. In the first event, the number of favorable outcomes is 4 because James was selecting one of the 4 aces. The total number of outcomes is 52 because there are 52 cards in the standard deck of cards. So Wendy knows the probability of James selecting an ace on the first draw is 4 out of 52. James turns over the first card that he selected to show it in fact was an ace. The crowd cheers with excitement. Wendy now must calculate the probability of James getting an ace on the second draw. She knows that James did not replace the card, so there are only 51 cards left in the deck. She also knows that there could only be 3 aces left, because the first card he selected was an ace. So the probability of him getting an ace on the second draw was 3 out of 51, or 3 over 51. To find the probability of James getting an ace on the first card, and then without replacing it getting an ace on the second card, Wendy needs to multiply these two events together. She will need to multiply 4 over 52 times 3 over 51. By multiplying these two probabilities together, she gets 12 over 2,652. She reduces the fraction to 1 over 221. So the probability of James selecting an ace from a deck of cards and then without replacing the card selecting another ace is 1 out of 221. Let's look at another example. What is the probability of selecting a spade from a standard deck of cards and then not replacing the card selecting an ace? By looking at this question, we know that this is a dependent event because the card is not replaced. Therefore, the first event will affect the result of the second event. To calculate the probability of both of these events occurring, we will need to find the probability of each event separately and then multiply the two probabilities together. To calculate the probability of the first event, selecting a spade from a standard deck of cards, we will use the formula total number of favorable outcomes over the total number of outcomes. In a standard deck of cards, there are 4 different suits, each containing 13 cards. So there are 13 spades in each deck of cards, which would be the number of favorable outcomes. The total number of outcomes would be the same as the number of cards in the deck, which is 52. So the probability of selecting a spade from a standard deck of cards is 13 out of 52. To make this problem easier, though, we can reduce the probability 13 over 52 to 1/4. Now let's find the probability of the second event, selecting an ace from a standard deck of cards of occurring. Remember that after the first event, the card was not replaced. This affects the number of cards that are now in our deck of cards. With one card selected, there are only 51 cards remaining in our deck of cards. So the total number of outcomes left is 51. As far as the number of favorable outcomes, one spade was selected in the first event. The card an ace of spades. Since this card was discarded, the number of favorable outcomes that we know for certain remain in our deck of cards is 3. We know that the probability of the second event occurring is 3 out of 51. And again, to make this problem easier, we can reduce that probability to 1 over 17. To calculate the probability of both events occurring in connection with each other, we need to multiply both probabilities together. So the first event of selecting a spade and then not replacing it was 1/4, and the probability of selecting an ace as the second event was 1 over 17. By multiplying these two probabilities together, we get 1 over 68 as the probability of both of these events occurring together. In this lesson, we've looked at 2 types of probabilities, independent and dependent events. Independent events are events that do not affect the outcome of subsequent events. To calculate the probability of an independent event, we use the formula total number of favorable outcomes over the total number of outcomes. Dependent events are just the opposite. Dependent events are events in which the previous attempts affect the outcome of subsequent events. The key difference is where the second event is affected by the first event. To calculate the probability of each of these events, we will use the same formula as we did for the independent event. But once you find the probability for each event, we multiply them together to find the probability of both events occurring together. Remember that to make the problem easier, we can reduce the probability if possible.
Both permutations and combinations are groups or arrangements of objects. However, there is one big difference between them. When dealing with combinations, the order of the objects is insignificant, whereas in permutations, the order of the objects makes a difference. For example, assume you have 10 coins in your pocket, and you take 5 out, a dime, 2 quarters, a nickel, and a penny. If I said you grabbed those same 5 coins, but I said you grabbed 2 quarters, a nickel, a penny, and a dime, it's still the same group of coins. That is, the order I named them in is insignificant. Therefore, the coins are a combination of 5 of 10 coins. Now, consider the scenario where we are talking about 5 finishers in a race, runners A, B, C, D, and E. If I tell you they crossed the line in the order A, B, C, D, E, this would be different than if I told you they crossed the line in the order C, B, A, E, D. Therefore, the order makes a difference. So, the order in which the 5 runners finish is a permutation of the 5 runners. There are 2 questions you have to answer before solving a permutation-combination problem. 1. Are we dealing with permutations or combinations? In other words, does order matter? And 2. Is repetition allowed? In other words, can we name an object more than once in our permutation or combination? Once we have answered these questions, we use the appropriate formula to solve the problem. Those formulas are shown here. As we can see with permutation formulas, we have the formula calculating the number of permutations of n objects with no repetitions allowed, the formula calculating the number of permutations of r objects from n objects with repetitions allowed, and the formula calculating the number of permutations of r objects from n objects with no repetitions allowed. And as we can see with combination formulas, of which there are only 2, we have a formula in which repetition isn't allowed when calculating the number of combinations of r objects chosen from n objects, and a formula in which repetition is allowed when calculating the number of combinations of r objects chosen from n objects. Don't worry if all of these different formulas are hard to remember. Take a moment to pause the video and look at each of the formulas themselves if you want. Let's look at some examples to get comfortable solving these types of problems. 1. How many distinct ways can the letters of the word friend be arranged? Solution. We will start off by determining if we're dealing with permutations or combinations. To do this, consider the arrangement friend and the arrangement DIREFN. We see that these represent 2 different arrangements, so the order of the letters makes a difference. Therefore, we can say that we're dealing with permutations. Now, we must consider if repetition is allowed. When we create an arrangement of the letters, we put one letter in the first spot, then the second spot, and so on, until all 6 spots are filled. Once we put a letter in a spot, we can't put it in another spot, because it's already been used. Therefore, repetition is not allowed. We know that we're dealing with a permutation of 6 objects, letters, where repetition is not allowed. Therefore, we use formula n factorial. We plug 6 in for n in the formula to get the following. 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1 equals 720. We see that there are 720 ways to arrange the letters in the word friend. 2. Assume you must select 3 people from a group of 20 people. How many ways are there to do this? Solution. If we select 3 people, say George, Frank, and Jessica, it's still the same group if we said we selected Frank, Jessica, and George. Therefore, order is insignificant, so we're dealing with combinations. Once we have selected a person, we can't select them again, since they are already in the group. Therefore, repetition is not allowed. Based on this information, we use the formula NCR equals n factorial divided by r factorial times n minus r factorial, where we plug in 3 for r and 20 for n. Doing so gives the following: 20 factorial divided by 3 factorial times 20 minus 3 factorial equals 20 factorial divided by 3 factorial times 17 factorial equals 20 times 19 times 18 divided by 3 times 2 times 1 equals 1,140. Therefore, there are 1,140 ways to choose 3 people from a group of 20. 3. How many 3-digit numbers can be formed from the digits 3, 7, 0, 2, and 9? Solution. Let's consider the 3-digit number 702, formed using 3 of the 5 digits. If we change the order to 207, this represents a different number. Therefore, order makes a difference. So we're dealing with permutations. Now, we can make the number 777 using the 5 given digits, because 7 is one of the digits. Therefore, repetition is allowed. We see we have a permutation of 3 objects from 5 objects, where repetition is allowed. Therefore, we use the formula n to the r, where n equals 5 and r equals 3. Plugging these values in gives 5 cubed equals 5 times 5 times 5 equals 125. Therefore, we can make 125 3-digit numbers from the numbers 3, 7, 0, 2, and 9. 4. There are 9 bikers in a bike race. In how many ways can the first 3 finishers come in? Solution. Consider bikers A, B, and C finishing in that order. Now, consider those same bikers finishing in the order C, A, B. This is a different order of finishers, so we see that order makes a difference, so we're dealing with permutations. Now, consider biker A coming in first. That biker has now finished, so the biker can't come in second, third, etc. Thus, repetition is not allowed. We are dealing with permuting 3 of 9 objects, where repetition is not allowed. Therefore, we use the formula NPR equals n factorial divided by n minus r factorial, and we plug 3 in for r and 9 in for n. 9 factorial divided by 9 minus 3 factorial equals 9 factorial divided by 6 factorial equals 9 times 8 times 7 equals 504. Therefore, there are 504 ways for the top 3 finishers to come in during a race with 9 participants. All right, let's now wrap up and take a moment or two to review. As we learned, when solving permutation and combination problems, we first ask ourselves 2 questions. First, are we dealing with permutations, or sets of numbers where order matters, or combinations, or sets of numbers where order doesn't matter? Second, is repetition allowed? Based on the answers to these questions, we use the appropriate formula to solve the problem posed, which all have their own rules. Again, please feel free to pause the video on these sets of formulas to memorize the details.
Signed numbers are also referred to as integers. Integers are the set of whole numbers and their opposites. The set of integers would include values -3, -2, -1, 0, 1, 2, and 3, etc. Sam's friends decided to surprise him with a scavenger hunt for his birthday. His friends started the scavenger hunt from the big oak tree at the park. Sam knows that his journey will begin at the oak tree, so the oak tree will represent 0 on a number line. Adding integers is the process for adding both positive and negative numbers. When adding integers, if the signs of the values are the same, you will add the 2 values. If the signs are different, subtract the 2 values. You will always keep the sign of the largest value. Back at the oak tree, Sam finds a note that tells him to take 15 steps forward and 26 steps backwards. Sam has decided to just add these 2 values. 15 steps forward would be positive 15, and 26 steps backwards would be negative 26. So Sam decides to add 15 plus negative 26. Looking at these 2 values, Sam sees that they have different signs. This means that he will subtract the 2 values. 26 minus 15 would equal 11. Since 26 is the largest value, and it's negative, the 11 would also be negative. So Sam knows that the answer to the problem is negative 11. This means that he will need to take 11 steps backwards from the tree. Subtracting integers is actually the process of adding the opposite of the stated value. To work a subtracting integer problem, you must first change the problem by changing the operation to addition and the sign of the last number to its opposite. Let's check back with Sam as he continues the scavenger hunt. Sam is now 11 paces back from the tree where he started. This number would be represented by the integer negative 11. On the ground, Sam finds a fortune cookie. Inside the fortune cookie, the directions tell Sam to subtract 8 paces from his current location. Sam knows that he needs to subtract negative 11 minus 8. Sam knows that in order to start this subtraction problem that he must change the problem to adding its opposite. To do so, Sam will change the subtraction sign to addition and the positive 8 to a negative 8. Now Sam has an adding integer problem. Since the signs are the same, he will add the two values. 11 plus 8 equals 19. The sign of the 19 would be negative since the larger value 11 was also negative. Sam knows that his next clue will be 19 paces backwards from the tree. When multiplying and dividing integers, you will need to multiply and divide as normal. The sign of your answer is determined by the sign of the values that were multiplied and divided. If the signs of your two values are the same, your answer will be positive. If the signs of your two values are different, your answer will be negative. Sam feels that the end of the scavenger hunt is getting near. As he looks up, he sees a balloon floating above him. Sam takes the balloon and pops it. Inside, he finds his final clue. The clue states that he needs to take his current location and multiply by negative 3. Sam now knows that he needs to multiply negative 19 times negative 3. 19 times 3 equals 57. Because the signs of the 19 and 3 are the same, negative, the answer to this problem will be positive. Sam knows that the prize for the scavenger hunt can be found 57 paces forward from the tree. To reach the destination of positive 57, Sam must return to the oak tree, which is represented 0. Sam now needs to go 57 paces past the oak tree in order to reach the clue. Sam sprints past the oak tree 57 paces to a set of bushes. Behind the bushes, Sam finds all his friends hiding and waiting to wish him happy birthday. Let's recap these 4 operations that we can perform with signed numbers. Adding integers is the process for adding both positive and negative numbers. When adding integers, if the signs of the values are the same, you will add the two values. If the signs of the values are different, subtract the two values. You will always keep the sign of the largest value. Subtracting integers is actually the process of adding the opposite of the stated value. To work a subtracting integer problem, you must first change the problem by changing the operation to addition and the sign of the last number to its opposite. When multiplying and dividing integers, you will need to multiply and divide as normal. The sign of your answer will be determined by the sign of the values that were being multiplied and divided. If the signs of the two values are the same, your answer will be positive. If the signs of the two values are different, your answer will be negative.
Sometimes a number is just a number, but sometimes it's carrying a small number on its shoulder, like this, 5 cubed. That 3 is an exponent. With exponents, we're taking a number and multiplying it by itself. How many? Well, that is what the exponent tells us. In this case, it's saying we want to multiply 3 5s together, or 5 times 5 times 5. Exponents can get us big numbers, but what if we see something like this? That symbol over the 27 is called a radical symbol, and it means we want to find a root of 27. The root of a number is the number that can be multiplied a certain amount of times to get us that number under the radical symbol. So roots get us to the root of a number. That little 3 in the radical means that we want to find the number that, when multiplied by itself 3 times, equals 27. If there's no number over the radical symbol, it's presumed to be a 2, which is called a square root. Let's look at examples of exponents and roots. Remember that 5 cubed? We said that's 5 times 5 times 5, so 5 cubed equals 125. Exponents make numbers explode very quickly. If we have 12 to the 4th, we want to multiply 4 12s together, or 12 times 12 times 12 times 12. The first 12 times 12 equals 144. 144 times 12 equals 1,728. 1,728 times 12 equals 20,736. So 12 to the 4th equals 20,736. What happens if the base number is negative, as in negative 3 squared? We do the same thing, but we need to include the negative sign. So this one is negative 3 times negative 3, which is positive 9. If we had negative 3 cubed, it would be negative 3 times negative 3 times negative 3. A negative times a negative is positive, but then a positive times a negative is negative. So negative 3 cubed equals negative 27. So far, we've only looked at expressions with positive exponents. What if the exponent is negative? Here's one, 4 to the negative 2. What is this asking us to do? If a positive exponent means multiplying, then a negative exponent means the opposite of multiplying, which is dividing. Really, we just can't have a negative exponent. To make it positive, we put the same expression without the negative sign as the denominator of a fraction. 1 over 4 to the 2nd is the same as 1/16. There's one other exponent situation, 2 to the 0. How can we multiply 0 2's together? We can't. But anytime you see a 0 as an exponent, know that the answer is 1. So 2 to the 0 equals 1. Why is this so? It's called the zero exponent rule. It's a bit complicated to explain, so just keep in mind that expressions with a 0 for an exponent are 1. Now that we've covered exponents, let's talk about roots. Let's start simple. This is called root 4, or the square root of 4. To simplify this, we just need to find what number times itself is 4. We know that 2 times 2 equals 4, so the square root of 4 is 2. Of course, negative 2 times negative 2 equals 4 is also true, but when using the radical symbol, we stick to the positive result. Here's another one. What's the square root of 81? We could try a few numbers to find out. 7 times 7 equals 49. 8 times 8 equals 64. 9 times 9 equals 81. There it is. The square root of 81 is 9. Remember this one? That's the cube root of 27. This time, we need the number that equals 27 when multiplied together 3 times. You can use trial and error again here. 2 times 2 times 2 equals 8. That's too small. 4 times 4 times 4 equals 64. That's too big. 3 times 3 times 3 equals 27. That's just right. So the cube root of 27 is 3. An exponent tells us how many of a number will be multiplied by itself. So if we have 8 cubed, we want to multiply 3 8s, or 8 times 8 times 8. A root is basically the opposite. We're trying to find the number that we multiply by itself a certain number of times to get the number under the radical sign.
In this video lesson, we are going to take a look at scientific notation. This is a special way to write numbers. Who uses scientific notation? If you guessed scientists, you are 100% correct. Scientists use it because it is a way to write out really large and really small numbers without having to write a whole bunch of zeros. What does it look like? You will know that you are looking at scientific notation when you see a number multiplied by 10 to a power. For example, 2.7 times 10 to the power of 3 is the number 2700 written in scientific notation. See the multiplication by 10 to a power? We'll see later how we get the number of the power. Another example is 2.7 times 10 to the power of negative 3, which is the number 0.0027 written in scientific notation. While it's easy for us to write and read 2700 and 0.0027, when we get to much larger numbers, scientific notation makes it much easier to write them. For example, instead of writing 1988000000000000000000000000, We could just write 1.988 times 10 to the power of 30. Doesn't that look much neater? This really large number is actually the mass of the Sun in kilograms. It's quite easy to convert our regular numbers into scientific notation. Let's convert the number 3,400,000 into scientific notation. First, we write out the first few non-zero digits and place a decimal after the first digit. We have 3.4. Now, we're going to count how many digits there are after the 3. We have 6. This tells us that our power is 6. So we finish off by writing 3.4 times 10 to the power of 6. This tells us that we have a total of 6 digits after the 3. We would add zeros until we have a total of 6 digits after the decimal. If our number is smaller than 1, our scientific notation will have a negative exponent. Let's convert the number 0.00041 into scientific notation. This time, instead of taking the first few non-zero digits, we are now taking the last few non-zero digits and placing a decimal after the first non-zero digit. We have 4.1. Now we count the number of digits away from our beginning decimal. We get 4. So this tells us that our power is -4. Our scientific notation then is 4.1 times 10 to the -4. Another way you can remember whether the power is positive or negative is by the direction you need to move the decimal point. If you need to move it to the left, then your power is positive. If you need to move it to the right, then your power is negative. Let's look at a couple more examples. Convert 6,800,000,000 into scientific notation. We begin by writing our first few non-zero digits with a decimal point after the first digit. We get 6.8. Now we count how many digits we have to move our beginning decimal point to get to the 6.8 spot. We have to move the decimal to the left, so our power is positive. We count 9 spaces, so our power is 9. Our scientific notation then is 6.8 times 10 to the 9th power. Convert 0.000056 into scientific notation. This time, our number is smaller than 1. So we write the last few non-zero digits and place a decimal point after the first non-zero digit. We get 5.6. Again, we count how many digits we have to move the decimal to get to the 5.6 location. We have to move the decimal to the right, so our power will be negative. We count 6 spaces, so our power is -6. Our scientific notation then is 5.6 times 10 to the -6. Let's review what we've learned. We learned that scientific notation is a special way scientists use to write very large and very small numbers. You will see some non-zero digits with a decimal place after the first digit multiplied by 10 to a certain power. This power tells you how many digits to move the decimal to get to your number. To convert any number into scientific notation, you write the non-zero digits, placing a decimal after the first non-zero digit. Then you count the number of digits you need to move the beginning decimal to get where your decimal is now. If you move the decimal to the left, then your power is positive. If you move the decimal to the right, then your power is negative.
In math, there is a particular order that we work problems. Without this order, it is possible that we could all get different answers. The order that we use to simplify expressions in math is called the order of operations. The order of operations is the order in which we add, subtract, multiply, or divide to solve a problem. The steps that we use to solve any mathematical expression are: Step 1. Simplify all of the parentheses. This includes all forms of grouping symbols, such as brackets and braces, in addition to parentheses. Step 2. Simplify all exponents. Step 3. Simplify all multiplication and division from left to right. When simplifying the multiplication and division, work from left to right. Step 4. Simplify all addition and subtraction from left to right. Again, when simplifying the addition and subtraction, work from left to right. By following this order, we can all solve problems and get the same solution. All of those rules can be a little overwhelming. However, I do have a shortcut to help remember these steps. It is called PEMDAS. It stands for P parenthesis, E exponents, M multiplication, and D division from left to right, A addition, and S subtraction from left to right. Remember that the step for multiplication and division is one step. We work all of the multiplication and division in one step from left to right. Multiplication does not always come before division. They're worked in the order they appear. This is also true for addition and subtraction. They're worked in the same step from left to right. An easy way for me to remember these steps is to remember the phrase, "Please excuse my dear Aunt Sally." P parenthesis, please. E exponents, excuse. M multiplication, my. D division, dear. A addition, aunt. S subtraction, Sally. Let's look at an example of how to apply these ordered rules. The problem is 3 plus 6 times 11 plus 1 minus 4 divided by 8 times 2. Remember, to work this problem, we will follow the order of operations. Let's think PEMDAS. The first step to solve this problem is to work the P or parenthesis. In this problem, they used both parentheses and brackets. We will need to start inside the parenthesis and work out until we complete all of the grouping symbols. Also, when working inside the grouping symbols, we must follow the remaining order. To begin, we will need to add the 11 plus 1 and then subtract the 4, which is 8. We still must now work inside the bracket. 6 times 8 is 48. The next letter in our acronym is E for exponents. Since there are no exponents, we continue on. The next step is to simplify the MD, multiplication and division, from left to right. Since division comes first from left to right, we will first divide 48 divided by 8, which is 6. There is still multiplication in our problem, so next we will multiply 6 times 2, which equals 12. The only step left is the AS, addition and subtraction. There's only one thing left in this problem, which is 3 plus 12, and it equals 15. So, as you can see, the answer to this problem would be 15. Let's do another problem together. Let's solve 20 minus 4 plus 5 squared over 5. Step 1, check for any parentheses, and there are none, so we can go to step 2. Step 2, exponents are next, and we have an exponent in 5 squared, which simplifies to 25. This changes the problem to look like 20 minus 4 plus 25 over 5. Step 3, the next step is to simplify the M and the D, multiplication and division, from left to right. The only multiplication or division in the problem is 25 over 5, so we will do that now. 25 over 5 is 5. The problem now looks like 20 minus 4 plus 5. Step 4. Now we only have A and S left. We should work through addition and subtraction from left to right, in whichever order they appear. 20 minus 4 equals 16. The problem simplifies to 16 plus 5, and this gives us our final answer of 21. As the old adage goes, practice makes perfect. So let's look at another example problem and solve it. The next problem is 6 minus 5 times 2 squared over 3 plus 7. Step 1. We have work to do inside two sets of parentheses. The numerator parenthesis has subtraction and multiplication. PEMDAS tells us to do the multiplication first. This gives us 6 minus 10 squared. Now we can subtract these values, giving us minus 4 squared, which is 16. This is our numerator. The denominator parenthesis is addition, which results in 10. The problem now simplifies to 16 divided by 10, which is 1.6. Since we're getting so good at this, we'll do one more problem to show off our new skills. The new problem is 16 minus 4 times 2 plus 3 over 17 minus 4 squared times 32. Step 1. Do we see parentheses? Yes. Let's solve that first. Inside the parenthesis is 4 squared, which is 16. Finishing the math inside the parenthesis gives us 17 minus 16 equals 1. The problem now looks like 16 minus 4 times 2 plus 3 over 1 times 32. Step 2. No exponents exist anymore, so we can go to step 3. Step 3. The next step is to perform multiplication and division in whatever order they appear from left to right. We have minus 4 times 2, which is minus 8. This makes the problem look like 16 minus 8 plus 3 over 1 times 32. Going from left to right, we then have 3 over 1, which is 3. This makes the problem look like 16 minus 8 plus 3 times 32. Finally, we have 3 times 32, which is 96, so the problem looks like 16 minus 8 plus 96. Step 4. The last step using A and S is to add or subtract from left to right. First, 16 minus 8 gives 8, so the problem becomes 8 plus 96, which gives us a final answer of 104. Now, let's review what we've learned. The order of operations is the order in which we add, subtract, multiply, or divide to solve a problem. The steps that we use to solve any mathematical expression are: Step 1. Simplify all of the parentheses. This includes all form of grouping symbols such as brackets, braces, and parentheses. Step 2. Simplify all exponents. Step 3. Simplify all multiplication and division from left to right. When simplifying the multiplication and division, work from left to right. Step 4. Simplify all addition and subtraction from left to right. Again, when simplifying the addition and subtraction, work from left to right. A helpful way to remember this order is "Please excuse my dear Aunt Sally," which stands for P parenthesis, E exponents, M multiplication, D division, A addition, S subtraction. Remember that multiplication and division are included in the same step and simplified from left to right, and this is also the same for addition and subtraction.
In this video lesson, we will talk about rational numbers. These are the numbers that can be written as the fraction of two integers. Recall that integers are your whole numbers, and they can either be positive or negative. Integers are not decimal numbers, but rational numbers can be decimal numbers, since 3/2 equals 1.5. Think of rational numbers as taking a number of people and sharing a number of things such as donuts or burgers with them equally. Both numbers have to be integers. We end up dividing what we are sharing with the number of people. For example, 3/2 can be 2 people sharing 3 burgers. Each person would get 1.5 burgers. What we are going to do to these rational numbers is to take their absolute value, or the distance the number is away from 0. In math, the symbol for absolute value is 2 pipes or straight lines on either side of our number. So the absolute value of 2 is written like this. The absolute value of 3/2 is written like this. I've given you the technical definition of absolute value. In problems, it is much easier to remember your absolute value as simply the positive version of your number. For example, the absolute value of -2 is 2. The absolute value of -3/2 is 3/2. Yes, basically what the absolute value symbol does is just delete your negative symbol. -11 becomes 11. -5/6 becomes 5/6. Looking at the number line, the absolute value is the distance away from 0. We can see that 5/6 is 5/6 away from 0. -3/2 is 3/2 away from 0. Distance is always positive, so absolute value is also always positive. While you may come across absolute values of just one rational number, you may also see problems where you have a mini problem inside the absolute value. When you see this, do the problem first, and then find the absolute value of the mini problem's answer. Think to yourself, how far away from 0 is the answer to the mini problem? For example, say you have the problem the absolute value of 5/4 minus 7/4. You would first do the subtraction of 5/4 minus 7/4. You get -2/4 as your answer, which simplifies to -1/2. Now that we've finished the problem inside the absolute value, we can take the absolute value of our answer, -1/2, which is 1/2. So our answer is 1/2. Let's review what we've learned. Rational numbers are the numbers that can be written as the fraction of two integers, and that absolute value is the distance a number is away from 0. If we look at a number line, the absolute value is the distance any number on the number line is away from 0. Distance is always positive. An easy way to remember absolute value is simply the positive version of any number. If there is a mini problem inside the absolute value, we first solve the mini problem before finding the absolute value of the answer.
Do you ever have trouble putting what you want to say into words? Maybe you're trying to explain something and it's like you're speaking in another language that the other person can't understand. I think this is how my high school chemistry teacher felt while teaching me. Or maybe you're trying to tell someone you like them, or like them, but he or she just isn't hearing you. It's frustrating, I know. Or, I've heard. Life would sometimes be simpler if we could just use math to speak for us all the time. Fortunately, there are endless real-life situations we can express using algebra. We just need a few tools. First, of course, are numbers. This is math, after all. We also need variables. A variable is a symbol that represents an unknown number. Then we'll need some operators, like addition and division. With these tools, we can say all kinds of things with ease. We use the tools to build algebraic expressions. An algebraic expression is a mathematical phrase that may include numbers, variables, and operators. It's basically like a sentence, but you're substituting these numbers, variables, and operators for words. Algebraic expressions can look like x plus 1, 17y, 4a minus 3, or q over 6. The most common and useful application of this idea is in solving word problems. We need to take the real situations that are in regular language in the problem and translate them into algebraic language to better understand them. These can involve several different types of operations. Let's start with addition and subtraction expressions. Here's one. There are two competing lemonade stands run by siblings April and Mike. We want to describe the relationship between the prices for a cup of lemonade between the two stands. April is selling her lemonade for 50 cents less than Mike's. What do? First, we need a variable for the cost of April's lemonade. Let's call that A. We use that in place of a number we don't know. Now, if Mike's lemonade is 50 cents more than April's, we can describe his as A plus 50. That A plus 50 describes the cost of Mike's lemonade relative to the cost of April's. We can test our expression by substituting a number for our variable. Let's say A equals 75 cents. A plus 50 equals $1.25. Is $1.25 50 cents more than 75 cents? Yes, so we know we have the correct expression. We could also use subtraction here. We could use M as the cost of Mike's lemonade. Since April's is 50 cents less than Mike's, hers would be M minus 50. Again, we could test this. Let's say M equals 80 cents. So M minus 50 equals 30 cents. Is 30 50 cents less than 80? It is. It's also a very cheap cup of lemonade. Next, let's look at multiplication. Let's say it's the holiday season and you're buying gifts for your siblings. Since you live in an algebra problem, let's say you have 15 siblings. That's a lot, so you have to keep these gifts small. Let's say you can spend $D on each gift. How do you describe the total cost of the gifts? We could add them together and say D plus D plus D plus, 15 total Ds. It would be simpler to just say 15 times D, or 15D. That's the cost of one gift times 15. So if you spend $10 per gift, you'd spend 15 times 10, which is $150. Here's one that involves division. Let's say you're working with a study group. You all get hungry and order some pizza. There are 3 of you. If everyone's going to get the same amount, how much pizza can you eat? Well, you don't know how many slices there will be, so let's use S to stand in for the total number of slices. Since there are 3 of you, each of you gets S divided by 3 slices. That's the total number of slices divided by 3. If there were 9 slices, you'd get 9 divided by 3, or 3 slices each. So far, all of our expressions use just one variable. But life isn't always that simple. Let's say you're going on a date. It's dinner and a movie. You want to express how much this date will cost. Entrees cost E, and movie tickets cost T. How do you write this? Well, there are 2 of you, so 2 entrees will be 2E. And supposing your date doesn't bail on you before the movie, you'll need 2 tickets, or 2T. The total cost is 2E plus 2T. Sometimes we need to mix operators as well as variables. Don't worry, you can handle this. Let's say you don't have 1 date this week, but 3. How do you show that? Just take our expression, 2E plus 2T, and multiply the whole thing by 3. So 3 times 2E plus 2T. In summary, an algebraic expression is a mathematical phrase that may include numbers, variables, and operators. We use variables in place of the numbers we don't know. Then, using our operators, we explain the relationship between different values. If you've ever played a sport, you know the importance of practice. No track star just shows up at a meet and expects to run a record-breaking 100 meters without training. And the more challenging the concept, the more practice you need. If you ever watch professional football, you know that even with an incredible amount of practice, athletes can still make mistakes sometimes. A receiver may forget a route, or a punt returner may drop the ball. But we know we can get better at whatever we're trying to accomplish with practice. What's true in sports is also true in algebra. Simplifying algebraic expressions can be as tricky as mastering a play in football. Fortunately, when we practice algebra, we're unlikely to get knocked to the ground, unless you're playing full contact algebra. But let's not do that here. Here, we're going to practice simplifying algebraic expressions. Simplifying algebraic expressions is more or less defined by its title. It involves distributing terms across parentheses and combining like terms in order to make an expression simpler. By simpler, we usually mean shorter, or more condensed. Why is this useful? Algebraic expressions can get cumbersome with all their various bits and pieces. Think of it like food. What if every time you wanted a cookie, you had to ask for it by its parts? Flour, sugar, butter, eggs, etc., as opposed to just saying, I want a cookie. That would be tedious, and it would interfere with your cookie eating. When we simplify an expression, we're combining what we can, so we're just dealing with cookies, not the things that make up cookies. There are two main skills involved in simplifying algebraic expressions. First, there's combining like terms. This is the process of simplifying expressions by joining terms that have the same variable. So if you have x plus 2x, you can combine them to get 3x. If you have 5x squared plus 3x squared plus 9x, you can only combine the 5x squared and 3x squared, since they are the only terms that share the same exponent. But we can still make that expression simpler by saying 8x squared plus 9x. Second, there's a distributive property. This helpful law tells us that a times b plus c equals a times b plus a times c. So let's say we have 7 times x plus 2y. Since they're not like terms, we can't add that x and 2y. But the distributive property tells us we can distribute the 7 across the parentheses, giving us 7x plus 14y. Okay, time for some practice. Let's start simple. 2y plus 4y plus 9. How can we simplify this? Well, we have two like terms, 2y and 4y. Both of these terms have the same exponent, y. Let's combine them to get 6y plus 9. Can we go any further? No, the 6y and 9 don't share an exponent, so that's as far as we can simplify this one. Here's a good one, 9 plus 3t minus 5. In this one, all we can combine are the 9 and the minus 5. So our final expression is 4 plus 3t. That's it. Those first two were a good warm-up. Let's try a longer one. What if we have 3x squared plus 4x plus x squared plus 2 plus 11x? A good first step is to get like terms next to each other. What are our like terms? 4x and 11x both have an x. What about 3x squared and x squared? They are like terms as well. If we move things around, we get 3x squared plus x squared plus 4x plus 11x plus 2. Now we just need to combine the like terms. We add 3x squared and x squared to get 4x squared. Then we combine 4x and 11x to get 15x. So our simplified expression is 4x squared plus 15x plus 2. That's much better. Up to this point, we've only dealt with one variable. That's kind of like flag football. Let's jump to the NFL by using 2. 9m plus 8n plus 3mn plus 4m minus 2mn plus n. It's a little trickier with multiple variables, isn't it? But let's do the same thing we did before, moving like terms next to each other. There are two terms with just one m, 9m and 4m. Then there are two with one n, 8n and n. What else? Those two with an mn, they're like terms too. So with a little shuffling, we have 9m plus 4m plus 8n plus n plus 3mn minus 2mn. 9m plus 4m is 13m. 8n plus n is 9n. And 3mn minus 2mn is just mn. That gives us 13m plus 9n plus mn. Let's do one with some serious exponent work. 5 times x squared times y cubed. First, let's handle that 5 cubed. That's 125. And what do you do with an exponent raised to an exponent? you multiply them together. So that x squared to the third will be x to the sixth. And the y will just become y cubed. So our simplified expression is 125 times x to the sixth times y to the third. Okay, here's one that involves the distributive property. 4ab plus a times 3b plus b squared. Remember, we can distribute that a across the parentheses. That gets us 4ab plus 3ab plus ab squared. And do we have any like terms? 4ab and 3ab. Combine those to get 7ab plus ab squared. That's as far as we can take this one. It's like in a chocolate chip cookie. The flour, eggs, and whatnot just become cookie dough. But the chocolate chips, represented here by the ab squared, are still chocolate chips. They're just tastier when baked into cookies. I think we're ready for a bigger challenge. 6x times x plus 2y plus 3y times 2x minus y plus 4 times x squared plus y squared. Okay, lots to do here. First, note that nothing inside the parentheses can be simplified. They all involve addition or subtraction with different variables. So let's use the distributive property and distribute the terms outside the parentheses. First, 6x times x is 6x squared. 6x times 2y is 12xy. Next, 3y times 2x is 6xy, and 3y times negative y is negative 3y squared. Then, 4 times x squared is 4x squared, and 4 times y squared is 4y squared. That gives us 6x squared plus 12xy plus 6xy minus 3y squared plus 4x squared plus 4y squared. Let's do some shuffling and get 6x squared plus 4x squared minus 3y squared plus 4y squared plus 12xy plus 6xy. 6x squared plus 4x squared is 10x squared. Negative 3y squared plus 4y squared is just positive y squared. Then 12xy plus 6xy is 18xy. Okay, that means our final simplified expression is 10x squared plus y squared plus 18xy. That's much simpler than where we started. Cookie metaphor or not, I think we've earned a treat. In this lesson, we practiced simplifying algebraic expressions. We became experts at combining like terms and utilizing the distributive property. With these methods, we made long, complicated expressions much simpler and easier to understand. We also talked football and cookies, because all things should involve exercise and baked goods.
A rational equation is an equation that contains fractions with x's in the numerator, denominator, or both. Here's an example of a rational equation. 4 over x plus 1 minus 3 over x minus 1 equals negative 2 over x squared minus 1. Let's think back for a moment about solving an equation with a fraction. 1/3 x equals 8. We think of the 3 in the denominator as being a prisoner, and we want to release it. To set the 3 free, we multiply both sides of the equation by 3. Think of it as 3 letting both sides of the equation know he's leaving. 3 times 1/3 x equals 8 times 3. This process freed our denominator and got rid of the fraction. X equals 24. It is also the process we use to solve rational equations with one extra step. In rational equations, sometimes our solution may look good, but they carry a virus. That is, they won't work in our equation. These are called extraneous solutions. The steps to solve a rational equation are: find the common denominator, multiply everything by the common denominator, simplify, check the answer or answers to make sure there isn't an extraneous solution. Let's solve a couple together. Example number 1. Solve. Remember to check for extraneous solutions. 3 over x plus 3 plus 4 over x minus 2 equals 2 over x plus 3. Our first step is to figure out the terms that need to be released from the denominators. I look at 3 over x plus 3. I write down x plus 3 as one of my common denominators. I look at 4 over x minus 2. I write down x minus 2 as another part of my common denominator. I look at 2 over x plus 3. Since I already have x plus 3 written in my denominator, I don't need to duplicate it. Next, we multiply everything by our common denominator, x plus 3 times x minus 2. This is how that will look. 3 times x plus 3 times x minus 2 over x plus 3, 4 times x plus 3 times x minus 2 over x minus 2 equals 2 times x plus 3 times x minus 2 divided by x plus 3. It isn't easy for the denominators to be released. There is a battle, and like terms in the numerator and denominator get canceled or slashed. Slash or cancel all of the x plus 3's and x minus 2's in the denominator and numerator. Our new equation looks like 3 times x minus 2 plus 4 times x plus 3 equals 2 times x minus 2. Distribute to simplify. 3x minus 6 plus 4x plus 12 equals 2x minus 4. Collect like terms and solve. 3x plus 4x is 7x. Negative 6 plus 12 is 6. We end up with 7x plus 6 equals 2x minus 4. Subtract 2x from both sides. 7x minus 2x equals 5x. Subtracting from the other side just cancels out the 2x, and we get 5x plus 6 equals negative 4. Subtract 6 from both sides. Negative 4 minus 6 equals negative 10. Again, subtracting 6 will cancel out the positive 6, so we end up with 5x equals negative 10. Divide by 5 on both sides, and we cancel out the 5 and give us x equals negative 2. It turns out x equals negative 2. The reason we check our answers is that sometimes we get a virus, or, in math terms, extraneous solutions. To check, I replace all of the x's with negative 2. 3 over negative 2 plus 3 plus 4 over negative 2 minus 2 equals 2 over negative 2 plus 3. Let's simplify. 3 over 1 plus 4 over negative 4 equals 2 over 1. Since 3 plus negative 1 equals 2 is true, x equals negative 2 is the solution. Example number 2. Solve. Remember to check for extraneous solutions. 4 over x plus 1 minus 3 over x minus 1 equals negative 2 over x squared minus 1. First, we need to release our denominators. To release our denominators, we write down every denominator we see. I have found the easiest way to do this is to first factor if needed, then list the factors. X squared minus 1 equals x plus 1 times x minus 1. Our new equation looks like this. 4 over x plus 1 minus 3 over x minus 1 equals negative 2 over x plus 1 times x minus 1. I look at 4 over x plus 1. I write down x plus 1 as one of my common denominators. I look at 3 over x minus 1. I write down x minus 1 as another part of my common denominator. I look at negative 2 over x plus 1 times x minus 1. Since I already have those written in my denominator, I don't need to duplicate them. So my common denominator turns out to be x plus 1 times x minus 1. Catherine, why aren't we using the factors of x squared minus 1? Great question. We already have x plus 1 and x minus 1 being released. We don't need to do it twice. Now, we multiply each part of the equation by the common denominator, x plus 1 times x minus 1. Think of this as the key to the prison. 4 times x plus 1 times x minus 1 over x plus 1 minus 3 times x plus 1 times x minus 1 over x minus 1 equals negative 2 times x plus 1 times x minus 1 over x plus 1 times x minus 1. It isn't easy for the denominators to be released. There is a battle, and like terms get canceled or slashed. Slash or cancel all of the x plus 1's and x minus 1's in the denominator and numerator. This leaves us with 4 times x minus 1 minus 3 times x plus 1 equals negative 2. Now we need to solve for x. Distribute 4 into x minus 1 and negative 3 into x plus 1. 4x minus 4 minus 3x minus 3 equals negative 2. Collect like terms. X minus 7 equals negative 2. Add 7 to both sides of the equal sign. X equals 5. It looks like our answer is 5, but we need to double check. I replace all of the x's with 5 and simplify. It turns out 5 works, and it is the solution to our equation. And so our solution checks. The steps to solving a rational equation are: find the common denominator, multiply everything by the common denominator, simplify, check the answer or answers to make sure there isn't an extraneous solution.
In this lesson, we will talk about how coefficients and variables combine together to form different things. Your coefficients are your numbers multiplied with an unknown value. Your variables are your letters representing an unknown value. So why do you need to know this information? This information is important because understanding these combinations will help you to solve your math problems more easily. Once you know what you are working with and the kind of combination that you have, you are in a better position to use the proper techniques to solve that particular combination. However, we're not going to discuss these problem-solving techniques in this lesson. Let's take a look at a couple of possible combinations: monomials and polynomials. The first we will look at are monomials. Monomials are a combination of coefficient and variables that is just one term. A term includes just a coefficient multiplied by a variable or variables. You will not have anything else being added to it, subtracted from it, or divided from it. For example, 4x, 3x squared, 8y, and 14s to the power of 8 are all monomials. It is okay for your variables to include an exponent. This exponent simply tells you how many of that variable you have. So, the x squared tells you that you have 2 x's. The s to the power of 8 tells you that you have 8 s's. It is also possible to have a monomial with several variables like these: 7x to the power of 6, y to the power of 4z, a cubed, b squared c. If we see a monomial with just variables, the coefficient in this case is a 1. Now let's talk about polynomials. Polynomials are more than one monomial connected together via addition or subtraction. Each monomial is referred to as a term of the polynomial. We have a particular way of writing polynomials. The standard form of writing polynomials involves ordering the terms so that the variable with the highest exponent is written first, and then the other terms are written in decreasing order based on the exponent. Many times, the terms of a polynomial will have the same variable included in them. These are all examples of polynomials written in standard form. 3x squared plus 4x plus 9. 10t to the 4th power plus 7t squared minus 91t. Notice how each of these polynomials all share the same variable in each term. In the first polynomial, you might have noticed that the single 9 without a variable. Because all the other terms have an x as a variable, we can actually say that this 9 also has an x variable. However, this x variable connected with the 9 has an exponent of 0. So, what happens when our exponent is 0? Our value is 1. Therefore, x to the power of 0 is equal to 1. What is 9 times 1? 9. That is why we don't write out the variable if our variable has an exponent of 0. It is very possible for a polynomial to consist of more than one variable. In this case, we choose a variable and use that to order our variables, starting out with the term that includes the variable to the highest exponent. 10x to the power of 8, y cubed plus 8x to the power of 7 minus 2x to the power of 5, y squared plus xy. In this polynomial, we chose the x variable to order our terms by. We started out with a term that includes a variable to the highest exponent. In this case, the x in our first term has an exponent of 8. The next term's x variable has an exponent of 7, and then our x variable exponent keeps decreasing after that in order. We can actually say that a monomial is a special kind of polynomial with just one term. Our polynomials and monomials also have a degree connected with them. The degree of a term is the sum of the exponents. Because our monomial has just one term, the degree of the monomial is just that of the term. If our term or monomial has just one variable, then the exponent of that variable is the degree. If our variable doesn't have an exponent written, the degree is 1, so 9x has a degree of 1. If there is no variable, the degree is 0, so 10 has a degree of 0 since there is no variable. If our term has more than one variable, then the degree is the sum of the exponents of the variables. So 8x squared y has a degree of 3, 2 from the x and 1 from the y. The degree of a polynomial is the highest degree of its terms. Each term of a polynomial has its own degree. The largest degree of these terms is the degree of the polynomial. So 3x squared plus 4x plus 9 has a degree of 2 because that is the highest degree of all the terms. The polynomial 10x to the power of 8, y cubed plus 8x to the power of 7 minus 2x to the power of 5 y squared plus xy has a degree of 11 because that is the highest degree of any of the terms. Let's review what we've learned. Coefficients are your numbers multiplied with an unknown value. Variables are your letters representing an unknown value. Monomials are a combination of a coefficient and variables that is one term. A term includes just a coefficient multiplied by a variable or variables. Polynomials are more than one monomial connected together via addition or subtracted. Polynomials are written ordered so that the variable with the highest exponent is written first, and then the other terms are written in decreasing order according to their exponents. The degree of a term is the sum of the exponents. In the case when a term has no variable, the degree is 0, whereas the degree is 1 when the variable has no exponent. The degree of a polynomial is the highest degree of its terms.
Adding polynomials is very easy. There are many ways to add polynomials that have been taught, but here's my favorite. I look at the problem and put a circle, square, or triangle around the like terms so I don't get them confused. Let's look at this example. 2x squared plus 3x plus 4 plus x squared minus 5x plus 7. I like to start from the left. I circle 2x squared. Now I look for another term to 2x squared. Of course, that's x squared, so I circle it. Then I add them. 2x squared plus x squared is 3x squared, and then I write that down as part of my answer. The next term is 3x. I put a square around that one. Then look for another one. Of course, we have negative 5x, so I put a square around that one too. Then we add them. 3x plus negative 5x is negative 2x, and I write that down as the next part of my answer. You always want to double check that there aren't any more. Finally, we have 4. I continue the same idea, but I put a triangle around it. Now I look for another like term to 4. Of course, that's 7, so I put a triangle around that one. Then I add them. 4 plus 7 is 11, and I write that down as the last part of my answer. It's always good to double check that you have everything in a circle, square, or triangle. When you get longer polynomials, it's easy to miss terms. So here's my final answer, 3x squared minus 2x plus 11. Okay, Catherine, do I have to use circles, squares, and triangles? No. If you're good at adding polynomials, you can cross off as you go. But for those that haven't had enough practice, this is definitely my suggestion. Catherine, what about problems that have more terms? What other shapes or ideas do you have? Great question. You can use different colors to circle like terms. I don't use it here for the benefit of students who are colorblind. But you could have used red to circle the x squareds, blue to circle the x's, and green for the numbers. I have also used the method of underlining like terms too. Whatever you choose is how you will distinguish the different terms. In subtraction, let me show you the underlining method. 3x squared minus 2x plus 5 minus 2x squared minus 6x plus 7. First, I'm going to distribute the negative 1 into the second expression. That will make this an addition problem. The first expression stays the same, 3x squared minus 2x plus 5. We will distribute the negative like this. Negative 1 times 2x squared, which is negative 2x squared. Negative 1 times negative 6, which is positive 6x. And negative 1 times 7, which is negative 7. This gives us our new subtraction problem. 3x squared minus 2x plus 5 plus negative 2x squared plus 6x minus 7. Remember, I'm going to show you the method of underlining instead of circling to add the expressions. We look at the first term, 3x squared, and underline it. Now I continue to look for a like term. Here it is, negative 2x squared, and I underline it. Now I add them. 3x squared plus negative 2x squared, and we get x squared. That's going to be the first term of our answer. The second term is negative 2x, and this time I put a squiggly line under it. Now I continue to look for a like term. Here it is, 6x, and I put a squiggly line under that one. I add negative 2x plus 6x, and I get 4x. That's the second term in our answer. The last term is 5, and this time I'm going to put a jagged line under it. Now I continue to look for a like term. Here it is, negative 7, and I underline it. Now I add them, 5 plus negative 7, and we get negative 2. This will be the last term in my answer. X squared plus 4x minus 2. Now we get to multiplication. This problem won't quite work like addition or subtraction, and we can't use FOIL because these are larger than a binomial times a binomial. First, multiply the first term in the product, x, times everything in the second expression. I like to draw arrows to remind me which multiplication I have done. Otherwise, I tend to get lost. This is how it'll look. X times x squared plus x times 3x plus x times negative 2. Let's multiply. X times x squared is x to the third, plus x times 3x is 3x squared, plus x times negative 2 is negative 2x. This isn't our final answer. You need to multiply everything in the second expression by 5. So we'll have 5 times x squared plus 5 times 3x plus 5 times negative 2. Are you ready for the final answer? We simply add the like terms together. X third plus 3x squared minus 2x plus 5x squared plus 15x minus 10. Start from the left and circle x to the third. It looks like there aren't any like terms for x to the third, so we write that down as our final answer. Put a square around 3x squared. I look and find 5x squared, so I put a square around that term too. I don't see any more, so 3x squared plus 5x squared is 8x squared. 8x squared is written next to x to the third as part of our final answer. Put a triangle around negative 2x. I look and find 15x, so I put a triangle around that term too. Why? Well, they're like terms. I don't see any more like terms for negative x. So, negative 2x plus 15x is 13x. 13x is part of our final answer, and I'm going to write it next to 8x squared. Finally, I see negative 10. I underline this term and look for another one like it. I don't see one, so negative 10 is written in my final answer. So, what is the final answer then? X to the third plus 8x squared plus 13x minus 10. Adding. No trick here. Just add like terms together. If you get lost at first, use circles, squares, triangles, lines, anything to separate the different terms. Subtraction. Multiply the second expression by negative 1 and add the two expressions together. Multiplication. Multiply each term in the first expression by each term in the second expression. Add like terms together, and you're done!
We've looked at some basic polynomial long division and synthetic division. Now, let's have a look at a couple more complicated problems. They work exactly the same, except we have larger divisors, or parts of the dividend are missing. Here's our first. X to the third minus 9 divided by x squared plus 3. Did you notice that we don't have an x squared or an x term in the dividend? We need to put something in as a place marker. Whenever we have a missing term, we will put in 0 as their coefficients. For example, in this problem, we will have x to the third plus 0 times x squared plus 0x minus 9. Why zeros? Because anything multiplied by 0 is 0, so we aren't adding anything to the problem. To fill in our long division, we now have x to the third plus 0 times x squared plus 0x minus 9 as the dividend, so it goes under the long division symbol. The divisor is x squared plus 3. Do you notice it's also missing a term? Just like the dividend, we need to put in a place marker. So, x squared plus 0x plus 3 goes to the outside in the front of the long division symbol. Now we're ready to start the division. The steps are the same every time. It's easier to show and talk about the steps than just listing them. To find the first term of the quotient, we take the first terms from the divisor and dividend and then divide them. X third divided by x squared. I like to write them as a fraction. It's easier to divide or reduce that way. X to the third over x squared equals x. X is the first term of the quotient, so we'll write it above the long division symbol. To figure out what we will subtract from the dividend, we multiply x times the divisor. X squared plus 0x plus 3. X times x squared plus 0x plus 3 equals x to the third plus 0x squared plus 3x. X to the third plus 0x squared plus 3x is written under the dividend matching like terms. Here's where I like to make life easy. To subtract the polynomials, I just change the signs of its terms and then add. X to the third plus negative x to the third equals 0. 0 times x squared plus negative 0 times x squared equals 0. 0 times x plus negative 3x equals negative 3x. Just like we did in long division, we bring down the next term, which is 9. Now we have a predicament. X squared doesn't go into negative 3x minus 9. So this turns out to be our remainder. What's our answer then? X plus negative 3x minus 9 divided by x squared plus 3. There isn't a need to put 0x as part of the denominator in the remainder. This one is almost ready for synthetic division. The divisor is a first-degree binomial with a leading coefficient of 1. Place the coefficients of the dividend under the symbol, just like in long division, but do not write the variables. Make sure to leave space in between each number. You don't want to get them confused. Wait, did you write it as you see it? Oh no. The dividend and divisor must be in descending order. So what does that mean? We need to list the terms from the largest exponent to the smallest. Even if we are missing one, we need to put it in as a place marker. So now we have 2 times x to the third plus 0 times x squared minus 14x plus 10, all divided by x plus 3. Next, look at x plus 3. We write negative 3 to the left of the long division symbol. Remember, you always take the opposite of what you see in the divisor. Now we are ready to start synthetic division. Our first step is to bring down the leading coefficient 2. Multiply negative 3 times 2 and place the result underneath the next coefficient 0. So we have negative 6 written underneath the 0. Add 0 plus negative 6 and write that next to the leading coefficient 2. Multiply negative 3 times negative 6 and place the result underneath the next coefficient, negative 14. So we have 18 written under the negative 14. Add negative 14 plus 18 and write the sum of 4 next to the negative 6. Multiply negative 3 times 4 and place the result underneath the next coefficient, 10. So we have negative 12 written underneath the 10. Add 10 plus negative 12 and write the sum of negative 2 next to the 4. Here is our final answer with the remainder. How do I know there's a remainder? Because our last term is not a 0. But what is the answer going to look like? In synthetic division, the degree of the final polynomial answer is 1 less than the dividend polynomial. Since 2 times x to the third plus 10 minus 14x is degree 3, our answer will be degree 2. Starting from the left, we will have 2 times x squared minus 6x plus 4 with a remainder of negative 2. The remainder will be written the same as if we had done this problem as long division, a fraction. So our answer will look like 2 times x squared minus 6x plus 4 plus, open parentheses, negative 2 over x plus 3, close parentheses. Here's our next example. 6 times y to the third plus 7 times y to the second minus 5y plus 5 divided by 3y minus 1. To fill in our long division, 6 times y to the third plus 7 times y to the second minus 5y plus 5 is the dividend, so it goes under the long division symbol. 3y minus 1 is the divisor, so it goes to the outside in the front of the long division symbol. Now we're ready to start the division. To find the first term of the quotient, we take the first terms from the divisor and dividend and divide them. 6 times y to the third over 3y. I like to write them as a fraction. It's easier to divide. 6 times y to the third over 3y equals 2 times y to the second. 2 times y to the second is the first term of the quotient. We write it above the long division symbol. To figure out what we will subtract from the dividend, we multiply 2 times y to the second times the divisor, 3y minus 1. 6 times y to the third minus 2 times y squared is written under the dividend, matching like terms. To subtract the polynomials, I just change the sign of the terms and add. 6 times y to the third minus 6 times y to the third equals 0. And 7 times y squared plus 2 times y squared equals 9 times y squared. Just like what we did in long division, we bring down the next term, which is negative 5y. Guess what? We do the same exact step. To find the next term of the quotient, we take the new first terms and divide them. 9 times y squared over 3y. I like to write them as a fraction. 9 times y squared over 3y equals 3y. 3y is the next term of the quotient. Remember, that gets written next to the 2 times y squared above the long division symbol. To figure out what we will subtract from the dividend, we multiply 3y times the divisor, 3y minus 1. 3y times 3y minus 1 equals 9 times y squared minus 3y. 9 times y squared plus 3y is written under the dividend, matching like terms. To subtract the polynomials, I just change the signs of the terms and add. 9 times y squared minus 9 times y squared equals 0. Negative 5y plus 3y equals negative 2y. Just like we did in long division, we bring down the next term, which is positive 5. You'll notice that the dividend is now negative 2y plus 5. When we divide to find the next term of the quotient, we take the new first terms and divide them. Negative 2y over 3y. Do you see that we end up with a fraction, negative 2 over 3? Well, we don't like fractions in the quotient except as a remainder, so negative 2y plus 5 turns out to be our remainder. This is what the final answer will look like. 2 times y squared plus 3y plus negative 2y plus 5 divided by 3y minus 1. Before we end this video, let's review when to use long division and when to use synthetic. My students really like synthetic, but it isn't right for every division problem. How do I know the difference? Any division problem that has a divisor as 1-degree binomial is perfect for synthetic division. That's why we used it on 2 times x to the third plus 10 minus 14x over x plus 3. X plus 3 as a 1-degree binomial with a leading coefficient of 1. Okay, it is true that we can use synthetic division with a divisor that does not have a leading coefficient of 1, but that'll give us a fraction. Fractions are messy and students tend to make more mistakes when using them, so keep to a 1-degree binomial with a leading coefficient of 1. Any other division problem needs to be done using long division. That's why we used it on 6 times y to the third plus 7 times y squared minus 5y plus 5 over 3y minus 1, and x to the third minus 9 over x squared plus 3. One final rule to keep in mind as you do polynomial division: always make sure your polynomials are in the descending order, largest exponent to smallest. If you are missing a term, put in a 0 to hold that place, like we did in example number 1.
In algebra, being able to factor polynomial expressions, expressions made of terms that are the product of variables and a number, is an essential skill. It's like us. To grow up, we need to learn how to walk. In algebra, to grow in our skills, we need to know how to factor. Factoring is about breaking up our polynomial into its parts. Just like we are made up of our body parts, such as our arms and legs, so our polynomials are made up of its factors. Also, just like there are different exercises we can do to stretch each muscle, so we have different factoring methods depending on the kind of polynomial we are looking at. Examples of polynomials include 2x plus 4, x squared plus 3x plus 2, and x to the fifth plus 2x squared. The first method we will look at is the quadratic method for factoring polynomials that are quadratics and whose first coefficient is 1. These are the polynomials whose highest degree, or exponent, is a 2. So a polynomial, such as x squared plus 3x plus 2, is an example of a quadratic whose first coefficient is 1. Notice the highest exponent of 2 that we have, and the coefficient of 1 for the x squared term. Quadratic polynomials are made up of two factors, and by using this quadratic method, we can find them if they are there. Not all quadratic polynomials factor nicely into their two parts. If they do, then this method will find what they are. To use this method, you first identify your three numbers, your three coefficients. Because quadratics have a general algebraic form of ax squared plus bx plus c, we are looking for the values of a, b, and c. Our first value, a, is 1, and we look for two numbers that multiply to the c value and add to the b value. In our example, our a is 1, our b is 3, and our c is 2. So we ask, what two numbers multiply together to make 2 and add together to get 3? Isn't it 1 and 2? 1 times 2 is 2, and 1 plus 2 is 3. So x squared plus 3x plus 2 factors into x plus 2 times x plus 1. Do you see how we have written our numbers 1 and 2? That is how you factor a quadratic polynomial where the first coefficient number, a, is 1. Now remember, your quadratic polynomial does not necessarily need all three terms. It could have just two terms and you may still be able to use this method. If you can't find two numbers that fit, then you may have to use another method. The second method we will look at is the greatest common factor method. This works for any kind of polynomial if all the terms in the polynomial have a common factor. For example, we can use this method for the polynomial x to the fifth plus x to the third because all the terms of this polynomial have the common factor of x to the third. I can divide each term by x to the third. If I do that, x to the fifth plus x to the third factors into x to the third times x squared plus 1. Notice how I've written what I've divided each term by on the outside of the parentheses, and I wrote what I got after dividing each term inside the parentheses. This is how you factor using this method. A third method you can use is the grouping method if your polynomial has 4 terms. We can use this method to factor a polynomial such as x cubed plus 2x squared plus 2x plus 4. To use this method, we group our 4 terms into groups of 2, like this: x cubed plus 2x squared plus 2x plus 4. We then use the greatest common factor method to factor each set of parentheses. The greatest common factor in the first set of parentheses is x squared, and the greatest common factor in the second is 2. We rewrite our polynomial as x squared times x plus 2 plus 2 times x plus 2. Notice how we now have two compound terms, x squared times x plus 2 and 2 times x plus 2, where each has a common factor of x plus 2. We can now repeat the greatest common factor method and factor out the x plus 2. We get x plus 2 times x squared plus 2, and we are done. If we see a polynomial in one of the forms above and we can't use the particular method mentioned above, then that means that the polynomial can't be factored. If we liken factoring a polynomial to stretching a muscle, then that means there are no exercises to strengthen that particular polynomial. The muscles of that polynomial are way too tight to stretch. What have we learned? We've learned that polynomial expressions are expressions made of terms that are the product of variables and a number. Just like there are different exercises to stretch different body parts, so there are different methods of factoring for different kinds of polynomials. Here is a summary of the different methods we learned in this video lesson. Quadratic, x squared plus 3x plus 2. You look for two numbers that multiply to give you the last number and add to the middle number. This polynomial factors into x plus 1 times x plus 2. Greatest common factor method. X to the fifth plus x to the third. Look for a common factor that you can divide each term by. This polynomial factors into x to the third times x squared plus 1. And the grouping method. X cubed plus 2x squared plus 2x plus 4. You group into pairs of two terms, and then use the greatest common factor method for each grouping, and then repeat the greatest common factor method for the two remaining compound terms.
In math, we get all kinds of numerical expressions. We can have ones with just numbers and ones with variables. We have ones with one variable and ones with lots of variables. We have simple ones and not so simple ones. We have some without denominators and some with. In this video lesson, we are going to be looking at the ones with variables and a denominator. It is only with denominators where you might end up with a point that is undefined. What does undefined mean? Undefined means there is no answer to the expression at that point. Think of it as the value where you end with more question marks at the end. How do we know when a numerical expression is undefined? It is when the denominator equals 0. When we have a denominator that equals 0, we end up with division by 0. We can't divide by 0 in math, so we end up with an expression that we can't solve. We end up with more question marks. Most calculators will tell you that you cannot divide by 0. Try it on your computer calculator and see. There is no answer to a problem when you have division by 0. But if you are able to find the points where you have division by 0, then you can say that this numerical expression is valid except at these points. So, how do we find the points where a numerical expression is undefined? We do this by solving our numerical expression's denominator for 0. What we do is set the denominator equal to 0 and solve. The numbers that we get for our answer are the points where our numerical expression is undefined. Let's look at an example to see how this is done. We want to find the points where this numerical expression is undefined. 2x squared plus 3x minus 2 divided by x minus 7. We first notice that this numerical expression has a denominator. So, we might have some points where this expression is undefined. How do we find out what these points are? We set the denominator equal to 0 and solve. We get x minus 7 equals 0. Solving for x gives us x equals 7. This tells us that at the point x equals 7, our expression is undefined because we will be getting division by 0. We can say that this expression is valid for all points except x equals 7. We can use this process for any numerical expression with variables and a denominator. Let's review what we've learned now. We learned that a numerical expression is undefined when there is no answer, or when you get division by 0. We might get division by 0 for those numerical expressions with variables and a denominator. To find the points where the numerical expression is undefined, we set the denominator equal to 0 and solve. Once we find the points where the denominator equals 0, we can say that our numerical expression is valid for all numbers except the numbers where it is undefined. We would list the numbers that we found.
Many equations in algebra require you to perform multiple steps to solve for a particular variable. What this means is that you will need to perform more than one operation to solve the equation. This involves combining either addition or subtraction with either multiplication or division. Don't worry, it's not as difficult as it may sound. There's actually a method to solving these types of equations, and it's quite simple. Let's try solving one right now to see how easy it can be. Let's solve the equation 4x plus 3x minus 7 equals 0. What do we do first? First, we simplify our equation by combining like terms. When we simplify our equation, we make sure that our equation is in its simplest form, which will save us time and make our work easier as we go on solving. We look at all our terms and notice that 4x and 3x are our like terms. The negative 7 is by itself with no other like terms, so we go ahead and combine the 4x and 3x by adding. Notice that when I look at the terms, if I notice a minus sign in front, then I keep that sign with my term so that I know that the term is a negative term. So, I combine my 4x and 3x to get 7x. I can now rewrite my equation with my combined like terms to get 7x minus 7 equals 0. Next, we locate our variable. I see it being multiplied by the 7. Now you need to look for any addition or subtraction of numbers that is only happening on the same side as the side with our variable. If you see one of these operations, then you know that you need to move the number that is being added or subtracted. To do this, you perform the opposite operation. So if you see addition, subtract. If you see subtraction, add. I see a subtraction going on, so I'm going to add. What is being subtracted? A 7 is being subtracted, so that tells me I need to add a 7. Remember in algebra that to keep the equation the same, what you do to one side of an equation, you also must do the same to the other side. So if I add 7 to one side, I need to add a 7 to the other side as well. So I get 7x minus 7 plus 7 equals 0 plus 7, which turns into 7x equals 7. Why do we do addition and subtraction of numbers first? We do addition and subtraction first because this gets us closer to isolating our variable. What we are trying to do is get closer and closer to our variable. We are working our way in to our variable. If we view our variable as being hidden inside a stack of boxes, we can view the addition and subtraction as opening the outermost box to get to our variable. Next, we look to see if the variable is being multiplied or divided by anything. You can view this as opening the box that the variable is in. How do we do this? We do this the same way we did for the addition or subtraction. We do the opposite operation. So if we see multiplication, we will divide. If we see division, then we will multiply. What do we see in our equation? We see our variable being multiplied by a 7. So what do? We divide by 7 on both sides. Doing this, we get 7x divided by 7 equals 7 divided by 7, which turns into x equals 1. We are done, and 1 is our answer. That wasn't so bad, was it? Let's try another. Let's try solving 9x plus 1 minus 1 equals 9. What is our first step? It is to simplify our equation. The 1 and negative 1 are like terms, so we can combine those. The 9 is by itself, since it is on the other side of the equation, and nothing else is on that side. If there were other numbers on that side, then the 9 would have other like terms with which we could combine it. So combining the 1 and negative 1 gives us 0, and our equation becomes 9x equals 9. Next, we identify or locate our variable. It is being multiplied by the 9. Now I look to see if there is any addition or subtraction of numbers on the same side as our variable. I don't see any. Next, I look to see if the variable is being multiplied or divided by anything. I see the variable is being multiplied by 9. So I do the opposite operation and divide by 9 on both sides of the equation. Doing this, I get 9x divided by 9 equals 9 divided by 9, which turns into x equals 1, and I am done. My answer is 1. What have we learned? We've learned that solving equations that require multiple steps is not so hard. It starts with simplifying our equation, which means combining like terms. We then locate our variable. If there is any addition or subtraction of numbers on the same side as our variable, then we do the opposite operation to those numbers so that they move to the other side of the equation. This means if we see addition, then we subtract. If we see subtraction, then we add. We finish by seeing if the variable is being multiplied or divided by anything. If it is, then we perform the opposite operation again to isolate our variable. If there is multiplication, we divide. If there is division, we multiply. In this video lesson, we are going to learn how to solve multi-step algebra word problems. These are problems written in English that require you to perform several operations to find the answer. I know, word problems are the worst thing ever, but keep watching and see whether or not you will find them easier to work with once you've learned what is in this video. We begin with a problem. See, there is this concert coming up that I really want to go to. The tickets cost $200. That's just for one ticket. Anyways, I'm not complaining about the price, just saying it's expensive. My problem is I want to bring some of my friends with me, but I can only bring so many. I want to know how many friends I can bring with me. The amount of money I have to spend comes from working 20 hours at a job that pays $20 per hour. Can you help me figure this out? Our first step to solve this problem is to really understand the problem and what we need to solve for. So after carefully reading the problem and understanding its meaning, we highlight the important parts of the problem. We see that the tickets are $200 each. I work 20 hours at a job paying $20 per hour. And I want to know how many friends I can bring. Those are my important parts of the problem. Everything else I can ignore. Now that I have highlighted the important parts, we can label them with appropriate math symbols. I first want to label what I'm supposed to solve for. I ask myself, what is the problem asking for? After looking over the highlighted important parts of the problem, I see that the problem is asking for the number of friends that can come. I place an X next to that part to tell me that this is what I want to solve for. I can label the 20 hours worked with the words hours worked, and the $20 per hour with the words pay per hour. Now we need to think about how all this information goes together to help us find the answer. We want to find the number of friends that can come. In order to do that, we need to find out how much money we have to spend. To find the amount of money we have to spend, we need to find out how much money is earned after working the 20 hours. How do we do that? We need to multiply the hours worked with the pay per hour. Once we have the amount of money we can spend, we then can split it into groups of $200 to see how many tickets can be purchased with that amount. One of the tickets will be for me, and the rest will be for the friends. The number of extra tickets is what we are looking for. We know how all the information is tied together now, and what we need to do with the information. We can now write our mathematical equation. Sometimes, we may even need to write several smaller equations to get us our answer. What was the first thing we needed to find out? We needed to find out how much money we earned after working 20 hours. What did we say we needed to do to find that out? We needed to multiply the hours worked with the pay per hour. So our equation here is this. Money earned equals 20 times $20. Next, we take our money earned and split it into groups of 200 to see how many total tickets we can purchase. What operation would we need to do that? Isn't it division? Yes, we divide our money earned by 200 to see how many tickets we can purchase. Number of tickets is equal to money earned divided by 200. But I'm not just looking for the number of tickets, I'm looking for how many friends I can invite. So what do I need to do to the number of tickets? I need to subtract 1 from it to account for my ticket. Number of friends equals number of tickets minus 1. Now that I have all my equations written down, I can go ahead and solve them. I take it one equation at a time, starting with the first. Why the first? I can't solve the second or third equation without the information from the first. So solving the first equation gives me money earned, $400. This $400 is the money earned, and I see that I need that bit of information for my second equation. Plugging in this information into my second equation, I get number of tickets equals $400 divided by $200, which equals 2. I see that after working 20 hours, I can purchase 2 tickets. Now, my final step is to solve the third equation for this equation. I need to know the number of tickets I can purchase. I already found this information, so I can plug that into the equation and solve. Number of friends is equal to 2 minus 1, which is equal to 1. Cool, I have enough money to take one friend with me. My last equation is solved, and I have finished solving my problem. My answer is 1. What have we learned? We've learned multi-step algebra word problems are problems written in English that require you to perform several operations to find the answer. To solve them, we need to first carefully read the problem. We highlight the important parts of the problem and ignore the rest. We then label those important parts with symbols or other math labels. Then, we think about how all the information ties together and what operations will help us answer our problem. We label the answer that we are looking for with an X and the other parts with appropriate labels so that we know what they are referring to. After everything is labeled and we have figured out how everything ties in together, we then write our equations to show how they are related to each other. Then we go ahead and solve the equations. As you can see from our example, sometimes we can end up with several smaller equations that lead us to the answer. What do you think? Are you more confident about solving word problems now?
You are visiting John today, who works for a computer company. John has invited you to a dinner at a restaurant and then games at his house when he's done at work. You're excited for the night to begin, so you ask John how much longer he needs to work. He tells you, oh, less than 2 hours. Since John also likes math a lot, he writes what he has said out on paper in math speak. He writes, X is less than 2 hours. This is a linear inequality, a linear mathematical statement with inequality signs instead of equal signs. So you wait for John to finish his work. John likes to play games to work the brain, so he now tells you that it will take 40 minus X is greater than 10 minutes to get to the restaurant where you guys are going to have dinner. You have a confused look on your face, so John tells you that if you want to find out how many minutes that really is, you'll need to solve that problem for the variable X. How do you solve these types of problems? Well, you want to get the X by itself, and you want the X to be positive. So you need to perform some operations to make this happen. How do you know what operations to do? Well, first you look to see if there is any addition or subtraction going on. If there is, then you go ahead and perform the opposite operation to move things around so that your X becomes positive and is by itself. So if you see addition, you perform subtraction, and vice versa. Second, you look to see if there is any multiplication or division connected with the variable. If there is, you perform the opposite operation to get the X by itself. So, if there is multiplication, you divide, and vice versa. In this video lesson, we are covering only those linear inequalities that require just 2 steps to solve. Usually this involves performing either addition or subtraction, and then following it up with either multiplication or division. Let's take a look at solving the problem 40 minus X is greater than 10. This step requires 2 steps. First, we see that a 40 is being added to our variable. We can subtract the 40 from both sides of our linear inequality. We get 40 minus X minus 40 is greater than 10 minus 40, which turns into negative X is greater than negative 30. Now, we see that there is a negative 1 being multiplied with the X. This tells us that we now need to divide by a negative 1 on both sides of our inequality. We get negative X divided by negative 1 is greater than negative 30 divided by negative 1, which turns into x is less than 30. It's important to note that if we multiply or divide by a negative number, then our inequality sign flips. See how we began with a greater than and ended up with a less than? So what does this answer tell you? It tells you that it will take less than 30 minutes to get to the restaurant. You're getting hungry, so that works out well. On the way to the restaurant, John gives you 2 more problems to do just for the fun of it. He tells you it's good for your brain, that it keeps your brain young. The first problem he gives you is this: 3x minus 2 is less than 10. You see that the x is being multiplied by 3, and a 2 is being subtracted from it. Since you are looking for addition or subtraction going on first, you tackle the 2 first. To make it go away, you need to add the 2 to both sides of this inequality. You get 3x minus 2 plus 2 is less than 10 plus 2, which becomes 3x is less than 12. Then you tackle any multiplication or division. There is multiplication by 3, so you divide by 3 on both sides of the inequality. You get 3x divided by 3 is less than 12 divided by 3, which becomes x is less than 4. John smiles, so that means you got the right answer. John gives you another one. X divided by negative 4 plus 1 is greater than 8. Here you see that the x is being divided by a negative 4, and a 1 is being added to it. You tackle the 1 first. You need to subtract 1 from both sides of the inequality first. You get x divided by negative 4 plus 1 minus 1 is greater than 8 minus 1, which becomes x divided by negative 4 is greater than 7. Now you can tackle the negative 4. Since this is division, you go ahead and multiply the negative 4 to both sides of the inequality. You get x divided by negative 4 times negative 4 is greater than 7 times negative 4, which becomes x is less than negative 28. Yes, you remember to flip the inequality sign since you are multiplying by a negative number. John gives you a big smile. You got this one right too. Yay! And you guys have arrived at the restaurant. John says since you get all those answers right, he is going to pay for you, so go ahead and order whatever you want. Let's review what we've learned. A linear inequality is a linear mathematical statement with inequality signs instead of equal signs. In this video lesson, we look at how to solve those linear inequalities that require only 2 steps to solve. To solve these types of problems, you first look to see if there is any number that is being added or subtracted from the variable. If there is, you perform the opposite operation to move the number over and away from the variable. If you see subtraction, you add, and vice versa. Next, you look to see if there is any multiplication or division going on with the variable. If there is, you again perform the opposite operation. If you see multiplication, you divide, and vice versa. If you are multiplying or dividing by a negative number, then you need to make sure that you flip your inequality sign.
Math sentences are also considered word problems because they are a mixture of numbers and words to put together. Your job is to understand the words and then turn them into a math problem that you can easily solve. This is the goal of this video lesson. We want to be able to take a math sentence, a sentence made up of numbers and words, and turn it into math symbols we can easily understand and solve algebraically. This particular lesson will focus on inequalities. Usually in algebra, our goal is to find some unknown number. We will see how this plays out in our math sentences. I know you are getting worried about word problems, but you don't have to be afraid of them. Just keep watching and you will see that they are not so bad. The key is in knowing how to translate some key words or phrases into math symbols, as well as understanding the math behind the words. So let's get started. We are talking about inequalities, so first I want to tell you the key phrases to look for that signal inequalities. We only have 4 phrases to look for. one phrase for each inequality symbol. We have the greater than symbol, the less than symbol, the greater than or equal to symbol, and the less than or equal to symbol. And yes, you are right, the key phrases we are looking for are simply the names of our symbols. If we are talking about the greater than symbol, then we will see the phrase greater than. And if we are talking about the less than symbol, we will see the phrase less than. Now let's see how these words work inside some real math sentences. We have a math sentence that says the number of donuts that Chris has eaten is greater than 10. Our job here is to translate this into math symbols. What do? We first identify the important parts. Our important parts are the number of donuts eaten by Chris, the number 10, and the phrase greater than. We can label the number of donuts eaten by Chris with an X because that is our unknown number. We can label our phrase greater than with our greater than symbol. Our 10 we will leave as 10. Now we can write our math sentence using math symbols. X is greater than 10. We can do a mental check to see if what we've written is the same as our math sentence. What we wrote down tells us that Chris is eating more than 10 donuts. Is this what our original sentence is also telling us? It is, so we are right. Let's see another sentence. The number of baby bunnies plus 5 is greater than or equal to 12. Our job here is to translate our math sentence into math symbols, and if we need to solve the problem the best we can. We begin by identifying our important parts and labeling them accordingly. We have the number of baby bunnies, which we will label X. We have the word plus, which we will label plus. Our numbers 5 and 12 stay as they are. The phrase greater than or equal to we will label with its corresponding symbol. So we have this. X plus 5 is greater than or equal to 12. We see that we can solve it a bit more by subtracting the 5 from both sides to get our variable by itself. Doing that, we get x is greater than or equal to 7, and that is our answer. Now let's look at a problem using the less than or equal to symbols. See if you can translate these on your own as we go along. A number of donuts less 5 is less than 10. Here we have a number of donuts which we will label x. The word less I will label with minus. The 5 and 10 stay as they are. The phrase less than is labeled with the less than symbol. Now I have my math sentence of x minus 5 is less than 10. I can solve this a bit more for my x by adding 5 to both sides. Doing that, I get x is less than 15 for my final answer. Let's look at one more problem. 100 cars is less than or equal to the number of trucks in Susie's garage. We keep our 100 as it is. The phrase less than or equal to is labeled with its corresponding symbol. The number of trucks in Susie's garage is labeled with X. Our math sentence becomes 100 less than or equal to X, and we are done. What have we learned now? We've learned that a math sentence is a sentence made up of numbers and words. To translate our math sentence into inequalities, we look for the key words greater than, less than, greater than or equal to, and less than or equal to. We match these with their corresponding symbols, other words such as less or plus. We match with their corresponding subtraction and addition symbols. We label our unknown number with a variable such as x. Once we have translated our math sentence, we see if we can solve it further to get the variable by itself. Once our variable is by itself, we are done.
You just passed level 1 of Furious Fowls, the game that asks you to launch birds across the screen to get back at those pesky pigs that stole your eggs. You learned that we could figure out where our bird would hit the ground by solving the given quadratic equation where it equals 0. That required us to factor the equation and then use the zero product property to determine which two values would give us 0. But now we're on to level 2. It's going to get harder, but your goal will still be the same. Use the equation given to you on the screen to make sure that your bird will hit its target on the first try. Alright, so here we go. Let's go ahead and make a guess at where we'll need to launch our bird this time. Well, I think this looks about right. Now let's check our equation to see if this will actually work out or not. So the game tells us that our bird will fly in a parabola given by the equation y equals negative x squared plus 4x plus 7. Since we're again shooting for a pig on the ground, we're curious where this equation equals 0. So let's go ahead and substitute that in. Okay, now we need to try to factor in order to find x. Let's divide out the negative, leaving us with this. And now look for a pair of numbers that have a product of negative 7 and a sum of negative 4. This isn't looking good. I don't think this trinomial can be factored. So what now? In level 1, this worked every time, so we never had to do anything else. Looks like we're going to have to learn some new skills. Situations just like this, where we're trying to solve a quadratic that is unfactorable, is what the quadratic formula was made for. It's a little long and messy, but if you can remember it, you'll be able to solve any quadratic equation out there. You'll have to first remember the standard form of a quadratic equation, y equals ax squared plus bx plus c. This will tell you what your a, b, and c values are, but then it simply becomes a matter of putting the numbers into the right spots. Let's see if we can successfully do this to pass the second level of furious vowels. Going back to the original equation and identifying a, b, and c should be our first step. A is in front of the x squared, where there's only a negative symbol. That means that a is just negative 1. B is the number in front of the x's, which makes it 4, and c is the constant on the end, 7. Now we can substitute these values into the quadratic formula and evaluate the resulting expression to find our answers. While this is theoretically pretty straightforward, there are quite a few spots that can easily trip you up. Because this is our first time, let's evaluate this one step by step together and go over some of the common mistakes. We're going to have to remember our order of operations and make sure we also keep track of all our negative signs. For this problem then, the first thing we'll have to take care of is the exponent we see. The exponent I see is a 2, which means a square, which means multiply that number by itself. So we do 4 times 4 to get 16. Next in order of operations will come multiplication. Doing the multiplication on the inside of the square root, 4 times negative 1 times 7 gives us negative 28. Then doing the multiplication on the bottom of the fraction, 2 times negative 1, is simply negative 2. We're now left with this, and we're going to focus on this inside of the square root in the top of the fraction. The inside of the square root in the formula is b squared minus 4ac. And this part is one of the hardest parts to evaluate, one of the easiest parts to make a mistake on. And it also has a special name. It's called the discriminant. It has some important features that we'll talk about in other lessons, but for this lesson, you just need to know to be careful when evaluating it, specifically for the reason I'm about to mention. Notice that we ended up with a negative 28 after we did the multiplication, but I still have 16 minus negative 28. Minus a negative is plus a positive, so 16 plus 28 gives us 44. Now that we have the square root of 44, we'd like to check to see if we can take the square root of 44 nicely. Is there a number that multiplied by itself gives us 44? Well, 7 times 7 is 49, which is pretty close, but not quite. And 6 times 6 is 36, so again, not quite. So the square root of 44 is an irrational number. It's going to be a really long decimal. That means that what we have is actually a pretty good answer. But there are 2 mistakes that students tend to make without realizing that this is an okay answer. One of those mistakes is to divide the negative 4 by the negative 2 to get this. This is not allowed because the plus root 44 kind of gets in the way of you doing that division. Another mistake is to divide the negative 4 and the 44 by the negative 2 to give us this. The problem with this is that dividing inside a square root like that isn't really allowed. That means that what we have here is actually the most mathematically correct answer. But since we're estimating, let's change it to a decimal by rounding the answers off. The square root of 44 is in between 6 and 7. It's actually about 6.633. That means we'll find our two answers by doing negative 4 plus 6.633 divided by negative 2, and also negative 4 minus 6.633 divided by negative 2. Doing that gives us our two estimated answers as negative 1.316 or 5.316. Our negative 1.316 answer is what would happen if the slingshot broke, so we're not too worried about that one. But over at 5.316, it looks like we're pretty close to our target, but maybe a little short. Maybe if we leveled out our shot a little bit, our bird might fly a little further. Maybe like this. Okay, apparently now our equation is y equals negative 3x squared plus 15x plus 29. But again, we want to know when the bird will hit the ground, or what the roots of the equation are. That means we substitute in y equals 0 and begin thinking about which way we want to solve. We could try the factoring method here, but those numbers seem pretty messy, and there's also a good chance it won't work anyways, so let's go straight into the quadratic formula. This means identifying a, b, and c from our standard form quadratic. That makes a negative 3, b 15, and c 29. Now it's just a matter of carefully substituting these values into the quadratic formula and then following the order of operations to come up with our two answers. Substituting the numbers in will look like this. One other common mistake I see students make is to mess up the b value in the front left of the fraction. In the formula, it's a negative b. So in this case, 15 turns into negative 15. But oftentimes your b value itself will be negative. When you have a negative b and you plug it into the formula, negative b will turn out positive again, so you got to be careful with that b in front. Anyways, moving on to evaluating. We can start with the exponent on the inside, the b squared part of the discriminant, and 15 squared gives us 225. Next, we do 4 times negative 3 times 29 to get negative 348. And we do 2 times negative 3 to get negative 6 on the bottom. Again, changing a minus a negative and 2 plus a positive will make our discriminant equal to 573. The square root of 573 is about 23.937. Doing negative 15 plus this and divided by negative 6 will give us negative 1.489. And doing negative 15 minus this divided by negative 6 will give us 6.489. We can again focus on the positive answer, even though the negative one is a valid mathematical solution, and it looks like this one's going to work. I'm feeling pretty confident. Let's let our furious fowl fly, and hey-o, we got it. You've now passed level 2 of Furious Fowls and are getting pretty good at solving quadratics. But are you ready for level 3? Let's quickly review what we learned from level 2. Not every quadratic equation is factorable, so we need another way to solve them. Enter the quadratic formula. Using a, b, and c from the standard form quadratic, we substitute these values into the formula and then use the order of operations to end up with our two answers. Welcome to Level 1 of Furious Fowls, the game that puts you in control of the birds that are trying to get their eggs back from those pesky pigs. Can you launch your bird at the exact right angle to make sure your bird gets a direct hit? We're about to find out. The only difference from Furious Fowls and other games out there that are similar is that you only get one shot to make your hit, so it better be worth it. But because you only get one shot, we will give you a hint to help you out to make sure your first shot is always a direct hit. What kind of a hint am I talking about? Let's check out level 1. So here we go. Our bird's all set in our slingshot, ready to go, and our pig is waiting very smugly over there, thinking it's safe. But we want to make sure we get him. I can try to eyeball it by swinging my bird up and down here, and notice that as I swing it in different directions, the mathematical equation in the corner of the screen is changing. It's going to be your job to use that mathematical equation to make sure that your one shot hits its target. Let's go ahead and try to line up a shot. Maybe like this. That looks about right. The game has told us that if we fire at this angle, our bird will fly in a path that follows the quadratic equation y equals negative x squared plus 6x plus 16, where y is the height of the bird and x is the distance it has traveled. Since we're trying to hit a pig that's sitting on the ground, we're curious when our bird will hit the ground, which is where y equals 0. Substituting this value in gives us this equation. This equation is asking us the question, how far will our bird go before it hits the ground? We normally solve equations by using inverse operations to get the variable by itself. But in this case, we'd run into some problems with that strategy. Because there are x's, but also x squareds in this equation, there isn't just one variable we can get by itself. This means we need a new strategy for solving quadratic equations. While there are a few different ways to do this, the most basic is through factoring. While this way won't always work, it is probably the easiest way to do it, so knowing how to is really helpful. Factoring the quadratic will change it from standard form into intercept form, which will tell us exactly where the parabola crosses the x-axis, where its x-intercepts are, or in this problem, where the bird hits the ground. To factor a quadratic, it's really nice not having a negative x squared term, so let's divide that part out first. Pulling a negative from each term leaves us with this equation instead. Now we can begin to look for the two numbers that have a product of negative 16 and a sum of negative 6. The reason we're doing that is all about factoring. So if you're struggling with factoring, probably should go back and check out a previous lesson to get the basics. Finding the pair of numbers that satisfy these two equations will be easiest if we write out the different factors of 16 and look for the pair of them that can add or subtract the negative 6. Doing that makes it look like 2 and negative 8 are our winners. Therefore, we can rewrite our equation as this. But why did we do that? How has that gotten us any closer to solving this equation for x? I still have two of them. I can't get one of them by themselves. Well, what we now have is a product that equals 0. And this allows us to use what is called the zero product property, which says that any time a product equals 0, at least one of the things we are multiplying must be 0. Another way of saying that is this. The only way to multiply two things and end up with 0 is by having one of the two things from the beginning be 0 itself. What this allows us to do is split the equation up and say that either x minus 8 or x plus 2 is equal to 0. Now that the x's are separated, we can again use inverse operations to solve for them. Undoing minus 8 and plus 2 tells us that the two places where our bird will hit the ground are at x equals negative 2 or x equals positive 8. Well, in our game here, that negative 2 answer might happen if the slingshot broke, but we're more concerned with the answer of 8. And it looks like now, if our bird flies out to 8, it's going to go right over the pig we're trying to hit. So making this shot would be a waste of our bird. But if we slightly adjust it, maybe aiming up a little bit so that our bird flies higher in the air but doesn't go as far, we are told it will now fly the path of this parabola. Y equals negative 2x squared plus 11x plus 21. Let's see if this is what we want it to. We'll again substitute in y equals 0 in order to find out when our bird will hit the ground, and then factor the quadratic to separate the x's and allow us to use the zero product property. We again begin by taking out the negative in order to help us factor, leaving us with this. We then need to find a pair of numbers whose product is now negative 42, the first term times the last term, and again whose sum adds up to negative 11. Writing out the factors of 42 and comparing the pairs of numbers makes it appear that 3 and negative 14 are our winners. But since we have a 2 in front of our x squared term, we'll need to use the area method to figure out exactly how this all factors. Putting the two values we just found in one diagonal of our box as coefficients on x's, with the 2x squared and the negative 21 in the other diagonal, allows us to work our way to the outside and find our factored expression. We do this by finding the greatest common factor in each row and column. In the far left column, both terms have a 2 and an x. In the right column, both terms have a 3. In the top row, both terms only share an x, and in the bottom row, both terms share a negative 7. This makes the factored form of 2x squared minus 11x minus 21 the same as 2x plus 3 times x minus 7. Again, for more help on factoring, check out the previous video. Now that we've factored the quadratic, we can use the zero product property to split up the x's and say that either 2x plus 3 equals 0 or x minus 7 equals 0. A few quick inverse operations later tells us that our bird will hit the ground at either 7 or negative 3 halves. Our negative 3 halves answer doesn't concern us too much, but it looks like having our bird land at 7 is exactly what we want. We can fire this bird feeling confident that we'll hit it on our first try and pass level 1. Congratulations! You've just passed level 1 of Furious Fowls. You can now move on to level 2, where things are going to get a little bit harder. Before you do that, though, let's quickly review what we've learned from level 1. If you are trying to find when an object launched in the air will hit the ground, you must set the quadratic equation equal to 0 and solve it. Solving quadratic equations with only inverse operations won't work because there are x's and x squareds. What we need is a way to break them up first. One way to do this is with factoring and then using the zero product property. This allows you to set up two separate equations that can be solved with inverse operations to get our two separate answers.
In this lesson, we'll talk about points on the coordinate plane. The coordinate plane is a two-dimensional surface with an x-axis and a y-axis. Why do we need to learn about points on the coordinate plane? This is an important topic to learn because we see these points in many applications. Not only will we see them in our math class, but we will also see these in use in real-world applications such as on maps. Our coordinate plane looks like this. We have our x-axis as the horizontal line and our y-axis as the vertical line. Where the x-axis and the y-axis intersect is the very center of the graph. As we move to the right, the values on the x-axis get higher. As we move to the left, the values on the x-axis get smaller. As we move up, the values on the y-axis get higher. And as we move down, the values on the y-axis get smaller. When we write down points on our coordinate plane, we call it an ordered pair because we have two numbers. We need the two numbers to tell us where the point is on the coordinate plane. The first number tells us where it is on the x-axis, and the second number tells us where it is on the y-axis. The very middle of the coordinate plane is the point 0, 0. The first number tells us that this point is located where the x-axis is equal to 0, and the second number tells us the y-axis value for this point is also at 0. The point 3, 4 is located 3 spaces to the right of the center and 4 spaces up. This is where the x-axis value is 3 and the y-axis value is 4. If we were given a point to plot on the coordinate plane, we would look at the first number to see where on the x-axis our point is located, and then we would look at the second number to get the exact location of the point. The second number tells us the y-axis value of the point. Only one point can have the same x and y-axis value. For example, if we were told to plot the point 1, 3, we would first look at the first number, the 1. We would find on the coordinate plane the x-axis is equal to 1. This would be 1 space to the right of the center. Then we would look at the second number. This number tells us that our point is also located 3 spaces up from the center. So our point is located 1 space to the right of the center and 3 spaces up. Let's look at another example. Plot the point -1, -3 on the coordinate plane. This problem has us plotting a point with negative numbers. Looking at our coordinate plane, we see that our values are negative when we are to the left and down of the center. The first number is -1, so we are 1 space to the left of the center. The second number is -3, so we are also 3 spaces down from the center. And we are done. Let's review what we've learned. The coordinate plane is a two-dimensional surface with an x-axis and a y-axis. We refer to our point as an ordered pair because there are two numbers associated with it. The first number tells us where it is on the x-axis, and the second number tells us where it is on the y-axis. 1, 2 is an ordered pair that tells us our point is located 1 space to the right of the center and 2 spaces up. To plot these points, we look at the first number to tell us where it is located on the x-axis, and then we look at the second number to tell us where it is on the y-axis. There will only be one point that has the same x and y-axis values.
This video is on the different forms of a linear equation, specifically slope-intercept form and standard form, and how we can graph lines given to us in either of those forms. Slope-intercept form, y equals mx plus b, is the one that most people are familiar with. It's the most common one you see, but that doesn't mean it's the only way to represent a linear equation. So, for example, if I had the line y equals 3x plus 4 given to me in slope-intercept form, by using inverse operations and taking a positive 3x and undoing it with a minus 3x on both sides, I end up with the equation negative 3x plus y equals 4. And these two equations are equivalent. They mean the same thing. They are the same thing. They're just written differently. And what I end up with in this second one is what's called standard form. Essentially because the x's and the y's are on the same side of the equation. And the generic standard form equation is ax plus by equals c. This is probably the second most common form of a linear equation that you see. But unlike slope-intercept form, the a's and b's do not necessarily give us any useful information like the m and b does in slope-intercept form. But that doesn't mean that there aren't still some advantages to standard form over slope-intercept form. What we're going to find out is that the orientation of the variables in standard form makes finding the x and y intercepts pretty quick and easy, which will allow us to kind of use a shortcut when it comes to graphing. So here we have a question that asks us to graph the line negative 3x plus 2y equals 6. So let's do it the way we know how, which is by using slope-intercept form to use the m value and the b value to graph our line. But because this isn't given to us in slope-intercept form, it requires us to first put it in slope-intercept form by using inverse operations to get the y by itself, which means we first have to undo the negative 3x with a positive 3x to both sides. Then we have to undo a times by 2 with a divide by 2 to both sides. Now we have the equation y equals 3 halves x plus 3. This equation is equivalent to the one we started with, just written in a different way. But now that it's written in slope-intercept form, I know that I can use my m, my slope, and my b, my y-intercept, to graph it. I begin at 3 on the y-axis, and then I go up 3 and over 2 to find my next point using the slope. You could continue going up 3 and over 2 as many times as you wanted, but you'd notice that all your dots are in the same straight line. You can connect that line and you have your graph, which isn't too bad. But these steps in the beginning that required us to first get the y by itself are unnecessary, and sometimes they can be a little complicated, especially with the fractions, and we'd rather know a way to do it without having to solve for y. So let's take a look at the exact same problem, graph negative 3x plus 2y equals 6. But this time try to do it without having to do all those beginning steps where we get y by itself using inverse operations and have to deal with fractions and all that messy stuff. We know that at the x-intercept, y is 0, and at the y-intercept, x is 0. So because we know this, it turns out the x and y intercepts are really easy to find. Check it out. If I know that the x-intercept is y is 0, I can simply substitute 0 in for y into my equation, which gives me negative 3x plus 2 times 0 equals 6. Well, 2 times 0 just turns into 0, so this term kind of just cancels out, and all we're left with is the x's. And it's a very simple, quick and easy division to both sides, because division undoes the multiplication of the negative 3, and we find that x equals negative 2, which is my x-intercept. So I have the coordinates negative 2, 0. I can find the y-intercept in exactly the same way. This time, plugging in 0 for x gives me the equation 2y equals 6, because the x's disappear. Again, I simply undo the times by 2 and divide by 2, and I find that y equals 3, which gives me the point 0, 3. And I have 2 points, and we're done. I can put those 2 points on my graph, negative 2, 0, 0, 3, and as long as you have 2 points, you connect them with your line, and we end up with the exact same line that we did before, but this time we didn't have to solve for y, we didn't have to deal with fractions. It was actually a little bit easier. So to review, we've talked about slope-intercept form and also standard form. We should also probably quickly discuss the pros and cons to each. Slope-intercept form is a little more intuitive because it gives us more information straight from the rule. It tells us the m and the b that are obvious right from the rule that I can translate quickly into information on the graph. But standard form is nice if we're trying to find intercepts, because it makes it easy to substitute in 0 and solve for the remaining value. And so if you're given an equation in standard form and you're asked to graph, there's no reason you really have to change it into slope-intercept form first, and we can use the shortcut of finding the intercepts to do it without having to do all the work of solving for y.
The slope of a line is how steep the line is and whether the line is an uphill or a downhill. Slopes can be whole numbers or fractions, and either positive or negative. All slopes can be converted to a fraction form that tells you how much the line changes in the y direction over how much the line changes in the x direction. This is easy to remember as the phrase rise over run. For example, let's take a look at the slope 1 over 2. This slope is in fraction form. The top number tells you how the line changes in the y direction, or how much it rises. The number is a 1 and it is positive, so that tells us that the line goes up or rises by 1. If it was negative, then our line would go down by 1. The denominator is a 2, which means that the line goes in the x direction or runs to the right for 2 spots. If we had a whole number such as 3, we can convert to a fraction by remembering that all whole numbers have a 1 in the denominator. So our 3 becomes a 3 over 1, which tells us that the line goes up 3 spots in the y direction and to the right 1 spot in the x direction. Why do we need to know this information? Since equations for lines tell us about various situations and how much growth or decline there, being able to find the slope allows us to learn about how fast or slow the growth or decline is. Equations of lines come in different forms, and from these equations we can find the slope directly by looking at the equations. One type of equation that we come across is the point-slope form. Y minus y subscript 1 equals mx minus x subscript 1. The y sub 1 and the x sub 1 stand for the coordinates of the point, and the m stands for the slope. Because the m stands for the slope, we can find the slope directly from this form of equation. For example, if we are given the equation y minus 3 equals 4 times x minus 2, we can see right away that the slope is 4 because the 4 is in the location of the m. The other equation form of a line is the slope-intercept form, y equals mx plus b. In this form, the m stands for the slope and the b stands for the y-intercept, where the line crosses the y-axis. Again, because the equation has the m for the slope, we can see directly what the slope is. For example, if we had the equation y equals negative 3 over 4x plus 5, we look for where the m would be, and we see that there is a negative 3 over 4 in its place. That tells us that the slope is negative 3 over 4. Finding the slope from these two equation forms is pretty straightforward. We can find the slope directly by looking at the equations. Finding the slope of a parallel line is also straightforward, but finding the slope of a perpendicular line requires a bit of manipulation. A parallel line is a line with the same slope but in a different location. Because the definition of a parallel line calls for the same slope, we know right away that a parallel line will have the same slope. So if our line has a slope of 3 over 2, then our parallel line will also have a slope of 3 over 2. The actual equation may be different, but the slope is the same. The slope of a perpendicular line is a bit different. Although different, it is not hard to calculate. All you have to do is to place your current slope underneath a negative 1. In other words, divide a negative 1 by the slope to get the perpendicular slope. This is called the negative reciprocal. You can check to see if you did it correctly by multiplying your current slope with the perpendicular slope. Multiplied together, it should equal negative 1. For example, if our current slope is 5, then our perpendicular slope is negative 1 over 5. We have placed our current slope underneath a negative 1. We are dividing by a negative 1 by our current slope. To check to see if we did it right, we multiply the 5 with the negative 1 over 5. What do we get? We get 5 times negative 1 over 5 equals negative 1. Check. That is what we need, so we did it right. What have we learned? We've learned that the slope of a line tells us how steep the line is and whether the line is an uphill or a downhill. To remember the slope, think of the phrase rise over run, which tells us that in fraction form, the top number gives us how much change the line has in the y direction, while the bottom number gives us the change in the x direction. For both the point-slope form and the slope-intercept form of equations, we can directly see what the slope is because both have an m in their equations that tells us the slope. All we have to look for is what number is in the m spot. For example, the equation y minus 3 equals 2 times x minus 1 is in the point-slope form, and the slope is 2, since the 2 is in the m spot. The equation y equals 3x plus 4 is in the slope-intercept form, with a slope of 3 since the 3 is in the m spot. For parallel lines, the slope is the same. For perpendicular lines, the slope is the negative reciprocal, which we find by dividing a negative 1 with our current slope.
In this lesson, you will see how you can interpret or solve a system of linear equations by graphing it. Knowing how to use this graphing method can help you visually solve such a system without having to use algebra. Remember, a linear system of equations is a set of linear equations. If you have one variable, then you have one equation. If you have two variables, which is the usual case for problems you will encounter, then you will have two equations. If you have three variables, then you will have three equations, and so on. But since they are all linear equations, none of the variables will have exponents. Here's an example of a linear system in two variables. This is the one that we will be solving too. Y equals 2x minus 3, y equals negative 3x plus 2. See how each equation has the same two variables, x and y, and because we have these two variables, we have two equations. And because this is a linear system, none of our variables have exponents. Right now, all our equations are written in slope-intercept form, which is y equals mx plus b, making it easy for us to graph. If our equation were written in standard form, which is ax plus by equals c, then we can rearrange the equation into slope-intercept form to make it easy for us to graph. So, on to graphing our two equations. This is what we get. The red line is for the equation y equals 2x minus 3, and the blue line is for the equation y equals negative 3x plus 2. To graph these two lines, we begin with our y-intercept, the last number in our equation. For y equals 2x minus 3, it is negative 3. For y equals negative 3x plus 2, it is 2. The y-intercept is where these lines cross the y-intercept. After we have this point, then we find our next point by looking at the slope of the equation. For y equals 2x minus 3, the slope is 2, which means our next point is 2 up and 1 to the right of our y-intercept. We follow the same procedure for the other equation. To find the solution to this system of linear equations, we look to see if the lines intersect. If they do, then the point of intersection is the solution. If the lines don't intersect, then there is no solution. But if you only see one line, then you have an infinite number of solutions. Looking at our graph, we see that our two lines do cross. We have a solution. What is it? Because we have graphed our equations, we can easily find this answer by looking at the graph. Where do our two lines meet on the graph? Our two lines intersect at 1 and negative 1. That is our answer. Our x equals 1 and our y equals negative 1 at this point. We can check to see if this is correct by plugging in these x and y values into our original equations. If they come out correctly, then this is the right answer. Most times, if you have graphed your equation correctly, then the answer that you see is correct. Let's look at another example. Find the solution to this linear system by graphing it. Negative 4x plus 2y equals 6. Y equals x. Looking at these two equations, we see that the first equation is written in standard form, while the second is in our slope-intercept form. We need to rearrange the first equation so it is in the slope-intercept form so we can easily graph it. To do this, we add 4x to both sides and then divide both sides by 2. We get 2y equals 6 plus 4x, after adding 4x to both sides. Now dividing both sides by 2, we get y equals 3 plus 2x. The slope-intercept form is y equals 2x plus 3. Now, graphing these two equations, we get this. The red line is the first equation, y equals 2x plus 3, and the blue line is the second equation, y equals x. Do these two lines intersect? Yes, they do. We have a solution. What is it? It is negative 3, negative 3. This means our x is equal to negative 3 and our y is equal to negative 3. And we're done. Let's review. A linear system of equations is a set of linear equations. You will have one equation for each variable in your system. If your system has two variables, you will have two equations. If your system has three variables, then you will have three equations. There are no exponents in a linear system. For a system with two variables, you will want your equations to be in slope-intercept form, which is y equals mx plus b, so you can graph them easier. Once you have graphed your equations, you look to see if they intersect. If they intersect, then you have a solution. If they don't intersect, then you have no solution. If there is only one line, meaning they are the same line, then you have an infinite number of solutions.
In this video lesson, you will learn how to solve a system of linear equations in two variables. There are systems of two equations where each equation has only two variables. These variables are usually x and y. Why should you learn about solving these types of problems? It is because you will come across these types of systems, and even larger ones, as you progress in math. You will also see that many real-world problems are modeled using these systems, so being able to solve them easily will be a real help to you. For example, the number of girls and boys in a classroom can be modeled using a system of linear equations in two variables. If there are a total of 30 students in the classroom, and if there are 10 more boys than girls, we can write this system with these two equations. G plus b equals 30, g plus 10 equals b. The first equation tells us that when we add the number of girls, g, and the number of boys, b, together, we get a total of 30 students in the classroom. The second equation tells us that the number of boys is 10 more than the number of girls. How can we solve this system? We can solve it by using the substitution method. This method can be applied to any other system of linear equations in two variables. What this method involves is solving one equation for one of the variables and plugging this into the other equation to solve. Let's see how it works with our system. We will begin by solving one of the equations for one of the variables. I look closely at my two equations to see which one will be easier to solve for one of the variables. And I see that my second equation is already solved for the variable b for boys. If this wasn't the case, I can easily solve the first equation for boys by subtracting g from both sides to get b equals 30 minus g. But I didn't have to do that because I already have b equals g plus 10. Okay, I have what my b equals. I can now substitute this into the other equation. I will substitute b equals g plus 10 into g plus b equals 30. I get g plus 10 equals 30. I have just substituted what my b equals into the b variable. I can now solve for g. I get 2g plus 10 equals 30. Subtracting 10 from both sides, I get 2g equals 20. Dividing by 2 on both sides, I get g equals 10. So there are 10 girls. What about the number of boys? I can find this by substituting the number of girls into the equation for boys that I used in the very beginning. I get b equals 10 plus 10, which equals 20. So there are 20 boys. Is this right? Well, there are 10 girls and 20 boys. That makes a total of 30 students. That's right. There are 10 more boys than girls. That is right, too. My answer is correct. Let's try another problem. Let's try solving this system of equations. 2x plus y equals 10. X minus y equals negative 1. We first need to solve one of the equations for one of the variables. I will solve the second equation for x. I add y to both sides to get x equals y minus 1. Now I substitute this x into the x in the first equation. I get 2 times y minus 1 plus y equals 10. Solving this for y, I get 2y minus 2 plus y equals 10. Adding like terms, I get 3y minus 2 equals 10. Adding 2 to both sides, I get 3y equals 12. Dividing by 3 on both sides, I get y equals 4. I go back to the equation I got when I first solved for x. I plug my y into this equation to solve for x. I get x equals 4 minus 1, which equals 3. My x is 3. So my complete answer is x equals 3 and y equals 4. What did we learn? We learned that a system of linear equations in two variables is a system of two equations where each equation only has two variables. It is important to learn how to solve these systems because you will come across these systems in future math classes. The method discussed in this video lesson is the substitution method. This method can be used to solve any system of linear equations in two variables. What you do with this method is solve one equation for one variable and plug it into the other equation to solve. Once you have found one variable, you can then plug this value into the first equation you solved for to find the other variable.
Do you have a different outfit that you wear each day of the week? If so, you might be surprised to learn that the relationship between the day of the week and your outfit represents a mathematical concept called a function. In mathematics, a function is a relationship between two sets of elements in which no element in the first set relates to more than one element in the second. We can think of a function as a rule that takes inputs from the first set and relates them to an element in the second set, which is the output. In mathematics, we represent functions in many different ways. We can use words, tables, mappings, equations, and even graphs. Consider this example. If a state has a 6% sales tax, then we can use a function to calculate it. We can use the following equation to represent this function. T equals 0.06x. If we purchase a product for X dollars, then to calculate the tax, we would multiply X by 0.06, or the tax rate in decimal form. For instance, if you bought a shirt for $25, then you can calculate the sales tax by plugging in 25 for X. T equals 0.06 times 25 equals 1.5. We see the sales tax is $1.50. We can also represent this function using our other representations. Because our purchase price can be any number, we could never list all of the inputs and outputs. Using a table or mapping wouldn't be the best method in this situation, but we can easily represent it graphically by simply graphing the equation T equals 0.06x. We see that there are many ways to represent a function, and each one depends on its context. Now that we are reminded what a function is in mathematics, let's talk some more about using them in real-world settings. When it comes to recognizing functions in the real world, it is useful to think of the term is a function of as is determined by. You see, in a function, no input can be related to two different outputs. Otherwise, given the input, we couldn't determine the output. Therefore, the input determines the output, so the output is a function of the input. For instance, think about those outfits again. If it's Tuesday, what outfit will you be wearing? Well, we look to see what outfit to which Tuesday is mapped, and we see that you will be wearing your jean shorts with your green t-shirt. That's not too hard, is it? You can see that your outfit is determined by the day of the week, so your outfit is a function of the days of the week. Pretty neat, huh? You may have been familiar with functions involving numbers, but it's totally cool to see that the function concept can actually be applied to real-world situations. Let's consider a couple more examples. Suppose you and your friend are trying to raise money for your favorite charity and decide to have a cupcake sale. You bake a variety of cupcakes and sell them for $3 each. If we let the number of cupcakes you sell be your input and the total amount of money you raise be your output, we can represent this relationship using the following equation. A equals 3x. We see that the amount of money you raised is determined by the number of cupcakes you sell. This tells us that your total money raised is a function of the number of cupcakes you sell. Once you have a function in equation form, it can be used to determine all sorts of things about the situation. For instance, let's say you and your friend made 150 cupcakes, and you want to know the most money that you can make if you sold them all. To determine this, we simply plug 150 for x into the function and simplify. A equals 3 multiplied by 150 equals 450. We see that if you sell all your cupcakes, you can make $450 for your charity. That would be awesome. Okay, let's take a look at another example. Let's consider birthdays. After all, who doesn't get excited for their birthday? Suppose you have a group of friends with the following birthdays. Observe that one person can't have more than one birthday, and that, given one of your friends, you can determine their birthday. Because of this, the birthday is a function of your friend. I bet you never thought of a birthday list as a function. This is extremely useful because this function allows you to determine your friend's birthday, so you never have to forget their gift. A function is a relationship between two sets of elements in which no element in the first set relates to more than one element in the second set. In mathematics, we represent functions in a variety of ways. We use equations, words, tables, mappings, and graphs. We can also use these representations for functions in the real world. To recognize these functions, it is helpful to think of is a function of as is determined by. In doing this, we see that functions show up in the world around us all the time. They are extremely useful in applications for business, finance, engineering, and in everyday events like remembering someone's birthday. It is definitely worthwhile to be familiar with functions and their uses in the real world.
Jessica has a square garden. To make watering her plants easier, she would like to create a diagonal pathway that connects opposite corners. If one side of her garden is 13 feet long, what will be the length of her diagonal pathway? This scenario presents a perfect example of geometry in real life. Since the garden is in the shape of a square, we will be able to use the Pythagorean theorem to figure out how long the diagonal pathway will be. Let's take a closer look at this theorem and how it's used so that we can calculate the solution to this problem. Written by the Greek mathematician Pythagoras, the Pythagorean theorem states that in right triangles, the sum of the squares of the two legs is equal to the square of the hypotenuse. In clearer terms, if you square both of the legs and then add these numbers together, you will end up with the same value as the hypotenuse squared. As a formula, this theorem is written as a squared plus b squared equals c squared, where a and b represent the two legs of the triangle and c represents the hypotenuse. When labeling any right triangle with these variables, it is important to know that A and B can be written on either leg. However, C must be written on the hypotenuse, which is the longest side and opposite the right angle. The purpose of the Pythagorean theorem is to make it possible to find the length of any missing side of a right triangle. For the theorem to be usable, the value of the other two sides must be known. Let's take a look at a few basic problems. In our first triangle, one leg has a length of 4 centimeters and the second leg has a length of 7 centimeters. Let's find the length of the hypotenuse. Since I have the value for the two legs, which are represented by A and B, we will let A equal 4 and B equal 7. We are now ready to plug this information into the formula. Once we do, we get 4 squared plus 7 squared equals C squared. After simplifying, we end up with 16 plus 49 equals C squared, and when we combine our like terms, we have 65 equals C squared. For our last step, we will take the square root of both sides to get a final answer of C equals 8.06. Therefore, we can see that the length of the diagonal is 8.06 centimeters. In our next triangle, the measure of one leg is 12 inches and the measure of the hypotenuse is 20 inches. For this triangle, we have the value of the hypotenuse, but must find the length of the missing leg. Therefore, we will let A equal 12 and C equal 20. By substituting this information into the formula, we have 12 squared plus B squared equals 20 squared. When we simplify, we get 144 plus B squared equals 400. At this point, we should subtract 144 from both sides to get B squared equals 256. Once we take the square root of both sides, we see that B, the missing leg in our triangle, has a value of 16 inches. Did anything about the numbers in that last example stand out to you? Notice that all of the side lengths are whole numbers, not fractions or decimals. This means that the side lengths for this triangle are a Pythagorean triple, which is defined as a set of non-zero whole numbers that satisfy the Pythagorean theorem. A few more examples of Pythagorean triples are 3, 4, 5, and 28, 45, 53. If you plug these numbers into the Pythagorean theorem, you will see that 3 squared plus 4 squared does indeed equal 5 squared, and 28 squared plus 45 squared equals 53 squared. Now that we have an understanding of the Pythagorean theorem, let's apply it to a few everyday examples, beginning with Jessica's garden from the beginning of the lesson. Let's review the problem again. Jessica has a square garden. To make watering her plants easier, she would like to create a diagonal pathway that connects opposite corners. If one side of her garden is 13 feet long, what will be the length of her diagonal pathway? For this situation, we should definitely use the Pythagorean theorem. We know that in a square, all 4 angles measure 90 degrees and all 4 sides are congruent. So if one side has a length of 13 feet, then all the other sides have a length of 13 feet. By taking half of the square, the diagonal becomes the hypotenuse and we have a right triangle with both legs equal to 13 feet. We are now ready to plug in our information to find the length of the hypotenuse. When we do, we will see that 13 squared plus 13 squared equals C squared. By simplifying and combining like terms, we end up with 338 equals C squared, and C equals 18.38 as our final answer, which will be the length of Jessica's diagonal pathway. Let's do another. Elizabeth needs to repair her roof. She props a 21-foot ladder against the side of her 20-foot home. If the top of the ladder reaches the top of her house, how far away from her home is the base of the ladder? In this problem, we are still working with the right triangle. The ladder is the hypotenuse, while the height of the home and the ground between the home and the ladder are the legs of this right triangle. Using the given information, our beginning equation is 20 squared plus b squared equals 21 squared. Simplifying brings us to 400 plus b squared equals 441. From here, we subtract 400 from both sides to get b squared equals 41, from which we see that b equals 6.40. Therefore, we can conclude that the base of the ladder is 6.40 feet away from the home. In summary, the Pythagorean theorem, which can only be used with right triangles, is a very important theorem that allows us to find the length of a missing side in a triangle. The theorem is interpreted as the formula a squared plus b squared equals c squared. The legs are represented by a and b and can be labeled interchangeably, but the hypotenuse must be labeled c. In order for this theorem to be used, two sides of the right triangle must be known.
The word perimeter means a path that surrounds an area. It comes from the Greek word peri, meaning around, and metron, which means measure. Its first recorded usage was during the 15th century. In mathematics, the perimeter refers to the total length of the sides or edges of a polygon, a two-dimensional figure with angles. When describing the measurement around a circle, we use the word circumference, which is simply the perimeter of a circle. There are many practical applications for finding the perimeter of an object. Knowing how to find the perimeter is useful for finding the length of fence needed to surround a yard or garden, or the amount of decorative border to buy to cover the top edges of a room's walls. Also, knowing the perimeter or circumference of a wheel will let you know how far it will roll through one revolution. The basic formula for finding the perimeter is just to add the lengths of all the sides together. However, there are some specialized formulas that can make it easier, depending on the shape of the figure. Before we begin, let's define some abbreviations or variables we'll be using in our formulas. We'll represent the perimeter, the value we're trying to find, with a capital P. For a shape that has all of its sides the same length, we'll use an S to represent a side. We can also use S with a number after it to represent sides of shapes that have more or less than 4 sides, which may be the same or different lengths. We can write these variables like this: S1, S2, S3, etc. For a shape that has 2 of its opposite sides the same as each other, and its other 2 opposite sides the same as each other but different from the first 2 sides, we'll need 2 variables. We'll call the longer of the 2 distances length and the shorter of the 2 distances width. We'll represent length with an L and width with a W, as follows. Each side of a square has the same length, so we can use our abbreviation S to represent a side. A square has 4 sides, so we can find its perimeter by finding the length of any side and multiplying it by 4. We write the formula this way: P equals 4S. In the picture shown here, each side of the square has a length of 6 feet. Using our formula P equals 4S, we plug in the value of the length of one side for S. P equals 4 times 6 feet. 6 times 4 equals 24, so the perimeter of our square is 24 feet. A rectangle has right angles, like a square does, but it has 2 longer sides that are the same length and 2 shorter sides that are the same width. If we know the length of one side and the width of another, we can add them together and multiply by 2. We write the formula this way: P equals 2 times length plus width. To find the perimeter of the rectangle shown here, we need to have the length of one of the longer sides and the width of one of the shorter sides. We see from the labels that the length is 6 and the width is 3. Starting with our formula P equals 2 times length plus width, we then substitute 6 for the L and 3 for the W. P equals 2 times 6 plus 3. Adding 6 and 3 equals 9, so our equation now looks like this: P equals 2 times 9. Multiplying 2 times 9 gives us 18, which is the perimeter of the rectangle. A triangle has 3 sides, which may be the same or different lengths. The easiest way to find the perimeter is just to add the sides together. We can write the formula like this: P equals S1 plus S2 plus S3. For a triangle, we often represent the 3 sides with the letters A, B, and C, so we can also write the formula as P equals A plus B plus C. For the triangle shown here, we start with our formula and then plug in the lengths of each side in place of the variables representing the sides. Now, we add up the lengths of the sides. Adding 4 plus 8 plus 11 equals 23, so the perimeter of our triangle is 23 centimeters. A triangle is a polygon with only 3 sides. To find the perimeter of a polygon, add up the lengths of all the sides just as you did for the triangle. The difference here is that the polygon shown here has more sides than the triangle did. This polygon, called a pentagon, is a polygon with 5 sides, so we write the formula this way: P equals S1 plus S2 plus S3 plus S4 plus S5. Now we substitute the lengths of the sides for the variables representing them. P equals 5 plus 4 plus 2 plus 7 plus 1. We add up the sides. 5 plus 4 plus 2 plus 7 plus 1 equals 19, so we write our result this way: P equals 19. One thing to remember when finding the perimeter of an object is that you can only add lengths that have the same unit. If one side of an object is in inches and another is in feet, you must convert either inches to feet or feet to inches before adding. If no units are given, you can assume they are the same. Now, we're going to work through a couple of example problems on perimeters. Andrew is going to build a wooden hat box. He decides that each side should be 5 inches long. He also decides to make the box so that the lid and bottom are the shape of a regular hexagon. What will the perimeter of the lid be? Before we answer this question, we must first define some terms. A hexagon is a 6-sided figure. A regular hexagon is a hexagon where all 6 sides are the same length. We know that Andrew wants a box with 6 sides of equal lengths. We write our perimeter formula this way: P equals S1 plus S2 plus S3 plus S4 plus S5 plus S6. Each side is 5 inches long, so we replace each of the side length variables with 5 inches, like so. Then we can find the perimeter by adding up the sides. The perimeter of the box is 5 plus 5 plus 5 plus 5 plus 5 plus 5, or 30 inches. P equals 30 inches. Paula wants to fence in an area to make a rectangular garden, but doesn't want to spend any money to buy fencing. She has 36 feet of fencing left over from another project, and she knows she wants her garden to be 10 feet long. What can the width of her garden be if she uses all the fencing she has? Starting with the information that Paula wants a rectangular garden, we can use the formula for the perimeter of a rectangle. P equals 2 times length plus width. Then we fill in what we know. The length of the garden is to be 10 feet, and its perimeter is to be 36 feet, because that's how much fencing Paula has. Now our formula looks like this. 36 equals 2 times 10 plus W. To solve for W, which will be the width of her garden, we multiply both values inside the parentheses by 2. Now our equation looks like this. 36 equals 20 plus 2W. Subtract 20 from both sides. 36 minus 20 equals 20 plus 2W minus 20. 16 equals 2W. Finally, divide both sides by 2. 8 equals W, or putting the variable on the left, we write W equals 8. Paula's garden will be 8 feet wide. The perimeter is the distance around the outer edge of a two-dimensional figure. To find the perimeter, you need to know the length of one or more sides, depending on the shape of the figure. Finding the perimeter has many practical applications, including finding how much material is needed for a building project.
The mathematical term area can be defined as the amount of two-dimensional space taken up by an object. The use of area has many practical applications in building, farming, architecture, science, and even deciding how much paint you need to paint your bedroom. The area of a shape can be determined by placing the shape over a grid and counting the number of squares that the shape covers, like in this image. The area of many common shapes can be determined using certain accepted formulas. Let's take a look at the most common formulas for finding area. To find the area of a rectangle, you use this formula. Area equals length times width. The area of a square is found with this formula. Area equals s squared, where s equals side. The formula for the area of a triangle is area equals 1/2 b times h, where b equals base and h equals height. To find the area of a circle, use this formula. Area equals pi times r squared, where r equals radius. The area of a parallelogram is found using this formula. Area equals b times h, where b equals base and h equals vertical height. The formula for the area of a trapezoid is area equals 1/2 times a plus b times h, where a equals base 1, b equals base 2, and h equals vertical height. An ellipse's area is found this way. Area equals pi times a times b, where a equals radius of major axis and b equals radius of the minor axis. Finding the area of a shape always requires a multiplication of two lengths. In a square, it's side multiplied by side. In a circle, it's the radius squared. For an ellipse, it's the radius of the major axis multiplied by the radius of the minor axis. Due to this, the units given to area will always be squared. Feet squared, inches squared, etc. Anything multiplied to itself is squared, whether it is a number or not. Let's practice finding the area with some example problems. What is the area of a square with side length of 5 inches? Remember, the formula for finding the area of a square is a equals s squared. The sides of this particular square are 5 inches. Plug that into the formula to get a equals 5 squared equals 25 inches squared. What is the area of this parallelogram? Remember, the formula is a equals b times h. So, for this example, the area would be a equals 3 times 12 equals 36 millimeters squared. If you are asked to find the area of an uncommon shape, it can be done by breaking the shape into more common shapes, finding the area of those shapes, and then adding the areas together. Let's look at some examples. Find the area of this shape. The first step to solving this problem is to divide the shape into shapes we can find the area of easily. This shape can be divided into a triangle and a square. You can use the information given to determine the lengths you need to calculate the area. Since you know the height from the point of the triangle to the bottom of the square is 10 centimeters, and the height of the square is 8 centimeters, the height of the triangle must be 2 centimeters. The base of the triangle is equal to a side of the square, which is 8 centimeters. You can use these numbers to determine the area. A of square equals s squared equals 8 squared equals 64 centimeters squared. A of triangle equals 1/2 times b times h equals 1/2 times 8 times 2 equals 8 centimeters squared. Then you just add the areas together to get the total area of the figure. A equals 64 plus 8 equals 72 centimeters squared. Find the area of the figure shaded in red, given that the dimensions of the rectangle are 11 inches by 7 inches. This example is a bit different since you only want the area of a small portion of the figure. This figure can be broken down into a rectangle and a circle, only this time the area of the circle needs to be subtracted from the area of the rectangle to get the remaining area. A of rectangle equals L times W equals 11 times 7 equals 77 inches squared. A of circle equals pi r squared equals pi times 3.5 squared equals 38.47 inches squared. The radius of the circle is determined from the diameter of the circle, which is equal to the width of the rectangle because the circle is as wide as the rectangle. The radius is half of the diameter. 1/2 times 7 equals 3.5. A equals 77 minus 38.47 equals 38.53 inches squared. The area of a two-dimensional figure is a calculation of the space taken up by the figure. Figures such as squares, triangles, circles, and others have specific formulas that can be used to find their area. The area of other figures can be determined by breaking the figure into parts whose area can be easily determined.
As you may recall, area is the amount of space taken up by a two-dimensional figure, and it's measured in units squared. Most shapes require a formula to calculate area, and circles are no exception. To calculate the area of a circle, use the following formula: A equals pi times r squared. In this formula, r represents the radius, which is a segment that connects the center of the circle to a point on the edge of the circle. It is half the size of the diameter, and every radius inside of a circle will be the same. Let's take a brief look at how to find the area of circles. Take a look at circle M. Here, we see that the diameter is 12 inches long. To calculate the area of circle M, we must cut the diameter in half to determine the radius. When we divide 12 by 2, we see that the radius has a length of 6 inches. From here, we will substitute 6 into the equation. A equals pi times 6 squared. Remember to follow the order of operations. We must square the radius before multiplying by pi. When we do, we are able to determine that the total area of circle M is 36 pi, or 113.097 inches squared. Now, let's take a look at a real-world example. Joe is purchasing material to build his first trampoline. If he wants the diameter of the mat to be 14 feet long, how much nylon will he have to purchase? Once again, we will cut the diameter in half to determine the radius. When we do, we will see that the radius of the mat will be 7 feet. Next, we substitute this radius into the equation. A equals pi times 7 squared. Once we complete our calculations using the order of operations, we will find that the total area of the mat is 49 pi, or 153.938 feet squared. In both of these examples, we've found the radius of our circle from a given diameter. However, we don't necessarily have to do this. We can also find the area of a circle using just the diameter. Remember, radius is half the diameter. This means we can insert d over 2 into our area formula in place of radius. Squaring the 2 in the denominator of this formula will give us the area of a circle formula with diameter in its conventional form. A equals 1/4 times pi times diameter squared. Let's look back at our second example again, but this time using this formula. We need to find the area of Joe's trampoline, given that it has a diameter of 14 feet. This time, we can insert the diameter directly into our formula. A equals 1/4 times pi times 14 squared. If we square the 14, we get 196, and dividing this by 4, we get 49. This gives us an area equal to 49 pi, or 153.938 feet. This is exactly the same answer we got using radius, which is what we should find. So that takes care of calculating the amount of space taken up by a circle. But how can we determine the total distance around a circle? For other shapes, this is referred to as perimeter, which is the sum of the lengths of all the sides in the figure. But circles don't have actual sides like other shapes. Therefore, the term circumference is used. It is defined as the distance around a circle, and is represented by the following formula, where r is the radius. C equals 2 times pi times r. Let's examine a few circumference problems, beginning with Joe's trampoline. In addition to buying nylon for the mat, Joe needs to create a steel frame. With a diameter of 14 feet, how much steel must he purchase to build a frame that will enclose the entire mat? As we discovered earlier, with a diameter of 14 feet, the radius of the trampoline will be 7 feet. Let's plug this into the formula for circumference. C equals 2 times pi times 7. After simplifying, we see that the circumference of the mat is 14 pi, or 43.98 feet. And that is how much steel Joe will need to purchase to build the frame. Here's one more. Clara has started her own hat decorating business. For her current design, she wants to line the brim of the hat with ribbon. If the brim has a diameter of 24 inches, how much ribbon will she need? Since the diameter of the hat is 24 inches, we must divide this number by 2 to determine the radius. When we do, we see that the radius is 12 inches, and we are ready to plug this into the formula. C equals 2 times pi times 12. Solving this equation gives an answer of 24 pi, or 75.398 inches. Therefore, she will need 75.398 inches of ribbon to line her hat. Dominic is an engineer working for a construction company tasked with building a stadium. The stadium's design is circular, with a circumference of 3,200 feet. How much area will this stadium take up? Wait a second. This time, we weren't given diameter or radius. How are we supposed to find area? Luckily, with a little bit of algebra, we can use circumference to find the area of a circle. We start by taking the circumference formula, c equals 2 times pi times r, and dividing both sides of it by 2 pi to get radius by itself. We can then take the left side of this equation and insert it for the radius in our area formula. A equals pi times r squared. A equals pi times c over 2 times pi squared. Performing our order of operations, as we have done for the previous problems, and simplifying, we get the following equation. A equals c squared divided by 4 times pi. We can then insert 3,200 as our given value for circumference in the formula. A equals 3,200 squared divided by 4 times pi. Working through these calculations, we find that the stadium will have an area of 2,560,000 divided by pi, or 814,873 feet squared. The area, A, of a circle is defined as the amount of space covered by the circle and is calculated using two formulas. The first finds area using radius, r, and the second finds it using diameter, d. 1. A equals pi times r squared. 2. A equals 1/4 times pi times d squared. Circumference, c, on the other hand, is the distance around a circle, and it is calculated using the following formula. C equals 2 times pi times r. If you are asked to solve for the area of a circle while given only its circumference, you can rearrange the circumference formula using algebra to get r on one side of the equal sign. You can then substitute what's on the other side of the equal sign into the area formula for r to solve the problem. The concepts of area and circumference are not just abstract ideas to be used only in a math class. From jumping on a trampoline to designing hats or baking cakes, area and circumference of circles are present everywhere in everyday life.
Volume is defined as the amount of space taken up by an object. It is most often described in terms of meters cubed, m to the third power. One way to find the volume of an object is to completely submerge the object in water and measure the volume of water that is displaced by the object. The amount of water displaced is equal to the volume of the object. If you don't happen to have a large amount of water handy, or the object you are interested in would not fare well in water, there are formulas you can use instead. Determining the volume of cubes or rectangular prisms can be found quite easily. You can also determine the volume of more complex shapes such as cones, pyramids, cylinders, or spheres. Determining the volume of an object can be of practical importance. Knowing the volume of an object can help you determine how much would be needed to fill that object, like the amount of water needed to fill an aquarium. Knowing how to determine volume can also help you win some money. How? Well, if you can determine the volume of a container and the volume of a jelly bean, you can win the guess how many jelly beans are in this jar contest. The basic geometric shapes for which there are volume formulas are the cube, rectangular prism, cylinder, cone, pyramid, and sphere. The formulas for each of these shapes are: cube volume is equal to s cubed, where s is the side of the cube. Rectangular prism volume is equal to L times W times H, where L is the length, W is the width, and H is the height. Cylinder volume is equal to pi r squared times H, where r is the radius and H is the height. Sphere volume is equal to 4/3 pi r cubed, where r is the radius. Pyramid volume is equal to 1/3 AH, where A is the area of the base and H is the height. And cone volume is 1/3 pi r squared h, where r is the radius and h is the height. Let's look at some examples. 1. A swimming pool is 8 meters wide, 25 meters long, and 1.5 meters deep. What is the volume of water in the pool? To determine the answer, we use the formula for finding the volume of a rectangular prism. V equals L times W times H, which equals 25 times 8 times 1.5, which equals 300 cubic meters. 2. The radius of a basketball is 19 centimeters. What is the volume of air contained in the basketball? This time, use the formula for the volume of a sphere. V equals 4/3 pi r cubed, which equals 4/3 times 3.14 times 19 cubed, which equals 28,716.3467 cubic centimeters. 3. What volume of ice cream could you pack into a cone that is 12 centimeters tall with a radius of 4 centimeters? The formula for the volume of a cone is V equals 1/3 pi r squared h, which is equal to 1/3 times 3.14 times 4 squared times 12, which equals 200.96 cubic centimeters. Volume refers to the quantity of space that a three-dimensional object occupies. Determining the volume of shapes can be done using certain formulas. The formulas for each of these shapes are cube volume equals s cubed, where s is the side of the cube. Rectangular prism volume equals L times W times H, where L is the length, W is the width, and H is the height. Cylinder volume equals pi r squared times H, where r is the radius and H is the height. Sphere volume is equal to 4/3 pi r cubed, where r is the radius. Pyramid volume equals 1/3 AH, where A is the area of the base and H is the height. And cone volume equals 1/3 pi r squared h, where r is the radius and h is the height. A three-dimensional shape is a solid shape that has height and depth. For example, a sphere and a cube are three-dimensional, but a circle and a square are not. A prism is a three-dimensional shape that has non-curved sides. A cube is a prism, but a sphere is not. A prism has a pair of congruent sides, called bases, like the cube, triangular prism, and the rectangular prism. Don't confuse a prism with a pyramid, which only has one base. Notice that the prisms each have a pair of congruent bases. The surface area of a three-dimensional shape is the sum of all the surface areas of each of the sides. I like to think of the shape as a birthday present and the surface area as the wrapping paper. If we carefully took the wrapping paper off the present and added up each side, the total would be the surface area of the shape. When we are finding the surface area of a 3D shape, think of it as unfolding the shape or flattening it out, and then finding the area of each side. When we add all of these areas up, we have the surface area. There are two types of 3D shapes we will need to find the surface area of: prisms and non-prisms. When we are looking for the surface area of a prism, we add all of the areas together to find the total. Another way to find the area of a prism is to find the perimeter of the base and multiply by the height. SA of a prism equals perimeter of the base times h plus area of the bases. In order to find the area of a 3D shape, we must know how to find the area of the basic shapes that make up the sides of the 3D shape. Here is a list of basic shape formulas to help with finding the surface area of the 3D shapes. When we are finding the surface area of a prism, we need to find the area of each side, which is one of the basic shapes listed above, and then add all of the areas together to find the total. There are specific formulas for 3D shapes that are not prisms. When we are looking for the surface area of a non-prism, like a sphere, cylinder, pyramid, and other non-prisms, they each have their own formula, as shown in this table. First, we need to identify the shape so we know which formula to use. This is a triangular prism, since there is a pair of congruent bases. Next, we need to find the area of each side. Since this is a triangular prism, it is made up of 2 triangles as the bases and 3 rectangles as the sides. First, look at the triangular bases. To find the area of a triangle, use A equals B times H divided by 2. A equals 3 times 4 divided by 2, which equals 6. Now look at the rectangular sides. Since the area of a rectangle is A equals L times W, find each side. A equals 8 times 5, which equals 40. A equals 8 times 4, which equals 32. And A equals 3 times 8, which equals 24. Our last step is to add them all up. A equals 6 plus 40 plus 32 plus 24, which equals 108 square units. Another way to find the surface area is to use the formula SA equals perimeter of the base times H plus area of the bases. Since this is a prism, this formula will work. Since the base is the triangle, we find the perimeter, or distance around it, by adding the sides together. P equals 5 plus 4 plus 3, which equals 12. Now multiply 12 by the height, which is 96. Now find the area of the triangular bases. To find the area of a triangle, use A equals B times H divided by 2. A equals 3 times 4 divided by 2, which equals 6. Finally, add them together to find the surface area. Surface area equals 96 plus 6 plus 6, which equals 108 square units. First, identify the shape so we know which formula to use. Since this is a cylinder, which is a special shape with its own formula, we should first write it out. SA equals 2 times pi r squared plus 2 pi rh. Let pi be the number 3.14. Next, we plug in the numbers for pi, 3.14, r equals 3, and h equals 6. Surface area equals 2 times 3.14 times 3 to the second power plus 2 times 3.14 times 3 times 6. Then add them together to get the surface area of the cylinder. When finding the surface area of a three-dimensional shape, you first identify the shape in order to decide which formula to use. If it is a prism, you have two choices. Find the area of each side using the area formulas for each specific shape that makes up each side for a prism and sum the sides to get the total surface area, or use the formula surface area equals perimeter of the base times height plus area of the bases. If it is not a prism, use one of the special formulas for a non-prism. We learn about triangles, squares, and circle in math. We know how to find the perimeter, the area, and the volume of each of these shapes on their own. But what happens when you have a combined figure, a shape that is the combination of several simpler shapes? Many shapes that we come across are combined figures. Look at your house, and you can see that you have a rectangular box plus a triangular box on top. How would you find the perimeter, the area, and the volume of such a figure? This is the question that we will be answering in this video lesson. We will look at this combined figure that is the combination of a rectangle and a triangle. It kind of looks like a house. All the lengths are in feet, and we'll look at how to find the perimeter of this shape, the area of it, and also the volume of the shape when our shape is in 3 dimensions. The method that you will learn in this video lesson can be applied to any combined figure. We begin with finding the perimeter. Our shape looks like we drew a house on a piece of paper. To find the perimeter of our shape, we can highlight just the sides that make up the outside of our shape. Think of the outside as the fence that keeps our shape contained, so we need to know the distance of this fence. We need to know the length of each side. If we don't know the length of some of the sides, we need to figure them out. To find the length of some sides, we can look at the other sides to see if we can calculate them. For example, for our shape, we have 4 sides that are labeled with their lengths, but the 5th side isn't. However, because the 5th side is the other side of our triangle, we can calculate it, since this side is the same length as the side that is opposite it, in our case, 6 feet. Now we have all the lengths for our sides, so all we have to do now is add up all these lengths to find our perimeter. Our perimeter is 5 plus 5 plus 6 plus 8 plus 6 equals 30 feet. Notice how I've basically gone around the shape. This way I make sure that I'm adding up all my sides. I recommend you do the same. Start with one side and then methodically work your way around the shape until you get back to the side you started with. Next, we need to find the area of our combined figure. For this part, we want to separate our shape into its separate shapes. We already know that we have a rectangle with a triangle on top, so what we can do is to draw a line to separate the two shapes. Now we can clearly see our two shapes. We do this to make finding our area easier. We can easily find the area of a rectangle as well as of a triangle. So if we separate our combined figure into these easy shapes, then all we have to do is to find the area of each of our simple shapes, and then add the areas up. We first calculate the area of our rectangle. We know the area of a rectangle is its length multiplied by its width, so we have 6 times 8. This equals 48, so the area of our rectangle is 48 square feet. Next, we calculate the area of our triangle. The formula for the area of a triangle is half the base times the height, 1/2 times BH. Our base is the longer side of our triangle. We can see that this equals 8 from the other lengths that are given to us. Our height is given to us, and it's 4. If we are missing any one of these numbers, we might need to use our other math skills to figure them out. Now that we have all our needed measurements, we can calculate the area of our triangle as 1/2 times 8 times 4. This equals 16 square feet. To find the total area of our shape, we add our two separate areas. We get 48 plus 16, which equals 64. So the area of our combined figure is 64 square feet. To find our volume, we use the skills we learned to find the area of our combined shape and apply it here as well. We do the same as we did for our area and separate our shape into easy, simple shapes. So far, we've dealt with our shape in 2 dimensions. Let's add a third dimension to our shape by turning it into a cake that is shaped like a house. We now have a third dimension, the height of our cake. We separate our shape into its 2 simple shapes. We draw a line to cut our cake into its rectangular part and its triangular part. We can then easily find the volume of each part separately, and then add them together to find the total volume of our combined figure. We see that our cake has a height of 0.5 feet. To find the volume of these pieces, we multiply the height of each of our pieces by the area of our flat 2-dimensional shape. Our rectangle has a flat area of 48 square feet. Multiplying this by the height of 0.5 feet gives us 24 cubic feet. Our triangle has a flat area of 16 square feet. Multiplying this by 0.5 feet gives us 8 cubic feet. Adding these two volumes together gives us 32 cubic feet for our combined 3-dimensional figure. We've covered how to find the perimeter, area, and volume now, so let's review what we've learned. A combined figure is a shape that is the combination of several simpler shapes. To find the perimeter, we add up all the outside sides of our shape. To find the area, we divide our shape into its simple shapes, calculate the area of these shapes separately, and then add these areas up to get our total. To find the volume, we also divide our shape into its simplest shapes, calculate the volume of each separately, and then add up the pieces to get the whole volume. Believe it or not, math is responsible for so many things in our everyday lives. Without math, we wouldn't have things like maps or model drawings or cars, for example. I don't know about you, but I can't travel without a map. I would get lost somewhere and I wouldn't be able to find my way out. If I wanted to build a car, I would need a model drawing of the car so that I can know my measurements. Now, you might be asking, what does all this have to do with math? Let me tell you. Both maps and model drawings are examples of scale drawings, accurately sized drawings that are either smaller or larger than what they represent. Both maps and model drawings are smaller version drawings. You can fit a map and a model drawing of a car in your pocket, but you can't fit a city or a whole car in your pocket. These scale drawings are all about math. How so? Well, the author of the maps and model drawings needed math to figure out how much smaller to draw things. Everything needs to be smaller or larger by the same amount so that they are accurately sized smaller or larger versions of the original. This is where the legend comes in. The legend tells us how much smaller or larger things in the drawing are. For example, on a map we might see a legend that tells us that 1 inch on the map equals 50 miles in real life. We might see it written out in math forms such as 1 inch, 50 miles. And we might see it in the form of a ruler with inch marks that read 50 miles, 100 miles, and so on, instead of 1 inch, 2 inches, and so on. We might see the same on a model drawing, but with different numbers, of course. A model drawing might read 1 inch, 12 inches. So 1 inch on the drawing would equal 12 inches in real life. Why don't we look at a couple of real-life examples? Look at this map. It is a map of the San Francisco Bay Area. There are a few places here that I really want to visit. Starting in San Francisco, I want to make my way down to Santa Cruz, and then to Sacramento. How can I make use of this map to find out how far away San Francisco is from Santa Cruz, and Santa Cruz from Sacramento? I see my legend that tells me how much smaller the map is. It tells me that for every bar at that distance, it is 50 miles in real life. How can I use this to help me find my information? Well, I can take the bar and use it to measure the distance from San Francisco to Santa Cruz by seeing how many bars it takes. It looks like it takes a bit more than 1 bar to go from San Francisco to Santa Cruz, so that tells me that the distance is about 70 miles from San Francisco to Santa Cruz. Doing the same for the distance between Santa Cruz and Sacramento, I see that it takes about 3 bars, so the distance is about 150 miles. Now let's take a look at a model drawing of a car. These model drawings are also called blueprints. Yes, you can use these drawings to build their life-size versions. You can see that this model drawing shows the real-world measurements of the car. I can use this information to build the car pictured here to its proper size. I see that the measurement between the front tires is 1,345 millimeters. This is a rather small car. I can look at the other measurements that are listed to continue building the car. Now it's time to review what we've learned. We've learned that a scale drawing is an accurately sized drawing that is either smaller or larger than real life. The legend tells us how much smaller or larger things in the drawing are. Examples of scale drawings and legends can be found in real-world maps and model drawings of things such as cars. You will find on the drawing itself a legend that tells you how big something is supposed to be in the real world. You can refer to this legend to find the distance between places on a map and to measure the size of objects in a drawing. A legend can say something like 1 inch, 12 inches, meaning that every inch in the drawing equals 12 inches in real life. The legend could also be a bar that looks like a ruler, which shows the distance in real life of that bar. We use this legend to read and interpret our scale drawings.
Before there were circles, the world was a very sad place. When you ordered a pizza, the delivery guy took forever to get to you. Then the pizza slices didn't always have helpful handles. And pepperoni? There was no pepperoni. There was only saber-toothed tiger sausage, which was kind of gamey. Fortunately, we now have circles. And while you may not think of circles as much more than those round shapes of pizza and wheels, they actually contain many interesting parts and properties. Let's take a closer look. First and foremost, let's define a circle. A circle is the set of all points that are a fixed distance from a center point. Every circle starts with a center. If you had a compass, you'd stick the point in that center, and then you could draw an infinite number of dots that are all the same distance from that center. Those dots would comprise your circle. The distance from the center to any point on the circle is called the radius. In your pizza, it's the length of your slice. If we consider the distance across the circle passing through the center, that's the diameter. When you use your awesome pizza slicer, which itself is a circle, to slice up your pie, you're cutting diameters. Well, if you can get it through the center, you are. I sometimes navigate around pepperoni slices in order to achieve equal meat distribution across all slices. I'm not proud of that. So how do you remember which line is the radius and which is the diameter? Well, the word radius is shorter than the word diameter, just like the radius is shorter than the diameter. Then there's the circumference. This is the distance around the circle. And stick with me here, the word circumference is the longest in letters of these three terms, and it's the longest part. You could also think about circumnavigating the globe. You're going around the planet. Those are the most critical parts of a circle. But there are more things you should know. We've been focusing on pizza, but there's another type of pie you've probably heard mentioned. That's pi without an e. This is the circumference of a circle divided by the diameter, or 3.14. Doesn't matter how big or small your circle is, the circumference divided by the diameter will always be 3.14. Actually, it's 3.14159265358979. Well, it goes on forever, but we usually just abbreviate it 3.14 or use this symbol. There are also other pieces of circles. For example, if you draw a line connecting 2 points on a circle, it's called a chord. This chord is an example of someone who doesn't really get how to slice a pizza. And that piece formed by the chord, that's a segment. That makes sense. It's a segment of a pizza. If the line doesn't stop at the edge of a circle, but goes on beyond it, it's a secant. That's your runaway pizza slicer. If you go to slice your pizza and totally miss, but just touch the edge, then you should probably slow down. But you also just cut a tangent into your table, which is a line that touches but doesn't cross a circle. Maybe you've heard tangent used in other contexts. For example, you might say that my opinion on equal pepperoni distribution is tangentially related to this lesson. It's connected, but barely. Finally, there's a name for a part of the circumference of a circle. That's called an arc. If we could talk about something other than pizza for a moment, I'd like to think of an arch, like the one in St. Louis. An arch is a curved shape that's like part of a circle, and an arc is very similar. But back to pizza. When you take an arc and connect its ends to the center, you have a sector. That's your traditional pizza slice. Depending on the length of your arc, your sector may or may not have as much pepperoni as everyone else's. You're at the mercy of the person slicing it. In summary, we looked at the many properties of the circle, or the shape created by the set of all points a fixed distance from a center point. There's the radius, which is the distance from the center to any point on the circle, and the diameter, which is the distance across the circle passing through the center. If we're looking at the distance around the circle, that's the circumference. We learned that pi is the circumference divided by the diameter, or 3.14. Then there were other fun parts like the chord, arc, and tangent. Finally, may all your geometry lessons require you to get pizza to study.
In recent years, a satellite television provider made some humorous ads in which a person with cable television eventually had some negative consequences. For example, one went like this. When you pay too much for cable, you throw things. When you throw things, people think you have anger issues. When people think you have anger issues, your schedule clears up. When your schedule clears up, you grow a scraggly beard. When you grow a scraggly beard, you start taking in stray animals. When you start taking in stray animals, you can't stop taking in stray animals. So, what we end up with is, when you pay too much for cable, you can't stop taking in stray animals. This sure seems like a strange conclusion, doesn't it? Reaching a conclusion is not always easy. Sometimes there is no correct answer. Even when there is one, it can be hard to know what it is. At the end of the lesson, I'll explain why there is a problem with the conclusion of these ads. But for now, let's consider conclusions in mathematics. Thankfully, when it comes to mathematics, the conclusion is not always so uncertain. The law of syllogism, also called reasoning by transitivity, is a valid argument form of deductive reasoning that follows a set pattern. It is similar to the transitive property of equality, which reads, if A equals B and B equals C, then A equals C. There are also 3 parts involved in the law of syllogism, and each of these parts is called a conditional statement. A conditional statement has a hypothesis, which follows after the word if, and it has a conclusion, which follows after the word then. A letter is used to represent each phrase of the conditional statement. Let me introduce the pattern, and then we can look at some examples. Statement 1. If P, then Q. Statement 2. If Q, then R. Statement 3. If P, then R. Statements 1 and 2 are called the premises of the argument. If they are true, then statement 3 must be the valid conclusion. Now that we know what a syllogism is, let's test our knowledge with some examples. First, an example with a valid conclusion. Statement 1. If it continues to rain, P, then the soccer field will become wet and muddy, Q. This becomes if P then Q. Statement 2. If the soccer field becomes wet and muddy, Q, then the game will be cancelled, R. This becomes if Q then R. Statement 3. If it continues to rain, P, then the game will be cancelled, R. This final statement is the conclusion, and it becomes if P then R. This follows the pattern for the law of syllogism, therefore it is a valid conclusion. Now let's try an example with an invalid conclusion. Statement 1. If the bank robber steals the money, P, then the sheriff will track him down, Q. This is if P then Q. Statement 2. If the sheriff tracks him down, Q, then the bank robber will be arrested, R. This is if Q then R. Statement 3. If the bank robber steals the money, P, then the bank robber will be rich, S. This is if P then S. Instead of building on Statement 2, this final statement simply offers another possibility of Statement 1. This does not follow the law of syllogism pattern, so Statement 3 is an invalid conclusion. Now we'll look at an example that we'll call valid conclusion possible. Statement 1. If the truck runs over some nails, P, then a tire will go flat, Q. If P then Q. Statement 2. If a tire goes flat, Q, then the deliveries will not be made on time, R. If Q then R. If this is all the information we have, then we know that statements 1 and 2 follow the pattern for the law of syllogism so far. Therefore, we know that a valid conclusion is possible for statement 3 before we even see it. However, for this statement to be truly valid, it must also follow the pattern. For example, statement 3. If the truck runs over some nails, P, then the deliveries will not be made on time, R. If P then R. Finally, let's take a look at an example where there is no conclusion possible. Statement 1. If she smells the flowers, P, then she will begin to sneeze, Q. If P then Q. Statement 2. If she has allergies, R, then she will have sinus troubles, S. If R then S. Since statements 1 and 2 do not follow the pattern of the law of syllogism, there is no conclusion possible for statement 3 using this law. Have you figured out what the problem was in the logic of the television ads? The law of syllogism makes an assumption that the first two statements are true. If these are not actually true, then the third statement may not be reasonable. The example of the television ad didn't use exactly the same wording as we have used in our examples, but the idea is the same. The ridiculous conclusions were the results of faulty premises. Let me illustrate this with another outlandish example. If I can hold my breath, then I can swim underwater. If I can swim underwater, then I am a fish. If I can hold my breath, then I am a fish. Remember, even though this follows the pattern of the law of syllogism, the conclusion is unreasonable because of some faulty premises. If, for example, you are using the law of syllogism to work a problem or complete a proof, then make sure that your premises are true. Mathematics requires logical decisions to be made. The law of syllogism is a pattern that can be used to help make a logical decision. If you presume that two statements are true and these statements follow the prescribed pattern for the law of syllogism, then there is a logical conclusion that can be reached by using this pattern. Statement 1, if P then Q. Statement 2, if Q then R. Statement 3, conclusion, if P then R. However, don't forget, the pattern will only yield trustworthy results if it is based on trustworthy premises.
Analogies are a popular way to make sure that people understand the connections between words or ideas. One of the most common forms of analogies is the part-to-whole analogy, in which a part of something is compared to the whole in a way similar to another part of something is compared to the whole. For example, fin is to fish as wing is to bird is a part-to-whole analogy, and works because it demonstrates that just as a fish uses a fin to move, So too does a bird use a wing to move. Clearly, there can be quite a bit of meaning packed into one of those analogies. Oftentimes, you'll be asked to solve analogies that are missing either the part or the whole. To do so, you'll have to follow a number of steps. First of all, establish whether or not it is the part or the whole that is missing on the side of the analogy that you're trying to solve. Keep in mind that there's no rule that says the part has to come before the whole. So instead of fin is to fish, you could have fish is to fin. To do this, you'll have to see how it mirrors on the other side. Second, look to the completed side of the analogy to figure out the relationship. In our earlier example, the relationship between wing to bird is that a bird uses a wing to move. It's a big help if you can write a sentence that is as detailed as possible to help with this stage. It isn't enough to say that a bird has a wing, but instead, try to find the deeper meaning of the analogy. From there, it's simply a matter of asking yourself what term would complete the analogy on the other side. Let's try an example in which the part is missing. Here's our analogy. Blank is to dining table as sheet is to made bed. First of all, what's missing? Look to the completed side. A sheet is a part of a made bed, right? In fact, you could say that a sheet is a covering for a made bed. Now, go back to the problem side. Since dining table came at the same point as the term made bed, we can assume that it is the whole, so we're solving for the part. What is a part of a dining table that covers it? A tablecloth, which happens to be the right answer. Now that we have solved an analogy missing a part, let's try solving for one that is missing the whole. For example, book is to blank as dishes is to china cabinet. Again, we could look at the completed side of the analogy and determine that the whole is the term that is missing. From there, try to come up with a sentence that describes the relationship between the terms of the completed side. For example, dishes are stored in a china cabinet. So where are books stored? A bookshelf, which is the term that completes the analogy. All right, let's review what we've learned. In this lesson, where we looked at analogies, i.e., a way to look at the connections between words and concepts, we learned that part-to-whole analogies compare the relationship between a part of a given whole. Often, they're compared in not only being part of the whole, but also the functional relationship. To solve them, first determine if the part or the whole is missing. Then, write a sentence that describes the relationship between the two terms on the completed side of the analogy. Finally, just remember to ask yourself, what term would complete the same relationship, but on the side of the analogy that is missing a term?
Imagine that you are interested in measuring the level of anxiety of college students during finals week in one of your courses. You have 11 study participants rate their level of anxiety on a scale from 1 to 10, with 1 being no anxiety and 10 being extremely anxious. You collect the ratings and review them. The ratings are 8, 4, 9, 3, 5, 8, 6, 6, 7, 8, and 10. Your teacher asks you for a summary of your findings. How do you summarize this data? One way we could do this is by using descriptive statistics. Descriptive statistics are used to describe or summarize data in ways that are meaningful and useful. For example, it would not be useful to know that all of the participants in our example wore blue shoes. However, it would be useful to know how spread out their anxiety ratings were. Descriptive statistics is at the heart of all quantitative analysis. So, how do we describe data? There are 2 ways, measures of central tendency and measures of variability, or dispersion. You are probably somewhat familiar with the mean, but did you know that it is a measure of central tendency? Measures of central tendency use a single value to describe the center of a data set. The mean, median, and mode are all the 3 measures of central tendency. The mean or average is calculated by finding the sum of the study data and dividing it by the total number of data. The mode is the number that appears most frequently in the set of data. The median is a middle value in a set of data. It is calculated by first listing the data in numerical order, then locating the value in the middle of the list. When working with an odd set of data, the median is the middle number. For example, the median in a set of 9 data is the number in the 5th place. When working with an even set of data, you find the average of the two middle numbers. For example, in a data set of 10, you would find the average of the numbers in the 5th and 6th places. The mean and median can only be used with numerical data.
The mode can be used with both numerical and nominal data, or data in the form of names or labels. Eye color, gender, and hair color are all examples of nominal data.
The mean is the preferred measure of central tendency since it considers all of the numbers in a data set. However, the mean is extremely sensitive to outliers or extreme values that are much higher or lower than the rest of the values in a data set. The median is preferred in cases where there are outliers, since the median only considers the middle values. Knowing what we know, let's calculate the mean, median, and mode using the example from before. Again, the anxiety ratings of your classmates are 8, 4, 9, 3, 5, 8, 6, 6, 7, 8, and 10. Mean: 8 plus 4 plus 9 plus 3 plus 5 plus 8 plus 6 plus 6 plus 7 plus 8 plus 10 divided by 11 equals 74 divided by 11. The mean is 6.73. Median: in a data set of 11, the median is a number in the 6th place. 3, 4, 5, 6, 6, 7, 8, 8, 8, 9, 10. The median is 7. Mode: the number 8 appears more than any other number. The mode is 8. We've got some pretty solid numbers on our data now, but let's say that you wanted to look at how spread out the study data are from a central value, i.e. the mean. In this case, you would look at measures of dispersion, which include the range, variance, and standard deviation. The simplest measure of dispersion is the range. This tells us how spread out our data is. In order to calculate the range, you subtract the smallest number from the largest number. Just like the mean, the range is very sensitive to outliers. The variance is a measure of the average distance that a set of data lies from its mean. The variance is not a standalone statistic. It is typically used in order to calculate other statistics, such as the standard deviation. The higher the variance, the more spread out your data are. There are 4 steps to calculate the variance. 1. Calculate the mean. 2. Subtract the mean from each data value. This tells you how far each value lies from the mean. 3. Square each of the values so that you now have all positive values. Then find the sum of the squares. 4. Divide the sum of the squares by the total number of data in the set. The standard deviation is the most popular measure of dispersion. It provides an average distance of the data set from the mean. Like the variance, the higher the standard deviation, the more spread out your data are. Unlike the variance, the standard deviation is measured in the same unit as the original data, which makes it easier to interpret. It is calculated by finding the square root of the variance. Let's calculate the measures of dispersion using the examples from before. Remember, the anxiety ratings of your classmates are 8, 4, 9, 3, 5, 8, 6, 6, 7, 8, and 10. Range: 10, the largest number, minus 3, the smallest number. The range is 7. Variance: this is a multi-step process. 1. Calculate the mean. We can see here it's 6.73. 2. Subtract the mean from each data value, as shown on the table. 3. Square each of the values so that you now have all positive values. Then find the sum of the squares, which is 46.18. 4. Divide the sum of the squares by the total number of data in the set to get our variance, 4.20. Standard deviation: the square root of 4.20 is 2.05 is the standard deviation. We know a lot about our initial data sampling now, but imagine that you wanted to take the anxiety ratings of the study participants and use them to draw the conclusion that the anxiety level of all college students during finals week is pretty high. You could not do this with descriptive statistics, since they simply describe the data in your study. However, you could use inferential statistics. Inferential statistics allow you to take the data in your study sample and use it to draw conclusions or inferences that extend beyond the study participants. In other words, descriptive statistics provide a description of the study data. Inferential statistics allow us to make inferences from our study data to the general population. Descriptive statistics describe or summarize a set of data. Measures of central tendency and measures of dispersion are the 2 types of descriptive statistics. The mean, median, and mode are 3 types of measures of central tendency. The range, variance, and standard deviation are three types of measures of dispersion. Inferential statistics allow us to draw conclusions from our data set to the general population.
It seems that as soon as one election season ends, the next one begins the next day, even though it won't actually occur for another 2 years. During that 2-year gap, news agencies and pollsters bombard us with all sorts of data and statistics predicting one thing or another. But, as you're going to learn thanks to this lesson, you need to be very careful when interpreting data and statistics, as looks can be very deceiving. The 1936 presidential election was a notable example of this. It was between Democratic nominee Franklin D. Roosevelt and Republican nominee Alf Landon. Let me summarize the polling data compiled by the Literary Digest prior to Election Day. Alf Landon will defeat FDR by 57 to 43%. The sample was obtained from a large enough number of people using questionnaires that were mailed to addresses obtained from telephone directories. How can we interpret this data? Well, it seems that a large enough sample was obtained to justify the statistics. That's good. But what about the methodology involved here? This is the hidden part about all these lies, darn lies, and statistics. The way the stats were compiled misconstrues the voting public's true overall opinion. Questionnaires were sent to people with telephones, but back then poor people who had telephones were in relatively short supply, and many of FDR's supporters were poor. The outcome of the election? FDR won with a massive 61% of the vote. So the next time you read any statistics telling you one thing or another, find out exactly how the data was obtained and how that in itself can really skew the results. Here's another wicked example of making sure you interpret data and statistics correctly. What if I told you that a newly approved second-generation pill increases the risk of getting a life-threatening blood clot by 100%? Meaning it has literally doubled the chances that you'll get a blood clot compared to a now discontinued first-generation pill. How likely would it be that you would take the new pill? Not likely, right? I mean, that's pretty scary. The thought of having to take a new pill increases your chances of probably dying by 100% or double that of an old pill. But what if I were to give you the real data behind this? Of the 7,000 people who took the first-generation pill, only one had a life-threatening blood clot. Of the 7,000 people who took the second-generation pill, 2 had a life-threatening blood clot. An increase from 1 to 2 is indeed a doubling, an increase of 100%. However, the actual risk of getting a blood clot increased from 0.014% to 0.029%. Would you be scared of taking the second-generation pill now if the chances that you'll get a life-threatening blood clot are still way less than 1%? Probably not. And here's another cool example. Not long ago, a famous toothpaste company, Brand X, we'll just call them, claimed in its ad that 80% of dentists recommend their toothpaste. Logically, this would make you think that 20% would recommend an entirely different brand, right? In other words, 80% of dentists recommend brand X in preference to all other brands. Well, again, you need to be careful how you interpret statements like this. If you were to carefully look at the collection methodology for this study, you'd see that dentists could choose more than one brand that they liked, not just one brand. This meant that brand X wasn't recommended in preference to all other brands. It was just one of many brands recommended, and in actuality, there was another brand that received almost as many recommendations as brand X as a result of the survey methodology. As you saw with the 1936 presidential election between Democratic nominee Franklin D. Roosevelt and Republican nominee Alf Landon, and the example between the two different pills, you need to really carefully read a passage and any supporting documentation about how the data and statistics were compiled. It could very well be that while the numbers may seem overwhelming and strong on the surface, they are actually built on very weak footing.
When it comes to organizing data, there is no shortage of ways to present it. Just look at different shopping catalogs and you can see the different ways that data is presented. Your school schedule itself is an example of a way to organize data. All of these ways show you useful information in an organized and easy-to-understand manner. Why do we have visual ways of organizing data? We have all these different ways of organizing our data so that we can better understand our data. If our data were written down randomly with no order, then we wouldn't be able to make much sense of all that information. Take your school schedule, for example. If it was written out of order, would it help you to get from class to class throughout the day? It probably wouldn't. You'd probably get lost somewhere trying to make sense out of it. It is the same with all the other data that we have to deal with. And that is why in this video lesson, we are going to discuss two ways we can present or otherwise organize our data. We are going to talk about tables, data organized into rows and columns, and schedules, a special table for listing times and events. We will see how to create tables and schedules from data we have already collected, as well as how to read them. We actually see tables and schedules all around us. Your school schedule is a perfect example of a schedule. A shopping catalog is a perfect example of a table that we see and use often in real life. Creating and organizing tables and schedules is actually not all that difficult. Reading and understanding them is fairly straightforward and easy to do as well. So let's get going and see how we can create and then read a table. Say we had a list hidden in one of our sock drawers where we wrote all the items we ever wanted if we could afford it. It also has the prices of the items written down. We also made a note of where to buy the items from when the day came that we could afford them. The items include a convertible for $80,000 available at the local car dealer, a Great Dane puppy for $2,000 available from the local breeder, and a dream vacation island home for $500,000 available from the realtor. To write all this information down in table form, what I need to do first is to decide what kinds of information I have. I see that I have an item type, item price, and where to purchase the information. I begin creating my table by writing my kinds of information all on one row, leaving just a bit of space in between so I know that they are separate pieces of information. I draw a line underneath as well as vertical lines to separate my kinds of information. My next step is to fill in my table by writing the information for my items one line at a time. I use one line for each item, so if I begin my second line by writing convertible, I will write down the other information for the convertible in the other two spaces that are left on that line. I continue with my other items until I have filled in my table completely with all my data. Once I have written down all my data, I am done creating my table. That wasn't so hard, was it? To read our table, we can easily scan it to find the information we are looking for. Say we wanted to find the cost of our vacation home. We look at our table and look for the line where our vacation home is written down. Once we have found that line, we follow the line until we reach the column for the price of the item to find the cost of our vacation home. We see that it is $500,000. We follow this same method of finding information for any other kind of information that we are looking for. And this is how you read tables. Let's take a look at schedules now. To create a schedule, we need a list of times and the events associated with those times. For example, we can have a list of special dates and events that we have planned to go to. If our list has something like April 16, special dinner with special person, June 15, soccer tournament, and March 10th, day trip to small town, we can create a schedule out of this. Because our schedule is a special type of table, we begin creating our schedule in the same way as we did our table. We first write in our top row with the types of information we have on hand. What we have here is a date and an event. We then go on and fill in our table with the events that we've planned, one event at a time. Because this is a schedule, we will organize our list by writing down our dates from the earliest to the latest. We begin with our event for March 10th first. We then write the event for April 16th, then the one on June 15th. To read our schedule, we just go down our first column until we reach the day that we are concerned about to see what is going on for that day. If our schedule has times, we look for the row with our time to find out what is going on at that time. Alternately, we can look for the event to find out when that is happening. Now let's review what we've learned. We've learned that organizing our data visually helps us to better understand and read our data. We can do it by means of a table, data organized in rows and columns, or by a schedule, a special table for listing times and events. To create a table, we first begin by writing our types of data on the first row. Then each row after that will be for one item. So we will have one item per row. Each item will have the various descriptive types of data written down in the columns for that row. To create a schedule, we list our times and dates in chronological order, from earliest to latest, followed by our events in the next column. To read both tables and schedules, we look down one of the rows until we find the item we are looking for. We then read the information in the other columns to get our information.
One of the more fascinating ways to record data is to put the data in a graph. Two of the more popular graphs are bar graphs and pie graphs. In this lesson, we will examine how to read and interpret the information that can be found on these graphs. A bar graph is a graph that can be used to compare the amounts or frequency of occurrence of different types of data. Bar graphs are helpful when comparing groups of data and comparing data quickly. Let's look at the important parts of a bar graph. All bar graphs have a graph title, which gives the reader a brief overview of the type of data that the graph contains. The graph title in this graph is percentage of U.S. population that is foreign-born. Bar graphs also contain two axes that are labeled and also have a scale. The axis that is labeled at the bottom of the bar graph is referred to as the group data axis. This axis details information about the type of data that is displayed. The other axis in a bar graph is called the frequency data axis. This axis has a range of values that measures the frequency that the data occurs. The most important part of a bar graph is the bars. These bars provide an instant comparison of data in a graph. The reader can easily compare the data to see which measure occurs the most often, and if any data points have similar frequencies. Let's look at a different bar graph to sharpen our skills on labeling its parts. Looking at this new graph, there is one obvious difference. The bar graph is going horizontal instead of vertical like the first example. The title of this graph is Sport Shoe Sales, and is located at the top of our graph. The group data axis is located along the left side, which is directly under the bars. The title of the axis is Types of Shoes. The frequency data axis is located at the bottom of the graph and is labeled Average Cost. The bars of this graph are running horizontally. When reading a bar graph, it's important to pay attention to the intervals used on the frequency data axis. An interval is the amount of data that occurs between each section or tick mark. Looking at the graph Sport Shoe Sales, we can see that the frequency data axis is located at the bottom of the graph. Along this axis, we can see each tick mark represents $10. That is important because there is data between each of these tick marks. Data located between the two marks is often estimated to the closest value. For example, look at the bar for gym shoes. The bar for gym shoes ends between the $20 and $30 marks. The bar appears to be more than halfway between these 2 points, so a good estimate would be either $26 or $27. To read a bar graph, find the point where each bar would meet the frequency data axis. Let's look at the favorite syndicated programs 1999 to 2000. This graph is also displayed horizontally, so the frequency data axis is located at the bottom of the graph. Which program had almost 9% of TV household viewing? The answer is Jeopardy! Looking at the Jeopardy bar, it is slightly more than 9%, so a good estimate would be about 9.5%. Which program had the least percentage of TV household viewing? The answer is The Jerry Springer Show. The Jerry Springer Show had the shortest bar and lies between 3% and 6%. A good estimate would be 4.5%. Approximately what percent of TV viewing households watched Friends? Friends had slightly more than 6% of viewers. A good estimate for this would be 6.2% of viewers. Shifting gears slightly, let's look at another popular type of graph used to display and compare data. Pie charts, also referred to as a circle graph, is a circular graph used to show the relationship of a part to a whole. A pie chart displays its data in sectors, which are parts of the circle and are proportional to the other parts displayed in the graph. Pie chart values are represented by percentages, with each chart representing 100%. Let's examine a pie chart and identify the important parts. Looking at the pie chart, the first important part is the graph title. The graph that we are looking at is titled What Tops Pizza? It compares the most popular pizza toppings in relationship to one another. The title and the created picture used for this pie chart give the reader information about the type of data displayed in the chart. Another important part of this pie chart is the sectors. These sectors are different size areas that divide up the circle into proportional parts. This is such a tasty graph. Let's now examine how to read the information that it displays. Each sector in a pie chart is labeled with the sector title and its numerical data. In this chart, each sector is labeled with its percentage. All pie charts represent a whole amount which equals 100%. If you were to add up the percentages of each sector, it would equal 100%. For example, let's look at the pizza pie chart. The percentages listed in each sector are 13%, 14%, 19%, 43%, 4%, and 7%. By adding all of these percentages together, 13% plus 14% plus 19% plus 43% plus 4% plus 7%, it equals 100%. The size of each sector is also proportional to its percentage. For example, the largest sector is pepperoni at 43%. Since the pepperoni sector is the largest percentage, its sector is also the largest size. Using the data in the pie chart, we can calculate other values. For example, there were 1,000 people surveyed to create this chart. We can calculate the number of people who preferred each sector. In this pie chart, 14% of the people surveyed preferred mushrooms. To calculate the number of people who chose mushrooms in this survey, we would set up a proportion. The proportion would show X number of people out of 1,000 chose mushrooms, and 14% out of 100%. To solve this equation, we will cross multiply. Multiply 100 times X, which equals 100X, and 14 times 1,000, which equals 14,000. So, 100x equals 14,000. To solve this equation, divide by 100. 14,000 divided by 100 equals 140. So there were 140 of 1,000 people surveyed who selected mushrooms. Now let's look at a few more examples of these two important graphs. Let's first look at a fascinating bar graph about the best-selling games in the U.S., titled Game Crazy. Which game is the most popular game in U.S. history, and how many units have been sold? Looking at the graph, we can see that Uno has the tallest bar, meaning it is the most popular game. The bar for Uno is almost 2 million. A good estimate for the number of Uno games sold is 1.9 million. Which game has sold almost 1.3 million games? Looking at the bar on the left, 1.3 million would almost be between 1 million and 1.5 million. As I follow a line over between these two values, the Jenga bar appears to be the closest to 1.3 million. The other type of graph we talked about is a pie chart. Let's look at a pie chart that examines the earnings of college students beyond the classroom. The title of this pie chart is College Students' Earnings. How many students of the 2,000 students that were surveyed have no job? To calculate this total, we will set up a proportion X students over 2,000 students surveyed equals 33% over 100%. To solve this equation, we will cross multiply 100 times x, which equals 100x, and 33 times 2000, which equals 66,000. So 100x equals 66,000. To solve this equation, divide by 100. 66,000 divided by 100 equals 660. There were 660 students out of 2,000 surveyed who did not have a job. Let's review these two types of graphs. Bar graphs are graphs that can be used to compare the amounts or frequency of occurrence of different types of data. To read a bar graph, find the spot on the frequency data axis where the bar would meet. A pie chart can also be called a circle graph. A pie chart is a circular graph used to show the relationship of a part to a whole. All of the sectors in a pie chart add together to equal 100%. The data in a pie chart can also be used to calculate other data.
Line graphs are cool. They are cool to look at, and they provide so much useful information once you know how to read them. You know when you're looking at a line graph when you see a graph with a line connecting the data points. The line can be straight, or it can be curved, or it can look like a connect the dots line. Whatever the case, there is so much information to be gained from these graphs. Let's look at this line graph that shows us the number of correct math problems a particular friend of ours gets right in 1 minute over the course of a week. Our friend Joe is taking a timed math test every day for a week. He is given a minute to solve as many basic arithmetic problems as he can. At the end of the minute, his work is graded and the number of correct answers is noted down. Let's see what information we can gather from the line graph that was produced from his results. We see that on day 1, the first day, Joe didn't do very well with only one correct math problem. I see this by looking at the bottom x-axis first to locate day 1, drawing an imaginary line straight up, and then looking to find where our actual line crosses the imaginary line for day 1. I find the point where they cross, and then I draw another imaginary line across to see where it hits on the y-axis. I see that it hits the y-axis at 1, so Joe only got one correct math problem. I keep reading the graph to gain more information. I look at day 2. How many math problems did Joe get right that day? I see where my line crosses day 2, and I see that it is where the y-axis equals 5. So Joe got 5 correct math problems on day 2. On day 3, Joe got 8 correct answers. Day 4, he got 15. Day 5, it is 22. Day 6, Joe got 34 correct answers. And at the end of the week, on day 7, Joe was able to get 50 correct answers in 1 minute. Now that we've read our graph, what kind of interpretations can we make about Joe? Reading a bunch of mathematical information from a graph is kind of meaningless unless we can interpret the data. What do all the numbers we read from the graph tell us about Joe? Looking at the line, we see that it keeps getting higher and higher. That is good for Joe. We can see that as the line gets higher, Joe's number of correct answers also get higher. That means that Joe is doing really well. He's progressing in his math ability every day. He started out a bit slow, but then he started understanding more quickly. We can see this by the way the line curves slightly upwards. We can also make an interpretation of what may happen to Joe's mathematical ability if he keeps going. It would make sense for the line to keep following the same pattern of going up, so if Joe kept this up, he'd be able to do more math problems in a minute on day 8 and day 9. Whether this will happen, we can't be sure, but based on the information we have, it seems likely. We just can't say that it will definitely happen. Now, let's look at how we can read and interpret a line graph from a real-world scenario. We will see how being able to read and interpret the data will help us in our decisions. This particular line graph shows the cost of a cell phone plan that includes 250 minutes. This particular cell phone plan includes 250 minutes per month along with unlimited texting. The basic cost of the plan is $40 per month. Now, I read my line graph and see that after 250 minutes, my cost rises with the number of minutes. I went from $40 for 250 minutes to $65 for 300 minutes. That's a lot of money. I see the cost gets higher and higher the more minutes I use, all the way up to $115 for 400 minutes. Doing a little math, I figure out that for every 50 minutes I go over my 250 minutes, I have to pay $25 more. If I divide $25 by 50, I figure that for each minute over 250 minutes, I am paying 50 cents. I don't want to pay that much for a minute of talking if I go over my allotted time for the month. I stop and think about this for a minute. I have to think about how much I really use this cell phone. Will I use more than 250 minutes per month with a cell phone? 250 minutes per month works out to a little over 4 hours of talk time. Do I talk that much on the phone every month? Or do I text more? I like the $40 a month cost, but how likely am I to go over the 250 minutes? Answering these questions will help me decide whether I should take this plan or upgrade to the next higher plan. After some thought, I decide I will take this plan because I don't talk on the phone that much. Because I text more than I talk, this plan will work for me. What have we learned? We have learned that a line graph is a graph with a line connecting the data points. To read the graph, we look at the x-axis to find one part of what we are looking for. We then draw an imaginary line straight up. We look for the actual line to see where it crosses our imaginary line. Then we draw another imaginary line across from the point where our line crosses our imaginary straight up line to see where it meets the y-axis. We now know the information for that point. We can keep repeating the process until we have read all the points we are interested in. After gathering the data and looking at the line, we can make some interpretations about the data. If our line goes higher and higher, we can say that whatever it is keeps growing. If the line keeps going down, then it's shrinking.
Have you ever been in the middle of a test, happily going along question by question, trying to pace yourself, and all of a sudden, wham! They smack you with a huge scary graph and a whole page of questions about it. It takes you 5 minutes just to read the questions through, and another 5 minutes to try and interpret the graph. Complex chart problems are just as stressful as table problems during an exam. But just like you learned in our lesson on table problems, there are certain tactics that can help you get by. In this lesson, we'll walk through 2 chart problems and learn 3 simple rules for solving them efficiently. Our first chart problem describes a situation with enzymes. Let's see what it says. The graph below illustrates the percentage of maximum activity for 3 different enzymes over a range of pH levels. Use the graph to answer the following 3 questions. The first thing to do with a problem like this is to orient yourself to the x and y axes. Here's the line graph that the problem provides. Before you read through any of the questions, it's a good idea to read the axes titles and make sure you understand how the graph is supposed to work. The x-axis here is titled pH. We can see that the graph covers the full range of pH levels from 0 to 14. The y-axis measures enzyme activity in terms of percentages. When one of the lines reaches the height of the graph, that means that the enzyme represented by that line reaches the highest activity level at that pH. Now that we've oriented ourselves to the axes, we need to identify the trends of the chart. We need to be sure we understand the relationships that are represented by the lines in the graph. This will usually require us to remember the relevant material from our previous science studies. We already know that different enzymes peak in their activity at different pHs. This graph is just showing that relationship for 3 hypothetical enzymes. The first enzyme, A, reaches its highest activity at a low pH, like 3 or 4. Enzyme B peaks at a pH of 7, and enzyme C looks like it peaks around pH 11 or 12. The 3 lines cross over one another at intermediate pH levels. So at the pHs of 5 and 9, none of the enzymes are all that active. Alright, so we have a good understanding of what this graph is about. Now we can go ahead and look at the questions. Our first question asks which enzyme does best at pH 3. So looking at our graph, we'll find pH 3 along the x-axis. Move straight up to follow the y-axis, and we intersect with that line that corresponds to enzyme A. That was easy. We'll pick enzyme A. The next question asks us to do the same thing, only backwards. Instead of finding the enzyme that peaks at a certain pH, we need to find the pH at which a certain enzyme peaks. Our question reads, what is the optimum pH for enzyme C? You know that the optimum pH for an enzyme is the pH level at which it reaches maximum activity. So let's find the graph for enzyme C, locate the highest point, and then move vertically downward to see where we end up on the x-axis. We end up right around pH 11, so we'll choose pH 11 from our list of choices. Did you notice that in both questions we found our own answer before looking at any of the choices? It's usually best to answer the question on your own when you're solving complex chart problems. If you come up with the right answer before you look at the other choices, you'll save yourself from becoming distracted or even swayed by the other options available. Let's try this tactic with our third question. It reads, what is the order of enzyme activity from greatest to least at a pH of 8? Let's look at what's going on at pH 8 in our graph. If we go up from the x-axis, we first cross the line for enzyme A, then C, then B. So that means at a pH level of 8, enzyme B is the most active, enzyme C is less active, and enzyme A is the least active. Our answer to this question, without looking at any of the choices, would be enzyme B, then C, then A. Now, is that answer listed as one of our choices? Yep, it's right here. So we circle that answer, and now we're done the problem. Next, we'll try a chart problem that's a little bit harder. Here's what it says. The following chart illustrates how many families of species exist in the fossil record as a function of geologic time. Use the chart to answer the next 4 questions. This problem may look like it's going to take a lot of work, but remember that before you read through any of the questions, you should first orient yourself to the x and y axes. The x-axis here reads geologic time in millions of years ago. That word ago should tell you something important. Notice that the numbers down here run backwards, with the 0 at the right-hand side of the graph. Instead of counting up the years from left to right, we're counting back the years from right to left. This chart sort of functions as a timeline. And look, down here we have the different periods of geologic history labeled and sectioned off for us. The y-axis here reads number of families. They must be talking about families in a phylogenetic sense. Rather than tracking the number of species that existed through time, they've tracked organisms in larger groups, families. Now that we know what the axes represent, it's time to identify the trends of the chart. This line moves generally upward from left to right, meaning that over time, the number of families increased. That makes sense with what we know about the history of life on Earth. We started with just a few kinds of organisms, which diversified greatly over time. But we see 5 points where the line dips down. These must represent times when the number of families suddenly decreased. In other words, major extinction events. We can probably assume that the questions we're asked in this problem will relate to these 5 extinction events that are evident in the fossil record. It's finally time to read the first question. Remember to try and answer the question on your own before you go looking at any of the choices. Our first question asks us to identify which period had the largest number of families. Number of families is our y-axis, so we just need to find the highest point on our graph. This corresponds to the tertiary period on the x-axis, so that's our answer. The next question asks at which point the largest extinction occurred. This one's going to take a bit of thought. We can recognize the 5 extinction events, but how do we know which is the largest? It must be the one with the largest dip, the region in which the line plummets the furthest distance from top to bottom. We can eyeball each of the extinction events and see that this one in the middle is the largest. This event happened right at the end of the Permian period, so we'll pick this one as our answer. Our third question asks when the dinosaur extinction occurred. You probably know that dinosaurs went extinct 65 million years ago, so you could use that to find the answer on the x-axis of your graph. But the question gives us some information about the fossil record, that dinosaurs are found in the Cretaceous period but not the Tertiary. Therefore, they must have gone extinct near the end of the Cretaceous before the Tertiary began. We'll choose the answer that reads end of the Cretaceous period. Finally, our last question wants us to identify the extinction event that made the smallest impact on the number of families. Notice that they didn't say which is the smallest extinction. If they had, we would compare the heights of the valleys of each extinction event, just like when we were trying to find the largest dip. Sometimes the wording of a test question can lead you to believe it's asking something it's not. So pay close attention to the phrases they use, especially words like always, never, only, every, and except. When you're asked to identify the highest or lowest of something, be careful to note exactly what it is you're looking for. In this question, they're asking about how the extinctions affected the number of families at the time of the extinction. So we need to compare the size of the dips with the total number of families at each time point. We need the dip that accounts for the smallest percentage of existing families. It looks to me like these two are the smallest extinctions, but the first one makes up about 1/6 of the total, while the other extinction only knocks out about 1/10 of the number of families. This has got to be the extinction with the smallest total impact. It occurred at the end of the Cretaceous period, right before the Tertiary. The best answer choice for our conclusion is the Cretaceous-Tertiary extinction event. The next time you get smacked in the face with a complex chart problem on an exam, don't panic. Just try to follow the 3 rules we talked about. First, orient yourself to the X and Y axes. Read the headings and units and make sure you know what they mean. Next, identify the trends of the chart. Be sure you understand where the lines are going in a line graph and what it means for them to be shaped the way they are. Finally, when you're ready to read through the questions, try to answer the questions on your own. Reading through all of the choices might distract you from drawing your own conclusions from your chart interpretation. Take your time with problems involving graphs and charts, and you can solve them pretty easily. They're not nearly as scary as you might think. Taking a timed science exam doesn't have to be stressful. Usually, if you pace yourself and save the most difficult questions for the end, you won't have to worry about finishing on time. But one problem that trips up test-taking students is the multi-question problem involving a data table. These problems give you a scientific scenario and a table that sums up the relevant data. You're required to use and interpret the table to answer a series of questions. This whole process takes a bit of time. It can be unnerving to adjust to a longer problem like this, especially if you've gotten into the groove of taking your test one question at a time. Fortunately, you can learn a few simple rules that will help you streamline your process. Let's take a look at 2 test examples and learn how to get through these pesky table problems. First, we'll check out a 2-question problem involving a 2-column table. It reads, the following table contains data for a person's change in exhaled carbon dioxide in response to an increase in respiratory or breathing rate. Use the table to answer the questions below. The best thing to do with a problem like this is to scan the table first, before you read any of the questions. Many students make the mistake of jumping right into the questions before they understand the table. It doesn't take very long to read the column headings and get oriented to the information. Our first column shows the respiratory rates measured in breaths per minute. From top to bottom, the breathing rates gradually increase. The second column lists the concentration of carbon dioxide in exhaled air, measured in millimeters of mercury. It looks like the concentrations gradually decrease. So already we can tell that as breathing rate increases, exhaled carbon dioxide decreases. Maybe we'll be asked about that in this problem. Maybe we won't. But at least now we know what this table is about. Let's ask ourselves one more thing before starting. Does the table make sense with what we know about biology? In other words, would we expect exhaled carbon dioxide to decrease as breathing rate increases? It's always a good idea to verify the concepts that are referenced in a table problem. You'll want to identify the area of biology that this problem deals with. We know that carbon dioxide and oxygen are exchanged through the alveoli in our lungs. Blood carries carbon dioxide to the alveoli, where it diffuses through the membrane and into our lungs. That's where our exhaled carbon dioxide comes from. If we increased our breathing rate, there would be less time for gas exchange to occur. We'd gain less oxygen from every breath, and we'd lose less carbon dioxide from our blood. So it turns out this table does make sense. We would expect exhaled carbon dioxide to decrease as breathing speeds up. Now let's move on to our first question. What is the relationship between respiratory rate and carbon dioxide concentration? Nice, did you hear that? It's asking us something we've already figured out. We said that breathing rate increases while carbon dioxide decreases. But look at the options we're given in the answers. They're all worded in terms of proportionality and relationships. We can rule out option C because we know that there is a relationship. We can rule out D and E because we can see from the table that there aren't any wildly growing numbers that would indicate a logarithmic or exponential relationship. So is the relationship between breathing rates and carbon dioxide directly proportional or inversely proportional? In a direct relationship, both variables increase or decrease together. In an inverse relationship, one variable increases while the other decreases. That's the type of relationship we have, so that means A is our answer. The second question in this problem asks us to identify the line graph that accurately represents the data in the table. We're given 4 different choices. Now, instead of wasting our time with each little graph, we're going to try and answer the question for ourselves. For most multiple choice questions, you should try to answer the question on your own. This will encourage you to think critically, make you more confident of the answer, and save you from getting tripped up by other options. If we look at the table and imagine that we're plotting the points on a line graph, we'd end up getting a line that goes down as it moves to the right, a negative slope. You can do a rough sketch of this graph on your scratch paper if you're having trouble during a test. Now, we didn't get a perfectly straight line, so it doesn't match perfectly with any of our choices, but it's pretty obvious which one most accurately represents our data, so that's our answer. Now let's try a more challenging table problem. The following image depicts 4 lengths of sealed dialysis tubing submerged in a solution of 5% sucrose. Each dialysis bag contains a different concentration of sucrose inside. The bags were weighed before submersion, then weighed again every 15 minutes. Use the data in the table below to answer the following questions. Whoa, this looks like a tough table problem. But remember, don't look at the questions right now. Rule number 1 is to scan the table first. We're also going to look at the picture they gave us. It shows 4 different bags in 4 different beakers. The sucrose concentration is the same inside all the beakers, but we don't know what the concentrations are inside the dialysis bags. The table here will give us a clue. In the first column, we see time in 15-minute intervals over the course of an hour. Then we see the weights of each of the dialysis bags over time. Column C really stands out to me because its weight didn't change at all. It looks like bag B got heavier over time, and both bags A and D got lighter. So I know it's recorded in the table, but how does any of it relate to biology? This is where we need to verify the concepts. Think about the dialysis bags and why their weights are changing. The bags are sealed, so the only way they're gaining or losing weight is for water to diffuse in or out of the bag. Diffusion of water, we know, is called osmosis, and osmosis occurs across a semi-permeable membrane. If you didn't know before, you can easily figure out that dialysis tubing is semi-permeable. Remember, water diffuses through membranes when the solute concentration on one side is higher than the other. This question must be about osmosis between solutions of different solute concentrations. The dialysis tubing separates 2 solutions, one in which the solute concentration is 5% and one in which the solute concentration is unknown. We can only guess what the concentrations are inside the bags based on whether they gain or lose water through osmosis. That's what the table's for, and that's what they'll probably ask us about. Okay, first question. What accounts for the change in weight for bags A, B, and D? Don't forget to answer the question on your own. We already said the weight change is due to diffusion of water in and out of the bag. So now we can look at our choices and pick the one that fits our idea. The next question asks why bag C had no change in weight. If the weight changes were caused by osmosis, and bag C had no weight change, then it must have experienced no net diffusion of water. Bag C probably has a 5% sucrose concentration, which is equal to the solution surrounding the bag. So we'll pick this answer here. Let's take a moment to remind ourselves of the scientific terms that describe solutions. An isotonic solution is one which has the same solute concentration as its surroundings. Bag C contains the only isotonic solution here. Both A and D are hypotonic solutions because they have lower solute concentrations than the solution in the beaker. Bag B is the only one with a hypertonic solution. You can tell that bag B is hypertonic because it takes on water due to its higher solute concentration. Our third question in this problem asks which type of solution is contained in bag B, and we've already answered it, hypertonic. The fourth question wants to know which bag contains distilled water. Well, we know that distilled water doesn't contain any solutes, so whichever bag contains the distilled water is going to be hypotonic. But I see 2 hypotonic bags in this table. Which is the one with distilled water? Notice that bag D loses water more quickly than bag A. Bag D experiences a higher rate of diffusion, which would be caused by a greater difference in concentrations. So while both bags are hypotonic, bag D is more hypotonic than A. And you can't get any more hypotonic than pure water. So my guess is that bag A contains something like 1% sucrose, and bag D is the one with distilled water. The last question requires us to know about scientific experiments. It asks which one of these bags would be the control if we were testing diffusion rates. We know that the control in an experiment is supposed to be the one that experiences no variables. It provides a baseline against which to compare the other outcomes. Since bag C contains an isotonic solution, it wasn't meant to undergo any net diffusion. Bag C was the control in this experiment, so we'll pick C. Problem solving with tables can be difficult, especially during a timed test. But 3 simple rules can make it easier to solve the table problems efficiently. First, be sure that you scan the table first before reading any of the questions. Orient yourself to the column headings and the basic trends you see in the data. Second, verify the concepts that are laid out in the situation. Make sure the data table makes sense to you and identify the biological ideas that you'll need to reference. Once you're ready to read the questions, try to answer the question on your own before you look at the given choices. This will encourage you to think critically and keep the other options from distracting you. If you take your time with complex table problems, you'll find them no more challenging than the rest of your exam.
Probability is the likelihood of something happening. When someone tells you the probability of something happening, they are telling you how likely that something is. When people buy lottery tickets, the probability of winning is usually stated, and sometimes it can be something like 1 in 10 million, or even worse. This tells you that it is not very likely that you will win. The formula for probability tells you how many choices you have over the number of possible combinations. To calculate probability, you need to know how many possible options or outcomes there are and how many right combinations you have. Let's calculate the probability of throwing dice to see how it works. First, we know that a die has a total of 6 possible outcomes. You can roll a 1, 2, 3, 4, 5, or 6. Next, we need to know how many choices we have. Whenever you roll, you will get one of the numbers. You can't roll and get 2 different numbers with one die. So our number of choices is 1. Using our formula for probability, we get a probability of 1 over 6. Our probability of rolling any of the numbers is 1 over 6. The probability of rolling a 2 is 1 out of 6, of rolling a 3 is also 1 out of 6, and so on. Let's try another problem. Let's say we have a grab bag of apples and oranges. We want to find out the probability of picking an apple from the bag. One thing we need to know is the number of apples in the bag because that gives us the number of correct choices, which is the number of our possible choices in the top part of the calculation. We also need to know the total number of fruits in the bag, for this gives us the total number of choices we have, or the total number of options in the bottom part of the calculation. The person with the grab bag tells us there are 10 apples and 20 oranges in the bag. So, what is our probability of picking an apple? We have 10 apples, one of which we want, and a total of 30 fruits to pick from. Our probability is 1 out of 3 for picking an apple. If you compare this with our probability of rolling a number on a die, the probability of picking an apple from the bag is higher. It is more likely that we will pick an apple than that we will roll a particular number. In both cases, we can leave the probability in fraction form or we can convert it to decimal form. 1 out of 6 becomes 0.17 and 1 out of 3 becomes 0.33. Our total number of options will always outnumber our possible choices. So probability will always give you a number or fraction between 0 and 1. The closer the number is to 1, the more likely it is to happen. If the probability is 1, then this particular event will always happen. Having a probability of 0 or 1 are the only assured events in probability. Otherwise, things are only as likely as the probability to happen. No guarantees. The probability of uncertain events, such as rolling a die, only gives you the likelihood of something happening. It doesn't give you certainty. You can't be certain that the event will happen. Even though the odds of rolling a particular number on a die is 1 out of 6, rolling a die 6 times does not guarantee you will roll your number in those 6 times. There are instances where probability will tell you that you will definitely win if you try so many times. It is when there are only a limited number of combinations that you can pick from. Take the lottery, for example. There are only a limited number of combinations you can pick from. Although that is a large number, if you bought enough tickets so that you could mark every single combination, then you are guaranteed a win, because one of your combinations must be picked. So with odds of 1 out of 10 million, if you bought 10 million tickets and made sure to include every possible combination of numbers, you are guaranteed that one of them will win. Probability tells you the likelihood of an event happening. The lower the probability, the less likely it is to happen. The higher the probability, the more likely it is to happen. Probability is a number or fraction between 0 and 1. A probability of 1 means something will always happen, and a probability of 0 means something will never happen. Only a probability of 0 or 1 means certainty. All other times it means the likelihood of it happening, and it does not guarantee whether that something will happen or not. The only case where it does guarantee that something will happen if you try it so many times is in the case of a limited number of combinations, such as the lottery.
Cheyenne and her friends are playing a board game. Each person rolls a die on his or her turn and moves the number of spaces indicated on the die. Some of the spaces ask the player to pull a card from the deck of regular playing cards. Cheyenne needs to move 3 or 6 spaces to get to the next card space. Then, she needs to pick a black card or a 7. What is the probability of Cheyenne rolling a 3 or a 6 on the die? And what is the probability of Cheyenne picking a card that is a black card or a 7? In this lesson, you will learn about the addition rule of probability, which is a rule for finding the union of two events either mutually exclusive or non-mutually exclusive. Each of these scenarios represents an event in probability. The first event, rolling the die on either a 3 or a 6, is a mutually exclusive event, which is events that cannot happen at the same time. This Venn diagram represents the mutually exclusive events of rolling a 3 or a 6. Notice that there is no overlap between the two circles because the events cannot happen at the same time. The second event, picking a card out of a deck that is black or a 7, is an example of non-mutually exclusive events, where events that can happen separately or at the same time. This Venn diagram represents picking either a 7 or a black card from the deck. Notice that there is a place where the two circles overlap. This is because it is possible to pick a black card that is a 7. This is an example of non-mutually exclusive events because the two events can occur at the same time. Now let's look at how to use the addition rule of probability to find the probability of mutually exclusive and non-mutually exclusive events. Remember, rolling the die would be an example of a mutually exclusive event. The die cannot land on two sides at the same time, therefore the probability of each side of the die is mutually exclusive. You may also hear mutually exclusive events called disjoint events. When working with mutually exclusive events in probability, use the following formula. This formula is read as the probability of event A or B is equal to the probability of event A plus the probability of event B. To find the probability of mutually exclusive events, follow these steps. 1. Find the total of possible outcomes. 2. Find the desired outcomes. 3. Create a ratio for each event. And 4. Add the ratios or fractions of each event. First, the total possible outcomes of a 6-sided die are 6. You have 6 different possible outcomes when you roll the die. Second, find the desired outcomes. Cheyenne needs to roll a 3 or a 6. Therefore, a 3 or a 6 would be the desired outcome. A 3 appears on a 6-sided die once, and so does a 6. Remember this information for the next step. Third, create a ratio for each event. The first event, rolling a 3, would be a ratio of 1 over 6, because the die only has one side with 3 dots. The second event, rolling a 6, would also be a ratio of 1 over 6, because the die only has one side with 6 dots. Fourth, add the ratios or fractions of each event. This step will give you the probability of rolling a die and getting a 3 or a 6. 1 over 6 plus 1 over 6 equals 2 over 6, or 1 over 3. Therefore, Cheyenne has a 1 in 3 chance of rolling a 3 or a 6. Once she rolls a 3 or a 6, Cheyenne can land on a space that allows her to pick a card. She needs to pick a black card or a 7. Remember, picking a black card or a 7 card out of a deck of regular playing cards is an example of non-mutual events. If you are looking for the probability of two events happening at the same time, this is called the intersection of two events. Learn more about intersection in our multiplication rule of probability lesson. This is the formula for non-mutually exclusive events. This formula is read as the probability of event A or B is equal to the probability of event A plus the probability of event B minus the probability of event A and B. To find the probability of non-mutually exclusive events, follow these steps. 1. Find the total of possible outcomes. 2. Find the desired outcomes. 3. Create a ratio for each event. 4. Add the ratios or fractions of each event. 5. Subtract the overlap of the two events. First, the total number of possible outcomes of a deck of regular playing cards is 52, since there are 52 cards in a regular deck. Second, find the desired outcomes. Cheyenne needs to select a black card or a 7 card. Therefore, a black card or a 7 card would be the desired outcome. There are two suits that are black cards, spades and clubs. There are 13 cards for each suit. Therefore, the desired outcome of possibilities for a black card is 26. There are 4 sevens in a regular deck of playing cards, 1 7 for each suit. Therefore, the desired outcome possibilities for a 7 card are 4. Third, create a ratio for each event. The first event, selecting a black card, would be a ratio of 26 over 52. The second event, selecting a 7 card, would be a ratio of 4 over 52. I got these ratios by using the desired outcome number as the numerator and the total possible outcomes as the denominator. Fourth, add the ratios or fractions of each event like this. 26 over 52 plus 4 over 52 equals 30 over 52. You might be inclined to stop here and say that there is a 30 in 52 chance of picking a black card or a 7 card, but notice that we have the word "or" in that statement. That means you are not looking for a card that is a black 7, just all of the cards that are black and a 7. Therefore, you need to subtract the overlap of the two events in the probability. The probability of getting a black 7 is 2 over 52, because there are only 2 black 7s in the deck. Take this ratio and subtract from the previous probability like this. 30 over 52 minus 2 over 52 equals 28 over 52. Now we have the correct probability. Cheyenne has a 28 in 52 chance of selecting a card that is either a black or a 7. I'd say those are pretty good odds. Example 1. Abby is attending her first swimming competition. There are 7 girls she is racing against in the first heat. She has to place first or second to make it to the next level of the tournament. Assuming there are no ties, what is the probability Abby will get first or second? Abby has a 2 in 7, or approximately 29% chance of making it to the next level of the tournament. This is another example of mutually exclusive events. Abby can't get both first and second place. Therefore, there is no overlap of events. Because this is an example of mutually exclusive events, we can use this formula from the addition rule of probability. Abby has a 1 in 7 chance of getting first place and a 1 in 7 chance of getting second place. We can add these two probabilities together to find the probability of Abby getting first or second like this. 1 over 7 plus 1 over 7 equals 2 over 7. Example 2. Abby's team ranks first out of the other teams at the end of the swimming competition. The team goes out for pizza and ice cream afterward. There are 20 people on the team. 8 people order pizza and 12 people order ice cream. Out of the team, 5 people end up ordering both pizza and ice cream. What is the probability of a team member ordering pizza or ice cream, but not both? The probability of a team member ordering pizza or ice cream, but not both, is 15 out of 20, or 75%. This is an example of non-mutually exclusive events, since some of the team members were able to order both ice cream and pizza. The probability of a team member ordering pizza is 8 out of 20, since we were already given that information. The probability of a team member ordering ice cream is 12 over 20. First, we can add these two probabilities together. 8 over 20 plus 12 over 20 equals 20 over 20. You've probably decided at this point that there's something wrong, since there are only 20 people on the team. And that's because at some point there's an overlap in the numbers. Remember, some people ordered both pizza and ice cream. We knew from the problem that 5 people ordered both pizza and ice cream, so we need to subtract that probability, 5 over 20, from our problem like this. 20 over 20 minus 5 over 20 equals 15 over 20. Remember that probability is an estimation or a prediction in this case. We are trying to predict whether or not a team member would actually order both or one or the other. Therefore, we can only accurately say that there were 5 people that ordered both. We can say if a teammate does not order both, there's a 75% chance he or she will order one or the other. The addition rule of probability, which is a rule for finding the union of two events, either mutually exclusive or non-mutually exclusive. Mutually exclusive events are events that cannot happen at the same time. Non-mutually exclusive events are events that can happen separately or at the same time. To find the union of two events that are mutually exclusive, use this formula. The probability of event A or B is equal to the probability of event A plus the probability of event B. To find the union of two events that are non-mutually exclusive, use this formula. The probability of event A or B is equal to the probability of event A plus the probability of event B minus the probability of event A and B. Remember, the addition rule of probability helps you find the probability of event A or event B, not both events. To find the intersection of two events, check out our lesson on the multiplication rule of probability. Steve is campaigning to be a county commissioner on the board for his county. His friend Gary is a professor at the local college and has agreed to help Steve with his campaign. Gary and Steve are putting together campaign buttons for a rally they are both hosting in a few days. There are 30 buttons total. 13 buttons are blue and 17 buttons are red. Gary puts all of the buttons in a bag. Steve and Gary both want to wear red buttons to the rally. What is the probability that Gary will pull 2 red buttons in a row out of the bag without looking? To solve this problem, you need to understand the multiplication rule of probability. The multiplication rule of probability means to find the probability of the intersection of two events, multiply the two probabilities. When you want to know the probability of two events occurring, that is called the intersection of the two events. The multiplication rule of probability is used to find the intersection of two different sets of events, called independent and dependent events. Independent events are when the probability of an event is not affected by a previous event. A dependent event is when one event influences the outcome of another event in a probability scenario. To find the intersection of two events, whether they are independent or dependent, multiply the two probabilities together. Steve and Gary's button scenario is an example of dependent events. This is a slightly more complicated problem, so let's start with independent events first. Gary wants to help Steve in researching the voting trends of each of the towns in the county. Steve covers the 2 towns pretty well in his campaign. Steve talks to the townspeople about his policies. He passes out flyers and puts up signs in the 2 towns to spread the word about his candidacy. After doing this, Gary and Steve collect data about each town's feelings towards Steve as a candidate. Steve wants to know the probability of winning over the 2 towns in the county. This is an example of independent events because we are assuming that one town's voting patterns do not affect or depend on the other town. In Town A, 1 out of every 4 people felt favorable towards Steve as a candidate. Steve has a 25% chance of winning the votes from Town A. In Town B, 5 out of every 7 people felt favorable towards Steve as a candidate. Steve has a 71% chance of winning the votes from Town B. Steve asked Gary what is the probability of winning the votes in both towns. To figure this out, Gary will use multiplication rule of probability and this formula. This is the multiplication rule for 2 independent events. This formula is read: the intersection of event A and event B equals event A multiplied by event B. Event A is the probability of Town A voting for Steve, and Event B is the probability of Town B voting for Steve. To find the probability of both of these events happening, you can use the multiplication rule of probability by simply multiplying the two probabilities like this. 1 over 4 times 5 over 7 equals 5 over 28, or approximately 18%. To find the probability of two independent events occurring at the same time, simply multiply the two probabilities together. Remember, this is the intersection of two independent events. This is not looking good for Steve. Hopefully he will have better luck in the other towns. Let's return to our opening scenario. There are 30 buttons total. 13 buttons are blue and 17 buttons are red. What is the probability that Gary will pull 2 red buttons in a row out of the bag without looking? The first time Gary pulls a button out, he has the probability of 17 over 30, or approximately 57%. The numerator in this probability exercise is 17, the total number of red buttons. The denominator in this probability exercise is 30, the total number of buttons. If he does not put this button back into the bag, then the second probability of Gary pulling a red button from the bag is 16 over 29, or approximately 55%. The numerator in this probability exercise is 16, the total number of red buttons remaining in the bag. The denominator in this probability exercise is 29, the total number of buttons remaining. To find the intersection of these two events using the multiplication rule of probability, simply multiply the two probabilities together. 17 over 30 times 16 over 29 equals 0.308, or approximately 31%. This means that Gary has a pretty good chance of pulling out 2 red buttons independently, but for both to happen together is pretty unlikely. Now that you understand the multiplication rule of probability, let's practice with a few examples. Example 1. Lisa is baking cookies. She bakes a batch of a dozen cookies with peanut butter and chocolate chips, and one batch of a dozen cookies with just chocolate chips. When she finishes, she places both batches onto a platter together. What is the probability of someone selecting 2 plain chocolate chip cookies in a row? The correct answer is approximately 24%. The second cookie selection is dependent upon the first cookie selection, since the person will not be putting the cookies back. Therefore, the first cookie selection changes the probability of the second cookie selection. The first probability will be 12 over 24, or 50%. The first number is the number of plain cookies, and the second number is the total number of cookies. The second probability is 11 over 23. The first number is the number of plain cookies minus the first one that was selected. The second number is the total number of cookies minus the first cookie that was selected. Now multiply the two probabilities to find the intersection using this formula. 12 over 24 times 11 over 23 equals 24%. Example 2. Lisa, Gary, and Steve are playing a game at their weekly game night get-together. They decide to play Pretzel first, a game that has different colored squares on a mat where each player places a hand or a foot on a different color depending on the spinner. There are 2 different spinners. One is labeled right hand, right foot, and left foot. The second spinner is labeled with colors. There are 4 purple squares, 3 blue squares, 4 pink squares, and 3 orange squares, randomly arranged on the spinner. What is the probability of Gary getting left hand purple square? The correct answer is 7%. The 2 spinners are separate spinners, and they do not affect one another. Therefore, we have 2 independent events. We can determine the probability of the intersection of these independent events by using this formula. The probability of getting left hand is 1 out of 4, since there are 4 selections on the spinner and only 1 is the left hand. The probability of getting purple square on the second spinner is 4 out of 14, since there are 4 purple squares with a total of 14 squares on the spinner. To find the intersection of these independent events, simply multiply the 2 events like this. 1 over 4 times 4 over 14 equals 0.07, or 7%. You will often have to find the intersection of two events in probability. The intersection of the two events can be found by using the multiplication rule of probability, which means to find the probability of the intersection of two events, multiply the two probabilities. How you use this rule is dependent upon the types of events you are working with, independent or dependent. Independent events are when the probability of an event is not affected by a previous event. A dependent event is when one event influences the outcome of another event in a probability scenario. You can use the multiplication rule with many probability exercises. Just make sure you understand the types of events you are working with first.
In business, being able to predict the future is no small part of succeeding. No, I'm not suggesting that you resort to crystal balls or tarot cards. In fact, those would probably prove to do more harm than good. However, being able to make the most accurate predictions possible based off of a set of facts is a key skill. That is one of the reasons that Bayes' theorem is so useful. Unlike simple probability, which only tests the probability of unrelated events, Bayes' theorem allows us to run probability tests on dependent events. This allows us to more accurately base predictions on required events, which themselves are not guaranteed. In this lesson, we're going to learn how to use Bayes' theorem, including a walkthrough of the math involved, before trying it all out in a real-world example. Before we move on, I want to be sure that you really get just how amazing of a thing this is for business. Before Bayes, it was impossible to really get a handle on how related events would interact. Since so much in business follows on established events, being able to calculate the probability of events makes business predictions so much more accurate. Not only does Bayes' theorem allow us to check for future events, but also control for false positives. While not as much of a concern in the business world, the scientific and healthcare uses of Bayes' theorem allows for people to calculate the chance that someone identified as a positive match by a test could indeed be a false positive. As you might expect, this information is itself very useful in diagnoses of patients. Back to business. Now let's make sure you know how to use the math involved in the Bayes' theorem. From the first, it's a pretty intimidating formula. The probability of A happening if B happens is equal to the probability of A happening times the chance of B happening if A is true divided by the probability of just B happening. Even saying it is a mouthful. However, let's think it through. First of all, let's start with the easy side of the equation. By saying probability of A happening if B happens, I mean exactly that. The chance of A happening after B has already occurred. That's what we're trying to solve. Meanwhile, the hardest part of the rest of that is the chance of B happening if A is true. Isn't that the opposite of what we're trying to solve? Well, not exactly. In fact, we're seeing if there is even a chance of A and B coexisting. If the two couldn't coexist, then the whole thing goes to zero. Also, notice that because you're dividing by the probability of B, that has to exist in a form other than zero, or else the math simply falls apart. Let's plug some numbers in to get an idea of how it works. Let's say you were calculating the chance of someone getting chosen for a job interview after getting selected for a summer internship. You know that the chance of being selected for the job interview is 0.1, while the chance of getting selected for a summer internship is 0.4. Meanwhile, the likelihood of those getting job interviews having been summer interns is 0.7. Now let's crunch some numbers. First, multiply the probability of the job interview by the likelihood of those getting job interviews having been first summer interns. 0.1 times 0.7 gives us 0.07. Now, divide that number by the probability of getting a summer internship, or 0.4. That gives us a final probability of getting chosen for a job interview after having been selected for an internship at 0.175. In this lesson, we learned how to use Bayes' theorem to be able to predict the outcome of dependent events. Remember that Bayes' theorem is that the probability of A happening if B happens is equal to the probability of A happening times the chance of B happening if A is true divided by the probability of just B happening. Also, be sure to bear in mind that the probabilities cannot equal zero. If the probability of A and B coexisting is 0, then the probability of A happening if B happens is 0, while if the probability of B happening alone is 0, you are then dividing by 0.
Independent events are events that do not affect the outcome of subsequent events. In an independent event, each situation is separate from previous events. An example of an independent event would be selecting a card from a deck of cards and then returning the card to the deck. After you return the card, select another card from the same equal deck. Dependent events are just the opposite. Dependent events are events in which the previous attempts affect the outcome of subsequent events. Dependent events are just like they sound. Each event is dependent upon what happened in the previous attempt. An example of a dependent event would be selecting a card from a deck of cards and not replacing the card. Then you draw another card from the now smaller deck of cards. The probability of an event occurring is a ratio that states the likelihood of an event happening. To find the probability of a single event, you will use the ratio of the number of favorable outcomes over the number of total outcomes. Let's look at an example. What is the probability of selecting a king from a standard deck of cards? Looking at the deck of cards, we know that there are 52 cards in each deck. The number of total outcomes is 52, because we could select any of the 52 cards when choosing at random. We can also see that there are 4 kings in each deck of cards, so the number of favorable outcomes would be 4. We can see that there is a ratio of 4 to 52 chances of selecting a king at random from a deck of cards. All ratios must be in simplest form though, so 4 over 52 will be reduced to 1 over 13. The probability of selecting a king at random from a standard deck of cards is 1 over 13. Sometimes you will be asked to find the probability of more than one event occurring in consecutive order. When this occurs, you will need to multiply both probabilities together to calculate the combined probability. Let's look at an example where you'll be asked to find the probability of more than one event occurring. What is the probability of rolling a standard die and getting a 2, and then rolling again and getting another 2? To start this problem, you will need to calculate the probability of each event happening independently. The probability of rolling a 2 on a standard die can be found by using the formula, the total number of favorable outcomes over the total number of possible outcomes. On a die, there are 6 total outcomes, and only one of the outcomes is a 2. So the number of favorable outcomes is 1, and the number of total outcomes is 6. So the probability of rolling a 2 is 1 out of 6, or 1/6. Since the probability of rolling a 2 is 1 out of 6, or 1/6, the probability of rolling a 2 on the next roll would be the same. To calculate the probability of both events happening together, we will need to multiply the two probabilities together. By multiplying these two probabilities together, you get 1 over 36, or 1/36. So, the probability of rolling a die and getting a 2, then rolling a die again and getting another 2, would be 1 out of 36. Again, independent events are the events that do not affect the outcome of subsequent events. The last situation was an example of an independent event. The rolling of a die and getting a 2 did not affect the outcome of the second event of rolling the die again. Each rolling of the die is an independent event. Let's look at another example of an independent event. Jamie and Sam were having a debate and decided the best way to settle their dispute was by flipping a coin. Jamie decided to be heads and Sam decided to take tails. Jamie is now curious. What is the probability that by flipping a coin 2 times they will receive a heads each time? To find this probability, Jamie must find out the probability of each event occurring separately. To calculate the probability, Jamie must use the formula, the number of favorable outcomes over the number of possible outcomes. Jamie knows that her coin has two sides and only one of them is heads. So the probability of Jamie getting a heads on her first flip is 1 out of 2. As the boys prepare to flip a coin for the second time, they know the probability of flipping a coin and getting a heads is 1 out of 2. The probability of getting a head on the second flip is also 1 out of 2. To find the probability of these two events happening together, we need to multiply these two probabilities together. When we multiply 1/2 times 1/2, we get 1/4. Jamie now knows that the probability of flipping a coin twice and getting heads both times is 1 out of 4, or 1/4. Just the opposite of independent events, dependent events are events in which previous attempts affect the outcome of subsequent events. Dependent events are just like they sound. Each event is dependent upon what happened in the previous attempt. Let's look at an example of these dependent events. James the superb magician likes to dazzle and amaze his audience with a card trick in which he selects 2 cards at random from a deck of cards, but announces the cards that he will select prior to selecting them. James asks for an audience member to join him for the trick. Wendy, a female audience member, raises her hand to volunteer. The crowd gives her a rousing applause as she makes her way to the stage. James explains to Wendy that he will select a card at random from the deck of cards. Wendy examines the deck of cards to make sure the deck is fair. James announces that he will first draw an ace from the deck. Wendy wonders what is the probability that James will select an ace from the deck of cards. She knows that there are 4 aces out of 52 cards. James explains to Wendy that he will now select another card from the deck, and it will also be an ace. Wendy is perplexed at how James could be lucky enough to draw 2 aces in a row from the deck of cards. She thinks to herself, what is the probability of James selecting an ace and then without replacing the card selecting another ace? Wendy knows that to find the probability of him selecting an ace from the deck of cards, she will need to use the formula total number of favorable outcomes over the total number of outcomes. In the first event, the number of favorable outcomes is 4 because James was selecting one of the 4 aces. The total number of outcomes is 52 because there are 52 cards in the standard deck of cards. So Wendy knows the probability of James selecting an ace on the first draw is 4 out of 52. James turns over the first card that he selected to show it in fact was an ace. The crowd cheers with excitement. Wendy now must calculate the probability of James getting an ace on the second draw. She knows that James did not replace the card, so there are only 51 cards left in the deck. She also knows that there could only be 3 aces left, because the first card he selected was an ace. So the probability of him getting an ace on the second draw was 3 out of 51, or 3 over 51. To find the probability of James getting an ace on the first card, and then without replacing it getting an ace on the second card, Wendy needs to multiply these 2 events together. She will need to multiply 4 over 52 times 3 over 51. By multiplying these 2 probabilities together, she gets 12 over 2,652. She reduces the fraction to 1 over 221. So the probability of James selecting an ace from a deck of cards and then without replacing the card, selecting another ace is 1 out of 221. Let's look at another example. What is the probability of selecting a spade from a standard deck of cards, and then not replacing the card, selecting an ace? By looking at this question, we know that this is a dependent event, because the card is not replaced. Therefore, the first event will affect the result of the second event. To calculate the probability of both of these events occurring, we will need to find the probability of each event separately, and then multiply the 2 probabilities together. To calculate the probability of the first event, selecting a spade from a standard deck of cards, we will use the formula total number of favorable outcomes over the total number of outcomes. In a standard deck of cards, there are 4 different suits, each containing 13 cards. So there are 13 spades in each deck of cards, which would be the number of favorable outcomes. The total number of outcomes would be the same as the number of cards in the deck, which is 52. So the probability of selecting a spade from a standard deck of cards is 13 out of 52. To make this problem easier, though, we can reduce the probability 13 over 52 to 1/4. Now let's find the probability of the second event, selecting an ace from a standard deck of cards of occurring. Remember that after the first event, the card was not replaced. This affects the number of cards that are now in our deck of cards. With one card selected, there are only 51 cards remaining in our deck of cards. So the total number of outcomes left is 51. As far as the number of favorable outcomes, one spade was selected in the first event, the card an ace of spades. Since this card was discarded, the number of favorable outcomes that we know for certain remain in our deck of cards is 3. We know that the probability of the second event occurring is 3 out of 51. And again, to make this problem easier, we can reduce that probability to 1 over 17. To calculate the probability of both events occurring in connection with each other, we need to multiply both probabilities together. So the first event of selecting a spade and then not replacing it was 1/4, and the probability of selecting an ace as the second event was 1 over 17. By multiplying these two probabilities together, we get 1 over 68 as the probability of both of these events occurring together. In this lesson, we've looked at two types of probabilities, independent and dependent events. Independent events are events that do not affect the outcome of subsequent events. To calculate the probability of an independent event, we use the formula total number of favorable outcomes over the total number of outcomes. Dependent events are just the opposite. Dependent events are events in which the previous attempts affect the outcome of subsequent events. The key difference is where the second event is affected by the first event. To calculate the probability of each of these events, we will use the same formula as we did for the independent event. But once you find the probability for each event, we multiply them together to find the probability of both events occurring together. Remember that to make the problem easier, we can reduce the probability if possible.
This video lesson is about trigonometric identities. These are the true statements about trigonometric functions. You can think of these as definitions, if you will. They explain trig functions by using simpler trig terms. Just like there are many definitions in the English language, there are many identities in the trig world. A simple math identity is 4 equals 3 plus 1. In trigonometry, a simple identity can be tangent equals sine over cosine. Notice that both statements are true. Both have also been written in simpler math terms. Do you remember how I said that there are all kinds of trigonometric identities, just like there are all kinds of definitions? Well, just like we can group our English words into categories, such as nouns, verbs, and adverbs, we can cluster our trigonometric identities into groups. And just like some words in the English language are more popular, some of our trigonometric identities are more commonly used. The ones that are the most common have already been categorized into 7 well-known groups. Do you want to see what they are? I'll show you along with the identities themselves. First, we have the basic identities. These are your basic definitions of your 6 trig functions. The second group is called the Pythagorean identities. These are called Pythagorean because they make use of the Pythagorean theorem, which says that for a right triangle, a squared plus b squared equals c squared, where c is the hypotenuse and a and b are the legs. The next group is called the angle, sum, and difference identities. These tell you how you can break down a trig function that involves the addition or subtraction of 2 angles. The fourth group is called the double angle identities. These tell you how you can simplify a trig function where the angle is doubled. The fifth group is called the half angle identities. Similar to the double angle identities, these tell you how you can simplify a trig function where your angle has been halved. For the sixth group, we have what is called the sum to product identities. These identities show you how to convert the sum or difference of 2 trig functions into the product of 2 trig functions. The seventh and last group is called the product to sum identities. Similar to the previous group, these show you how you can go from the product of two trig functions to the sum or difference of two trig functions. What you have seen so far is just a small sampling of all the trig identities out there. But if you can memorize these, then you are well on your way to becoming a trig expert, because these are the most commonly used identities in trigonometry. How are these identities used? Well, you will use these in solving problems on tests. You will encounter problems that ask you to recall a specific identity. You will also be asked to simplify a trig problem by substituting in these identities. And you will be asked to prove various trig statements with the aid of these identities. So what you will need is to couple your knowledge of these trig identities with your algebra problem solving skills to successfully answer these kinds of questions. Mathematicians also use these trig identities in their calculations in higher math to solve problems that involve integration. Do you want to see a sample problem? Okay, I'll show you one. What does sine of x cosecant of x equal to? Well, we can solve this problem by substituting in one of our basic identities. We have a sine function and a cosecant function. We can substitute 1 over sine of x for the cosecant of x. When we do that, we see that the signs cancel each other. What are we left with? We are left with just a 1. So our answer is simply and easily 1. Let's review what we've learned so far. Trigonometric identities are the true statements about trigonometric functions. If we liken them to definitions, we see that we have a lot of trigonometric identities, just like there are lots of definitions. We also have categories or groups, just like definitions. We have 7 groups of identities that are most commonly used. They are the basic identities, the Pythagorean identities, the angle sum and difference identities, the double angle identities, the half angle identities, the sum to product identities, and the product to sum identities. You will use these identities in helping you to simplify and prove trig problems.
You're studying for an upcoming math exam, and you see that on the list is solving trigonometric equations, equations containing trig functions. You start thinking back to what you learned about solving trigonometric equations, and you remember what the equations look like. You remember that the variable is part of the trig function's argument. You get equations like cosine x equals 1, and you need to find what x equals. You also remember that our answers repeat based on the trig function's period. You also think of trigonometric identities, or true trig statements, that you learned, such as the Pythagorean identity of sine squared x plus cosine squared x equals 1, and others. You remember that there are many trigonometric identities that have been formally proven over the years that you can refer to. But you only had to remember the ones that are used more often than the others, such as angle sum and difference identities, double angle identities, sum to product identities, etc. If you need to, take a moment to refresh yourself on these identities. Check out our lesson, Trigonometric Identities, Definition and Uses here on this site, or research them on the internet. You also remember that to get the variable by itself in an equation like cosine x equals 1, you need to apply the inverse function. So, cosine x equals 1 becomes x equals cosine to the negative 1 times 1. Each of our basic 3 trigonometric functions has an associated inverse function. The inverse of the sine function is called the arcsine. The inverse of the cosine function is called the arccosine. And the inverse of the tangent function is called the arctangent. In math, we note the inverse function with an exponent of negative 1. All this you remember. So, now it's about putting it all together to help you solve more complicated trigonometric equations. Let's take a look at a couple. Solve 2 sine x minus 1 equals 0 for x between 0 and pi over 2. To solve this problem, we need to first get our trig function by itself. We add the 1 to both sides and then divide by 2. We get sine x equals 1/2. We can now apply the inverse sine function to both sides to get the x by itself. We get x equals sine to the negative 1, 1 over 2. Looking at the unit circle, we have two possible answers that fit. We have pi over 6 and 5 pi over 6 radians. Which one is the correct answer? These answers do repeat every 2 pi as well, since our sine function has a period of 2 pi. So, how do we choose the correct one? We look at what the problem tells us about the possible answers for x. It tells us that our x needs to be between 0 and pi over 2. So, which one of pi over 6 and 5 pi over 6 is within this range? Pi over 6 is, so this is the correct answer. Let's look at one more. Solve cosine x sine squared x plus cosine cubed x plus 1 equals 0. This one looks a bit more complicated than the other one. This looks like it might have a trigonometric identity in it. Let's see if we can factor something out. We can factor out a cosine x from the first two terms. We get cosine x sine squared x plus cosine squared x plus 1 equals 0. Hey, isn't the leftover part of this factoring out the cosine x the Pythagorean identity? So that means we can substitute the whole part with a 1. We get cosine x times 1 plus 1 equals 0. Cosine times 1 is itself, so we can rewrite it as cosine x plus 1 equals 0. Subtracting 1 from both sides, we get cosine x equals negative 1. Taking the arc cosine of both sides gives us x equals cosine to the negative 1 of negative 1. Using our unit circle, we get the answer of pi radians. We know our cosine function has a period of 2 pi, so our complete answer is pi plus 2 pi times n, which tells us that our answer repeats itself every 2 pi. We have this for our final answer because our problem didn't limit our answer in any way, so we have to cover all of our answers. Let's review what we've learned. Trigonometric equations are equations containing trig functions. Trigonometric identities are true trig statements. To solve more complicated trig problems, we may have to simplify our problem by making use of our trigonometric identities before applying the inverse function to isolate our variable. We keep in mind that because all trig functions have a period, the answers repeat every so often. We have to make sure that we either cover all the answers based on the period of the function or that our answer is within the specified domain or possible range of solutions.
When I was younger, I wanted to learn how to cook. Since I had quite the sweet tooth, I thought the best way to learn was to start by baking cakes and cookies. I got good at it and wanted to make a huge cake for my sister's birthday. I thought there was no way I could learn it in time, but then someone told me a secret. All you have to do is make 3 normal cakes and stack them into a big cake. I didn't need special pans and utensils. I didn't need different ingredients. What I thought was a whole different task to master was actually just a small twist on something I'd done before. When we first learned to solve functions, we learned that the goal was to get the variable completely by itself on one side of the equation. After everything on the other side of the equal sign was simplified, you had your answer. When we're dealing with trig functions, it's the same way. We still want to get the variable by itself on one side of the equation. For the numbers, we do this the exact same way we've learned. We simplify and perform inverse operations to slowly isolate the variable. But at some point, we'll run into a trig function. At that point, we're trying to find the value of a variable that is inside of a trig function. This variable represents an angle, and so we want to find what angle measurement will give us a true statement. Here's the catch. Trig functions are all repeating functions, which means they do the same thing over and over in both the positive and negative directions. This means that there are multiple answers to trig equations, and sometimes we will want only certain answers. Trig equations can be solved in a specific domain to get a particular answer, or they can be solved by listing all possible answers. In this lesson, we will focus on finding a few possible answers to the equations. Let's look at some examples. Let's solve the equation 2 times cosine of theta plus 1 equals 0 and list two possible answers. First, we identify the variable, theta. This is what we want to isolate on one side of the equal sign. Since it is on the left side, we will start there. Let's do inverse operations to get theta by itself. We start with the plus 1. Since it is added, the inverse operation is to subtract 1. We do this on both sides of the equation. This simplifies to 2 times cosine theta equals minus 1. The next thing we need to undo is the multiplication of 2. The inverse operation is to divide by 2, and we also do this to both sides of the equation. This simplifies to cosine of theta equals negative 1/2. Now, all we have left on the left side of the equation is our trig function, cosine theta. We need to figure out what angle theta needs to be to have cosine of theta equal negative 1/2. Using the unit circle, theta equals 2 pi over 3 is one possibility, and theta equals 4 pi over 3 is another. There are infinitely many more possible answers that can be found by going around the unit circle multiple times. This topic will be covered in a later lesson. Solving trigonometric equations might look harder, but they're very similar to solving any equation for a variable. Find the variable you want to solve for and do inverse operations to simplify it. To undo trig functions, just think about what angle you would need to get the result stated in the problem.
In this video lesson, we will look at solving trigonometric equations. These are our equations involving the trigonometric functions. So our variable will be part of the trig function's argument. Do you remember your trig functions? We have our basic ones of sine, cosine, and tangent. We also have cosecant, secant, and cotangent. So our trigonometric equations will have at least one of these functions in the equation, such as f of x equals sine x plus 2. It could even have a combination of trig functions such as f of x equals cosine x plus cotangent x. Notice how our variable is part of the argument in both of these equations? This is what makes these equations trigonometric equations. In this video lesson, we do have one additional criteria that we are adding onto our trigonometric equations, and this is called a restricted domain. What does this mean? It means that we are limiting the possible values that our variable can be. Because we are working with trigonometric equations, our variable will be in radian units. So you will most likely see a pi in the restricted domain. For example, you might see f of x equals sine x plus 2. 0 less than x less than pi. This tells you that if you are solving this function, then you are looking for the solution that lies between 0 and pi. Remember that our trigonometric equations are all periodic, which means that the solutions repeat every so often. For sine and cosine, the standard period is 2 pi. For tangent, it is pi. Remember that your calculator only gives you the primary solution, and you might have to do some additional calculations to find the right answer that is within the restricted domain. Sometimes, if our domain is too restrictive, though, we may not have a solution at all. Let's look at a couple of examples. Solve f of x equals 5 cosine x. 0 is less than or equal to x, which is less than or equal to 2 pi. This problem is telling us to find the solutions f of x equals 5 cosine x. This we can easily do. But wait, it also tells us that our answers are limited to between 0 and 2 pi inclusive. So this means that when we find our answers, we have to make sure they are within this range. Let's see what comes of this. Solving for x means we set our equation to 0. We get 5 cosine x equals 0. To solve for x, we divide by 5 on both sides, and then take an arc cosine. We get x equals cosine to negative 1 of 0. What does this equal? Our calculator tells us that it equals 90 degrees, or pi over 2 radians. Are we done though? Have we found all the answers? Let's graph out our function to see. I have marked our restricted domain by labeling the x equals 0 point and the x equals 2 pi point. We just look between these 2 points to see how many times our graph crosses the x-axis. We see that it crosses the x-axis twice between these 2 points. That means that we have a total of 2 answers. We found our first one, pi over 2. So what is the second one? I have already labeled it on this graph, but if this print isn't labeled for you, then you can refer to your unit circle to help you find it. Looking at our unit circle, we see that another point where cosine x is equal to 0 is when x equals 3 pi over 2. So our 2 answers are pi over 2 and 3 pi over 2. Both of these answers are within the limits of our domain, so both are valid answers, and now we are done. Let's take a look at one more. Solve f of x equals sine x minus 1. 2 pi less than x, less than 3 pi. This time our problem is telling us to solve the equation f of x equals sine x minus 1. We can do that by setting this equation equal to 0. Sine x minus 1 equals 0. But wait, this time our domain is limited to between 3 pi and 4 pi non-inclusive. So our answer must lie between 2 pi and 3 pi. Okay. Let's solve our equation to see what we get first. Adding 1 to both sides, we get sine x equals 1. Taking the arcsine of both sides, we get x equals sine to the negative 1 of 1. The arcsine of 1 gives us 90 degrees, or pi over 2 radians. This is not within our domain. So, what do? We remember that our sine function has a period of 2 pi, so that means our solutions repeat every 2 pi. So, we can add 2 pi to pi over 2. We get 5 pi over 2. Aha! This is between 2 pi and 3 pi, so 5 pi over 2 is one of our answers. Do we have more, though? Let's graph this equation to see if we have more solutions within our domain. I have marked our domain using blue vertical lines, so we are looking for a solution between those lines. How many times does our graph cross or touch the x-axis between these lines? Only once. So that means we only have one solution. We already have that one solution, 5 pi over 2, so we are done. Let's review what we've learned now. We learned that trigonometric equations are the equations that include trigonometric functions. A restricted domain means that we are limiting the possible values that our variable can be. If your problem has a restricted domain, it will show it right next to the problem. When we have a problem with a restricted domain, it means that we need to find solutions that are within the restricted domain. We remember that our trig functions are periodic. Our sine and cosine functions have a standard period of 2 pi, and our tangent function has a standard period of pi. If a function is periodic, it means that solutions repeat every so often. When solving, our calculators will only give the primary answer. If this answer is outside the restricted domain, then we need to make an additional calculation based on the period of our equation to find the right answer within our restricted domain.
In this video lesson, we talk about trigonometric equations. What are they? Remember your basic trig functions of sine, cosine, and tangent? Well, your trigonometric equations are simply equations that include trig functions. For example, the equation sine of x equals 1 is an example of a trigonometric equation. Do you see the sine function in this equation? You will know that you are looking and working with a trigonometric equation if you see any one of the trig functions in the equation or any combination thereof. We have 6 of them. They are sine, cosine, tangent, and they're reciprocals of cosecant, secant, and cotangent. One more thing, trigonometric equations will also have the variable as part of the argument of the trig function. Like in our example, we had sine of x, where x is the argument of the sine function. To help us solve these types of problems, we can use the inverse trig function buttons on our calculator, a graphing calculator, or we can use the unit circle. Our special circle with a radius of 1 that has solutions to common angles for the cosine and sine functions. Keep watching and you will find out which one of these methods is the best. There is one interesting characteristic that trigonometric equations have, and that is that they have an infinite number of solutions. You might think this sounds weird, especially since your calculator only returns one answer. Let's look at the graph of the sine function, and you will see something interesting. Do you see the waves? Yes, our sine function graphs out as waves. Do you see that these waves keep crossing our x-axis? Well, every time our graph crosses the x-axis, when y equals 0, it gives us another solution. This graph keeps on going forever. What you get when you calculate inverse trig functions in your calculator is the answer closest to the origin. So if I wanted to solve sine of x equals 0, I would take the inverse sine of 0. I get an answer of 0 on my calculator, but in reality, sine x equals 0 has an infinite number of solutions. As you can see on the graph, I get 0 for sine of x every 2 pi spaces. So my answers are actually x equals 0 plus 2 times pi times n, where n stands for the number of extra solutions that we have. N increases by 1 each time. We get x equals 0 plus 2 times pi times 0 equals 0 for our first solution. The next solution is x equals 0 plus 2 times pi times 1 equals 2 pi. The next one is x equals 0 plus 2 times pi times 2, which equals 4 pi, and so on and so forth. This spacing is the period. It is different depending on the trig function we are using. The sine and cosine functions both have a period of 2 pi. This means that your answers are 2 pi spaces apart. The tangent function, on the other hand, has a period of pi. This means that these answers are pi spaces apart. These are the standard periods of our trig functions. These periods can be changed if our trigonometric equation is more complex, but we won't discuss that in this video lesson. So for this video lesson, focus on learning the standard period of the sine, cosine, and tangent functions. Just remember that sine and cosine share a period of 2 pi, while tangent, which doesn't sound like the other two, has a period of just pi. Let's look at how we use this information now. Solve 2 cosine of x minus 1 equals 0. To solve this, we use our algebra skills to first isolate the cosine of x. We first add 1 to both sides, then divide by 2. We get cosine of x equals 1/2. Now, we can use our calculator to perform the inverse cosine function to isolate the x, or we can go to our unit circle to see what angles will give an answer of 1/2 for our cosine function. One word of warning. If we use our calculator, we only get one answer. We may not get all the answers. Using the calculator in radians mode, we get x equals cosine to the negative 1, 1/2, which equals 1.047, or pi divided by 3. However, looking at our unit circle, we see that there are actually 2 angles that will give us an answer of 1/2 for our cosine function. We have pi over 3 and 5 pi over 3. Why is this? Well, let's go to the graph. Look at the part of the graph that crosses the y-axis, the part of the graph that curves up from y equals 0 and then goes back down to y equals 0 again. And you will notice that there are 2 places where we get y equals 1/2. That means we have 2 primary solutions. So finding the answers from the unit circle gives us the total number of solutions. Remember, we need to account for the period of our cosine function. Our solution repeats every 2 pi spaces. So our full answer is x equals pi over 3 plus 2 times pi times n, and x equals 5 pi over 3 plus 2 times pi times n. If our period is simply pi, then instead of a plus 2 times pi times n, we would have a plus pi times n. Let's review what we've learned now. Trigonometric equations are equations that include trig functions. Our trig functions are the functions of sine, cosine, tangent, and their reciprocals, which are cosecant, secant, and cotangent. One interesting characteristic of trigonometric equations is that they have an infinite number of solutions. For the sine and cosine functions, the solutions repeat every 2 pi spaces. For the tangent function, it repeats every pi spaces. This spacing is called the period. When solving trigonometric equations, it is better to use the unit circle so that all the answers can be found. Sometimes there are 2 primary solutions. After finding the primary solution, we must then take the period into consideration and write plus 2 times pi times n for the sine and cosine function, or plus pi times n for the tangent function. This period, this spacing, can change for more complex trigonometric equations.
You're probably familiar with the prefix tri. It pops up in a lot of places. There's trilogy, like the Star Wars trilogy. Okay, trilogies. There's triathlon, with its running, cycling, and swimming. There's trio, like Nirvana or Destiny's Child. What do all these have in common? Was Beyoncé in Star Wars? No. All these tri things have 3 of something. A movie trilogy has 3 movies. A triathlon has 3 events. And a trio has 3 members. And this is where a triangle gets its name and defining characteristics. A triangle is a 2-dimensional shape with 3 sides and 3 angles. Triangle. 3 angles. Yep, it's as simple as that. A power trio needs a guitar, drums, and bass. Likewise, a triangle has a few parts that come in 3s. There are its 3 sides, then there are the 3 angles. Without these sides and angles, it's not a triangle. You might hear these corners referred to as vertices, or vertex if it's just one. Vertex isn't unique to triangles. It refers to the corner of any shape, and in the triangle, there are 3 vertices. When you have a musical trio, like the Police, you usually have 3 people who all want to be the star. But while Stuart Copeland and Annie Summers can be awesome, they're not Sting. Sting is the star. I mean, he doesn't even have a normal name. His name is what bees do. It's no different in a triangle. Sure, they all have 3 sides, but when we work with triangles, we need a point of reference. There has to be a spokesperson. That's where the base comes in. The base is one side of the triangle. It's usually the bottom, but you can call any side the base. It doesn't matter. Oh, don't tell Sting we said that. The base is useful when we want to identify the dimensions of a triangle, such as when we're finding its area. The other dimension we want is the height. Wait, the what? Is it just another side? No. Think of the triangle like a mountain. Now, I live near the Rockies, so I'm often looking at 14,000-foot peaks and thinking about their amazing height. If a mountain is 14,000 feet, that's not the length of the trail to its top. No, it's the perpendicular distance from the base to the top. Well, supposing the base is sea level. For a triangle, the height is the same, the perpendicular distance from the base to the top. As with a mountain, this is sometimes also called the altitude. Oh, and the top can also be called an apex. This is also like a mountain. Apex is just another word for the highest point, or summit. You know how a 3-person band is usually set up? The drummer's in the middle in the back. Towards the front, to one side, is the guitarist. On the other side is the bass player. On a stage, we say things like downstage left or upstage center. In a triangle, we use terms like adjacent and opposite. These refer to sides in relation to angles. In our musical triangle, the drummer is at one angle in the back. This side, where the audience is called the opposite side. That's what you'd expect, right? The opposite side is opposite the angle in question. The adjacent sides are the sides next to the drummer. They're adjacent to the angle. For the guitarist in this angle, the side over here is the opposite side, and these 2 sides are adjacent. These are relative terms that change based on the angle we're discussing. We learned that a triangle is a 2-dimensional shape with 3 sides and 3 angles. Each corner is called a vertex, or vertices for more than one. We can label one side as the base, then a perpendicular line from the base to the top, or apex, of the triangle is its height. Each angle has an opposite side, the side furthest from the angle. The sides next to the angle are called adjacent sides.
In addition to the trigonometric functions that we are familiar with at this point, such as sine, cosine, and tangent, we also have what are called the inverse trigonometric functions. It is these functions that we will be talking about in this video lesson. What exactly are they? They are the inverse functions of our trig functions. However, in trigonometry, the inverse function here is not 1 divided by the function. This inverse function allows you to solve for the argument. For example, if you have the problem sine x equals 1, we can solve the problem by multiplying both sides by the inverse sine function. The inverse sine function cancels the sine function on the left side, and we are left with x equals sine to the negative 1 of 1. Evaluating the right side allows us to find the angle of the sine function that fits the problem. As you have just seen, the notation for these inverse trigonometric functions is unique. We use an exponent of negative 1 to let us know that we are dealing with the inverse trig function. We can write our inverse trig functions like this. This is the notation that you will see most often in textbooks and various trig problems. And this is most likely the notation you will use when writing out your problems. But in trigonometry, we also have formal names for these functions. We call the inverse sine function the arcsine function, and the inverse cosine function the arccosine function, and the inverse tangent function the arctangent function. While you will see the first notation more often in problems, you will come across these formal names in math discussions, so it's good to know both. It's easy to remember these names if you link the arc with the negative 1 exponent. All the inverse trigonometric functions begin with the prefix arc, followed by the name of the trig function that we already know. Now, think back to the regular trig functions of sine, cosine, and tangent. Do you remember their graphs? The red line is the graph of the sine function, the blue line is the graph of the cosine function, and the purple line is the graph of the tangent function. What interesting thing do you notice about these graphs? All of these graphs repeat every so often. The tangent function repeats every pi spaces, while the sine and cosine functions repeat every 2 pi spaces. Each time the function repeats, we get the same output answer. Because these functions repeat, we have to limit the range or output values of our inverse trig functions. Otherwise, we would get different answers each time. By limiting the range of our inverse function, we find the principal or primary value of our inverse function. This is what is going inside your calculator whenever you perform an inverse trig function. It gives you an answer within the accepted range. If we didn't limit our range, our calculator wouldn't know which answer to give you since the answers repeat every 2 pi for the sine and cosine functions and pi for the tangent function. The following are the accepted limited range for our inverse trigonometric functions. These ranges don't exactly correspond to how our regular trig functions repeat. This time, we have the inverse cosine function that is limited between 0 and pi. The inverse sine function is limited to between negative pi over 2 and pi over 2, including those points. The inverse tangent function has the same limited range as the inverse sine, except the 2 points of negative pi over 2 and pi over 2 are not included. What do these limits mean? These limits tell you that the answer you will get from your calculator will be within those limits. And if you are calculating by hand, these limits tell you that your principal answer needs to be within this range too. But keep in mind that the answer you get is just the primary answer. You have more answers spaced every 2 pi numbers apart for inverse cosine and sine, and every pi numbers apart for the inverse tangent. For example, sine to the negative 1 of 1 equals pi over 2. This is the primary answer, but in reality we have answers every 2 pi apart. We can include all our answers by writing pi over 2 plus 2 times pi times n, where n is the number of spaces the answer is away from the primary answer. Because our inverse functions are limited to their range, so is our function when we graph it. Instead of our functions continuing forever, like our sine, cosine, and tangent graphs, our arcsine, arccosine, and arctangent graphs only show the graph within the accepted limited range. This graph shows the arcsine function as the red line, the arccosine function as the blue line, and the arctangent function as the purple line. See how we have limited the graph of each of these functions? If we didn't limit them, these graphs would continue forever, repeating themselves over and over, just like our sine, cosine, and tangent functions. Let's review what we've learned. Inverse trigonometric functions are the inverse functions of our trig functions. Our trig functions are our usual functions of sine, cosine, and tangent. There are 2 ways to write our inverse functions. We can call them by name. We have the inverse of sine is arcsine, the inverse of cosine is arccosine, and the inverse of tangent is arctangent. We can also write them using the -1 exponent symbol. This inverse function allows us to find the angle of a trig function. For example, to find the angle for the problem sine x equals 1, we apply the inverse sine function to both sides of the equation. It cancels with the sine function on the left side, and we are left with x equals sine to the -1 of 1. We evaluate the right side to find our answer. We can use our calculator to find the answer. If we do, we will get the primary answer. Remember, our sine and cosine functions repeat every 2 pi spaces, and our tangent function repeats every pi spaces. Because our inverse functions are limited to the primary answer, each inverse function also has a limited range. They are as follows. Inverse function, range, y equals arcsine x, -pi over 2, less than or equal to y, less than or equal to pi over 2. Y equals arccosine x, 0, less than or equal to y, less than or equal to pi. Y equals arctan x, -pi over 2, less than y, less than pi over 2. The graphs of the inverse functions also shows this limited range. This graph shows the arcsine function as the red line, the arccosine function as the blue line, and the arctangent function as the purple line.
Just like we make use of our imagination when we daydream, we also make use of imaginary things in math when we talk about complex numbers. These are our math numbers with a real and imaginary part. They are written in the form a plus bi, where a is the real part and b is the imaginary part. Just like a daydream can play out like a television show, so do our complex numbers graph out like our regular xy points on the Cartesian plane. The only difference is that instead of an xy point, we now have an AB point. Our x-axis is now our real axis, and our y-axis is now our imaginary axis, but everything else is the same. What are some examples of complex numbers? We can have 1 plus 2i, or 3 minus 4i, or even -2 plus 7i. Turning them into coordinate points, we have 1, 2, 3, -4, and -2, 7. This video lesson is about turning our complex number into polar form, so let's talk about that now. Remember that in polar form, instead of a real axis and an imaginary axis, or an x-axis and a y-axis, we now label the same points with a radius and an angle, telling us how far in a counterclockwise direction we go from the positive x-axis or positive real axis. The conversion of our complex number into polar form is surprisingly similar to converting a rectangle, xy, point to polar form. The formulas are identical, actually, and so is the process. It is just that instead of x and y, we now have a and b. Our formulas are the following. When we use these formulas, we turn a complex number, a plus bi, into its polar form of z equals r cosine theta plus I sine theta, where a equals r cosine theta and b equals r sine theta. Be careful when you are calculating the angle. Look first into which quadrant your complex number graphs. If it is the first quadrant, then you can rely on your calculator's answer for the inverse tangent. If it lies in either the second or third quadrant, then you need to add 180 degrees, or pi, to your calculator's answer. Lastly, if the complex number lies in the fourth quadrant, then you need to add 360 degrees, or 2 pi, to the answer you get from the calculator. This is because your calculator only gives you the very first answer that fits, but this answer may not put you in the right quadrant. Let's look at an example. Convert 2 minus 4i into polar form. We have our a equals 2 and our b equals negative 4. Plugging these into our r equals the square root of a squared plus b squared, we get r equals the square root of 2 squared plus negative 4 squared, which is the square root of 4 plus 16, which equals the square root of 20, which is 4.47. Okay, we have found our radius. It is the square root of 20, roughly 4.47. Now we need to find our angle. We calculate theta equals tangent to the negative 1 times negative 4 divided by 2, which is equal to tangent to the negative 1 times negative 2, which equals negative 63.4 degrees. But wait, my complex number is in the fourth quadrant, so I need to add 360 degrees to this answer to get my real angle. I get negative 63.4 plus 360, which equals 296.6 degrees. Now I have my angle, too. I can now plug these into my polar form of my complex number. Z equals r cosine theta plus I sine theta, which is equal to 4.47 times cosine of 296.6 plus I sine of 296.6. My answer then is z equals 4.47 times cosine 296.6 plus I sine 296.6. I am done. That wasn't too bad. Just keep in mind the quadrant that your complex number is in when calculating your angle and make the proper adjustments. Now let's talk about de Moivre's formula. This formula tells us how to find the power of a complex number. Looking at the formula, we can see that it tells us that the power of a complex number is simply the arguments of the cosine and sine parts multiplied by the power. This makes our life rather easy. Let's take a look. We will continue with our complex number in polar form. Z equals 4.47 times cosine 296.6 plus I sine 296.6. Find z to the 10th power. First, we will rewrite our numbers as z equals square root of 20 times cosine 296.6 plus I sine 296.6. Now, z to the 10th equals 20 to the 5th times cosine 296.6 plus I sine 296.6 to the 10th. We got 20 to the 5th since a square root taken to the 10th power turns into the power of 5. We can go ahead and evaluate 200 to the 5th. It is 3,200,000. We now have z to the 10th equals 3,200,000 times cosine 296.6 plus I sine 296.6 to the 10th. Applying de Moivre's formula, we get z to the 10th equals 3,200,000 times cosine of 10 times 296.6 plus I sine of 10 times 296.6. This turns into z to the 10th equals 3,200,000 cosine 2,966 plus I sine 2,966. Evaluating this, we get z to the 10th equals 3,200,000 times 0.07 plus I 0.997, which equals 224,000 plus I 3,190,400. And we are done. Let's review what we've learned. We learned that complex numbers are math numbers with a real part and an imaginary part. They are written in the form a plus bi, where a is the real part and b is the imaginary part. To convert a complex number into polar form, we use these formulas. We are careful when calculating the inverse tangent. If our original complex number is in the second or third quadrant, then we add 180 degrees to our answer. If our original complex number is in the fourth quadrant, then we add 360 degrees. If we wanted to find the power of a complex number, then we used de Moivre's formula. To use this, we first convert our complex number into polar form, and then use de Moivre's formula to help us with the calculation of finding the power of our complex number in polar form.
Let's talk about shapes. There are all kinds of shapes, and they serve all kinds of purposes. If the wheels on your bike were triangles instead of circles, it'd be really hard to pedal anywhere. And if bowling balls were cubes instead of spheres, the game would be very different. Here, we're going to focus on a few very important shapes: rectangles, squares, and rhombuses. All of them are quadrilaterals. That just means they all have 4 sides. Remember that quad means 4. That means no pentagons or octagons will be discussed here. Sorry, fans of Department of Defense headquarters or stop signs. But even though they all have 4 sides, they all have their own special properties that make them unique. Let's start with rectangles. A rectangle is a 4-sided shape with all right angles. If you want to know if a shape is a rectangle, you just have 2 tests. Is it 4-sided? If both answers are yes, then you're looking at a rectangle. Rectangles are everywhere. Think about your average room. What's a rectangle in it? Doors? Tables? Windows? Posters on the walls? They're all 4-sided shapes with all right angles. Even the screen you're looking at right now is probably a rectangle. Rectangles have a few special properties. First, opposite sides are equal in length. In this rectangle, we know side AB is parallel to side CD, and BC is parallel to AD. Also, if we know AB is 6, then so is CD. If BC is 4, then so is AD. The fun thing about rectangles is that each pair of opposite sides can be a totally different length than the other pair. You can have a super skinny rectangle like this skyscraper, or a very even one like this old album cover. Now that old album cover fits both the definition of a rectangle and the definition of our next shape, the square. Squares are a very special subset of rectangles. A square is a 4-sided shape with all right angles and sides of equal length. Does that definition look familiar? Here are the steps to define a square. Is it 4-sided? Are all the angles 90 degrees? If yes, then you have a rectangle. If all the sides are the same length, then it's not only a rectangle, it's also a square. That means that all squares are rectangles. But not all rectangles are squares, since a rectangle's pairs of sides can have different lengths. Just like rectangles, squares are everywhere. In addition to the album cover, think about the spaces on a chessboard, stamps, floor tiles, even a snack of crackers and cheese. Because each side of a square has the same length, you don't need to be given much information to solve most problems. For example, if you see this square, where you know this side is 5, then you know all the other sides are 5 as well. So the perimeter of this square is 5 times 4, or 20. The area of a square is s squared, or 1 side squared. So the area of this square is 5 squared, which is 25. Then there is the rhombus. A rhombus is a little different from a square or rectangle. Here are the questions to ask if you think you're dealing with a rhombus. Is it 4-sided? Are all the sides equal in length? If both answers are yes, then what you have is a rhombus. Did you notice what was missing? Right angles. A rhombus doesn't need to have right angles. It can, but that's the big difference with a rhombus. I like to think of it like this. The word rhombus is kind of like the word rhino. If a rhino charges at a square and knocks it askew, it's not a square anymore, but it is still a rhombus. Rhinos or no, the definition of a rhombus is a 4-sided shape with sides of equal length. There are a few notable properties for rhombuses. First, the opposite sides are parallel. That's true for rectangles and squares too. But in a rhombus, even if the angles aren't 90 degrees, the opposite sides are still parallel to each other. So in this one, AB is parallel to CD, and AD is parallel to BC. Also, the opposite angles are equal. Here, angle A equals angle C, and angle B equals angle D. Plus, here's a fun one. If you draw diagonal lines from the corners, those lines form right angles. Since a square is a rhombus, that's true for squares as well. And no matter how far that rhino pushes the rhombus, those diagonals still form right angles. A square is a rhombus, but a rhombus isn't necessarily a square. And a rectangle can be a rhombus, but if the sides of a rectangle aren't all equal in length, then it's not a rhombus. In summary, we looked at three different types of quadrilaterals, or four-sided shapes. First, there's the rectangle, which is a four-sided shape with all right angles. Its opposite sides are parallel and equal in length, but each pair of sides isn't necessarily the same length as the other pair. Second, there's the square, which is a four-sided shape with all right angles and sides of equal length. A square is a type of rectangle, just one where all four sides are the same length. Finally, there's the rhombus, which is a four-sided shape with sides of equal length. The angles can be 90 degrees, but they don't need to be. So a square is a rhombus, but not every rhombus is a square. Triangles. They're the three-sided shape you see everywhere you look. They're the symbol for play and the sign to slow down. They're the ears on a cat and a slice of pizza. They're the gateway to the unknown and the monument to a long-ago empire. They're even the musical instrument calling us to dinner if we live on a 19th century farm. Though I don't know how you're watching this online video from a 19th century farm. Let's take a closer look at the many facets of this seemingly simple shape. First, let's define what we're talking about. A triangle is a polygon with three sides and three angles. You can remember that triangles have three sides and angles by that tri in the name. Tri means three, whether you're talking about geometry, tricycles, or triceratops. In a triangle, the interior angles always add up to 180 degrees. So in this triangle, if this angle is 60 and this one is 60, which is 120 total, then this other one has to be 180 minus 120, which is also 60. If you ever know two angles of a triangle, you can always find the third by remembering the 180-degree rule. Triangles that have particular properties get their own names. For example, this one. Notice that all the angles are the same. As you might guess, there's a direct correlation between the angles and sides. When the angles are all the same, so are the sides. So this is an example of an equilateral triangle, which is a triangle with three equal sides and three equal angles. Do you hear equal in equilateral? The term literally means equal sides. Some triangles only have two equal sides. A triangle with two equal sides and two equal angles is called an isosceles triangle. I think of isosceles triangles as an equilateral triangle's younger sibling. Its equalness is not as complete. Note that the equal sides are always opposite the equal angles. So if these angles are equal, then these sides are equal. Then there's the awkward cousin to equilateral and isosceles triangles, the scalene triangle. A scalene triangle is a triangle with no equal sides or angles. Scalene means unequal, but it doesn't sound like unequal. It sounds like scale. Think about yourself on a scale. If you're like me, you probably don't weigh exactly what you like to weigh. You're a bit, or more than a bit, off. And scalene triangles are out of balance too. None of their sides match. We just compared triangles by their sides and angles, but we also classify triangles by just their angles. For example, a triangle with a right angle, which is a 90-degree angle, is called a right triangle. That makes sense, right? Right angle, right triangle. But what if you have a triangle that's an acute triangle? The opposite of this is an obtuse triangle. You may know that an angle less than 90 degrees is acute, and an angle more than 90 degrees is obtuse. That's where these triangle names originate. You can also think of it this way. Acute means sharp or pointed. Think of an acute pain. Or forget the Latin derivation and just think of what makes acute triangle, small angles. Conversely, obtuse means dull or blunt. Let's imagine we're early humans making arrowheads to kill some woolly mammoths. If your arrowhead looks like this, acute triangles, you might feast on mammoth steaks tonight. Gamey. If they look like this, obtuse, they're duller, less pointy, and that mammoth may feast on you. Trampled to death. These names for triangles are not mutually exclusive. For example, An equilateral triangle is necessarily an acute triangle. Think about that. All equilateral triangle angles are 60 degrees, so they're all less than 90 degrees. Also, you can have an isosceles triangle that's also a right triangle. If one angle is 90 degrees and it's an isosceles triangle, the other angles must add up to 90, so they're each 45 degrees. Scalene triangles can be acute, obtuse, or right triangles. That seems fitting since most people feel out of balance on a scale. In summary, we learned about triangles, which are polygons with 3 sides and 3 angles. We looked at 3 main types of triangles. First, equilateral triangles are triangles with 3 equal sides and angles. Second, isosceles triangles are triangles with 2 equal sides and angles. Third, the awkward cut sides or angles. Then we looked at the angles of one right angle. Then there are acute triangles, where all angles are less than 90 degrees, and obtuse triangles, where one angle is more than 90 degrees. Now, I think I hear a triangle being played. Must be time for a 19th century farm dinner.
In this lesson, we're looking at the measures of central tendencies. The measure of central tendency provides us with statistical information about a set of data. The 4 primary measurements that we use are the mean, median, mode, and range. Each one of these measurements can provide us with information about our data set. This information can then be used to define how the set of data points are connected. To really examine these data points, let's take a look at a football game between the Green River Ducks and the Southland Bears. The first measure is the mean, which means average. To calculate the mean, add together all of the numbers in your data set, then divide that sum by the number of add-ins. For example, let's look at the Bears' first offensive series. They have plays of 16, 14, 12, and 18 yards on their way to scoring a touchdown. To find the average number of yards, or the mean, we would first add all 4 of these values together. 16 plus 14 plus 12 plus 18 equals 60. Since there were 4 numbers in our data set, you would then divide that sum by 4. So 60 divided by 4 equals 15. So the average number of yards that the Bears gained was 15 yards. The mean is used to show us the true average of a set of data. Another measure of central tendency is the median, which is the middle number when listed in order from least to greatest. You may have heard the word median before, and it was likely on a highway. On a highway, you have opposite lanes of traffic. In the middle of those lanes, there is typically a grassy area or a turning area. This area in the middle of the highway is referred to as a median. Let's return to our game in progress and see how the Green River Ducks are doing. On the Ducks' first offensive series, they had plays of 10, 6, 19, 21, and 4 yards before scoring a touchdown. Let's find the median number of yards gained by the Ducks. The first thing you need to do with this list of yardages is put them in order from least to greatest. So, in order from least to greatest, we would have 4, 6, 10, 19, and 21. Now that your yardages are in order from least to greatest, find the middle number. Since there are 5 numbers, the middle number would be the third value. The median value of the set of data is 10. On the first offensive series for the Ducks, their median yards gained were 10 yards. Occasionally there will be an even number of values, which would provide you with 2 numbers in the middle. If this occurs, you will need to average the 2 values. At halftime of our game, the Bears quarterback has passes for 3, 8, 9, 12, 12, and 15 yards. Let's find the median passes thrown by the Bears quarterback. The first step is to make sure your numbers are in order from least to greatest, which they are in this problem. The next step is to find the middle number. Since there are 6 numbers in this set, the middle number would be the third and the fourth values. Since there are 2 numbers in the middle, you will average them together. Add these 2 numbers together, 9 plus 12 equals 21, then divide by 2, and 21 divided by 2 equals 10.5. The median of this set of data is 10.5. So in the first half, the Bears quarterback had a median passing yardage of 10.5 yards. When looking at a data set, the median is used when there is an outlier, which is a number that is significantly greater or smaller than the rest of the data. In the second quarter, the Ducks had plays that were 21, 24, 26, 20, 56, and 20 yards. You can see that the value 56 is significantly larger than the other values. 56 would be an example of an outlier. Compared to the other yards that the Ducks gained, 56 yards was much greater than the other numbers they gained. The mode is another measure of central tendency that tells us the number that occurred the most often in your data set. When looking for the mode, there can be more than one mode or no mode. The mode can tell us the most popular choice. The Bears threw the ball to the following jersey numbers in the third quarter: 5, 6, 6, 3, and 4. You can see that there was only one receiver that had the ball thrown to him more than once. The mode of this data set would be 6. The Bears receiver number 6 was the most popular choice to throw the ball to in the third quarter. The Ducks threw the ball to the following receivers: 12, 13, 15, 17, 19, and 20. You can see that none of these receivers caught the ball more than one time. This data set has no mode. Entering the fourth quarter, the Bears had scored the following points: 6, 7, 3, 0, 7, 3, 7, 3. You can see that there are two values that repeat 3 times each. The mode of this data set is both 3 and 7, which can sometimes be referred to as bimodal. This means that the most popular scoring values for the Bears were 3 and 7. The last measure of central tendency is the range. The range is the difference between the highest and lowest values. Simply put, find the largest and smallest numbers and then subtract them. The range tells us the distance between the values in our data set. At the end of the game, the Ducks kickers had kicked field goals of 10, 14, 17, 19, 21, and 30 yards. Find the range. The smallest value is 10 and the largest value is 30. To calculate the range, subtract the two values. 30 minus 10 equals 20. The range of this data set is 20. Let's put our new skills into practice with an example. Let's find the mean, median, mode, and range of how many medals the U.S. has won over the last 6 Summer Olympics. To find the mean of this data set, we would add 104, 110, 101, 94, 101, and 108, and then divide by 6, because there are 6 values. So, 104 plus 110 plus 101 plus 94 plus 101 plus 108 equals 618. And 618 divided by 6 equals 103. So, over the past 6 Summer Olympics, the United States has been awarded an average of 103 medals. To find the median, we must first put the data in order from least to greatest. So our numbers in order from least to greatest would be 94, 101, 101, 104, 108, and 110. The middle of this data set is actually two numbers, 101 and 104. To find the median, we will need to add these two numbers together and divide by 2. So 101 plus 104 equals 205. Then dividing by 2 makes the median 102.5. Looking at this data set, we can see that there is only one number that repeats itself, which is 101. This means that the mode of this data set is 101. The range of this data set is found by taking the largest value, 110, and the smallest value, 94, and subtracting. So 110 minus 94 equals 16. So the range of this data set is 16. In this lesson, we've discussed the 4 measures of central tendency. These measurements can provide you with information about a set of data. These 4 measures are the mean, median, mode, and range. The mean means average. To find it, add together all of your values and divide by your number of add-ins. The median is the middle number of your data set when in order from least to greatest. The mode is the number that occurred the most often. And the range is the difference between the highest and lowest values.
Professor Greenfield is looking at the grades for his latest math test. He notices that his morning classes scored pretty well, with most of the students scoring a B on the test. Greenfield's second class is a little different. He notices that the grades are spread really far apart, with equal amounts of students scoring D's and B's. Professor Greenfield is looking at an example of unimodal and bimodal distribution. You're probably familiar with the concept of mode in statistics. The mode of a data set is the value that appears the most frequently in the data set. For example, if the data set was 3, 4, 5, 3, 7, 3, 10, the value that appears the most frequently would be 3. Therefore, 3 is our mode. So what do unimodal and bimodal mean? Take a look at our data set again. 3, 4, 5, 3, 7, 3, 10. Are there any other numbers that appear frequently in the data set? No. 3 appears the most and is the only number that is repeated. Because this data set only has one number that repeats, it is considered a unimodal distribution. Unimodal distribution is when the data set has a single mode. Professor Greenfield's first class, the one that scored primarily B's on the math test, would be considered a unimodal distribution. Sometimes, a single mode doesn't describe the data properly. Take Professor Greenfield's second class, for example. It wouldn't be fair to the people that scored the B's to say that most of the people in this class scored a D. Likewise, it wouldn't be an accurate representation of the data to say that most of the people in the class scored a B. So what do we do? This class is a great example of a bimodal distribution, where the data set has two different modes. Let's look at another data set. Professor Greenfield surveyed his students to see how many hours each student studied for the math test. Professor Greenfield came up with the following numbers: 1, 3, 2, 1, 5, 1, 4, 3, 2, 1, 1. Each number represents the number of hours each student spent studying. Look at this chart to see how the information is organized. Notice that 5 of the students spent an hour studying for the math test. That's more than any other number of hours. We can also see this data represented in a histogram. This is a histogram, a graphical representation of the distribution of data. Histograms are very similar to bar graphs. Histograms show us how frequently certain numbers appear in a set of data. In this particular histogram, we can see that the mode for this set of data is 1. Since this set of data only has a single mode, it is unimodal. You can see that the histogram only has one peak. This is a great visual cue to know if a data set has unimodal distribution. Now Professor Greenfield wants to know the breakdown of the math test. He reviews each test and figures out how many students got each answer right. Then he creates a histogram to represent this data. On this histogram, the horizontal axis represents the question number, and the vertical axis represents the number of students who got the question right. Notice that there are 2 peaks on this histogram. 9 students got question number 2 and number 5 correct. Because this set of data has 2 numbers that appear the most, it is considered to have bimodal distribution. Be careful when you are looking at bimodal distribution. You must have 2 distinct peaks of numbers. Look at this data set. 4, 6, 2, 10, 4, 7, 6, 4, 9, 7. Notice that the number 4 appears 3 times in this data set. The number 6 appears 2 times, and the number 7 appears 2 times. Although these numbers repeat in the data set, the number 4 is what appears the most. Therefore, 4 is the mode in this data set. Take a look at this data set. 3, 2, 3, 7, 2, 8, 3, 1, 3, 2, 2. Notice that the number 3 appears 4 times and the number 2 appears 4 times in this data set. Because both 3 and 2 appear 4 times, they are both the mode for the data set. Professor Greenfield can describe his data using unimodal and bimodal distribution. Unimodal distribution is when the data set has a single mode, like the professor's first class that scored mostly B's. Bimodal distribution is where the data set has 2 different modes, like the professor's second class that scored mostly B's and D's equally. The mode of a data set is the value that appears the most frequently in the data set. We can see the distribution in a data set using a histogram. A histogram is a graphical representation of the distribution of data. Now it's your turn. Good luck!
A conditional probability is a type of dependent event. Conditional probability involves finding the probability of an event occurring based on a previous event already taking place. To calculate a conditional probability, we must use the process of dependent events because the first event will affect the outcome of the second event. Let's review the topic of dependent events to help us better understand this process. Dependent events are events in which the previous attempts affect the outcome of subsequent events. Dependent events are just like they sound. Each event is dependent upon what happened in the previous attempt. Let's look at an example of dependent events. Walt has a big bag of gumballs. In his bag, he has 3 red, 6 green, 8 blue, and 2 orange gumballs. What is the probability that Walt will reach into the bag and select a red gumball? Then, without replacing the gumball, reach into the bag and select another red gumball. This probability will look like probability of red without replacing and drawing another red. We first need to find the probability of Walt selecting the first red gumball. By adding together all of the gumballs, we can see that there are 19 gumballs in the bag. There are 3 red gumballs in the bag, so the probability of getting a red gumball in the first draw is 3 out of 19, or 3/19. Next, we need to calculate the probability of Walt selecting a red gumball on his second draw. Remember, Walt did not replace the first gumball, and this will affect our totals. Walt now only has 2 red gumballs left in the bag, and the total number of gumballs is now only 18. The probability that Walt's second draw will be a red gumball is 2 out of 18, or 2/18. To calculate the probability of these 2 events occurring together, we would multiply the 2 events. 3/19 times 2/18 would equal 6 over 342. Remember that all answers must be in simplest form. 6 over 342 would be simplified to 1 over 57. Walt has a 1 in 57 chance of drawing 2 consecutive red gumballs without replacing the first gumball. Remember, a conditional probability is a type of dependent event. Conditional probability involves finding the probability of an event occurring based on the previous event already taking place. The difference is that with conditional probabilities, we are just looking at the probability of one specific event occurring. For example, thinking about Walt and his gumballs. Walt had 3 red, 6 green, 8 blue, and 2 orange gumballs. After first reaching in and selecting a red gumball, and without replacing, what is the probability that Walt's second draw will be another red gumball? Walt knows that the probability of the first gumball being red is 3 out of 19, or 3/19. Now he has 1 less red gumball and 1 less total gumball. We can see that the probability of Walt's second gumball being another red would be 2/18. Remember, all fractions must be in simplest form. 2/18 would be simplified to 1/9. The conditional probability that Walt's second gumball will be red after first drawing a red and not replacing it is 1 out of 9, or 1/9. Let's look at another example of conditional probability. A group of teens are preparing to play a game of dodgeball. There are 30 teens that have arrived to play, 19 boys and 11 girls. What is the probability that the second player to be out is a boy, after the first person out was also a boy? We know that if the first person out is a boy, that there will only be 18 boys and 29 teens total left in the game for the second round. We can now see that the conditional probability that a boy is the second person to be out in dodgeball, after the condition that a boy was the first out, is 18/29. This fraction is in simplest form, so the conditional probability is 18/29. Let's review the important facts that we need to remember when calculating a conditional probability. A conditional probability is a type of dependent event. Conditional probability involves finding the probability of an event occurring based on a previous event already taking place. To calculate a conditional probability, we must use the process of dependent events, because the first event will affect the outcome of the second event. The difference is that with conditional probabilities, we are just looking for the probability of that one specific event occurring.
William is a horse enthusiast. He loves everything there is about horses and horse races. His favorite horse, Big Bertha, is about to race at the local horse racing track. Another horse is racing at the tracks too. Sleepy Sally is a local favorite. William believes that Big Bertha will place first and Sleepy Sally will place second. Meanwhile, William's friend Derek is watching his favorite basketball team play in the final game of their regional tournament. William promises Derek they will have a big celebration if Big Bertha wins first and Derek's team wins the tournament. William needs to understand the relationship between conditional probabilities and independent probabilities to understand the likelihood of these two scenarios. Before we understand William's probability problem, let's look at a common probability example to explain conditional probabilities and independent probabilities. Let's say you have a deck of cards. How many aces are in that deck of cards? Right, there are 4 aces in a deck of cards. What is the likelihood that you will pull 2 aces in a row from a deck of cards? This is an example of conditional probability. Conditional probability is probability of a second event given a first event has already occurred. You can't find the probability of drawing 2 aces in a row if your first draw is a king. However, if your first draw is an ace, then you need to look at the deck in a whole new way to determine the probability of drawing a second ace. You have 2 events happening in this scenario. To pull 2 aces from the deck, you must consider that pulling a second ace out of the deck is dependent upon you pulling out that first ace. When you pull the first ace from the deck, you are leaving only 3 aces and 51 cards left in the deck. Therefore, this would be an example of conditional probability, where the first event influences the probability of the second event. This is conditional probability with 2 dependent events. A dependent event is when one event influences the outcome of another event in a probability scenario. Since pulling an ace from the deck changes the number of aces in the deck, this is an example of dependent events in a conditional probability. What if you wanted to look at the probability of drawing just 1 ace from the deck? In this case, you would only have 1 event to consider. This is known as independent event, which is when the probability of an event is not affected by a previous event. You can also have conditional probability with 2 independent events. This happens when you have 2 events that can occur independently. For example, I might want to know the probability of pulling an ace out of a deck of cards while my friend pulls a green marble out of a bag of red and green marbles. The probability of you pulling an ace out of the deck won't influence the probability that your friend pulls a green marble out of the bag. These 2 events have nothing to do with one another, therefore they are independent events. When we look at conditional probability, we write it like this in statistics. This is read the probability of A given B, meaning what's the probability of A if event B also happens. This is more common and is read the probability of B given A, meaning what's the probability of B if event A also happens. Let's get back to our scenario of William and Big Bertha. Remember that William wants to know the probability of Big Bertha getting first place and Sleepy Sally getting second place. We now know that is an example of conditional probability. There are a lot of scenarios that could happen here. Big Bertha could get first place and another horse could get second place. Similarly, Sleepy Sally could get second place and another horse could get first place. Therefore, we could say that the probability of Sleepy Sally getting second place is dependent upon Big Bertha getting first place. Then these events would be dependent and not independent events. However, Derek's basketball team has no relation or influence on Big Bertha's performance, and because of this, these are two independent events. Therefore, the probability of these two events happening can be looked at as independent conditional probability. If Big Bertha wins, the probability of Derek's team winning is the same as the probability of his team winning if Big Bertha loses. That means when you are looking at independent events and conditional probability, the conditional probability of P, B given A is the same thing as the probability of P event B. This is because event B is an independent event. Remember, the definition of independent events is when the probability of an event is not affected by a previous event. Therefore, even though this is a conditional probability problem, the probability of an independent event B is unchanged by the condition. Independent events are when the probability of an event is not affected by a previous event. This can happen when you have one event, such as pulling a certain card out of a deck of cards, or when you have multiple events, such as pulling a certain marble from a bag and pulling a certain card out of a deck of cards. If you want to know the probability of one event happening given a first event has already occurred, you are looking for conditional probability, which is the probability of a second event given a first event has already occurred. Conditional probability will look like this, and is read the probability of B given A, meaning what's the probability of B if event A also happens. Conditional probability can involve both dependent and independent events. If the events are dependent, then the first event will influence the second event, such as pulling two aces out of a deck of cards. A dependent event is when one event influences the outcome of another event in a probability scenario. If you leave the first ace out, then it influences how many aces you have left in the deck, 3. However, you can also look at conditional probability with two or more independent events, such as drawing a certain card from a deck and pulling a certain marble from a bag of marbles. The two events do not influence one another, but you can calculate the probability of one event given a first event has already occurred. The important thing to remember here is when you are looking at independent events and conditional probability, the conditional probability of probability event B given A is the same thing as probability of P event B. When you are dealing with independent events, the probability of event B is unchanged by the condition.
The Jackson Wildcats play basketball in a highly competitive city district. There are 8 teams in the district, and they all play each other once during each season. The coach of the Wildcats wants to know how many games will be played in the district this season. To calculate this amount, he will need to use a combination. A combination is an arrangement of objects where order does not matter. The coach knows that there are 8 teams, but the order of the teams play each other does not matter. One way the coach could calculate the number of games is to list out each team and the teams they would play. The coach realized, though, that there were some games that would be repeated when writing them out. So he researched and found a formula to calculate the number of combinations. The formula to calculate a combination is n combination r, which equals n factorial divided by r factorial times n minus r factorial, where n represents the number of items and r represents the number of items being chosen at a time. To calculate a combination, you must know how to calculate a factorial. A factorial is the product of all positive integers equal to and less than your number. A factorial is written as a number followed by an exclamation point. For example, to write the factorial of 6, you would write 6 exclamation point. To calculate the factorial of 6, you would multiply all of the positive integers equal to and less than 6. 6 factorial would equal 6 times 5 times 4 times 3 times 2 times 1. By multiplying these numbers together, we find that 6 factorial equals 720. Let's look at another example of how we would write and solve the factorial of 11. The factorial of 11 would be written as 11 exclamation point, or 11 factorial. To calculate 11 factorial, it would equal 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And after multiplying these together, that equals 39,916,800. The coach of the Wildcats now knows that he must use the equation n combination r, which equals n factorial divided by r factorial times n minus r factorial, where n represents the number of items and r represents the number of items being chosen at a time. Using this equation, he must select 2 teams for each game from the 8 teams in the district. So the variable n would equal 8 and the variable r would equal 2. The equations would then look like 8 factorial over 2 factorial times 8 minus 2 factorial. To solve this equation, we would first need to perform 8 minus 2 in the parentheses, which would equal 8 factorial over 2 factorial times 6 factorial. Next, we would expand 8 factorial, 2 factorial, and 6 factorial. 8 factorial would equal 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 factorial, which is 2 times 1, times 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. By multiplying 8 factorial on the top, it equals 40,320. And 2 factorial times 6 factorial on the bottom equals 1,440. Finally, we would divide 40,320 by 1,440, which would equal 28. The Wildcats coach now knows that there are 28 games that will be played in the district this season. With such a tough season ahead of them, the Wildcat coach knows that his team must have a lot of practice. He decided that the team would play 3-on-3 games to work on their skills. There are 12 players on the team, and 3 of them will be chosen for each team. The coach now needs to know how many combinations of teams that he could create. To use the equations, the variable n would equal 12, and the r variable would equal 3. The coach needs to use the equation NCR equals n factorial over r factorial times n minus r factorial. The coach then substitutes 12 in for n and 3 in for r. Next, he subtracts 12 minus 3 in the parentheses, which would equal 9. So now he has 12 factorial over 3 factorial times 9 factorial. Now let's expand the factorials. 12 factorial would equal 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 on top. And 3 factorial times 9 factorial on bottom would equal 3 times 2 times 1 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. The easiest way to calculate this combination is to cancel out common terms. Since 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 appears on the both top and bottom of this equation, those terms can be canceled out. The coach now has 12 times 11 times 10 on top and 3 times 2 times 1 left on bottom. The coach now multiplies the top, which equals 1,320, and the bottom, which equals 6. Finally, the coach would divide 1,320 by 6, which would equal 220. The coach could choose 220 different combinations of 3-player teams for his practice. A combination is an arrangement of objects where order does not matter. To calculate a combination, you must use a factorial. A factorial is the product of all positive integers equal to and less than your number. The equation to calculate the combination is n combination r equals n factorial over r factorial times n minus r factorial, where N represents the number of items and R represents the number of items being chosen at a time. When solving the equation, remember the easiest way to solve is by canceling out common terms on both the top and the bottom of your equation.
John is an avid card player. His favorite card game to play is poker. The best part about playing poker for him is the moment when the cards are dealt. John has always been curious about how many different ways he could organize his cards. John seemed to remember that this was called a permutation. He researched and found that a permutation is an arrangement of items or events in which order is important. The next time he played poker, he wanted to calculate how many different ways he could organize the cards that he was dealt. The dealer dealt him an ace of spades, 7 of clubs, 7 of diamonds, jack of hearts, and a 2 of clubs. To calculate this permutation, John needed to use 5 blanks to represent the 5 cards that he was dealt. He knew that he had 5 different cards to organize, so for the first card he could use any of the 5 cards. So John had 5 choices for the first card. For each subsequent blank, John had 1 less choice because he had used cards in the previous blanks. So in the third blank he had 3 choices, in the fourth blank 2 choices, and in the fifth blank 1 choice. John realized that he had 5 options for the first card, 4 options for the second card, 3 options for the third card, 2 options for the fourth card, and 1 option for the fifth card. To find the number of ways that he could organize his cards, he needed to multiply these numbers together. John multiplied 5 times 4 times 3 times 2 times 1, and the product was 120. John now knew that there were 120 ways to organize his poker hand of cards. Another way to think about permutations is to understand factorials. A factorial is the product of all of the positive integers equal to or less than your number. A factorial is written as a number followed by an exclamation point. For example, to write the factorial of 5, you would write 5 exclamation point. To calculate the factorial of 5, you would multiply all of the positive integers equal to or less than 5. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. By multiplying these numbers together, we can find that 5 factorial is equal to 120. Let's look at another example. How would we write and solve the factorial of 10? The factorial of 10 would be written as 10 exclamation point. To calculate 10 factorial, it would equal 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 3,628,800. When writing permutations, we use the notation NPR, where N represents the number of items to choose from, P stands for permutation, and R stands for how many items you are choosing. To calculate the number of permutations, we use the following formula. N permutation R is equal to N factorial divided by N minus R factorial. John is still playing poker and enjoying a lot of success. The dealer asks the group of 6 players if 4 of them would like to join a private game. John is curious about how many different ways the 4 players can be selected and in what order. Using the formula N permutation R, N would represent the total number of players, which is 6. The R term would represent the number of players that are being chosen, which is 4. Plugging these numbers into the formula gives us 6 permutation 4, which is equal to 6 factorial divided by 6 minus 4 factorial. To solve this equation, John will calculate 6 factorial and divide it by 6 minus 4 factorial. The first thing John must do is subtract the 6 minus 4 in the denominator to get 2. John's equation now looks like 6 factorial divided by 2 factorial. To calculate 6 factorial, John will multiply 6 times 5 times 4 times 3 times 2 times 1, which is equal to 720. And 2 factorial is equal to 2 times 1, which is equal to 2. So now we have 720 divided by 2, which equals 360. There are 360 ways that 4 players from John's table can be selected to play at a private table. Before heading to the private poker game, John stops by the snack bar where they make pizza. There are a total of 10 pizza toppings to choose from, but they only sell pizzas with 4 toppings, each separated by a layer of cheese. How many different pizzas can John make if the stacking order is important? To calculate the number of permutations, you would need to use the equation 10 permutation 4, which is equal to 10 factorial divided by 10 minus 4 factorial. The first step that John must do is subtract 10 minus 4, which is equal to 6. So 10 factorial divided by 10 minus 4 factorial is equal to 10 factorial divided by 6 factorial. To calculate 10 factorial, you would multiply 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. To calculate the 6 factorial, you would multiply 6 times 5 times 4 times 3 times 2 times 1. The easiest way to calculate the total number of choices is to cancel out common terms. Since 6 times 5 times 4 times 3 times 2 times 1 appears on both the top and bottom, these terms can be canceled out. So this would leave 10 times 9 times 8 times 7, which equals 5,040. John can make 5,040 different pizzas. So let's review what we've learned about permutations. A permutation is an arrangement of items or events in which order is important. Permutations help us find the total number of ways that items can be chosen when order does matter. A key tool in calculating permutations is factorials. Factorials are written with an exclamation point, for example, n exclamation point. To find the factorial of a number, multiply all of the positive integers equal to or less than that number. For example, 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 5,040. To calculate permutations, we use the equation n permutation r is equal to n factorial divided by n minus r factorial, where n is the total number of items to choose from and r is the number of items being selected.
Edward is playing pretzel with his friends. Pretzel is a game that has different colored squares on a mat where each player places a hand or foot on a different color depending on the spinner. There are 2 different spinners. One is labeled right hand, right foot, and left foot. The second spinner is labeled with colors. There are 4 purple squares, 3 blue squares, 4 pink squares, and 3 orange squares, randomly arranged on the spinner. Can Edward and his friends predict which spinner will land on which outcome? We don't have the gift of foresight. We can't predict the future. So how do we lowly humans make any sort of educated guess on the outcome of events? We use probability. Probability is the likelihood of a certain event occurring out of a total possible number of events. We can use the possible outcomes of a scenario and compare those outcomes to the desired outcome to get an idea of how likely it is that something is going to happen. We can use the words like more likely than, less likely than, and equally likely to describe the probability of events. For example, what is the probability that the spinner will land on purple? How would you figure this out? First, how many total squares are there? Right, there are 14 total squares. 4 purple squares, 3 blue squares, 4 pink squares, and 3 orange squares. Next, what is the desired outcome? The desired outcome would be the spinner landing on a purple square. The total possible desired outcome is 4 because there are 4 purple squares. Therefore, our ratio would be 4 over 14, or approximately 29%. Okay, now find the probability of the spinner landing on an orange square. The ratio for the probability of the spinner landing on an orange square would be 3 over 14, or approximately 21%. We can say that landing on an orange square is less likely than landing on a purple square. Another classical approach to probability is relative frequency, which is the ratio of the occurrence of a singular event and the total number of outcomes. This is a tool that is often used after you collect data. You can compare a single part of the data to the total amount of data collected. Edward and his friends play pretzel and keep track of the colors that the spinner lands on. This is a frequency table. Edward and his friends used the color spinner 20 times. You can see that the spinner landed on a purple square 7 times, a blue square 3 times, a pink square 5 times, and an orange square 5 times. Now we can find the relative frequency of the data set by dividing each number by the total like this. We can use this information to say that the spinner landed on the purple square 35% of the time, the blue square 15% of the time, and the orange and pink squares 25% of the time. A relative frequency table allows you to compare the data to the total number of frequencies. The total of the relative frequency table should add up to 1 or 100%. This is because the spinner was used 20 times and the spinner landed on a color 20 times. You can also compare your predictions to the relative frequency table like this. This table shows the differences between theoretical and actual probability. Theoretical probability is the ratio of the desired outcome and the total number of possible outcomes. If you have the probability of a certain outcome without actually doing the experiment first, then you are working with theoretical probability. If you are working with numbers from a data set based on an experiment, then you are working with actual probability. Actual probability is the ratio of successful outcomes and the total number of trials. Let's say that Edward's friend Beatrice wanted to conduct an experiment to see how many times the spinner would land on a blue square out of 10 spins. Beatrice spins the arrow 10 times and it lands on blue 4 times. In this case, the total number of spins, 10, would be the number of trials, and the number of successful outcomes would be 4, which is the number of times the arrow landed on blue. The frequency and relative frequency column on this table represent the actual probability. Each frequency ratio shows us the number of successful outcomes for each color divided by the total number of trials. The theoretical probability shows us what should have happened in the trials. Notice that the spinner landed on the purple square 6% more than what it should have in theory, while the spinner landed on the blue and the pink squares less than the theoretical probability. A classical approach to probability is to use mathematics to predict the unknown. Since we can't see into the future, we have to use things like theoretical and actual probability to help us predict and understand data. Remember, probability is the likelihood of a certain event occurring out of a total possible number of events. Theoretical probability is the ratio of the desired outcome and the total number of possible outcomes, and actual probability is the ratio of successful outcomes and the total number of trials. You can use a relative frequency table showing the ratio of the occurrence of a singular event and the total number of outcomes to compare and analyze theoretical and actual probability. Remember, probability is just an educated guess. It's not foolproof. When you are trying to predict a certain outcome, remember that you are not guaranteed that outcome, even when it's based on high probability.
A probability is the likelihood of an event occurring. When calculating the probability of an event, use the formula number of favorable outcomes over the number of total outcomes. We can calculate the probability of any event occurring by examining the choices that are available. Let's look at an example and see how simple it is to find the probability. Jimmy bought a bag full of gumballs at the store. In the bag there were 20 red, 15 blue, and 12 yellow gumballs. If Jimmy reaches in the bag and selects a gumball at random, what is the probability that he will select a red gumball? The first thing that Jimmy knows is that if he adds the number of blue, red, and yellow gumballs together, he has a total of 47 gumballs in the bag. Jimmy knows that to calculate the probability of selecting a red gumball, he must use the equation the number of favorable outcomes over the number of total outcomes. Since there were 20 red gumballs, the number of favorable outcomes is 20. Also, there were 47 total gumballs, so the number of total outcomes is 47. We can see that the probability of Jimmy selecting a red gumball from the bag is 20 out of 47. To finish calculating the probability, we need to always check and see if our fraction is in simplest form. Fortunately for Jimmy, his fraction is in simplest form, so the probability of Jimmy drawing a red gumball from the bag at random is 20 out of 47. To calculate the total number of outcomes, you occasionally have to use a permutation. A permutation is a method to calculate the number of events occurring where order matters. To calculate a permutation, you will need to use the formula n permutation r, which equals n factorial divided by n minus r factorial. In this equation, n represents the number of items to choose from, and r represents how many items that are being chosen. Another function of this equation is the use of the exclamation point. This symbol stands for factorial. A factorial is the product of all positive integers equal to and less than your number. A factorial is written as the number followed by an exclamation point. For example, to write the factorial of 5, you would write 5 exclamation point. To calculate the factorial of 5, you would multiply the positive integers equal to and less than 5. 5 factorial would equal 5 times 4 times 3 times 2 times 1. By multiplying these numbers together, we can find that 5 factorial would equal 120. Let's look at another example. How would we write and solve the factorial of 10? The factorial of 10 would be written as 10 exclamation point. To calculate 10 factorial, it would equal 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 and times 1, which would in turn equal 3,628,800. Let's look at an example where we must calculate the permutation. At Rockland University, it is time for the student government election. There are 20 students who have submitted the necessary paperwork to appear on the ballot. How many different ways can the student body select a president, vice president, secretary, and a treasurer? First of all, this example is a permutation because the order in which the student body is selected for the position does matter. We know that there are 20 students who have been chosen to run for office. This will represent the n variable in our equation. We also know that the student government consists of only 4 positions, which is our R term. So in this permutation, we have 20 items to choose from for the 4 positions. The equation for our permutation would look like 20 permutation 4, which equals 20 factorial divided by 20 minus 4 factorial. To begin solving this permutation, we need to subtract the denominator. 20 minus 4 factorial would equal 16 factorial. Next, let's expand each factorial. As we work this equation, we're going to cancel out common terms in both the numerator and denominator. We can see that there is a 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1 on both top and bottom. These terms can be canceled out, leaving 20 times 19 times 18 times 17 on top and nothing on bottom, which becomes an understood 1. To solve this equation, we will now multiply the top and bottom of our fraction. 20 times 19 times 18 times 17 equals 116,280. The denominator has a term of 1, so our fraction is 116,280 over 1. We can now see that there are 116,280 ways that the student government can be selected from those 20 students. When calculating the probability of a permutation, we will be combining these two skills. The use of permutations will give us the total number of outcomes, and then we will need to calculate the total number of favorable outcomes. Let's look at an example to see how these two skills can be combined. Jim was given a new smartphone with a 5-digit passcode. The passcode can contain any single-digit number 0 through 9, but each number cannot be repeated. Unfortunately, Jim has forgotten his passcode and must try to guess the number. What is the probability of Jim guessing the correct 5-digit passcode? This problem will involve two processes. First of all, the use of permutations to calculate the number of passcodes that Jim can choose from. And secondly, the probabilities to calculate the chances of Jim selecting the correct passcode. First, we need to calculate the permutation of Jim's total outcomes. There are 10 items and 5 of them are being chosen. This permutation would look like 10 permutation 5 when written in notation form. Next, we will need to plug in our values into the formula for a permutation. Remember, the equation to calculate a permutation is n permutation r, which equals n factorial over n minus r factorial. Let's plug in our values. For all of the n variables, we will plug in a 10, and for the r variables, a 5. Our equation now looks like 10 permutation 5, which equals 10 factorial divided by 10 minus 5 factorial. To work this equation, we need to subtract on the bottom 10 minus 5, which equals 5 factorial. We now have 10 factorial divided by 5 factorial. Next, let's expand our factorials. On top, 10 factorial would equal 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And on bottom, 5 factorial would equal 5 times 4 times 3 times 2 times 1. As we continue working this equation, we will cancel out common terms in both the numerator and denominator. Since there is 5 times 4 times 3 times 2 times 1 on both the top and bottom, we can cancel out these terms. As these terms are canceled out, they disappear. Our equation now looks like 10 times 9 times 8 times 7 times 6 over 1. As we multiply 10 times 9 times 8 times 7 times 6 on top, which equals 30,240. This means that there are 30,240 different outcomes for passcodes that Jim could use. To calculate the probability that Jim selects the correct passcode, we will use the equation total number of favorable outcomes over the total number of outcomes. Since there is only one possible passcode that will unlock the phone, the number of favorable outcomes is 1. After calculating the permutation of events, we know that there are 30,240 total outcomes. So, the probability that Jim selects the correct passcode is 1 out of 30,240. In this video, we've looked at several examples in which we calculate the probability of a permutation. To find the probability of an event occurring, we will use the equation number of favorable outcomes over the number of total outcomes. When calculating the total number of outcomes, we sometimes need to use a permutation. A permutation is a method to calculate the number of events occurring where order matters. To calculate a permutation, we will need to use the formula n permutation r, which equals n factorial over n minus r factorial. In this equation, n represents the number of items being chosen from, and r represents how many items that are being chosen. Once you have found the permutation, you will plug it in as the total number of outcomes. Remember, after you find the probability, that all probabilities must be in simplest form.
Liam is a soccer player getting ready to try out for his varsity high school team. Each night he will scrimmage with a different group of players. Liam tracks his practice time during the day and the number of goals he makes each night. Liam wonders if there's a way to visually display this information and to analyze the relationship between the number of hours he practices and the number of goals he makes. Liam can do this by creating a scatter plot. A scatter plot is a graph of ordered pairs showing a relationship between two sets of data. In this lesson, you'll learn how to interpret bivariate data to create scatter plots. When creating a scatter plot, you will be looking at two sets of data. This data is known as bivariate data, which is two sets of variables that can change and are compared to find relationships. Take a look at this graph. Notice that there is an x-axis, the horizontal line in a graph, and a y-axis, the vertical line in a graph. Each point on this graph is called an ordered pair, which is two numbers that indicate a location on the coordinate plane. The first number is the location on the x-axis, and the second number is the location on the y-axis. This graph represents the relationship between the number of hours Liam practiced and the number of goals he made each night during the scrimmage. This is called a correlation, which is the relationship between two variables or sets of data. Notice that the more hours Liam spends practicing, the more goals he makes that night. Each ordered pair is the number of practice hours and the number of goals. This ordered pair represents the number of hours Liam spent practicing on Tuesday and the number of goals he made Tuesday night. When you are creating a scatter plot, each set of variables must have something in common. In this case, the variables have Liam and the day Liam practiced in common. We can't create an ordered pair out of someone else's practice hours and Liam's number of goals. They don't have anything in common. Ideally, when you create a scatter plot, you want to identify the independent and dependent variables in the scenario. An independent variable is a condition or piece of data in an experiment that can be controlled or changed. In this case, the independent variable would be the number of hours Liam spent practicing. Liam has total control over his practice time. A dependent variable is a condition or piece of data in an experiment that is controlled or influenced by an outside factor, most often the independent variable. In this case, the dependent variable would be the number of goals that Liam makes during the game. Now, you could make the argument that Liam has control over the number of goals he makes, and therefore the goals would also be an independent variable. And this is true. However, Liam can't simply make a wish to improve his performance, right? He has to practice to get better. Therefore, the only way Liam can control his performance and make it better is to increase his practice time. And that is where we get the relationship between the independent and dependent variables. Make sure that when you are creating a scatter plot, to put the independent variable on the x-axis and the dependent variable on the y-axis. To create a scatter plot, you want to take a close look at your two sets of data. Liam is now tracking two different sets of data, his practice time and his endurance. He wants to see how long he can run each night after practicing in the morning. Take a look at the table Liam has created. Can we make a scatter plot from this data? Absolutely. First, create ordered pairs from the two variables. In this case, we want to put the practice hours on the x-axis and the endurance time on the y-axis. Therefore, the first set of numbers 2 and 10 would make up our first pair, and so on and so forth. Next, plot each point on your graph. This will show if there is a correlation between your two variables. If the points seem to move in the same direction and are close together, then they likely will have a correlation. Notice that most of the points increase both vertically and horizontally. When a bivariate data set shows an overall increase in numbers like this, it is called a positive correlation, where the dependent variables and independent variables in a data set increase together. If the graph slopes downward like the bivariate data in this graph, then you have a data set with a negative correlation. If there is no relationship between the numbers, as shown in this graph, then the data set has no correlation. We will talk about this more in later chapters, so be sure to check out the other lessons in this chapter. A scatter plot is a graph of ordered pairs showing a relationship between two sets of data. When creating a scatter plot, you will have two sets of information, known as bivariate data, which is two sets of variables that can change and are compared to find relationships. Each point on this graph is called an ordered pair, which is two numbers that indicate a location on the coordinate plane. The first number is the location on the x-axis, and the second number is the location on the y-axis. To create a scatter plot, first create ordered pairs from the two variables. Put the independent variable on the x-axis and the dependent variable on the y-axis. Next, plot each point on your graph. This will show if there is a correlation between your two variables. If the points seem to move in the same direction and are close together, then they will likely have a correlation. Hannah is a scientist studying the time management and study skills of college students. She conducts an experiment at a local college with 50 students. She asks each student to track their time spent on social media, time spent studying, time spent sleeping, and time spent working over the course of a semester. She also asks the students to record their final GPA for the semester. In this lesson, you will be learning about the simple linear regression and how to find a regression line using a graphing calculator. A regression line is a straight line that attempts to predict the relationship between 2 points, also known as a trend line or line of best fit. Simple linear regression is a prediction when a variable y is dependent on a second variable x based on the regression equation of a given set of data. We'll see how Hannah uses simple linear regression to help interpret her data. Once all 50 students turn in their data, Hannah creates a scatter plot, which is a graph of ordered pairs showing a relationship between 2 sets of data. For her first scatter plot, Hannah uses 2 variables, time spent on social networking and amount of sleep. To simplify her information, we are going to look at the average time per week each student spent sleeping and on social media. Take a look at the scatter plot. Since we are using 2 variables, we can call this bivariate data. Bivariate data is 2 sets of variables that can change and are compared to find relationships. Bivariate data is most often displayed visually using a scatter plot. You may notice that this data has several points that create a sort of pattern. Many of the points increase in the x value as they decrease in the y value. This is a relationship between the 2 sets of data, known as a correlation. A correlation is the relationship between 2 sets of variables used to describe or predict information. A regression line is one way of predicting this information and finding a correlation in the data. There are 2 ways you can find the regression line of a set of data. The first way is to find the regression line by using a ruler, and the second way is to use a graphing calculator. Let's talk briefly about how to find a regression line by hand before we use a calculator. To find a regression line by hand, follow these steps. 1. Draw a line that is closest to as many points as possible. 2. Choose 2 points and calculate slope. 3. Write the equation of the line. Let's use this scatter plot to practice finding the regression line using a ruler. First, use the ruler to find a place that is closest to as many points as possible. Sometimes you can find 2 points to use. Second, pick 2 points that you think would be on the regression line. You can use points that are on the line, or you can make up new points. Use these points and plug them in to find the following equation. If you are unfamiliar with using this equation, check out our algebra lessons. Third, now you have the slope of your line. You can create an equation based on this information. Find the y-intercept by extending the line all the way to the y-axis. Use the slope-intercept equation to create the equation for your line like this: y equals mx plus b, y equals negative 1x plus 66. Now that you know how to find a regression line by hand, let's talk about how to find a regression line using a calculator. Every calculator is a little bit different. However, you should be able to get by with just about any graphing calculator using these steps. First, set the calculator to statistics mode. Second, enter the data, the first set on L1 and the second set on L2. 3. Adjust settings for a scatter plot and then graph the points. And 4. Set the calculator for regression line. We will use the data that Hannah collected about the amount of sleep and the amount of work the students did during the semester. This data is a weekly average for each student. To save time, I'm only using 20 students rather than the original 50. In this example, I am using a TI-83 graphing calculator. First, set your calculator to statistics by pressing the Stat button. This will take you to a screen with the options of Edit, Calc, and Tests. Select the Edit option by pressing Enter. The L1 is the X coordinates and the L2 is for the Y coordinates. Enter each of the coordinates using the number pad and hitting Enter when you are done entering each coordinate. After hitting the Enter button, the calculator will take you to the next line for the second coordinate. You can also use the arrow buttons to move between L1 and L2. Next, adjust the settings on your calculator to display a scatter plot. To do this, hit the second button, then hit Stat Plot. You should see this screen. Hit Enter to go into the next screen, which looks like this. Make sure your settings match mine by moving the cursor around with the arrow buttons and selecting each item with the Enter button. Selected items will have a black background and light text. You will also want to make sure you can see all of your points. I've adjusted the values in each field using the arrow keys, the Enter button, and the number pad. Push the graph key to see the points plotted on the graph. Now you are ready to find the equation of your regression line. First, press the Stat button again. This time, use the arrow keys to move to the Calc option at the top of the screen. Using the arrow keys, move your cursor down to item number 4, labeled Line Reg, parentheses, AX plus B, end parentheses. Press the Enter button. The calculator will show you the same line reg, parentheses, AX plus B, end parentheses, at the top of the screen. Hit Enter a second time to calculate the regression line. A equals 1.3 and B equals 40.6. Therefore, the equation for the regression line is y equals 1.3x plus 40.6. My graph would look like this. Now Hannah wants to compare the amount of time a student spends studying to the amount of time the student spends sleeping. Can you find the regression line and its equation from this set of data? Pause the video here to work on this problem. The equation for the regression line on this graph is y equals negative 0.0989x plus 12.643. If you rounded numbers here, that's okay for this problem. Don't forget to press Enter when you see the line reg AX plus B in parentheses on your calculator. It will not show you the values for A and B if you don't press Enter, telling the calculator to find these variables. Okay, try this. Hannah now wants to compare the time a student spends studying to his or her GPA. Can you find the regression line and its equation from this set of data? Feel free to pause the video here while you work. The equation for the regression line on this graph is y equals 0.1683x plus 2.0343. If you rounded numbers here, that's okay for this problem. If you did not get the correct answer here, feel free to go back in the video and follow the steps again with me. In summary, a regression line, also known as a trend line or line of best fit, is a straight line that attempts to predict the relationship between 2 points. Simple linear regression is a prediction when a variable y is dependent on a second variable x based on the regression equation of a given set of data. Every calculator is a little bit different. However, you should be able to get by with just about any graphing calculator using these steps. 1. Set the calculator to statistics mode. 2. Enter the data. First set on L1 and second set on L2. 3. Adjust settings for a scatter plot and graph the points. 4. Set the calculator for regression line. Finally, if you get any errors or the information doesn't look correct, double check the points you entered first and then review the settings on the calculator.
Jake has decided to start a hot dog business. He has hired his cousin, Noah, to help him with hot dog sales. But there's a problem. Noah can only work 20 hours a week. Jake wants to have Noah working at peak hot dog sales hours. How can he find this information? In this lesson, you will learn how to solve problems using concepts based on linear regression. First, let's check out some of our key terms that will be beneficial in this lesson. Jake will have to collect data and use regression analysis to find the optimum hot dog sale time. Regression analysis is the study of two variables in an attempt to find a relationship or correlation. For example, there have been many regression analyses on student study hours and GPA. Studies have found a relationship between the number of hours a student studies and their overall GPA. In other words, the number of hours a student studies is the independent variable, and the GPA is the dependent variable. The student's GPA will depend on the number of hours a student studies. Therefore, there is a relationship between the two variables. We'll talk more about this relationship, also known as correlation, in a minute, but let's define linear regression next. A regression line is a straight line that attempts to predict the relationship between 2 points, also known as a trend line or line of best fit. You've probably seen this line previously in another class. Linear regression is a prediction when a variable, y, is dependent on a second variable, x, based on the regression equation of a given set of data. To clarify, you can take a set of data, create a scatter plot, create a regression line, and then use regression analysis to see if you have a correlation. Once you have your correlation, you have linear regression. Okay, that probably sounded like Greek to you. Let's talk a little bit about correlation before looking at some examples. A correlation is the relationship between two sets of variables used to describe or predict information. The stronger the relationship between the two sets of variables, the more likely your prediction will be accurate. We will examine this concept of correlation more closely in other lessons, such as interpreting linear relationships using data and correlation versus causation. For now, let's focus on using the regression line to help solve Jake's hot dog sales dilemma. First, let's look at the data for Jake's hot dog sales. Jake has been working for the past few weeks from 1 p.m. to 7 p.m. each day. Each day, Jake has tracked the hour and number of hot dog sales for each hour. Take a look at this data set for Monday. 1, 10, 2, 11, 3, 15, 4, 12, 5, 17, 6, 18, 7, 20. To establish the relationship between the time of day and the number of hot dogs sold, Jake will need to put the data into the formula y equals ax plus b. You've probably seen the formula for slope-intercept form in algebra, y equals mx plus b. This is the same formula, but in statistics we've replaced the m with a. A is still the slope in this formula, so there aren't any big changes you need to worry about. To find the regression line for this data set, let's first put this information into a chart like this. Now we need to use the least squares formula to find our variables in y equals ax plus b. This is the formula to find the slope a. I know, it looks pretty complicated. First, we will need a little more information in our chart. Look at how I expanded the chart to include x times y and x squared. Look at the first row in this chart. In the first column I have 1, my value for the first x in the data set. In the second column I have 10, my value for the first y in the data set. Under x times y I have 10, which is the product of the first and second column. In the last column, under x squared, I have 1, which is the value of the first column squared. Notice that each row on this chart follows the same pattern. Now we've added a final row that shows the sum of each column. For example, the first column has all of the x values, 1, 2, 3, 4, 5, 6, 7. The last row is the sum of all of those values. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 equals 28. So let's review our chart. We have all of the x values, all of the y values, x times y for each ordered pair, x squared for each x value, and the sum of x, y, x times y, and x squared. Now that we have this information, let's look at our formula and our chart. I've circled the places in our formula with the corresponding values in our chart with similarly colored circles. In this formula, a equals n times the sum of x times y minus the sum of x times the sum of y, all divided by n times the sum of x squared minus parentheses the sum of x in parentheses squared. Whew! Notice that n equals the number of ordered pairs. In this scenario, we have 7 total ordered pairs. Therefore, our formula would look like this. A equals parentheses 7 times 458 minus 28 times 103 end parentheses, divided by 7 times 140 minus 28 squared, which equals A equals 322 divided by 196, A equals 1.64. Therefore, our slope is 1.64. Now let's use our chart to find the value for B, our line's intercept. Once again, I've circled the places in our formula with the corresponding values in our chart with similarly colored circles. This formula reads B equals 1 divided by n times parentheses the sum of y minus a times the sum of x in parentheses. Our formula would look like this. B equals 1 divided by 7 in parentheses times 103 minus 1.64 times 28. B equals 8.15. Therefore, our intercept is 8.15. Now you can graph your data set with the regression line like this. So what does this information tell Jake? Well, the intercept tells us that if he worked at 12, which would be 0 on the graph, he is likely to sell 8.15 hot dogs. More importantly, the slope tells us that as each hour passes, the likelihood that Jake will sell a hot dog increases by 1.64 hot dogs. The big difference in this problem compared to most linear regression problems is the hours. In this case, we use the x-axis as each hour on a clock, rather than a value in time. If you had a shift of hours that went from 8 a.m. to 6 p.m., I would recommend using military time to represent both a.m. and p.m. with individual values and to show the relationship between the evening hours and the morning hours. The later in the evening it is, the more hot dogs Jake will likely sell. He will want to have Noah working later in the evenings for his shifts because it is most likely going to be the busiest sales time. Remember, regression analysis is the study of two variables in an attempt to find a relationship or correlation. We found a correlation between the later evening hours and the hot dog sales. A correlation is the relationship between two sets of variables used to describe or predict information. To do this, we used linear regression, which is a prediction when a variable y is dependent on a second variable x based on the regression equation of a given set of data. First, we had to find our regression line and its equation. A regression line is a straight line that attempts to predict the relationship between 2 points, also known as a trend line or line of best fit. We first created a chart with the following values: all of the x values, all of the y values, x times y for each ordered pair, x squared for each x value, the sum of x, y, x times y, and x squared. We then use these values in the following formulas to find the values for each equation. Y equals ax plus b. You can double check your work by using a graphing calculator to find the regression line of a data set. Check out our lesson on simple linear regression to see how to do that.
Lauren is collecting information from her auto mechanics class. She surveys 6 different auto mechanic shops in her town and collects information to see if there's a relationship between the number of times the oil is changed in a vehicle and the longevity in the engine of the vehicle. Once she gathers her information, Lauren puts all of it into a scatter plot with a regression line like this. Now that she has collected all of her data, how can she interpret this data to usable information? In this lesson, you will learn how to interpret the meaning of slope and y-intercept in different examples of linear models. A linear model is a comparison of two values, usually x and y, and the consistent change between those values. The easiest way to understand and interpret slope and intercept in linear models is to first understand the slope-intercept formula y equals mx plus b. M is the slope or the consistent change between x and y, and b is the y-intercept. Often the y-intercept represents the starting point of the equation. Take a look at this graph. The line in the center is known as a regression line, a straight line that attempts to predict the relationship between 2 points. This relationship is the same thing as the slope, and you may also hear the terms consistent change or interval. These 3 words are used interchangeably and mean the same thing in this case. The points around this line represent the data that is collected in this scenario. The equation for this line is y equals 0.3136x plus 0.2644. Let's take a look at our regression equation. For this scenario, we have 0.3136 and 0.2644. 0.3136 is the slope in this equation, and 0.2644 is the intercept in this equation. First, let's talk about slope and how we can interpret slope in this equation. Remember that the slope is the consistent change or the relationship between two variables in a linear model. For example, let's say you were getting paid $8 an hour at your job. The rate, 8, would be multiplied by the number of hours that you worked to get how much you should be paid for the week. In this case, the two variables are the number of hours you worked and how much you get paid for the week. The relationship between the number of hours you work and how much you get paid is the amount you get paid per hour. In this case, you know the relationship between the two variables ahead of time. But sometimes you know the variables and not the relationship, also known as the slope. Notice on our equation that slope is 0.3136. So what does this mean? Remember, our two variables are the number of times the oil is changed in the vehicle and the longevity of the engine. The slope is a positive number, which means that when the one variable increases, the other also increases. Just like the amount you get paid at the end of the week increases when the number of hours you work increases, so does the longevity of your engine increase as the number of times you change out the oil increases. Since a positive slope tells us there is a positive relationship between the two variables, what does the number 0.3136 tell us? Remember, in the previous scenario, the 8 told us how much you were being paid per hour. In this example, 0.3136 shows us how much the longevity of your engine increases. Let's look at it like this. You have your vehicle sitting in your garage. Maybe you've had it for a couple of years. Each time you change the oil out in your vehicle increases the likelihood that the engine will last by 0.3136 years. That's right. In this case, the slope represents the number of years that you increase your engine's lifespan every time you change the oil. Remember, this is just an example, and statistics doesn't always show us the full picture. Obviously, if your vehicle's engine is broken, changing the oil in it several times will not fix the problem. Now that you understand slope in this scenario, let's move on to the intercept. We know that the intercept is 0.2644 in our equation, but what does that mean? First, the intercept is also called the y-intercept. This is because it is the place in the equation where the line intercepts the y-axis. The ordered pair for the intercept is 0, 0.2644. This means that x equals 0 and y equals 0.2644. To understand the intercept, you need to understand the ordered pair. The x variable represents the number of oil changes in the vehicle. Therefore, in this case, we are saying that there have been 0 oil changes in the vehicle. The y variable represents the number of years of longevity in the engine. Therefore, this ordered pair shows us that the vehicle's engine longevity is 0.2644 years. If we put this together, the intercept tells us that if there are 0 oil changes in the vehicle, the engine will last 0.2644 years. Obviously, in reality, this will differ depending on the maintenance on the vehicle, the age of the vehicle, and the freshness of the oil that is currently in the vehicle. You will find that many data sets will have more variables that influence the slope and the intercept of the equation. Lauren is now collecting data on the amount of gasoline used and how often a person sits idle when using their vehicle. After collecting the data and plotting the points, she has developed the following equation. Y equals 3.52x plus 17.32, where y equals the number of gallons used in a month and x equals the number of hours spent idle in a month. Can you interpret the slope and intercept of this equation? First, let's talk about the slope. In this example, the slope represents the gallons of gas that are used. Therefore, for every hour the vehicle spends idle, 3.52 extra gallons of gas are used per month according to this linear model. While this may or may not be true in real life, this is the interpretation of this particular model. Second, it's time to interpret the intercept. Remember that the ordered pair for the intercept is 0, 17.32. If x equals the number of hours spent idle in a month, and y equals the number of gallons of gas used in a month, then this means that a person will still use at least 17.32 gallons, even if he or she never has the vehicle idle. Every linear model is different. However, you can identify some similarities that will help you interpret the slope and intercept of the model. Remember, a linear model is a comparison of two values, usually x and y, and the consistent change between the values. Linear models will have a regression line, a straight line that attempts to predict the relationship between 2 points. You can use the slope-intercept formula y equals mx plus b to identify the slope and intercept of the regression line. In this equation, m is the slope, or the consistent change between x and y, and b is the y-intercept. Often the y-intercept represents the starting point of the equation. In our examples, the y-intercept represented what would happen if the x value did not exist, and this is true for all linear models. You can use these interpretations to predict information about a set of data. Learn more in our other lessons on regression and correlation.
If you think of functions with exponents, you're probably used to seeing something like this. That's the graph of y equals x squared, and it is indeed a function with an exponent, but it's not an exponential function. In an exponential function, the independent variable, or x value, is the exponent, while the base is a constant. For example, y equals 2 to the power of x would be an exponential function. Here's what that looks like. The formula for an exponential function is y equals a times b to the power of x, where a and b are constants. You can see that this conforms to the basic pattern of a function where you plug in some value of x and get out some value of y. But what are the two constants for? And why do you need two? To illustrate this, let's look at an example of something you might express with an exponential function. In this example, we'll look at the popularity of cell phones. Whenever a new piece of technology comes out, people don't all rush out to get it all at once. It starts with just a few people, and then gradually it catches on more and more, and then everyone's using it. Hey, that looks like an exponential function. Just for example, let's take cell phones. Back in the caveman days, also known as the 1980s, cell phones were pretty rare. Without going into the exact numbers, let's say that in 1980, 5 people in your town had a cell phone. Over the course of that year, each of those people persuaded one friend to get a phone. So then you had 10 people with phones after 1 year. Then each of those people persuaded a friend to get a phone. So after 2 years, there were 20 people with phones. If you kept doubling the number every year, you'd get a really huge number really fast. That's the whole point of exponential function. Every year, the number increases by an increasing amount. Now let's get back to our equation for an exponential function. Y equals a times b to the power of x. Y is the number of people with phones, because that's our dependent variable. X is the number of years since 1980, because that's our independent variable. We started with just 5 people with cell phones, so 5 is our starting value, the initial value of the function represented by the constant a. In the first year, we multiplied that by 2. In the second year, we took our number from the first year and multiplied that by 2. This gives us 5 times 2 times 2, which equals 5 times 2 squared. The result was 20 people. In the third year, each of those 20 people convinced a friend to get a phone, so we had to multiply by 2 again. This gave us 5 times 2 times 2 times 2, or 5 times 2 to the third power, which equals 40. You can see the pattern here. We're adding 1 to the exponent every year, which means that we multiply 2 by itself one additional time every year. In this example, 2 represents the number repeatedly multiplied each step, the value raised to the power of x represented by the constant b. This is why we need 2 constants in the equation, one for the original value and one for the value raised to the power of x. This can be a little confusing because a lot of exponential functions start with just one thing to begin with. So a equals 1. 1 times any number is that same number, so it looks like the function is just y equals b to the power of x. But don't be confused, a is still there, it's just equal to 1. A common way that you'll see exponential functions described in words is with a phrase like increases or decreases by some % per year. For example, an investment increases in value by 1% per year. If you're calculating interest on a loan, you'd use this kind of equation. Let's take a look at an example problem to see how it works. An investor buys a property in an up-and-coming area of town. As the area gets nicer, the value of the property increases. The value of the property increases by 2% per year. If the investor originally bought it for $500,000, then how much is it worth after 5 years? Let's plug this into our exponential function formula, y equals a times b to the power of x. X is the number of years after the initial purchase. Y is the value of the property. These are our input and output variables. A represents the initial value of the function. The initial value of this property is $500,000, so we'll plug that in for A. Now the tricky part is figuring out B. In the first problem, B was 2, because we had twice as many cell phone users every year. In this case, the property is only worth 2% or $0.02 more dollars, so its value is increasing more slowly. You might be tempted to plug in 0.02 for B, but just take a look and see what happens when you graph that. You can see right away that this is not an increase in value. This gives us a function showing how much the property would be worth if every year it were valued at 2% of its value the year before. But we don't want 2% of its value the year before. We want 2% more than its value the year before. To get that, we'd have to multiply it by 1.02. Y equals 50,000 times 1.02 to the power of x. If we determine some of the values of this function, we get... Here's what that looks like on a graph. That's better. You can't quite see the slope getting steeper because the numbers are so big, but notice how y is increasing by a little bit more every time. First it increases by 10,000, then by 10,200, then by 10,404, and so on. You can see that if you do the math by hand, it works out to the same values you get from the function. Multiplying each year's value by 1.02 to find the 2% increase gives you the same values for each year. So for year 5, which is what the question originally asked, the value would be $552,020.40. Our savvy investor made $52,000. So where did exponential functions come from? Historians believe exponential functions originated in the 17th century banking industry. Suppose I give you a loan of $100 and charge a 5% interest fee. The simple interest formula, I equals PRT, says I would charge you $5 and then you owe me $105. And that was pretty easy, but most lenders don't use simple interest. They prefer something a little more complex called compound interest. Instead of just charging you 5% interest, I'm going to add 5% every week until the loan is paid back. Then, after each week, the amount of money owed increases by a factor of 1.05. Let's see what the first 5 weeks looks like. From this table, we gain the exponential function a equals 100 times 1.05 to the power of t. This will tell us how much money you owe after t weeks. In general, we can compute compound interest by the formula a equals p times 1 plus r over n to the power of nt, where p is the initial amount called the principal, r is the interest rate in decimal form, n is how many times we add interest in a given time period, and t is the number of time periods. So if a bank loans me $2,000 at a 3% APR compounded monthly, then r equals 0.03, n equals 12, and a equals 2,000 times 1 plus 0.03 divided by 12 to the power of 12t, which equals 2,000 times 1.0075 to the power of 12t. So after 2 years, I would owe the bank 2,000 times 1.0075 to the 24th power, which equals $2,392.83. In this lesson, you learned about exponential functions. An exponential function is written in the form y equals a times b to the power of x. Y represents the output, a represents the initial value of the function, b represents the rate of growth, x represents the input. In an exponential function, a is multiplied by b x times to create y. The graph of an exponential function looks like a curve that starts off with a very flat slope, but starts getting steeper and steeper over time. You can use these functions to solve problems about everything from the growth of bacteria to the interest you earn on your bank account. Try some of the quiz questions and see how you do.
So we know that an exponential function is any pattern of numbers that is continuously multiplied by something. For example, 3, 6, 12, 24. This is an exponential function because I start with the number 3 and I continuously multiply by 2. We can represent this function with an equation by saying that y is equal to 3 times 2 to the x power, because the pattern begins at 3 and is multiplied by 2 each step of the way. If you substitute in x values starting at 0, and remembering that 0 exponents equal 1, you'll find that we get this exact same pattern. And this is an example of what's called exponential growth, because the numbers are growing exponentially. But there is another type of exponential function whose entries get smaller instead of getting bigger. And this is called exponential decay. Exponential decay still follows the same rule of repeated multiplication, only the number we multiply by has to be smaller than 1. What this is going to end up looking like is something that appears to be repeated division. So to show you kind of what I'm talking about, let's take a look at an example that most of us can relate to. Our computer becoming worthless way faster than we had expected it to. So say you buy a pretty nice new computer for $1,600, but after you've owned it for 1 year, it's already worth only 1/2 as much as it used to be. That makes it worth $800 after 1 year. Then if this pattern continues, it'd be worth $400 after 2, then $200 after 3, and $100 after 4 short years. The price of your computer is decaying, or getting smaller, by a factor of 1/2. Now it kind of looks like division by 2, but remember that division by 2 is the same thing as multiplication by 1/2, which means that because your pattern begins at 1600 and becomes repeatedly multiplied by 1/2, the exponential decay equation for this example would be y equals 1600 times 1/2 to the x power. So these exponential functions get pretty small pretty quickly. And if we assume this pattern continues, your computer would only be worth $1.50 after 10 years. But it's also important to note that no matter how long you keep your computer for, it's never going to be worth 0. Now, it might seem like it, and it might be worth pretty close to 0, but multiplying by 1/2 over and over and over again can only make a number that's really, really small, but it's still a little bit bigger than 0. Maybe you'd end up with 0.0000000000001, but there's always going to be that little 1 on the end, because now if I divide this by 2, it's just smaller, and now it's 0.000000005. But there's still a number down there. No matter how many times I divide by 2, it's still going to be a tiny bit bigger than 0. Which means that on our graph, my line is going to get closer and closer and closer to the x-axis, but it will never quite get there. And this is actually a math concept that comes up pretty often, and it's called an asymptote. In this case, we have an asymptote at y equals 0, because that is the line, which is basically the x-axis, that our graph will get infinitely close to, but never quite touch. Now that we're familiar with both exponential growth and exponential decay, it's important to take a look at their graphs and notice a very, hopefully obvious similarity. Here I have y equals 2 to the x, which is growth because I'm multiplying repeatedly by 2, which makes numbers bigger. And here I have y equals 1/2 to the x, which is decay because I have 1/2 being repeatedly multiplied, which makes things smaller. And looking at their graphs, you notice that they are almost the same, except they've been kind of flip-flopped or reflected around the y-axis, which means that the right-hand side of my decay graph is actually the exact same as the left-hand side of my growth graph. And this is true because I can plug negative values in for x in my growth graph, and when I plug in, for example, -1, negative exponents give me fractions, which means I have to take 1 and put it over 2 to the first power, and that gives me 1/2, which is exactly what I do if I do just 1/2 to the 1 over here in my decay function. And so the point on +1 in the decay is the exact same as the point on -1 in the growth, which means they both have an asymptote at y equals 0. It's just that the growth graph gets infinitely close to 0 as you go in the negatives, and the decay graph gets infinitely close to 0 as you go in the positives. Now that we're familiar with both exponential growth and exponential decay, we can begin to solve some more complex examples. Ones that, for example, ask us to determine the starting value of an exponential function when we are only given 2 random entries. Let's say I told you that after owning my car for 3 years, it was worth $7,168, and then 3 years later, it was only worth $3,670. If we assume that it was decreasing by the same percent each year, which means it's an exponential function, an exponential decay function, that means that I had it worth 7,168 at year 3, and then I multiplied by the same value 3 times, and that ended up being worth 3,670. I can turn this into equation simply by saying 7,168 times b times b times b, where b is my base, equals 3,670. Condensing the b's as a b to the third gives me this. And now I simply have to undo everything that's being done to the b to figure out what my base, or what my multiplying factor, is. I undo multiplication with division and divide both sides by 7,168. That leaves me with b to the third equals 0.5119977, on and on. I undo a third power with a third root, and I find that b, my base, must be 0.799999, which we're going to round to 0.8, which means that the base of my exponential is 0.8. Now that I know that, I can simply work my way backwards to figure out how much it must have cost the very day I bought it. Now, instead of multiplying by 0.8, to go backwards, I'm going to divide. First I divide by 0.8, then I divide by 0.8 again, I divide by 0.8 one last time, and it turns out that my car must have initially cost me $14,000. To review, exponential functions are patterns that get continuously multiplied by some number. It's exponential growth when the base of our exponential is bigger than 1, which means that the numbers keep on getting bigger and bigger and bigger, and it's decay when the base of our exponential is in between 1 and 0, and our numbers get smaller and smaller and smaller. Lastly, an asymptote is a value that a function will get infinitely close to, but never quite reach.
What happens when you take a number to a certain power? You multiply the number by itself a certain number of times as dictated by the exponent. For example, 5 to the power of 3 equals 5 times 5 times 5. In general, the rule is that x raised to the y power equals x multiplied by itself y times. If we wanted to write a rule for this relationship in general terms, we could write it as x to the y power equals z, where z is the result of x multiplied by itself y times. In this equation, x is called the base, the number raised to a certain power. Y is called the exponent, the number that tells you how many times to multiply the base by itself. You are probably familiar with math problems that give you x and y and ask you to solve for z. For example, what is the value of 3 to the power of 4? Or which is bigger, 5 to the power of 3 or 3 to the power of 5? But what if you looked at the equation a different way? What if you knew the base and the result, but you had to solve for the exponent? In other words, how many times do you have to multiply x by itself to get z? In both cases, the equation at work is 5 to the power of 3 equals 125. The two questions are simply asking you to find different parts of the equation. That is what logarithms do. A logarithm is the power that you raise a certain base to in order to get a given number. It's just another way of looking at exponential expressions, which you already know how to work with. Just like addition reverses subtraction and multiplication reverses division, logarithms reverse exponential expressions. To make it easier to solve for the exponents, logarithms use a special kind of notation. The expression x to the power of y equals z in exponent form would turn into log base x of z equals y in logarithm notation. In logarithm notation, the thing that we're solving for is isolated, so it's easier to solve for, just like it is in regular exponent form. This might look confusing at first, but it's just another way of writing the exact same concept. These two expressions are exactly the same. They're just two different ways of writing the same thing. Logarithm form can initially look like you're taking x to the power of z. This isn't what it means. Don't get confused by the fact that z is higher up on the line than x. X is the base, but you're raising it to the power of y to get z. A logarithm is basically the reverse of an exponent. In an exponential equation, you have the power, and you're solving for the result of taking the base to that power. In a logarithmic equation, you already have the result, and you're solving to find the power. So what could you possibly want to use this for? Well, for example, let's say you're a scientist studying earthquakes. The strength of an earthquake is measured on something called the Richter scale, where 1 is almost unnoticeable and 9 is extremely destructive. Here's how scientists calculate the Richter rating of a given earthquake. Don't worry too much about this. This part is just an equation that takes the amount of force measured and adjusts it according to how far away the station is from the earthquake. The interesting part here is the logarithm. To get the number from 1 to 9, scientists calculate what power they'd have to raise 10 to get the adjusted measurement of force. Let's say that the adjusted measurement of the force of an earthquake was 10,000. How big would the Richter rating be? In other words, what power do we have to raise 10 to in order to get 10,000? You'll go over more techniques for solving logarithms in another lesson, but if you know anything about the powers of 10, you can already crack this one, because 10 to the x power equals 1 followed by x zeros. So 10 to the second power equals 100, 10 to the third power equals 1000, and so on. In this case, we've got 4 zeros, so we can tell that we need 10 to the fourth power to get to 10,000. Log base 10 of 10,000 equals 4. That makes this earthquake a 4 on the Richter scale, which is enough to shake your floors a little and knock some books off the shelves, but it won't be toppling any skyscrapers anytime soon. In this lesson, you learned about logarithms. A logarithm is the power that you raise a certain base to in order to get a given number. Logarithms are like a way to undo exponents. Where exponents are all about taking a base to a certain power and figuring out the result, logarithms are about figuring out what power you need given the base and the result already. Logarithm notation can be confusing at first, but as you use it, you'll get used to it. Just think of it as another way to write exponents. The expression x to the power of y equals z in exponent form would turn into log base x of z equals y in logarithm notation.
The basic formula for a logarithm is y equals log base 2 of x is the same as 2 to the y power is equal to x, which means that the solution to a logarithm equation is the power you must raise a certain number to in order to obtain another number. The logarithm function is the inverse of an exponential, which is a term that has a variable in its exponent. For example, 2 to the x power is an exponential. It stands to reason, then, that the graph of a logarithm would be the inverse of the graph of an exponential. And you can see from this picture that that is correct. The graph of the logarithm is just the graph of the exponential inverted across a straight line. There are two methods you can use in order to graph a logarithm. The first is to substitute in numbers from one variable to get values for the other, then plot them on a graph and connect the dots. When using this method, remember that the log is undefined at 0 and less than 0, so x can only be greater than 0. Let's graph the following as an example. The log base 2 of x equals y. The first step is to draw a chart, then fill in the values for x and y. You can pick any value for y that you desire, but smaller is usually better. This way your graph is not huge. You can get the general idea for the graph from 5 or so points. Then, when you have your points, just plot them on the graph and connect the dots. Remember, with the graph of a general logarithm, it will never touch or cross the y-axis, but will come as close as possible. The second method for graphing a logarithm is to use a graphing calculator. Read the instructions that came with your calculator in order to graph logarithms using this method. The domain of any equation is the possible x values for that equation. It is any number that x could possibly be when that equation is graphed on a coordinate plane. For the general logarithm equation, the domain is x is greater than 0, because x cannot be 0 or below. The range, or possible y values for any equation, is any number that y could possibly be when the equation is graphed on the coordinate plane. For the general logarithm equation, the range is y is equal to all real numbers. So far, we have only talked about the general logarithm equation and its graph. But what if the equation is more complex, such as the log base 2 of x plus 2? Adding or subtracting to the equation causes the graph to shift, either up, down, left, or right, depending on how the addition or subtraction is framed. Graphing logarithmic equations that have been shifted can be done very easily if you remember the set of rules that govern these shifts. The first rule says that adding a number to the equation will cause the graph to shift up the number of spaces indicated by that number. The example shown previously has a plus 2 added to the equation, which means that the graph will shift up 2 spaces from the general graph. As you can see, the graph has been shifted up 2 spaces. The second rule states that subtracting a number from the equation will cause the graph to shift down that number of spaces. Take a look at this example. Y equals the log base 2 of x minus 2. Because of the minus 2 in the equation, the graph will be shifted down 2 spaces. The third rule says that adding a number inside the logarithmic argument will cause the graph to shift left. This time, the number being added will be in parentheses with the x, indicating that it is a part of the log function and not just a number to be added on at the end of the equation. The x plus 3 in parentheses in this equation causes the graph to shift 3 spaces to the left. And the fourth rule says that subtracting a number inside the logarithmic argument will cause the graph to shift right. The x minus 3 in parentheses will cause the graph to shift 3 spaces to the right. You can also have a graph that is translated in 2 directions. Take a look at this example. The log of x plus 2 minus 4. The graph of this equation will be shifted to the left 2 spaces and down 4 spaces. Earlier, we discussed the domain and range of logarithmic functions and defined the domain as the possible x values and the range as the possible y values of a function. When the basic graph is transformed in a certain way, it will change the values for the domain and range of that function. If the graph is shifted up or down, the domain will still be x is greater than 0, and the range will stay y equals all real numbers. If the graph shifts to the left or right, the range again will not change, but the domain will shift along with the graph. This is because we are moving the graph in the x direction, so the boundary line will change. If the equation is y equals log of x plus 2, then x can be less than 0, it just can't be less than or equal to negative 2. If x is equal to negative 2, then we get y equals the log of negative 2 plus 2, which equals y equals the log of 0, which is undefined. All that to say that for the equation y equals the log of x plus 2, the domain is x is greater than negative 2. The same rule applies if the graph is shifted to the right. If the equation is y equals log of x minus 3, then the domain is all numbers greater than 3, or x is greater than 3, in order to keep the number being evaluated a positive number. By adding or subtracting numbers from the logarithm equation or argument, you will shift the graph of the logarithm up, down, left, or right. It's easy to do if you remember the rules of transformation. If the transformation is to the left or right, it will affect the domain of the graph but not the range. Up or down shifts will not affect the domain or the range of the graph.
We learned that logarithms are the inverse operation of exponentials, and they give us a way to solve exponential equations. When we were trying to figure out how far into the future it will be before there are 200 billion cell phones, we were stuck with the equation 2 to the x power equals 34,359,738,368. And that's where the log came in, because the answer to our question, what exponent turns 2 into 34 billion, is exactly what log base 2 of 34 billion is. We decided that log base 2 of 34 million was 35, because 2 to the 35th power equals 34 billion. And what you see are two different ways of writing the exact same thing. I could write this equation in logarithmic form, which is log base b of y equals x, or I could write it in exponential form, which is b to the x power equals y. And both these forms are just two different ways of saying the same thing. Now, a lot of students get freaked out when they see a log because it's new and they're not used to it, and think that it means to multiply log with 5 or to raise 5 to the 25th power, but neither of these are actually true. The little 5 beneath the log is a subscript, and it goes with the log. Every log is going to have one of these, and it tells us which type of log we are doing. In this example, we are taking the log base 5 of 25. So we're taking the log 5 of this number. Therefore, we are being asked 5 to what power equals 25, which is, of course, 2. So the answer to our log is simply 2, because 5 squared equals 25. Let's try another one. The log base 3 of 27. The answer is the exponent that will turn the base of the log into the number we are taking the log of. Therefore, the answer is 3, because 3 to the 3rd power is equal to 27. Now, writing out the exponential form for these problems can be a way of proving your answer, but it's not the answer itself. The answer is just the number we get, and the exponential form is a way of saying why that answer is the answer it is, or a way of checking your work. Another example, how about log base 9 of 1? So what exponent turns 9 into 1? Well, you have to remember the 0 exponent property. Remember that anything to the 0 power gives you 1, so 0 is the exponent that turns 9 into the 1, so the answer to this one is just 0. Or finally, how about log base 2 of 1/8? For this one, you're going to have to remember the negative exponent property. Negative exponents give us fractions, and because I have to turn 2 into 8, that is the 3rd power, because 2 times 2 times 2 is 8. So 2 to the negative 3 is 1/8, and therefore the answer to log base 2 of 1/8 is simply negative 3. So as you can see, there are all types of logs: log base 2, log base 8, log base 55, log base pi, anything we want. But there are two logs that are used the most often: log base 10 and log base e. Now, just like we use pi to mean 3.14159 and on, we use the letter e to mean 2.718281 and on and on and on. And this one is called the natural base. It won't really become useful until calculus, so for now, we're just going to know that it exists and that it's about 2.7. So because these two logs are used so much, mathematicians came up with a shorthand way of writing them. Log base 10 became just plain log, and log base e became the natural log, abbreviated ln. So if you see a problem that just says log 100, that really means log base 10 of 100. And if you see a problem that says ln 5, that really just means log base e of 5. one last thing. Sometimes we'll be asked to evaluate a log that doesn't have a whole number answer. Say log base 2 of 5. Well, since 2 squared is 4, and 2 to the third is 8, and I'm being asked 2 to what is 5, I'm not really sure. It's somewhere in between 2 and 3, but it's probably closer to 2. I don't know, maybe 2.1? But we don't really know, so we'd like to be able to use our calculator for this. But most calculators only have log base 10 and log base E buttons on them. So how can we do log base 2? And for circumstances like this, we can use what's called the change of base formula. The change of base formula tells you that the log base B of A is equal to the log base Z of A divided by the log base Z of B, which basically means we can change the log to a different base. We can pick what base to change it to and just divide the log of A with the log of B. So we can evaluate log base 2 of 5 by changing the base from 2 to a button that's on my calculator, maybe 10. That allows us to say that log base 2 of 5 is equal to the log base 10 of 5 divided by the log base 10 of 2. I can use the buttons on my calculator to find that it's actually about 2.3. That wasn't too far off. To review, logarithmic form and exponential form are just two ways of writing the same thing. We can use that knowledge to evaluate logarithms by thinking, what is the exponent that would turn the base of the log into the number we're taking the log of? If the log does not have a whole number solution, then we can use the change of base formula to estimate it with our calculator. The two log buttons that are on most calculators are the log base 10, which is just the log with no number on it button, and the log base E, which is the button that just says LN. Once you've mastered evaluating logs, it's time to learn the tricks. Now, similar to how multiplication has the distributive property, logarithms have their own properties that will help us down the road when we are doing some of the real-world problems. Because this video is about the nuts and bolts behind the fun stuff, it won't be the most exciting video ever, but I will try to make it as painless as possible. The first property we'll learn is called the product property. Now, because logs are related to exponents, this is actually very similar to the exponent property called the product of powers property. It basically tells us that when we multiply two powers, we get to add their exponents. As long as we remember that, we can come up with the product property for logs in the following way. Now, what I'm about to do is a mathematical proof of the product property. I'm not going to do this for all the properties in this video, but I do think it's good to see at least one of them so that you know that these things aren't just made up. They actually come from some math. Now, all proofs need to start with some assumed information. So for this one, we'll start by saying let log base b of x equal m and log base b of y equal n. That's two equations in logarithmic form, but if I change those same equations to exponential form, I get b to the m equals x and b to the n equals y. Therefore, if I multiply x and y, all I'm really doing is multiplying b to the m times b to the n, which then allows us to use the product of powers property, like we mentioned before, of exponents, and add the exponent. So I get b to the m plus n. This is still in exponential form, but if I change it back to logarithmic form, I have the log base b of x times y equals m plus n. But then going back to our original definitions of what m and n were and substituting those in this equation, gives us that the log base b of x times y equals log b of x plus log b of y. And this is exactly what the product property of logarithms is. If we do the exact same proof, but with division instead of multiplication, we end up using the exponent property called a quotient of powers, and we get the quotient property of logarithms, which is that the log base b of x divided by y is equal to the log base b of x minus the log base b of y. Finally, if we use an exponent in our proof, we end up with the power property of logarithms, which tells us that log base b of x to the y is equal to y times log base b of x. So those are our three logarithmic properties: the product property, quotient property, and the power property. Now, having them written out formally like we do here is good when we want to be exact, but we can simplify the information from the properties by putting them into a table. What it really comes down to is this: what is going on the inside of the log, and what does the property tell us could be going on the outside? The product property says that if you see multiplying going on the inside of a log, you can change that to addition between logs on the outside. Similarly, the quotient property says that if we see division on the inside of the log, we can change it into subtraction between logs on the outside. And finally, the power property tells us that when you see an exponent on the inside of the log, we can change it into multiplication in front of the log. Notice how I have little arrows drawn between each of the corresponding operations. That's because we can go back and forth using this property either way. For example, the quotient property says that if I see division on the inside, I can change it to subtraction on the outside. But if I see subtraction on the outside, I can go backwards and change it to division on the inside. And we're going to be doing both. We can now use this chart as a cheat sheet for turning one complex log into a long chain of more simple logs. Or going the opposite direction and turning one long chain of simple logs into one complex one. For practice applying these properties to do problems just like this, check out the next video, titled Practice Problems for Logarithmic Properties. To review, besides the change of base property, there are three other logarithmic properties that allow us to manipulate logs. The product property says that when we take the log of two things being multiplied, we can split it up into two logs of those two things being added together. The quotient property says that when we take the log of a quotient, we can split it up into two logs that are being subtracted. The power property says that when we take the log of a power, we can bring down the exponent and bring it in front of the log and multiply it. When we learned about the logarithmic properties, we were able to boil all the useful information from the three major properties down into what's in this table. The product property told us that multiplication on the inside of a log can be turned into addition on the outside. The quotient property said that division on the inside can be turned into subtraction on the outside. And the power property said that an exponent on the inside of the log can be turned into multiplication on the outside. These properties come in handy when we're doing a math problem and we get to a step with a log in it that looks like this: the natural log of 6e to the 5th divided by 7. Now, logs are confusing enough when they've only got one number on the inside, but ones like this can be daunting. Luckily, we have the properties to break this complex log up into smaller, more manageable pieces. Now, because order of operations would tell us that the divide by 7 on the expression on the inside of the log would be the last thing we'd do to this expression, it's the first thing we're going to undo with the properties. Because it's divided by, I can use the quotient property to tell me that division on the inside of a log turns into subtraction on the outside. And I get this new expression, the natural log of 6e to the 5th minus the natural log of 7. Looking now at the natural log of 7, I know I have nothing left to do with this because it's just the log of a single number. There are no operations going on the inside of the log. But the first term, the natural log of 6 times e to the 5th power, there's still some stuff going on in there, so I still have a little more work to do. I can next use the product property to undo the most outside thing, the last thing order of operations would do, the 6 times e to the 5th, and end up with the expression, the natural log of 6 plus the natural log of e to the 5th minus the natural log of 7. So the product property just turned multiplication on the inside into addition on the outside. Lastly, I can use one more property on the middle term, this time the power property, to change the exponent on the inside to multiplication on the outside. And we now have our fully expanded expression, the natural log of 6 plus 5 times the natural log of e minus the natural log of 7. This expression that's expanded out might be a little bit easier to look at because I can actually think about evaluating or estimating in my head what the natural log of 6 is, or the natural log of e, or the natural log of 7. I could even get an estimate for what this thing is, whereas Back in the beginning, I really had no idea. It was just too complex. But the fully expanded expression can help us get a better sense of what it is. But it's also nice to be able to do the opposite. Condense a long list of logs into one single one. While it's nice to see each simple piece when we're trying to evaluate it or estimate it, if we have to write it over and over again, it's not fun writing it out each step. We'd rather pack it up into one log while we're using it, and then unpack it when we actually need to evaluate it. Take this for example. 2 times the log of 6 plus the log of x minus the log of 12. Writing this over and over again each line of my paper would get real annoying real quick. So let's use our properties and go backwards with this expression to condense it into one logarithm. This time we're going to do order of operations the normal way. So I first start by looking at my parentheses. I see there's addition, and I want to condense addition on the outside of logs, which means product property. Product property says that I can take addition on the outside and turn it into multiplication on the inside. So I get this slightly smaller expression, 2 times the log of 6 times x minus the log of 12. Next, I can use the power property by saying when there's multiplication on the outside, it turns into an exponent on the inside. Because the 6 and the x were on the inside, the exponent is on both of them, and then I can just distribute it in to find that this is the same thing as log of 36x squared minus log of 12. Lastly, I can use the quotient property to turn subtraction on the outside into division on the inside, and then log of 36x squared over 12 can actually be simplified to be the log of 3x squared, and we have our fully condensed expression. So not only did condensing this log make it easier to write, it also made some of the numbers cancel out. Finally, we can even use the properties to help us evaluate some logarithms as well. Take this example. Log base 3 of the square root of 27 minus the log base 5 of the square root of 5. While it is true that these logs can be evaluated without calculators, it isn't very clear how we would do that simply by looking at this problem right now. Let's try unpacking the logs a little bit, and maybe if we break them into some smaller pieces, we'll have a better idea of what these things equal. We're first going to have to remember that square roots written in radical form can be switched to rational exponent form, which basically means that the square root of a number is the same thing as a number to the 1/2 power. Remembering this allows us to rewrite our first expression as the log base 3 of 27 to the 1/2 power minus the log base 5 of 5 to the 1/2 power. This is already looking nicer because I know what to do with exponents on logs. I can use the power property to bring the exponents down in front of the logs and have it be multiplication. And now when I see the log 3 of 27 without the square root or the power, I can actually think, oh, what does log 3 of 27 equal? Well, 3 to the 3rd power is 27, so the log base 3 of 27 is just 3. Coming over to the log 5 of 5, what exponent turns 5 into 5? Well, that would be the power of 1, which means the log base 5 of 5 is just 1. And now I simply have an expression that I can multiply and subtract to get out. 1/2 times 3 is 1.5, 1/2 times 1 is 0.5, and finally 1.5 minus 0.5 is 1. To review, using the properties to expand logarithms can be helpful when we're trying to evaluate the log or simply when it looks too complicated to do anything with it. But condensing them back into a single log can make it much easier to write down and also will sometimes help cancel out some values.
Solving for your variable, usually x, is pretty straightforward when your x can easily be isolated through addition, subtraction, multiplication, or division. But if your variable is an exponent, then it becomes a bit harder to solve for it. These types of problems are called exponential equations. Here are some examples of exponential equations. E to the x equals 40, 10 to the x plus 2 equals 30, e to the 2x minus 7 e to the x plus 10 equals 0. At first look, it may seem that isolating the x is a difficult, if not impossible, task to do. That is, until you realize that you can use the logarithmic function to help you isolate the x. Let's see how you can do that. The log function is the inverse of an exponential function. It has a very useful property that can help you solve your exponential equations. If x equals b to the y, then y equals log base b of x. This means that if the variable you're trying to solve for is in the exponent, then you can use the logarithm function like this. Log base b of x to the y equals y times log base b of x. Let's see if you can use this to help you solve this exponential equation. 10 to the x plus 2 equals 30. Even though the x, the variable you're trying to solve for, is in the exponent, you're still going to use algebra techniques to solve this problem. This means trying to isolate your variable to the best of your ability. So you first subtract the 2 from both sides. Remember, whatever you do to one side, you have to do to the other as well. Now you can take the log of both sides to help you move your variable out of the exponent so you can solve for it. Log of 10 to the x equals log of 28. You can now use the useful property of the logarithm function to move your x out of the exponent area. Applying this property, you get this. X times log of 10 equals log of 28. Using the rule log base b times x equals 1 when b equals x, our log 10 term cancels out and we're left with x equals log of 28, x equals 1.447. And you're done. You've solved the problem. For some problems, you might see a little e. This e is called Euler's number, and it's approximately equal to 2.71828. If you see an exponential equation with this number in it, then instead of using the log function, you'll use the natural log function, ln, since the natural log has a base of e. You can use the natural log when your bases match. So if you have an e, then that means you have a base of e. If you see a 10 or any other number, then your base is a 10 and the standard log function will work. The process of solving an exponential equation with an e in it instead of a base 10 number is the same process, except you're now using the natural log function. Let's try solving this problem. E to the x equals 40. First, you'll take the natural log of both sides. Natural log of e to the x equals natural log of 40. Now you can move your x out of the exponent area to get this. Since we know that the natural log is base e, and log base b of x equals 1 when b equals x, our natural log of e term cancels out and we're left with x equals natural log 40, x equals 3.689, and you're done. Let's try solving another problem. E to the 2x minus 7e to the x plus 10 equals 0. This one is a bit more interesting. Instead of having just one term with the x in the variable, you now have two of them. To solve this, you'll need to go about it in a different way. Looking closer at your numbers, you see that you can actually go ahead and factor your problem to help you solve it like this. E to the 2x minus 7e to the x plus 10 equals 0. E to the x minus 2 times e to the x minus 5 equals 0. Once you've factored, now you can go ahead and solve each of your factors using the log method like you've done before. E to the x minus 2 equals 0. E to the x equals 2. Natural log of e to the x equals natural log of 2. X equals natural log of 2. X equals 0.69. That's one solution. The other one is this. E to the x minus 5 equals 0. E to the x equals 5. Natural log of e to the x equals natural log of 5. X equals natural log of 5. X equals 1.609. And you're done. Let's now look at a real-world example. Suppose you want to put money into your child's savings account for college. Your bank offers a 5% APY compounded monthly. If you want $30,000 in 15 years, then how much money must you put in the savings account each month? For this, we must use the following compound interest formula, where P is the monthly deposit, R is the interest rate in decimal form, compounded monthly means N equals 12, and T is time in years. We can update our formula to this. Because you want $30,000 in 15 years, A of 15 equals $30,000. Therefore, your monthly deposit must be $112.24. When will your child's savings account reach $15,000? With our updated formula here, we must now solve A of t equals $15,000 for t. We can do this using the previous technique. We now know how much you must deposit each month and when you'll be halfway to your goal of $30,000 for college. Let's review. An exponential equation is a problem with exponents that usually has a variable in the exponent area that you have to solve for. To solve these types of problems, you'll make use of the logarithm function. X equals b to the y with the function is y equals logarithm base b of x. Along with this property, log base b of x to the y equals y times log base b of x. This property only applies when your bases are the same. Use the standard log with a base of 10 when working with base 10 numbers. If you see an e, then use the natural logarithm, the logarithm of the base of e. You'll use the same methods that you use to solve all your other algebra problems, with the addition of the log function helping you to take the variable out of the exponent.
So, I'm not gonna lie, I'm kind of a nerd, and I got really into science fiction when I was just a little kid. Maybe it helps that I was named after Luke Skywalker, but either way, starting in elementary school, I couldn't stop thinking about the Force, or spaceships, and our solar system. My favorite planet was Pluto, although I suppose it's more of an X-planet now. But either way, I wanted to get a telescope so that I could see it. So my parents and I found a really cheap one at a store close to my house, but much to my dismay, when I got home and tried it out, it wasn't nearly good enough. As it turns out, the telescope I got could only see stars with an apparent magnitude of 8, but what I needed was one that could see stars with an apparent magnitude of 14. Too bad I wasn't a math teacher yet and didn't know the equation magnitude equals 5 times the log of diameter plus 2. This is the equation that tells you what magnitude star you can see with a lens that has a diameter of d millimeters. If I had been a math teacher, I would have known that I could substitute 14 in for m and then solve the equation for d, and our resulting answer would tell you exactly how big your lens would need to be in order to see stars with an apparent magnitude of 14. So how big of a telescope did I actually need? Well, it's again our job to use inverse operations to get the d by itself in this equation. We need to start peeling the layers off of this equation one at a time in reverse order, starting with the outermost step in this equation, which is the plus 2. I can undo addition with subtraction. Subtracting 2 gives me this. Now the outermost layer is 5 times. I undo multiplication with division, dividing both sides by 5, and I get this. But now I need to undo a log, and this is where the new skill comes into play. And we do know that the inverse operation to a log is an exponential, so I need to use an exponential to undo this log. I need to pick my exponential to be the same type of log that this is. I need to be taking the same base, log, and exponential in order to undo them. This log is blank, which means there's an imaginary little 10 in there, so I need to do the exponential base 10 on both sides. Now, this is a little strange. We haven't actually done this before. I see a very common mistake of people trying to raise the log to the 10th power, but that's not exactly what we want. An exponential has your variable in the exponent. So the 10 shouldn't be the exponent, the log d should be the exponent. So what I do is I write a little 10 to the bottom left of the log, and that is my base. So I get 10 to the log of d. Whatever I do to the one side, I have to the other side. So on the other side, I have 10 to the 2.4 power. Now the 10 to the log 10 undoes, because the exponential and the log are inverse operations. I just get the d, and if I plug 10 to the 2.4 power on my calculator, we get around 251. That means that I needed a telescope that has a lens with a diameter of 251 millimeters. That's almost 10 inches, which is a pretty big telescope. Maybe it's for the best I didn't know this equation, because if I would have asked my parents for something that big, I would have been rejected for sure. We can use similar skills to solve even harder logarithmic equations, like this one. Log base 2 of x plus log base 2 of 5 equals 10. This is more difficult than our telescope example because there are 2 logs instead of 1. What this means is that we'll get a chance to practice our property skills as well as our solving skills all in one problem. Before I can solve this equation like we did before, I need to use the product property to combine the 2 logs into one. I picked the product property because I saw 2 logs separated by addition. When I see that, the product property tells me that I can condense them into one log where the 2 things on the inside are now multiplied. So instead of log base 2 of x plus log base 2 of 5, I combine them into one. I multiply 5 and x, and I just get the log base 2 of 5x, and I still have equals 10. Now that it is written as one log, I can continue to do this problem and solve it exactly like I did the last one. The 5 and the x are both on the inside of the log, so the next thing to undo, the outermost layer, is the log itself. We just learned that I undo logs with exponentials by exponentiating. This time the base of my log is 2. which means I have to use the same base in my exponential, so I put a 2 to the power of log 2 of 5x equals 2 to the power of 10. That undoes the log on the left, I just get the 5x, and on the right, 2 to the 10th power is 1024. I quickly undo multiplication with division, and I get the x by itself and find that x must be equal to 204.8. We can even solve logarithmic equations that have logs on both sides of the equal sign, like this one. Log base 3 of 4x equals log base 3 of 2x plus 8. Because we're being asked to solve, the goal is still to figure out what x must equal for the equation to be true, and that means undoing. Luckily, both logs have the same base 3, and the logs are the outermost step on both sides of the equation. There's no plus 3 on the outside, or divided by 2, or times 4. On both sides, the log is the outermost thing. Another way of saying that is everything that's going on either side of the equation is on the inside of the log. Because of this, we can simply exponentiate both sides with the same base, 3, and the logs undo on both sides, and we're just left with a nice, easy linear equation. 4x equals 2x plus 8. Now it's simply a matter of undoing what we know with subtraction, then with division, to find that x equals 4. Unlike exponential equations, I've never seen an example problem like this that has logs with different bases. So don't worry about having to change the base of the logs before exponentiating for problems like this. That will never be asked of you. To review, we can undo logarithms by exponentiating. Just like we can multiply both sides of the equation by 2 to undo division, we can exponentiate both sides by 2, or by any number for that matter, turning x equals y into b to the x equals b to the y. If you are solving an equation with two logs on the same side of the equal sign, you must first use what you know about logarithmic properties to combine the logs into one before you can undo anything. And lastly, if you are solving an equation with logs on either side of the equal sign, as long as they have the same base, you can simply exponentiate to cancel both of them out. Imaginary and complex numbers might be the most abstract topic you'll be exposed to in an algebra class. Because they don't actually exist, and you just need to imagine that they do, a lot of students struggle with them. But if you can let go and accept that we can still do math with them, it turns out that there isn't anything too tricky about working with them. But before we get into that, let's quickly review what a complex number is. Anytime we take the square root of a negative number, we get an imaginary number. When this happens, we use I to represent the square root of negative 1. This means that I squared is just regular old negative 1. It turns back into a real number. When we take an imaginary number and add a real number to it, we end up with a complex number, often denoted by a plus bi, where a represents the real and b the imaginary portion of the number. Okay, so how do we do the basic operations on these numbers? This is where it gets nice. Although division will require you to learn a new skill, addition, subtraction, and multiplication of complex numbers will all come down to things you already know how to do. As long as you can combine like terms or multiply binomials with FOIL, you're good to go. What do I mean? Well, for example, adding the two complex numbers 3 minus 2i and negative 5 minus 4i is as easy as adding 3 and negative 5 to get negative 2, and negative 2i and negative 4i to get negative 6i. This makes our answer negative 2 minus 6i. That's it. You wouldn't even really have to know that we're adding complex numbers to do this problem. It's all just combining like terms. First combine the real parts, then the imaginary parts, and you're done. If you like keeping it simple and just thinking about it this way, that's cool. But this formula is basically another way of writing what I just said, but with math instead of words. Adding the complex numbers a plus bi and c plus di gives us an answer of this. Subtraction is basically the same, but does require you to be careful with your negative signs. Let's try the example negative 2 plus 4i minus 3 minus I. Combining the real parts looks like negative 2 minus 3 is negative 5, while the negatives will make the imaginary parts a little bit trickier. The first imaginary term, 4i, minus the second one, negative I, gives us positive 5i for our imaginary term. Remember that subtracting a negative turns into adding a positive. Therefore, our answer is negative 5 plus 5i. If you prefer the formulas, the one for subtraction of complex numbers looks like this. On to multiplication. This will again rely on an older skill, the multiplication of binomials. Whether you use FOIL, the area method, the distributive property, or one of the other many ways to do it, this is the process of multiplying two terms like x minus 5 times x plus 2. Now, though, we are simply doing the same thing, but with i's instead of x's. Take 3 plus 2i times 4 minus I as an example. I'll go ahead and use FOIL because it seems to be the most common method, but any way you would like to do this is totally fine. Multiplying the first terms, 3 times 4 gives us 12. The outsides will be 3 times negative I, giving us negative 3i. The insides, 2i times 4, is 8i. And finally, the last terms, 2i minus negative I, becomes negative 2i squared. We can then again use our combining like terms skills to simplify our expression down to this. And if you said you were done, you'd more or less be right, but you'd be forgetting one step that would prevent your answer from being completely simplified. This step requires you to remember that I squared is just plain old negative 1, no more imaginary numbers. Substituting this in for I squared into our expression, and then again combining like terms, gives us our final answer as 14 plus 5i. Let's do one last example that ties all these skills together. Simplify negative 7 plus 14i minus 3 plus 2i times 1 plus 4i. Well, order of operations tells us to do multiplication before subtraction, so we can FOIL out the first two complex numbers first. Multiplying the firsts, outsides, insides, lasts gives us this. In order to not forget, let's substitute negative 1 in for I squared right away, and then combine both the real and imaginary parts at once to give us negative 5 plus 14i. We can now move on to the subtraction part of this problem. It, again, comes down to just combining like terms. First, the real parts. Negative 7 minus negative 5. Again, subtracting a negative is like adding a positive, so we just get negative 2. And then the imaginary parts. 14i minus 14i is just 0. That means our answer is simply negative 2. This example illustrates why it's good to be able to use complex numbers. If you let yourself imagine that they exist, you might just end up with a number that truly does. To review, adding and subtracting complex numbers is simply a matter of combining like terms. You combine the real and imaginary parts separately and can use the formulas below if you like. Multiplying complex numbers is basically just a review of multiplying binomials. The only extra step at the end is to remember that I squared equals negative 1. Dividing complex numbers, on the other hand, is a little more complicated and will be taught in a later lesson. Complex numbers are a combination of a real number with an imaginary one. Because of that, we can express them generally as a plus bi, where a is the real part of the number and b is the imaginary part. As long as you remember that I squared is equal to negative 1, then adding, subtracting, and multiplying them is really just a review of combining like terms and multiplying binomials with FOIL. But when it comes to dividing complex numbers, some new skills are going to need to be learned. Along with these new skills, you're going to need to remind yourself what a complex conjugate is. If you haven't heard of this before, don't worry, it's pretty straightforward. A conjugate is a binomial where the sign on the second term has been switched. So the complex conjugate to a plus bi is just a minus bi, and vice versa. Here are some examples of complex conjugates. Maybe 2 plus 3i and 2 minus 3i, or negative 3 minus I and negative 3 plus I, or 4 minus 5i and 4 plus 5i. Just remember that the sign on the first term stays the same, but the sign on the second one switches. Conjugates are special because there is a pattern to multiplying them. Let's show this with two of our examples from above, 2 plus 3i and 2 minus 3i. Multiplying these two complex numbers with FOIL will give us this, but then when we combine like terms, the two groups of i's in the middle are going to cancel out. Substituting in negative 1 for I squared, and then doing 4 plus 9 gives us our answer as 13, a real number. Multiplying any two conjugates will make these middle terms cancel out, which means that multiplying two complex conjugates will always make the i's cancel out, leaving us with a real number every time. Okay, so why do I bring this up? Well, dividing complex numbers will take advantage of this trick. There really isn't a good way to figure out how many of these complex numbers fit into that one. So instead, we do some fancy hand waving, using the conjugate, to make the imaginary part of the complex number we're dividing by go away. Then it's just dividing by a real number, something that we know how to do. Whew, that's a lot of words. Let me show you what I mean. Take the example 3 plus 4i divided by 2 plus I. Like I said earlier, I have no idea how many 2 plus i's fit into 3 plus 4i. So writing the problem this way doesn't really give us much. Instead, changing it into a fraction, like this, will allow us to begin using our fancy math tricks. If we now remember what we just learned about the complex conjugate, we can change this from dividing by a complex number, something we don't know how to do, into dividing by a real number, something we do know how to do. So we want to multiply the denominator by its conjugate, 2 minus I. That would make it a real number. But we can't just do anything we want. We have to leave the problem the same. Multiplying by some random number will change it, but multiplying by 1 is actually not going to change it at all. Because of this, our next step to this problem will be to multiply our fraction by 2 minus I over 2 minus I. This is kind of like multiplying a fraction by 4 over 4 to get a common denominator, just with more complex numbers. Get it? Sorry for the nerdy joke. Okay, anyways, we're multiplying 2 minus I over 2 minus I. This means we have to FOIL out the top and the bottom. This means multiplying the first, outside, inside, and last terms, substituting in -1 for I squared, and combining like terms leaves us with this. Since this answer has real numbers and imaginary ones, we'd like to split it up and write it in the standard complex form. This means splitting our answer up into 10 over 5 plus 5i over 5. While this won't always be the case, it is true that this time we can take our answer one step further and simplify both fractions as well. 10 over 5 is 2, and 5 over 5 is 1, so our final solution is 2 plus I. Let's run through another example just to get a look at a problem that might not have numbers that work out so nicely. I'll highlight the process to give you a review of the sequence, but skip through the specific operations to save you some time. If you find yourself getting lost, either pause the video and check my math, or maybe check out a previous video to brush up on your skills. Alright, let's do it. 4 minus I divided by 2 minus 3i. First part of this problem is that we want to get the imaginary part of the complex number out of the denominator. To do that, we'll need to multiply it by the complex conjugate. That means taking 2 minus 3i and changing it to 2 plus 3i. But since we can't change what the fraction is, we need to multiply the numerator and the denominator by the same thing, leaving us with this. This is the main conceptual idea of this whole problem. Now we multiply the two complex numbers in the numerator, 4 minus I and 2 plus 3i, with FOIL. We multiply the two numbers in the denominator with FOIL, 2 minus 3i times 2 plus 3i, and we get this. Combining like terms will lead us here. Then substituting in -1 for I squared gets us to this. Finally, combining like terms one last time gets us to this. And then because there are real and imaginary terms in our answer, we split up the fraction into two new ones to put it in general complex form. This leaves us with 11 over 13 plus 10 over 13i. And we're done, because the fractions are as simple as they can be. While there are a lot of fancy math tricks in these types of problems, hopefully you're starting to get a feel for it and can handle the quiz questions following this lesson. Let's review. Conjugates are two binomials with everything the same except the sign on the second term. This makes the complex conjugate of a plus bi a minus bi. We take advantage of these conjugates when we divide complex numbers. In order to do this, we end up having to multiply the top and the bottom of the fraction by the complex conjugate of the denominator. This ends up changing the denominator into a real number, which then allows us to split up the fraction into a single complex number for our answer. Being a math guy, I was also pretty into my science classes during high school. Naturally, the one that I liked the most was the one with the most math in it, physics. It's now been a while since I've reviewed my physics, but I do remember a few things. And one of those things that I remember is that electric circuits are defined by two things: their voltage and their current. Well, this presented a problem for physicists. They would like to have one number that represents both of these pieces of information. But what one number can represent two things? Now, I suppose they could have used coordinates, like x comma y, but what if you wanted to multiply or even divide these two numbers? There's no method for dividing coordinates. Is there a better way? Aha! Complex numbers. Because they have a real part and an imaginary part, they can represent two pieces of information, and we know how to add, subtract, multiply, and divide them as well. This makes complex numbers the ideal way to represent two pieces of information in one number. But to make complex numbers better than coordinates in every way, we'll need to be able to graph them as well. Because there are two pieces of information in each complex number, we can put this info into a two-variable graph. This time, instead of having an x-axis and a y-axis, we'll have a real axis and an imaginary axis. But even though the axes will be a little bit different, the process of putting the numbers on the graph is essentially the same. Let's take a look at an example. Graph -2 plus 5i. The axes will look the same, but now our x-axis is instead going to be the real part of the complex number, so we call it our real axis. That makes the y-axis now our imaginary axis and will represent the imaginary part of the number. That makes graphing -2 plus 5i basically the same as graphing -2 comma 5 on a normal xy axis. We go over to -2 on the real axis and up to +5 on the imaginary one, giving us a point right here. That's all there is to graphing complex numbers. Any complex number will simply look like a point. 3 minus I would be a point at 3 - 1, like this. 2 plus 4i would be up here. 5 would be a point at 5, 0, like this. That means that any point on the x-axis, or what is really the real axis, is a complex number without any imaginary value. It's not a stretch to then say that any point on the y-axis, or the imaginary axis, is a complex number without a real value. That makes the point shown right here just -3i. When it comes to graphing complex numbers, that's it. Because complex numbers have two parts, they are great for representing topics that have two pieces of information. When graphing complex numbers, the xy axis becomes the real imaginary axis, and all complex numbers will look like points on a graph. By allowing ourselves to imagine that square roots of negative numbers actually exist, we are able to solve a lot of real-world problems. So what does that actually look like? How would you go about solving a problem that has an imaginary solution? That's what this lesson is all about. You'll need to remember that imaginary numbers come about when we take the square root of a negative number, and complex numbers are when we combine a real number with an imaginary one using either addition or subtraction. If this is a new concept for you, then you should check out one of the previous lessons that introduces these ideas. But if you already know this, we're ready to look at the example, find the roots of y equals 2x squared minus 5x plus 7. When a problem asks you for the roots, it is the same thing as asking you for the zeros, or the x-intercepts. These are the points where y equals 0, so we can substitute that value in to begin with. Given the fact that we're doing this example in the lesson all about complex number solutions, there is a good chance that's what this problem will have. But how could we know this if this problem wasn't in this context? It's all going to come down to the discriminant. Given a quadratic equation in standard form, like this, the discriminant is b squared minus 4ac. If the discriminant is positive, you'll get two real answers. If it's equal to 0, you're only going to get one real answer. But if the discriminant is negative, that's when you get two complex solutions to your problem. This is the case because of the way the quadratic formula works. If we begin to solve the example using the quadratic formula, as shown here, you might notice that the discriminant is the part of the formula that is inside the square root. Therefore, it makes sense that if that part is negative, we'll get an imaginary number there, making our answer a complex number. So back to our example, if we substitute A, B, and C into the formula, and then begin to evaluate the expression, we'll find the discriminant will, sure enough, become negative. You'll see that we end up with the square root of negative 31, which is going to be an imaginary number. While this is what makes this problem a little bit new and different, the only special thing to do is to put an I in front of the square root to indicate it's imaginary, make everything else on the inside of the square root positive, and then continue on just like we normally would. That's it. The I tells everyone that it is an imaginary number, but then we can move on and continue to solve the problem as normal. As it turns out, there isn't even anything else to do with this problem. It's as simplified as it can be. Maybe if we could simplify the square root somehow, we might have a few more steps, but we can't do that, so we're good to go. We can also solve polynomial problems with imaginary solutions that are bigger than quadratic equations. Take this example. Solve 0 equals x minus 9 squared times x squared plus 9. This isn't a quadratic equation anymore because there are two x squareds, here and here. We don't have any fancy formula for such problems like we do for quadratics, but because of the way this one is written, we can still solve it. We're going to use the zero product property for this one. That's the property that says anytime you multiply two things together and get 0, one of the things you multiplied in the beginning must have been 0. In this problem, that means that either the x minus 9 squared or the x squared plus 9 must be 0. Now that we've split the equation up, we've got two smaller equations that we do know how to solve simply with inverse operations. Getting the x by itself in this first one means undoing a power of 2 of the square root. The square root of 0 is still just 0, so that leaves us here. Now undoing minus 9 with plus 9 tells us that x equals positive 9. Moving over to the other equation requires us to undo similar steps, just in a different order. The most outside thing here is the plus 9, so we have to undo that first. That leaves us with this, and then again we take the square root of both sides to get the x by itself. When we take the square root of a non-zero number, we need to include the positive and negative root, giving us two answers here. We also have now taken the square root of a negative number, which means we have imaginary solutions as well. That means putting an I in front of the square root and continuing on like normal, just like before. This time we can go further because the square root of 9 is just 3. That makes our two other solutions here positive and negative 3i. While this video is about how to solve problems with complex numbers, because the only thing you do is add an I and continue like normal, it's more a review of older solving skills. As long as you keep this in mind and don't think that complex numbers require you to do anything really radical, you should be good. To review, the discriminant, b squared minus 4ac, will tell you whether you have real or complex solutions to a quadratic equation in standard form. When you need to take the square root of a negative number, just put an I in front of it, make the number on the inside positive, and continue on like normal. You can solve higher order polynomial problems using the zero product property, which says that when you multiply two things together and get 0, one of the things you started with must have been 0.
All right, let's go. We talk about vectors in this video lesson. What are they? We define them as measurements that include both magnitude and direction. Just think of an arrow. We can draw arrows at different lengths, but each arrow has its own direction. This is exactly what a vector is. And guess what? We draw them on our Cartesian plane. They look just like our arrows. Remember how we write our points on the Cartesian plane with parentheses and then our values separated by commas? Our points look like 3, 4, with our x value first and then our y value, x, y. We write our vectors similarly as well. When we draw our vectors on our Cartesian plane, we usually have the vector beginning at the point 0, 0, and we mark the point where the vector ends. We mark the endpoint the same way we mark our Cartesian points, with our x value first and the y value second. So, we label a vector that starts at the point 0, 0 and ends at the point 5, 6 with a notation 5, 6 to let us know that it has an x length of 5 and a y length of 6. Most times you will see vectors identified with just 2 values, but sometimes you will see vectors being identified with more than 2 values. Theoretically, vectors can be identified with as many values as needed. We could have a vector identified with 3 or even 5 values, for example, x, y, z, or even 1, 2, 3, 4, 5. Using this notation for our vectors, we can easily perform our operations of addition, subtraction, and multiplication. These vector operations become very easy when we break the notation apart into the vector's separate parts. Even though our vectors may have 2 or more numbers that identify them, when we do the operations, we do it in stages. First, we add, subtract, or multiply just the x values. Then we add, subtract, or multiply just the y values, and so on and so forth, until we've covered all our identifying values. Let's look at addition. Add vector A, 1, 2, and vector B, 5, 8. To add these two vectors, we separate each vector into its x part and its y part. For vector A, our x is 1 and our y is 2. For vector B, our x is 5 and our y is 8. Adding them, we get A plus B equals 1 plus 5, 2 plus 8 equals 6, 10. Do you see how we simply added the two vectors in parts? That's all we have to do. The addition part is the same as we've always done it. Subtraction is also very similar. We break the vectors into their separate parts and then perform a subtraction on each of the parts. Subtract vector A, 5, 6 from vector B, 11, 23. We have to be careful when we read problems versus when we see math problems written. When we read this problem, it tells us that we are subtracting A from B, so mathematically we write B minus A. We have to be careful not to write A minus B, because that will give us a completely different answer. When we see problems written out mathematically already, we can rest assured that everything is in the correct order. So, our problem is B minus A. Let's break our vectors into their separate parts. Vector A has an x part equal to 5 and a y part equal to 6. Vector B has an x part equal to 11 and a y part equal to 23. Performing the subtraction, we get B minus A equals 11 minus 5, 23 minus 6 equals 6, 17. We took each part and we performed the appropriate subtraction to each part. What do you think? Not too bad? Just remember, break the vector into its separate parts and then do the operation like you always do. The same goes for multiplication. Multiply the vector A, negative 2, 3 with 4. We are multiplying our vector with a number. Again, we break our vector into its parts and then perform the multiplication to each part. We get 4 times A equals negative 2 times 4, 3 times 4 equals negative 8, 12. We multiplied each part by 4 to get our answer, and that's all we had to do. Let's review what we've learned. We learned that vectors are measurements that include both magnitude and direction. If our vector begins at the point 0, 0, then we label our vector with its endpoint coordinates on the Cartesian plane. For example, the vector 7, 4 ends at the point 7, 4. This means that this vector has an x length of 7 and a y length of 4. It is pointing away from the origin towards the endpoint. To add, subtract, and multiply vectors, we separate the vectors into its separate and then perform the operation to each part. Imagine holding two arrows with their flat ends touching. What do they look like? Since we are talking about math, they look like two vectors. See, a vector is a measurement with both magnitude and direction. Hence, we have a particular length and an arrow telling us which direction our vector is in. So an arrow is a perfect real-world representation of a vector. Just think about it. When you hold an arrow in your hand, no matter which direction you point it in, it is always the same length and same magnitude long, but the direction changes depending on which way you point the arrow. It is the same with a vector. In math, we can draw our vector on our Cartesian coordinate plane. We can note the vector two ways. We can note it with its starting point and its end point on the Cartesian plane. Or we can note it with its magnitude and direction. When we have two vectors, we can note both with their start and end points. Or we can note the magnitudes along with the angle between the two vectors. Since we are not always given the magnitude, we need a way to find the magnitude of a vector if we are just given the beginning and end points. To do this, we use this formula. This formula is telling us that for a vector A, the magnitude is found by squaring the x length and the y length, adding them together, and then taking the square root. If you notice in our vectors so far, I've shown them starting at the point 0, 0. If they start at a different point, we'll need to calculate the x length and the y length before using the magnitude formula. Alternatively, we can move the vector so that its starting point is at 0, 0, and then use the new endpoint to calculate our magnitude. Let's look at how we use this formula. Let's say we have an arrow that has its flat end at the point 0, 0 and is pointing to the point 3, negative 4. To calculate its magnitude, we plug in 3 for x and negative 4 for y. We get the square root of 3 squared plus negative 4 squared. This evaluates to 9 plus 16 equals 25. Taking the square root of this, we get 5. So the length or magnitude of this arrow is 5. Notice that we kept the negative sign since the arrow is pointing downwards. Because vectors have direction, it is important to keep any positive or negative signs that we have. Now let's talk about the dot product. This is the multiplication of two vectors. We get a scalar result, meaning we get a simple number instead of a number with direction. We have two formulas we can use to find the dot product, depending on whether we are given beginning and end points, or we are given magnitudes with an angle. The formula to use when we are given beginning and end points is this one. So, what we do is we take the x lengths of each vector and multiply them together. Then we take the y lengths of each vector and multiply those together. Then we add them up to find our dot product. The formula to use when we are given magnitudes and an angle is this one. This formula is telling us to multiply the two magnitudes together, then find the cosine of the angle between them. We then multiply it all together to find our dot product. Even though these two formulas are completely different, you will find that they will give you the same answer for the same situation. Let's take a look, shall we? Let's use the first formula for the beginning and end points. We will call the vector on the right vector A, and the vector on the left vector B. So, for vector A, the x length is 3 and the y length is 4. For our vector B, the x length is negative 6 and the y length is 8. Plugging these into our formulas, we get A times B equals 3 times negative 6 plus 4 times 8. This evaluates to A times B equals negative 18 plus 32 equals 14. So, our dot product from this formula is 14. Let's try the other formula. Our magnitude for vector A is 5, and our magnitude for vector B is 10. The angle between them is 73.7 degrees. Plugging these into our formula, we get A times B equals 5 times 10 times cosine 73.7. This evaluates to A times B equals 50 times 0.280667 equals 14 approximately. They both give us the same answer, except that for the second formula, we just needed to do a little bit of rounding. So, what did we learn? We learned that a vector is a measurement with both magnitude and direction. We draw vectors on our Cartesian coordinate plane. We can note vectors with either beginning and end points or their magnitudes with direction. The dot product is the multiplication of two vectors. The formula to use when we are given beginning and end points is this one. We multiply the x lengths of each vector and the y length of each vector together and then add them up. The formula to use when we are given the magnitudes and the angle between the vectors is this one. We multiply the magnitudes together, take the cosine of the angle, and multiply it all together. The result of the dot product is a scalar number without direction.